Hello, welcome back. It's the 4th Applied Active Inference Symposium, Day 2, Part 2, on November 14th, 2024. We're kicking off this session in the darkness of the pre-dawn on the West Coast, appropriately with Mehran, Hossein, Zadeh, Bazargani, ML Dawn, Brain in the Dark, Design Principles for the Neuromimetic Inference under the Free Energy Principle. So thank you, Mehran, for joining. Looking forward to your presentation.
Thank you very much. It's a pleasure to be here. So today I'm going to be talking about the design principles for neuromimetic inference under the free energy principle, namely the methods that are inspired by the brain in order to model human perception. Just want to preface this by saying that this is a collaboration with my colleague Simon Orbas from Maynooth University and Professor Friston from UCL. And this work has recently been accepted at the Neuro AI workshop at NeurIPS 2024. So let's just get started. The content is going to be as follows. We're going to be talking about first the motivation behind this work, why we got started with this idea anyway, to introduce the design principles, particularly for these models. And then I'm going to do a quick refresher on the math side, just so we all get comfortable with the upcoming derivations that I'm going to be expanding on, which covers the math behind the free energy principle, particularly variational free energy. Then I'll do a brief discussion on what free energy principle is. I presume everybody knows by now because we've had so many talks since the beginning of the symposium, but I'm going to do a quick run at that. Then we'll be talking about the Bayesian brain hypothesis that furnishes the foundation for the idea of modeling human perception as a kind of inference, namely Bayesian inference. Next, we dive into the juxtaposition between the generative model and a generative process. What do we mean by each one of them? Knowing the distinction is crucial for understanding the free energy principle because FEP lies on this notion that there is a boundary that separates an entity from the environment, and separating basically my internal state from the external state beyond my Markov blanket. Next, we'll talk about variational free energy and how it's driven, how it's derived, basically. And then we jump into the design principles in terms of the experiments, that the things that you need to consider, the things that you need to define, and how you should go about doing that in order to model human perception as a kind of online inference problem. We'll go through some final thoughts, some lessons learned, and then I'll introduce some of the resources for those of you who are interested in pursuing free energy principle more seriously and delving into the theory and the practical side of it. And then we're going to wrap it up with a demonstration using the GitHub repository that is publicly available by the way. So the motivation is this. You said deep learning has revolutionized artificial intelligence because it has automated the process of feature extraction from raw data. However, it actually faces a lot of problems. For example, lack of out-of-distribution generalizability, catastrophic forgetting, and poor interpretability. It is known as a black box, basically. And the catastrophic forgetting is basically when the new knowledge overwrites the previous knowledge. The weights are getting overwritten. So while the network learns the concept of a cat, it might momentarily forget the concept of a dog because the paths are shared between different concepts that are to be learned. You see, in contrast to deep learning, biological neural networks in your brain and in my brain, they do not suffer from these issues. And this inspires the AI researchers to actually explore this interesting and intriguing area called the neuromimetic deep learning that is all about replicating the brain mechanisms, namely the neuronal message passing and belief updating within the AI models, purely inspired by our best knowledge about how the brain works. A foundational theory for this approach is the free energy principle, FEP, which unfortunately, despite its potential, is often considered too complex to understand and to implement in AI, simply because one would need a myriad of disciplines under their belt, knowledge about disciplines under their belt, to be able to understand the free energy principle. Namely, you need to know things, for example, about dynamical systems, random processes. You need to know about Bayesian mechanics, some neuroscience, some maybe computational neuroscience, and so on and so forth. So as a result, it's an intimidating topic, let's say, for anybody who wants to just get started with it. So we seek to demystify FEP and basically provide a comprehensive framework for designing neuromimetic models where we are actually trying to mimic human-like perception capabilities. So here we present a roadmap for implementing these models. And by the way, a PyTorch code repository for applying FEP in a predictive coding network is going to be introduced here. The link is here, that's the code. It's publicly available. And also, as I said, the paper will soon be available by the Neuro AI workshop. And so hopefully you guys will have a chance to take a look at that as well. Now, let's get started with the refresher of the math. So first and foremost, the idea of a PDF. So it's an acronym for a probability density function, which is a function that describes the likelihood of a continuous random variable taking on a particular value. It has two conditions. It has to be positive. So for a given parameter theta 0, for example, the mean of a Gaussian, let's say, for any input x, it's always positive. And second, we have this normalizer sort of condition that if you integrate a PDF across the support space of the input, namely all possible values of x, you will inevitably must get to the actual value of 1. What this means is the probability of x, the input, getting any value in any range within its support is always 1, which means that x will always fall in a range in its own accepted range of values. So that's 100%. So you need these two if you want to have a PDF. Next is the idea of an expectation. I just want to remind you that the reason I'm going through this math is because later on when I introduce the steps of deriving variational free energy, these concepts are absolutely crucial. So hopefully I'm not going too fast, but just bear that in mind that these are very important. And for those of you who are math savvy and these are too basics, my apologies. Now, the idea of expectation is actually the weighted average of all the possible values that the variable can assume, weighted by their probability. So you have in the first line the expected value of x over the probability distribution, the PDF px. So as you notice, we're integrating all possible values of x multiplied by or weighted by their corresponding probability. And it's important to note that you're not limited to calculating the expected value with respect to a variable, but you can also do this exactly the same thing with a function. So the expected value of function is again the same thing, but you are summing up you're basically calculating a weighted average of a function where the weights are the probability of the input to that function, which is x. Now, some key probability components here. Now, we have this idea of a joint probability. So a joint distribution between two variables, x and y, you can divide it up between like some conditional term, which is the probability of x given y multiplied by the probability of y in the first place. Or you can go the other way around, the probability of y given x times the probability of x. You notice that if x and y are independent, this conditional term reduces to probability of x, or this conditional term will reduce to probability of y. So either way, on both sides, you're going to have the probability of x given y if x and y are indeed independent. Next, if you want to move from a joint distribution to a marginalized distribution where you're actually marginalizing one of the variables out, this is how you can do it. So in this case, if you integrate P of xy across all possible values of x, in other words, like if you literally break this down and, basically write it down in its, constituent terms, if you do this integration, you're inevitably what you're doing is you're getting rid of x, and then you end up with a term with a probability distribution that is only a function of y, and that's what you call a marginalized probability distribution, or PDF. Again, this is key. Where will this come in handy? It's going to come in handy when I'm going to be talking about the Bayesian brain hypothesis and Bayes' rule and so on and so forth. So keep these two equations in mind, please. Now, some properties of logarithms. So this is basically just the definition of a log. So log of a with base b equals c. The definition says that it just means a equals b to the power c, right? So for example, the log of 8 with base 2 equals 3, because 2 to the power 3 is 8. So the log of a multiplication is sum of the logs of individual terms. The log of a division is the subtraction of individual log terms. That's the log of the numerator minus the log of the denominator. The log of a fraction is literally minus the log of the swapped fraction. If you literally swap b and a together, from you end up with just a negative of the new log term. The power law. The log of b to the power c, so basically c drops down as a coefficient, so you end up with this term, c times log of b with base a. Log of a with base a, if the value and the base are both the same, you end up with value 1, and by extension, if you have this term, c drops down as a coefficient, and this term equals 1, so you end up with c. Log of 1 with any base is always equal to 0. Why? Because a, whatever it is, to the power 0 is 1. And last but not least, this one is again very important. Ln of a is basically just a logarithm with, where the base is natural number e, or it's called the natural log, and e is basically the Euler's number. So you got log of a with base e. It's called just the natural log. So when in Python, when you say numpy dot log, it's basically the natural log. Now, the free energy principle, it is a theoretical framework in neuroscience. It's been developed by Carl Friston. So basically, things that persist over time, especially living systems, look as if they are minimizing a certain quantity. It's called free energy. It is as if they're sort of maintaining this boundary that is called a Markov blanket to persist in the face of random fluctuations in the environment. And this really connects well with the Bayesian brain hypothesis, as you will see shortly. So the brain, from the perspective of Bayesian brain hypothesis, it's actually in the game of inferring the hidden causes behind its sensations. So namely, if you let's say use y to denote the sensations and x as the hidden state, and then this inference basically means that given my observation y, I want to estimate the probability distribution over x, right? It's basically called a posterior probability, which means that after having seen an observation, what is causing in the world beyond my Markov blanket this particular sensation or observation? Inevitably, this requires having a generative model, GM, of the world. And this actually connects really well with Helmholtz's concept of unconscious inference. And it is defined like that perception is kind of unconscious inference, which means that we are in the game of, inferring the hidden cause behind our sensations. For example, right now you're looking at the monitor and the photons, but the light is hitting your sensory epithelia on your eyes. Those excitations, those hits, those are your sensation. And when you realize that I'm watching this presentation at Active Inference Institute, And this guy is talking, his name is Mehran. This is the slide of a face. Helmholtz picture is here. These are the inferences that your brain is making given that particular sensation that is hitting the neurons on the surface of your eyes, right? So it's estimating this probability distribution about what's happening beyond your Markov blanket. Now, let's talk about the idea of a generative model versus generative process. This is actually very, very important. On the right-hand side, you see this idea, this generative model as a box, and it has some internal states. Let's call them hidden states. This represents the neuronal activities in your brain, the excitabilities of different, the voltage level, let's say, of your neurons that keep changing all the time. They fluctuate all the time. And these guys are basically holding information about what's happening beyond your Markov blanket, right? Remember, what's happening beyond your Markov blanket is out of your reach. You have absolutely no way of observing exactly what's happening, right? And here we have the generative process where X star denotes the actual things that are happening in the world, which are completely out of reach to you. Now, if you imagine here, you have the face of a person, let's say Steve Jobs is standing in front of me, but this is no, like, I'm not going to see the truth. What I'm going to see is some sort of a map, some sort of a noisy transformation of the truth, X star, right? Let's call it Y. This is what I'm going to be experiencing. This is what's going to hit and induce excitation at my sensory epithelia on my eyes. And then if you want to look at, like, basically dig deeper into the idea of perception as unconscious inference, the game is this. Your brain, the generative model in your brain, predicts a sensation. Like, I'm expecting this sensation to be felt or received at my sensory epithelia, on my Markov blanket. And then the actual sensation Y is received. So the difference between the actual sensation and my prediction is called the prediction error. So using that prediction error, I will update my generative model about the world. Namely, I will update my belief about what's happening in the world. So this is where my internal states will change to reflect a better image of the unknown world beyond my Markov blanket. Or the parameters of my generative model are going to change to, again, do a better estimate of what's happening in the world so that I will have a better prediction about the sensations that that world is going to cause, right? So generative process, again, is not directly observable. And the internal states X, this is very important, carry information about the invisible external states X star beyond my Markov blanket. This is where this connects to the idea, the discipline of information theory. This is a very important link, by the way. So the generative model, what do we mean by that, mathematically speaking? Now, in a dynamical world, a generative model has a belief about the dynamics of the world. What it means is, how fast is the world changing, for example, or how is it changing? Now, if the world is at a given state X, right, what does its dynamics look like? For example, its velocity, or acceleration, or even higher temporal derivatives like jerk. Basically, all sorts of rates of change about the world. That's what I mean by dynamics. So in a generative model, your generative model will have an understanding, it has to have a belief about how the world is changing beyond the Markov blanket. So in other words, if I'm in the game of estimating the dynamics of the world, it means I'm chasing a moving target. What it means is, at any given time when I want to infer what's happening in the world, by the time I've made that inference, the world has already moved. So that basically makes inference a tricky task, especially if I'm in a highly dynamical world. It makes it more challenging. The second thing that in a generative model we should have is the generative model has a belief about how the world causes its sensations. Namely, if the world is at any given state, that by my estimation, beyond my Markov blanket, what is the most likely sensation Y that I will be experiencing, right? So these two are the key components of a generative model. So like mathematically, this is how you show it. X dot is literally the velocity of the world, how fast it's changing. Mathematically, it's just dx over dt. And then you have some function of the states, x, and causes, nu, and theta, the parameters of my generative model, plus some random fluctuation, omega x. So that equation is called the state dynamics equation. But what it basically is telling you is that the dynamics of the world is driven by x, by the position of the world, basically. And these are all my belief about how the world is changing, dx over dt, the velocity of the world. And technically speaking, F is called the flow of the state dynamics. It's the deterministic part of the state dynamics. Omega x, random fluctuation, is what encodes your uncertainty about your belief about how the world is changing. Yeah. The second equation basically connects to the second concept that I introduced here. It's basically telling you that my belief about my sensation, about like what's the most likely sensation that I'm going to be receiving, is encoded in this equation, where my observation is equal to the g of the function of, again, hidden states, the causes nu, and the parameters, some parameters, plus some random fluctuation, omega y. It's called the observation model. Again, omega y encodes your uncertainty about your belief about the most likely sensation that you will be experiencing, a sensation that is caused by the world. You notice that we have these, again, your hidden state here, x, and then the cause is nu. Now, if you're wondering, so you know what the thetas are. These are just the parameters of the functional form of f and g. But if you're wondering what causes are, this is something that I'm not going to be focusing in this particular talk. But just imagine that if you have a hierarchical generative model, these causes are just a subset of the hidden states. These are like the hidden states that do not have dynamics, but they're the tools that different levels in the hierarchy use to be able to talk to each other. So interlayer communication is done using these nus, or the causes. These are the ones that basically drive the dynamics. You notice that that's why we have x dot equals f of x and nu. They drive the dynamics. Without them, the layers cannot talk to each other, basically. Now, if you want to like turn this into a belief-based system where you have probabilities in play, you just need to assume a Gaussian distribution over your random fluctuation, namely with mean 0 and some precision over your random variable x and your observation y. Just open brackets, precision is just inverse uncertainty, and close brackets, that's just a notion in statistics. Now, using this, if you literally replace, this notion of Gaussian distribution into your original equation, you end up with this probabilistic sort of, notion that the probability of x dot given all of these three elements is distributed according to a normal distribution, where again the precision is the same as the precision of your random fluctuation, but you notice that because we're summing up f with this guy over here, the mean of that Gaussian distribution becomes this f term. Same story for your belief about your y, your observations. And that is why I'm saying that f of x and nu and theta is your expected dynamics about x dot, because it's literally the expected value of the Gaussian distribution. Same story here. G of x, nu, and theta is your expectation about your observation, your sensation. Again, it is the sort of expected value of this Gaussian distribution, the value that is most likely to occur. So that's generative model. Two things. We know the dynamics of the world. We have belief. Let's say we don't know it. We have beliefs about the dynamics of the world, and we have belief about basically the most likely sensation that we will be experiencing if such and such was the state of affair of the world. Let's say X was the state of affairs in the world. Now, we talked about inference. Let's talk about Bayes' rule really quickly. Now, here, this is Bayes' rule, and the components of Bayes' rule are as follows. We have the likelihood term, which is the probability of my observation given the state of the world. We have a prior belief, which means that before observing Y, this is my belief about what the world looks like. We have the model evidence, which is probability of data. And these two together is called basically the generative model. Again, like this is in line with what we discussed here. This is basically your prior belief about the dynamics, and this is literally the mapping between X and Y, which is your likelihood term. So I'm not saying anything new here. These two together are your generative model, and this is your model evidence. This is a devil, right? This is intractable. You notice that in a real life scenario, we will not be able to calculate this. And this term on the left-hand side is called the posterior probability. It's your belief about the distribution over hidden state of the world, X. And when you map your generative model using Bayes' rule to this posterior distribution, we call this model inversion, right? So whenever you hear model inversion in the context of FEP, that's what we mean by that. So this evidence, again, going back to our idea of marginalizing a variable out, if you, again, just remind yourself that this is how you marginalize the hidden state or X out, you just end up with probability of, let's say, sensation Y. You notice that this integration could get really nasty really fast, which means that if you have, you could have basically any number of hidden states X, and for each X, you would have a range of possible values. So this thing could turn into a potentially infinite number of nested integrals. Basically, it can become intractable really, really quickly. So what this means is we will not be able to calculate this posterior probability exactly. So what should we do? The answer is variational inference. So because you see probability of data, your model evidence is intractable, but at the same time, ironically, it's the true measure of how good your generative model is, which means that we call this also marginal likelihood, right? So if it is high, it means whatever sensation you're experiencing right now, under your model of the world, under your generative model of the world, the probability of that particular sensation is very high. It means under your model of the world, everything that you're sensing, you already expected to sense it. So it means you have such a strong and precise belief and precise belief about the dynamics of the world and how the sensations are generated from those dynamics, that whatever you're receiving is not surprising. That's why model evidence is such a strong metric for evaluating how good a generative model is. But unfortunately, it's intractable. So can we find a bound to this, namely a lower bound? And the answer is yes. I'm going to introduce the idea of an evidence lower bound in the next slide. So by doing this, I'm turning the problem on its head. So I'm converting, let's say, an intractable exact calculation of the posterior, and I'm replacing that with a tractable approximation, basically a tractable approximate estimation of the posterior. And that's called variational inference. And I'll tell you why we call this variational, by the way, because the objective function that we're going to be minimizing to do that is variation of free energy is actually a function of a function. It's a functional. So wherever you're dealing with functionals and optimizing functionals, that's where the calculus of variation comes into play. That's what it means by variational inference. Now, on the right-hand side, I'm just going to put some reminders, the expected value, and this particular law of logarithms, and in the middle, this is called Jensen's inequality. Just keep an eye on this one. It just says that the expected value of a log of something is always a lower bound to the log of the expected value of that thing, right? So this is going to come in handy. So let's study this amazing concept of evidence lower bound. Remember, P of Y is intractable. We want to find the bound to it. So this is log of probability of data. This is how we marginalize X out. And you can multiply and divide by this by something, right? Whatever it is. So here QX is, we call this surrogate, the surrogate posterior over the hidden state. This is going to be a representative, or your approximation to the true unknown posterior belief, right? So let's call it QX. And it's, by the way, it's really a key factor in variational inference and FEP. So keep that in mind, this Q variable, this Q function. So moving on, you do a little bit of play here. So this sort of Q moves to the denominator, and you notice that this is the definition of expectation with respect to this particular distribution Q, right? Just getting the definition from here. And according to Jensen's inequality, this term has a lower bound, and this is the lower bound to it. So the expected of this term, the expected value of this term over this probability distribution. You have the joint here, and you have the surrogate distribution here. And you see, so this right-hand side, again, remind yourself, this is your log model evidence, and we found the lower bound to it using Jensen's inequality, right? So the lower bound is found. This guy is your evidence lower bound. And that's a key finding. By maximizing this evidence lower bound, you're actually maximizing your log model evidence, and you're getting closer and closer to the true posterior. Now, elbow and VFE, just want to make sure that we're clear on this. We have elbow here, but VFE, or variational inference, is just negative of your elbow. So if you multiply -1 by both sides of this, you end up with this term, always bigger than minus log probability of data. This is called surprisal, and this is called variational free energy. That's why we say VFE is always an upper bound to surprise. So maximizing elbow or minimizing VFE, they both mean the same thing. And this is basically called variational free energy, and that's why we call it a functional, because this thing is a function of another function, and this is called surprisal or surprise. And just shows you in a plot that here you've got variational free energy. That's always an upper bound to the true unknown surprisal, or by extension, you got your elbow here. That's always a lower bound to the true log model evidence. So VFE has multiple incarnations. It comes in different forms by playing with the math. So if this is your VFE, just expand. You can just expand the joint in the denominator, and then literally use the log rule of the division turned into the subtraction, and then you can distribute the expectation across the two different terms. And this basically results into just basically swapping these two terms by each other. You end up with this equation, right? And these terms have names. So this one, actually, this expected value between your belief about the hidden state and the true unknown posterior, this expectation is called a KL divergence. It measures how different your belief about X, QX, is from the true unknown posterior. That's why it's called an approximation error. And the second term is your surprise, right? So if I want to show you what this actually means visually, this is really interesting. So this is your surprisal, right? And on top of surprisal, you're adding this approximation error. This is this sort of length over here, and then this constitutes your free energy. What this means is free energy is always an upper bound on surprisal, and the error, that gap, is your approximation error, is how far your belief about X is from the true posterior. So by tuning your generative model, your variational free energy goes down. And when it goes down, this gap is reducing. So which means that your Q gets closer and closer to the true posterior, which means a better and better perception about the world. And this doesn't end here. Your free energy will get closer and closer to the surprisal, basically by extension to the model evidence, which is the metric that we're going to be using for comparing different models with one another. A second incarnation of VFE is, again, we're going to expand the denominator again into this joint. So previously was P of x given y times probability of y. Now we go probability of y given x times p of x. And again, distributing the log, and then we distribute the the expectation, and then just swapping the terms. Again, you have this KL divergence over here, and you have this negative expectation. Now, this thing over here is called accuracy. It means how accurate am I under my belief of the world, the expected value of observing y under my estimation of where the world is x. So the higher this is, it means the more accurate your belief about the world is that is basically causing your observations. But at the same time, this term over here is called complexity. It means that if you have some prior belief about the world, you will not be able to just move your Q wherever you want. It has to stay close to your prior belief over here. So this is basically a regularizer, if you will. And the third incarnation is basically, again, here, this is the definition of VFE, again, the log rule. So we end up with these two terms. So this guy over here is called expected internal energy. And this guy is your entropy. So this is the expected value of log of QX. We call this entropy. How do we minimize variational free energy? We have to maximize our entropy, and we have to maximize our internal energy. Now, this term makes sense that we need to maximize it, but what does this one mean? It means that your Q will stay as smooth as possible, as simple as possible. This connects really well with Occam's razor if you're from machine learning background, that the best model is the one that provides the most accurate account of the data, but at the same time, the simplest explanation for that data. This simplicity is enforced by this entropy term. It stays smooth. So this is very interesting. So these were just three incarnations of variational free energy. And the goal of inverting the generative model is basically, the GM strives to minimize its VFE. This achieves two things. I hinted this just a little bit previously, but it means that the actual value of VFE will approach the intractable minus log probability of data. This is going to be used for model comparison. And the surrogate distribution will approach the unknown posterior belief. Remember, that was the goal of perception in the first place. And once you reach that, basically minimize your variational free energy, you can use the actual value of free energy as the metric, as a proxy for the unknown model evidence to compare different generative models together, right? So the model with the lowest variational free energy is going to be the best model. Yeah, I think I've explained that one. Now, just to let you know that the true form of the posterior is unknown. And you see that the terms like the probability distribution, the joint distribution here, is not guaranteed that they're analytically simple to derive and work with. Because of that, there is this idea that we can actually use Laplace approximation to break down each one of the distributions and basically approximate them using a Taylor expansion, particularly up to the third term, which means that I'm providing a quadratic approximation using Taylor expansion for each one of the components within variational free energy. Unfortunately, I don't have the time to go over the detailed derivation, but suffice it to say that the result of approximating all the components is that the variational free energy simplifies to this equation. For those of you who are interested to know the details, I encourage you to look at a primer on variational Laplace paper, which is an amazing paper. It goes through all the details of derivation. So basically, free energy reduces to log of the joint distribution, and you have the posterior covariance, and then n is basically the number of parameters and the states that you have, and so on and so forth. Now, predictive coding. This is basically where it gets even more interesting. It is basically a hierarchical generative model that we're going to be using to model human perception, and the goal is to invert this hierarchical model. So it's a powerful framework to describe how the cortex accumulates evidence from noisy stimuli. It's an application of the free energy principle. It focuses on how this literally fantastic organ can perform probabilistic inference about the most likely hidden cause that has caused the sensory signal. It assumes that the brain has a generative model of the world through which it constantly infers the hidden states of the world, and it can also learn the parameters while inferring the hidden state of the world. So model inversion happens by minimizing variational free energy. Again, even though it's hierarchical, but the concept stays the same. So in predictive coding, we have this concept of top-down predictions, where predictions go from inside out about your sensations, right? And then the prediction error is calculated, like what I described before, and then these errors, if I want to be more precise, the precision-weighted prediction errors are sent back from outside in, or they call it bottom-up sort of direction, so that the estimations of the world, the estimation of the posterior beliefs about the world are corrected. Basically, that's what model inversion, that's when model inversion happens, when the posterior estimates get adjusted. And it looks like something like this. We have this hierarchical model that we have the same story of state dynamics and observation model, but here we have this happening at each level. And then you notice that these causes are the ones that link layer I to I minus 1. That's the important part, that without these without these causes, the layers cannot talk to each other. You notice that it is a hierarchical dynamical system, basically. Now, how do we design an experiment for this kind of perception neuromimetic modeling using the free energy principle? I just want to give you the sort of ingredients here. You, the designer, you first have to define your generative process. That's X. That's the true hidden states. I should have maybe said X star. Yeah, X star would have been a better notion. Then you will generate the observations. This is some transformation of the X's. You can add noise to it. You can transform it the way you want, but that's going to be the observations that's going to hit the Markov blanket. These are what this is basically where the sensory state observes and receives those sensations. You have to define your generative model. This part is the tricky part, right? The F's and G's in your dynamical system, that's where everything gets really tricky. How would you define them? If it's hierarchical, how many layers should it have, basically? These are the big questions. You have to define the evaluation metric, that how would you define different generative models with each other. And then you have to design the online state inference loop. Now, this is, by the way, just for this case, for this presentation, it's just about state inference. And then you have to compare different generative models. This is where Bayesian model comparison comes into play. Now, here, you basically use a dynamical system. Here, I'm just using a Lotka-Volterra process that captures the dynamics between a hunter and the prey together. It's a two-dimensional sort of world, if you will. So by solving the trajectories, by solving the differential equations, you get to this sort of trajectory. So you have 1,000 data points here, each of which is two-dimensional. So this is the unknown states of the world, right? This is the unknown dynamics of the world generative process. Again, it's unknown, it's beyond the Markov blanket. Again, so this is the figure that we saw before. Now you can assume that you got the brain here and you've got the generative process, X star on the left-hand side. The observations Y are basically a noisy version of the same hidden states that you notice that this is really noisy here, right? So the brain has to receive that and then infer the true states here, right? So for a one-layer predictive coding network for these particular experiments, you have just a simple sort of generative model. So it's just one layer. And then I'm sort of comparing two generative models here where the flow of the state dynamics are different. On the left-hand side, you have something that we call it's just a pullback attractor. We have this 2x2 matrix here, and we have this sort of point of attraction, which assumes that everything collapses into this world. Just to be clear, it means that my generative model of the world assumes that the world beyond the Markov blanket is attracted to a particular center called psi. right? That's what I mean by believing something about the world. Whereas the second flow, the second generative model, is a sinusoidal sort of belief. It means that I believe there is something periodic about the world beyond my Markov blanket. And the G's, I just kept them as identity, which means that whatever new is going to be my prediction about my sensation, right? So I kept the G's identical. Now, the evaluation metric, this is very important. As the inference is happening online, for every observation, you have to make an inference and then predict the sensation, and then calculate the prediction error, and then eventually calculate your variational free energy. Because it's happening online, you can actually literally accumulate your free energy, variational free energy, across the entire inference period. So at the end, you will end up with one scalar value. It's called the time integral of your variational free energy. They call it free action, right? It's just a fancy way of summing up variational free energy across the entire inference period. Basically, it's time integral. And it is, interestingly, it's an upper bound to the accumulated surprise. So variational free energy is an upper bound to surprise, and free action is an upper bound to the accumulated surprise, because free action is in and out itself an accumulation of variational free energy. And this is, you have to also then define the online state inference loop. I don't want to go into too much detail here, but basically for each observation, you will make predictions and you calculate prediction errors. You calculate your free energy. You calculate the gradient of free energy with respect to your estimations of the posterior. That's the key part. And then this is where you have to update your beliefs about the world. And you notice that it's a differential equation, because the way you're going to update your belief about the world, it's continuous. It happens in continuous time. It means between each two observations, yi and yi plus 1, I have to integrate over this update rule to move from my previous belief about the world, mu x, to a new mu x at the next time step. And that's why the integration happens here. And just so you know, this equation is basically saying that the amount by which I'm going to change my belief about the world, mu x, is, first of all, the gradient of free energy with respect to mu x, right? That's typical gradient descent. But the second term, it serves as a momentum. It means that if I'm going to update my belief about where the world is, I'm going to consider the velocity of the world as well, right? If I'm going to estimate the velocity of the world, I'm going to consider the acceleration of the world as well. It's similar to the idea of momentum in optimization algorithms. This is the bit that helps you catch up with the chasing target that is the world that I talked about in the beginning. And then you integrate this differential equation to update your belief about the world. And then the next observation happens. So this continues for all the observations, and you're accumulating your free energy as time goes by. And the result will be your free action. So the result is this. So this is the first generative model with the pullback attractor. So this is the inferred state, right? And this is interesting. This is the accumulated free action, right? Very, very interesting. You notice that free action is having these regular jumps. It means periodically I'm getting surprised about my sensations. Remember that if you note here, this is where these nonlinearities happen. It means that my simple pullback attractor fails to capture those dynamics. So it gets surprised. But interestingly, where things are linear and simple, I'm not getting much surprise. So it's almost constant here. So I'm good at capturing simple dynamics, but not the ones that are highly nonlinear. Whereas the sinusoidal one, you notice that we are capturing the magnitudes much better. We have a steady increase in free action. We don't get surprise for some dynamics and less surprise for other dynamics. We are always equally surprised for everything, which is interesting that here, we are getting surprised consistently for everything, but here we are not getting much surprise for these particular dynamics. So one is good in capturing nonlinear dynamics, periodic dynamics. The other one is better in capturing simpler linear dynamics, which is interesting. And notice that the reaction here is much lower than the free action here. So basically, this means that this model is much better. Now, looking at the generative power of these GMs. So this is the G function, if you remember, G of X and mu. That's the prediction of your one-layer predictive coding network about the sensation. That's the bit that gets compared with the true sensation, and the prediction error is calculated. Remember that observations, just like hidden states, are two-dimensional. So this is the first dimension of Y, the true sensation, and Y had the predicted sensation. You notice that they're almost close, and also with the second dimension, it's not doing a bad job, right? But for the second generative model, again, it's doing a much better job in capturing the magnitudes of this of the system. Again, you'll notice that it's not so good in generating these bits, whereas the first model is better in generating more accurate predictions of the first side. Now, these are the results: the pullback attractor and trigonometric, the sinusoidal sort of flow. You notice that the free action of the second model is lower, it's better. And MSE loss, which basically compares the estimated X and the true X, the inferred X and true X together, is also slightly lower. So free action shows that the second model is good. And this is where Bayesian model comparison comes into play, where we use Bayes factor for comparison. It basically says that we take the model evidence for each one of the models and we divide them. Now, because these are intractable, we're using free action as a proxy. And when you put the values of free action, you get to this value. Because it's higher than 1, it basically means that you have to pick the second model because it has a lower free action. It doesn't get as surprised as the first one. And at some point of caution, free action versus MSE. MSE, as a measure of accuracy, should never, and I repeat, never be consulted on its own because it ignores complexity. So, for example, what if the free action of model 1 and model 2, the model 1 had a lower free action, but what if the MSE of the first model was actually higher than the second model? Which one would you choose? Again, you have to choose model 1 because this has higher power of generalizability to the unseen data. So it has less chances of overfitting to the data. Recall that free action, again, is complexity minus accuracy. So what if we remove complexity? Again, we will overfit. So that was important. Some final thoughts. You can definitely learn the parameters and also estimate uncertainty about the world. So these are the things that are not covered in this presentation, but you can do that. This is where the separation of time scales will come into play. The DEM algorithm does exactly that. This is dynamic expectation maximization. I encourage you guys to take a look at that algorithm. Using that, you can solve the triple estimation problem. Now, can I go beyond X dot? Yes, you can. That's where you jump into the world of the generalized coordinates of motion, where you're not only using estimating X dot, but you're also estimating higher temporal derivatives of the world. You have a system of coupled differential equations rather than having just two equations, which is very, very interesting, actually. Also, remember that active inference is not the same as predictive coding, particularly in the philosophy communities. I've heard that people use active inference when they're talking about predictive coding. Remember that in predictive coding, we are simply doing making sense of the world. There's no concept of planning or action in play. The ML community, unfortunately, does not work with the dynamics of the world, and AI basically is going to the opposite direction. Instead of using smart data, we are just going bigger and bigger data. So we would like a world that ChatGPT would also ask you a question and becomes curious about you to receive information that it selects, basically. So where should you start with the free energy principle? These are the resources that I strongly recommend you. Some videos on YouTube. Hopefully you can later on pause this video and go through these links. Some papers that I'm recommending here. And the last one, the two books that I believe, the red one, the Predictive Mind, is for philosophy community. And the first one goes through the math extensively. It's a beautiful book. Yeah, and the videos, I recommend that you guys start with the videos in the first place. And I would like to just acknowledge our funding from the Marie Curie and also my colleagues, Simon Urbas and Professor Friston. and also acknowledge the folks at UCL, UCD, and Monash University who have always supported our work. And here's the link to the code that everybody can just take a look and run. The README file is self-explanatory. Unfortunately, I ran out of time and I won't be able to show a demo. But yeah, that's it. So
thank you, Mehran.
thank you.
That was great. And we have 10 minutes if you want to show anything, or I can ask some questions, but we have till 5 minutes after if you want to show anything, or even just scanning the repo could be cool.
Okay, sure. That's great. Thank you for that.
But just wanted to comment, your educational materials and the YouTube channel are great, and they're an excellent supplement to the textbook and to the math learning.
I appreciate that. Yes, absolutely. I also have a YouTube channel, ML Don. Feel free to take a look. I'm actually reading the Active Inference book on that channel, so hopefully it would be of interest to you guys. And this is the repository that is publicly available. The README file is pretty self-explanatory, and this is just a one-layer predictive coding network for the task of inference and modeling human perception as a task of inference. These are the same plots that you've seen. So basically, all the functions are here. Right? Everything you need is here. So the main function is the one that you're going to be dealing with. And this YAML file is where you actually choose the parameters of your experiment. Just to show you in action what it looks like. So if you actually clone this repository on your machine, you just have to go to the YAML file and just do a quick scan of the README file. But basically, this is where you define your generative process. For example, you can say, I want it to be a Lotka-Volterra process. And this is how I'm going to be picking the DT and the total time to actually solve the trajectories of my generative process. You can define your generative model here. You can define the dynamics to be like a pullback attractor or a trigonometric one. The likelihood, for example, is identity here. These are the dimensions of your X and Y, 2 and 1. You might wonder why it's 2 for X. It's because you have X and X dot together, where the world is and how fast the world is changing. And this is just Y in your generative model. You can increase them. That's where you jump into the world of generalized coordinates of motion, but this is beyond the scope of my talk today. Again, these bits are beyond the scope of our talk today. This is where you basically talk about the correlation between the noise process across different levels of the generalized coordinates. So the noise on the velocity, how does it correlate with the noise process on the acceleration, your belief about the acceleration of the world? So how do they interact with one another? That's where these values come into play. And then this is the kind of noise that you will use to alter the true states of the world and generate your observations. For example, you can use a colored noise here. You define the mean and basically the standard deviation of noise. And we're using the sort of kernel here that convolves with the white noise to actually generate a more smooth noise. The reason being that the biological systems are believed to be working with, so all the signals that you work with in biological and organic systems are believed to have been generated by some sort of dynamics. That's why we keep them as smooth noises, infinitely differentiable noises, rather than just white noise. And if you actually run this, so this is basically a pullback attractor. This is the first sort of generative model that we worked in. So you just run this main function. So we have 1,000 observations, noisy observations, right? And immediately this happens. So for every 10 observations, we are accumulating free action. You notice that free action is ever increasing because it just accumulates free energy. And on the right-hand side, you have VFE, or variational free energy. Again, if you look at the definitions inside the functions folder of how we calculate or compute the variational free energy, you notice that it's a far more simplified version of what you would see about free energies, because everything is under Laplace approximation. And you end up with far more simpler terms. And the final result is free action is this much, and basically your final MSE loss is 0.53. And if you want to see the final output, you just have to go into the results folder. And these are the folders that are generated, just so that you have 2 dimensions in X, 1 dimension in Y. Lotka-Volterra is a generative process. For example, the generative model follows a pullback attractor scheme, and then your G is just identity. This is your free action, and then that is your MSE loss. And if you open it, all the plots that I showed you in the presentation are saved as PDF here, just to give you an idea. Like, this is your X, this is your true invisible states of the world, right? And if you want to look at X hat, this is the inferred states of the world. And these are, for example, the noisy observations of the world. Yeah. So I hope that the repository would be of help and of interest to all of you. Thank you very much.
Great. What kinds of problems or settings do you feel that this could be adapted to or useful for?
I would say, first foremost, this could be used for basically it's all about any kind of problem that's about inference. You have some noisy observations that you want to infer the hidden state, but in terms of adaptability, you can build on that by introducing parameter learning as well as uncertainty estimation. So our goal is to develop this into a triple estimation sort of package, predictive coding network, and add more layers to it. So to have a hierarchical predictive coding capable of solving the triple estimation problem. Yeah, that's the ultimate thing that you can actually adapt this to.
Cool. What are you excited about for ML Dawn or for your learning or research in next year?
I'm very much excited in embedding these kinds of calculations into the world of AI, because as I said, AI is moving, in my opinion, in my humble opinion, is moving towards a wrong direction. Instead of bombarding models with all sorts of data, the model should be able to choose its data. So I'm very excited in developing this framework into a hierarchical predictive coding network, and then sort of compare the performance of such a model with other traditional AI-based generative models and basically show its superiority that I believe it has in different scenarios. And ultimately, this model is going to be used for, in my grant proposal, and a project I'm working on, is going to be used for modeling hallucinations as a kind of false inference about the world. And it's going to be used as a proxy for us to understand what happens in neuropsychiatric disorders when people actually suffer from hallucinations in the brain. So this predictive coding network is going to be a brain-inspired AI model for us to understand what goes wrong in the skull of a human being when they suffer from hallucinations about the world. So that's what I'm really, really excited about and really hoping to achieve.
Cool. It's like inspired by the brain, for the brain.
Absolutely.
Thank you, Mehran. Great presentation, and good luck with the continuation of the work.
Appreciate it. Thank you for having me.
Okay, till next time. Hello, we're back, and with Dmitry Bagaev and the RxInfer developers and community. So thank you for letting us peek and join into your meeting. Really appreciative for all the collaboration and learning that we've had with RxInfer this year, and looking forward to your updates.
Thanks for having us. Yes, so yeah, usually we have update meetings about the developments for RxInfer. But since we have now ActiveInference Symposium and we also have new PhD students in our lab, I decided to make it a bit special. And today I will briefly introduce RxInfer again for people who are not familiar maybe with it, and then we will discuss actual recent developments of it. And it's just basically an open discussion, right? You can stop me at any moment with some questions. I unfortunately don't see YouTube, so if there are some questions on YouTube, just stop me and we'll discuss. So RxInfer is a library for scalable probabilistic programming, right? But what is a probabilistic programming by itself? And let's imagine we want to build an agent, like a drone, right? And we want to build a program for it and write some code. And usually what we do is we take some data and we feed it into our algorithm and we get the result. For example, we find the path, right? But in reality, it's much more complicated because we don't really have precise data, precise measurements of our sensors, or maybe we have some wind outside, so our formula is not really correct in these conditions. And basically, we don't have exact values, but we have some uncertainty around our parameters and how do we actually compute the result given the uncertainty around the parameters. That's the first question. But more interesting question is actually the backward question. So given the observations of our path for our agent, what were the conditions under which it has been operated, right? And usually it's circling around some uncertainties. And in the context of active inference, we can go even further. So we can say, okay, given the desired observations, like given what we want to see, what actions we actually should take, given that we don't also know the conditions under which we operate. So this is what essentially probabilistic programming is about. And it's very challenging, but good news is that we have the solution for it. We already have it. We know how to solve it. And this is the formula that solves everything, essentially. And this is the Bayes rule. And it looks pretty simple, right? It's just like one multiplication, one, not a big deal. But it turns out that, so this formula is really, really challenging. Is extremely challenging to apply in real situations. And why is that? Well, okay, I can demonstrate why. So if we have a simple program with not a lot of parameters, this formula indeed is quite simple. So you can actually solve it on a piece of paper and you will get the exact result and it's all fine. But in real situations, we actually have much more parameters, and this formula, it explodes pretty quickly. And as soon as you add more parameters to your model, you realize that it's no longer feasible to solve it on a piece of paper. Actually, you need to write like an entire article about how to solve it for like some specific case. But we want even more, right? So we want to not just have parameters, but we want to have some constraints in our system, like, for example, physical constraints, like maybe we have an engine power constraint and like we have some trees around in the environment. So when we deal with such a complex system, the math behind is just, you cannot even comprehend it at this point, right? And actually, in my opinion, this is a very big problem in so active inference community in general, is that math is pretty difficult to read and to double check and to implement, right? So usually in articles we have a lot of formulas and they work in theory, but as soon as we start implementing it, we make mistakes. Our programs, they have bugs, and then it just takes a lot of time to iterate through that. But ideally, we don't even want to think about it, right? We want to design an agent, and all of this math under the hood is known. So this base. And what we want to do is we want to have as many components as we want. We want to press a button, and we want to compile all this math. We want to test it works and just deploy it, right? And it should result in a robust systems that makes reasonable actions under uncertainty and unpredictable environments. And if you think that's too much to ask, I would actually draw an analogy with just the regular programming. So we're now talking about probabilistic programming, but regular programming also started or has the same path. So in the beginning, like a bunch of high-level professionals, PhDs, they were designing the very, very first algorithms, and it was error-prone. They spent months designing a very simple program, spent months designing a computer, but nowadays, every student or even in schools, you can just download Python and write simple programs. You don't need to think about how computers work to do. You just express your ideas in some sort of a high-level programming language, and compiler does the heavy lifting for you. So essentially, what we want to achieve here is to have a language for solving probabilistic programming, right? And you don't have to think about math. You only want to think about your application. You want to design your drone, or maybe it's a vacuum cleaner, or maybe something even more complex. Any questions so far? Maybe from YouTube?
Not yet. Thank you, though.
Okay. So, so this is kind of the set, right? But how do we approach it? How can we approach it? And in a sense, there are a lot of similar projects in various programming languages as well, and they try to solve the same problem in a slightly different ways, right? So, and given that even on this slide, there are like 8 solutions, but in reality, there are more. Why do we need a new one? Why did we decide to write RxInfer where there are so many solutions already developing? Well, the idea here is that for autonomous agents, we have a pretty unique set of requirements. So if we want to operate in real world, we want to have a very big program, because a program of a real world is quite complicated, has a lot of parameters, so it should scale. It also should be low power, because our autonomous agents, they usually operate on battery, and you don't really want to have an empty battery soon, right? So it should preserve energy in the most efficient way. It should be able to adapt to changes in the environment, because the real environment is chaotic. It may change. Maybe you didn't account for something in your model, so you should be able to change the model on the fly. Should work in real time. Should be as efficient as possible in terms of performance, and it also must be robust. So we basically are not allowed to stop our computation. It should run and should react to circumstances. And this is what RxInfer is essentially about and what it tries to achieve. And in order to achieve this, it combines these 3 main ideas. also in the literature, right? Factor graphs, variational inference, and reactive message passing. So these are the three key elements. And we basically try to understand here if we combine them, can we have these properties that I mentioned? And so to talk a little bit about each of them, so a factor graph is essentially a graph representation of a probabilistic model. And a good thing about factor graphs is that they are explainable and they are not a black box, right? So we can clearly see the structure of the model and dependencies between different parameters or hidden states, and also observations. And it's also modular, local. We can reuse certain pieces, and we can write specialized computations for certain pieces. So in RxInfer, we have a special language to write such programs. So I have this add model macro that takes the textual description of a probabilistic model and basically creates a factor graph under the hood. So a user should not create those graphs by hand, and then this is automated. And we can also create like submodels, and we can reuse them in a bigger context. And as I mentioned, we can, for example, do some local optimizations in our model because we clearly know the structure of it. So variational inference, I assume that most of you may be familiar, but for those of you who are not, that's basically an optimization procedure that approximates Bayes rule. So Bayes rule in many situations is very challenging to solve directly. So variational inference is a very clever technique to trade off accuracy and maybe solve the task a bit easier at the cost of accuracy. Yeah, and also it's faster because you don't have to solve the original problem exactly. So the formula actually looks a bit more complex than Bayes rule itself. But yeah, the math is sometimes strange, and in practice, it's actually easier to solve this problem than the original math. So instead of solving the Bayes rule directly, we approximate the result with a simpler set of distributions from exponential families, for example, which makes it simple. And we have also language for constraints for the variational inference, right? So sometimes we want to make a mean field over our hidden states, and maybe for some specific states we want to be a Gaussian. So a user also can specify different constraints for the inference procedure. And the last thing in our recipe is reactive message passing, which is a central part of the project. So, each message carries a small piece of information required to solve this very complex math behind the inference procedure. Essentially, in traditional message passing algorithms, they require fixed global shuttle, which has a lot of downsides. And in RxInfer, we allow messages to flow asynchronously, and each node in the graph simply reacts on changes in the neighborhood and recomputes the result locally. And it's more robust because if part of the system doesn't work, we simply stop reacting it. But also, it in principle supports variable update rates for different variables. For example, audio signals, they may update at a higher rate than video signals. Do we have any questions so far?
Yeah, I can ask one now, and you could go for it or address it later. Arun asked, what has been the biggest... Yeah, Arun asked, what has been the biggest challenge building RxInfer so far?
That's a very good question. So the biggest challenge, I may say that as I mentioned already, the math behind all of it is quite complex. but the implementation side is also complex. So in order to build such a system, you need an expertise in both. You need to understand both math and high-level programming to make it efficient. So the combination of both of these elements is, I would say, unique. And without understanding one or another, it's basically impossible to build such a system. Any other questions? Okay. Okay. So basically, to write a probabilistic program, we need to specify our model or a program, if you would like. We need to specify our variational distribution, and we also need to specify how do we compute posteriors. So we can define models in our package. We can define variational distributions. And for the minimization, we use free energy minimization, variational free energy minimization with just a single call to infer function that combines both model and constraints and runs the algorithm. And it supports both static data sets, but as I mentioned, the whole idea about RxInfer is reactivity, and it also accepts reactive streams of data sets from external sources. And this is basically, we believe that these three key elements, they do have properties which I mentioned earlier, and they do allow us to implement all of those. And RxInfer, is free. It's available on GitHub. We have a website. We have a documentation. We also presented at various conferences and also on YouTube. So yeah, we invite you to check it out essentially and see what it can do for you. So if you have any other questions right now, we can no, because we just had the questions. But again, free to stop me at any moment. Feel free. So okay, but the question is, does it actually work? So I had this example of the drone. And basically, if we want to implement the drone in RxInfer, we define the dynamics of the drone, how, for example, different parameters should influence its position and velocity and speed. And then we define a model in RxInfer. And then basically, we create an environment for it and see how the drone would infer the action given its current state and the goal. Right, so in this experiment, our drone is instructed to fly to the red dot, and it actively tries to infer its current position and the trajectory that it needs to take to reach the goal. And also on the bottom side of the screen, you see that we change the parameters of the world and also the parameters of the drone reactively, and the system still operates. And actually, to be honest, it was much more difficult to create the environment for this drone than the drone itself. So RxInfer simplified this task, but the environment was still a challenge. But for that, we also work on a solution, which is called Rx Environments, which essentially would also hide all of this complexity of building environments for different agents. And we have a set of other examples, both for static data sets or reactive data sets. Just feel free to check out our documentation. And we have reproduced many interesting Bayesian inference tasks with a good performance and scalability. So, and we are obviously not solving all problems in this world, but the set of possibilities is really. Other questions?
Yeah, I'll ask a few from the chat. So Discovery Block wrote, for the drone, would RxInfer be able to manage actual image input to infer the position or velocity of the drone instead of assuming the observation corresponds to real values with random error?
Okay, it's a good question. Not out of the box. It depends on your model. So in principle, it's possible to design a model that would process images, but we didn't try that. So, but RxInfer by itself is indifferent on the input, right? So the problem with images as input is that they're pretty high dimensional. And since RxInfer works on distributions, this image must be processed as a distribution. So this might be quite challenging in practice.
But that's a direction to go with the composition of these systems. So the drone kernel could be designed with an app model taking in beliefs about position or about other features, and then hypothetically, like an RxInfer or alternative approach to image processing could be brought in and concatenated and used, and then the kernel belief would remain the same.
Exactly. Yes, you are correct.
Okay, and one more question from Fraser. What is the largest remaining theoretical difficulty with this approach? Real-time inference, universal inference?
Okay, it's a good question. So the limitations, we will talk actually a little bit about it in the current developments, but I can already hint that indeed universal inference is quite difficult because in order to execute the inference procedure, we need to compute messages. And we can compute them in many situations, but in many situations it is still way too challenging. And we are actively working on that. But yeah, message computation is one of the main challenging components still.
Awesome. And one last question. Bert and Arun both asked, have you considered hierarchical or nested models or any of the renormalization type models we've been exploring?
Great question. Yes, we did. And actually, last year, we re-implemented completely the language that we use for models to support hierarchical models. And this is one of the directions that we are approaching currently in Vice Lab as well, to support more complex hierarchical models and also recent developments in active inference literature. Yes. Questions?
No, not online.
Okay. Yeah, these are good questions, but yeah, we can continue. So what about our current developments? I will talk about two, and then I will give a stage to Wouter. So we have an external collaboration with ActiveInference.institute about graph visualization that take the textual description of the model and actually display the graph. So we have a data structure for the graph, but we don't have a function that would create a nice PNG out of it, like a picture. And we have an ongoing project for the universal inference, essentially, to support more models. So for graph visualization, as I mentioned, it's an external collaboration, and it goes really well. So we have an open pull request. And for example, for this simple model, for a simple point toss model, I can generate this nice graph that will show the dependencies between variables in this model. And I can also generate more complex models or graphs for more complex structures. And we have also Fraser and Chris joined our meeting. So if you, Fraser or Chris, you want to talk something here, you can do that, basically.
Yeah, can everyone hear me? Is this coming through?
Yes, we can hear.
Yeah.
Yeah, just really quickly. So I'm Fraser. I'm the guy in the top right bubble there. So along with Chris and Kobus Esterhuizen, we have a project effectively at the Active Inference Institute, as Dmitry said, in collaboration with the Bias Lab, to visualize these models, to be able to get some handle on what they look like, and ultimately to be able to even debug where certain messages are and where issues are with respect to actual message computations. There's a page essentially at the I could show where this is, but there's a publicly available page where you can kind of see our progress, track what's happening, and even reach out to join us and collaborate where you will. So it's very much open for collaborators and participation. Absolutely. Chris, is there anything you'd like to say?
Nope, I think you covered it all. Thank you.
Excellent. Back to you, Dmitry.
Thank you, Chris. Or if you don't want to add anything, we can just continue.
Please continue.
Okay, that's great. Thanks. And thanks for your effort, by the way. This is a really cool stuff. So I was playing with it to prepare for the presentation, and it essentially just works. Yeah. So there are some. I suggested some improvement, but yeah, I think it's all good, even in the current stage. And also, for example, other probabilistic programming libraries in Python, for example, they do similar approach in their modeling and also display, how they display models. Okay, so so the next thing that I want to talk about is universal inference, essentially, and we already had a question about it. So suppose we have this model that essentially tells us that we have observations Y that are coming from a Gaussian, and the mean of this Gaussian is modeled as a beta distribution. And why beta is because the variable that is modeled as a beta distribution is constrained to be from 0 to 1. So basically, I say here that my observations are constrained from 0 to 1. And I also say that the precision of my observations is an exponent of R, and R is also from 0 to 1. So it's a pretty simple model at a glance. But the reality is that this is an extremely challenging model for message passing, because the messages that are that we need to compute are not easy to compute. And the problem is that the result of those computation is essentially a bad distribution. So it has a very strange form that is not parametric or cannot be easily described as a parametric distribution. So we can also always describe those distributions as a set of samples, but drawing a set of samples is costly. And is essentially very difficult to make it real time. So the idea here is that, okay, we want a nice distribution, usually parametric, and it's usually from exponential family. And the question is here, okay, how to find this best approximation? And essentially, RxInfer supports algorithms or approximations that would allow you to specify how you would like to find those approximations. And one of the recent algorithms is projections. So this is a very, very new feature. So what we can do is we can specify or instruct RxInfer to use the projection algorithm to beta or to other distributions from exponential family. And it also works around deterministic nodes or just for individual variables. And if we combine these specifications, so it's a little bit more complex than the original example, but given this specification, we can solve inference in this model. And the result is pretty good. So here I just display generated some data set, and I tried to infer the parameters back. So as I mentioned in the very, very beginning, we have a set of observations, and we want to know the parameters with which those observations were generated. And you can see that the inferred or projected distributions, they are extremely close to the ones that I used to actually generate the dataset. And it scales pretty well comparing to other probabilistic programming libraries. So here on the left side, bottom left side, nuts, which uses sampling, and it takes up to 3 times more real execution time to do this task. And on the bottom part, we have automatic differentiation variational inference algorithm, which is faster. But we basically, because it's a new feature, we still try to improve the performance, and the performance is not ideal at the moment. And we already know how to improve it essentially. We have a PhD student that works on this project, and it goes really well. And like around a week ago, we had yet a better performance, which is not reflected on this slide, but since it's like just last week, we didn't have really time to investigate it properly. Any questions so far?
What is NUTS stands for?
Huh?
NUTS, what does that stand?
NUTS, it's something like no U-turn sampler, and U-turn is a term that they use to describe their algorithm. It stands for no U-turn sampler. It's practically, as far as I understand, one of the best samplers right now to draw from an unnormalized distribution. And those timings, by the way, we implement RxInfer in July, and those timings are from a different probabilistic programming library also written in July. So these timings are from Turing. Okay, so we had already a question about generalized inference in grid models, and here I will give a stage to Wouter.
Hello, everyone. My name is Wouter. I'm also a PhD student in Bias Lab, and I'm going to have a short discussion about generalized inference in discrete models. So in active inference, we really like to work with POMDPs, partially observable Markov decision processes. And the simple POMDP, or the vanilla POMDP, you can see on the slide. So I have a joint distribution over states, observation, and transition matrices. And we see that we have transition distributions both for the observation model and the state transition distribution. Can you click? So both this observation distribution and this transition distribution, they're both categorical transition distributions, but they're slightly different, right? Because the observation model just depends on one categorical distribution or categorical variable, only the state, whereas the transition model depends on both the state and the control. Right. So if we draw the factor graph representations of both these nodes, you can see that they're extremely similar, but they're slightly different. Now, if we want to go towards this generalized inference, there's 2 things we can do. The first is we just implement this new node, this 2 categoricals in, 1 categorical out, and we can just be done with it. And we could do control in discrete environments, but it wouldn't be very general. And since these transition distributions are very similar, their functional forms are very similar, the inference rules are also very similar. So what I'm investigating right now is how we can generalize this inference in these discrete models such that we can have an arbitrary number of categoricals coming in and transition to a categorical variable coming out. So this would give us general contingency tables or general discrete categorical transition distributions in RxInfer. There are some problems with this because this B matrix has a rank which is proportional to the amount of categorical interfaces. So For the observation model, we just have a transition matrix. But if we want to do discrete control, then we already have a transition tensor, which maps states and controls to new states. Currently in RxInfer, we only support these rank 1 or rank 2 Dirichlet distributions. So this is something that we're working on right now to generalize this inference. So what we are currently doing is together with Raphael, we are working to replace the rank 1, rank 2 matrix Dirichlet implementation in RxInfer with a general arbitrary rank tensor implementation. The working name for now is a multi-Dirichlet, but we're very much open to suggestions. I am currently deriving rules for this general transition node. So Thijs already in his dissertation has the rules for the rank 1 and rank 2 factors and matrices, and I generalize them to arbitrary rank tensors, and then I will make this new transition node which takes an arbitrary number of interfaces. So what can we do with this? With this we can do control in discrete models. So you can see on this slide that we have an agent which is navigating a maze, and this is the type of stuff that will be possible with the generalized inference in discrete models, because we will have categorical states coming in with categorical controls coming in, and a categorical state coming out of this. So we would be able to go towards building agents in discrete environments with discrete controls. So we can go ahead and solve OmniPs as soon as we're done with this.
Thanks, Zadeh. And here it is. Here's the entire presentation that I hope gives an idea of what RxInfer project is about and what we are currently trying to develop. And yeah, maybe we were a bit too fast, but we have plenty of time for discussions. Do I have more questions online, or?
Razor, if you want to ask your question directly.
Razor has one, but he's also in the comments. Yeah.
Yeah, just I was interested. I'm very, very interested. I did mathematics and computer science for my actual degree. Very interested in the mathematics of the generalized inference and node constraints and all of that. To what extent does message passing per se, the process of message passing, to what extent does that influence issues around non-conjugate inference? Is it effectively kind of only dependent on the content of the messages, or does the actual process of message passing have some kind of non-trivial effect on the resulting inference? I'm just curious about that.
So the problem with non-conjugate inference in message passing lies in the fact that in order to compute a message, we need to compute an integral. And in general, computing an integral is not possible on a computer. I'm talking about indefinite integrals that has no boundaries. So for an integral that has a boundary from like A to B, let's say you want to do an integral from A to B, you can, indeed decompose it into regions and then solve this integral numerically. But for unbounded integrals that take from -infinity to infinity, basically it is impossible, right? Because we have a finite memory on computers, and you can always create a counterexample where it doesn't work. And it's even worse in multidimensional spaces, so-called cursive dimensionality. So, and this is why people are coming with many clever methods to take those integrals via sampling. So sampling is essentially an algorithm to take an integral. So with non-conjugate inference, so let me phrase it the other way around. So with conjugate inference, those integrals, they can actually be simplified to an exact formula. So you don't really need to solve the original integral. You solve a much simpler problem because you can rearrange some terms and something just cancels out, and you get the exact answer. With non-conjugate inference, you cannot do that in general, so you need to actually solve this integral. And here's why you need those approximation methods like sampling or projection, which essentially try to solve this problem, but at the cost of accuracy, because we cannot afford infinite memory in our computer.
Awesome.
I see. So if I just try and it's effectively boils down to clever ways to compute integrals in ways that it's not going to take too long. Okay.
Exactly. And you also have to remember about dimensionality of your problem. So for example, as I mentioned, one of the recent developments that we just included in RxInfer would allow you to project a high-dimensional Gaussian distributions. Because before, so a Gaussian distribution can be described with its mean and with its covariance matrix. So which means that for high-dimensional Gaussian distribution, the covariance matrix is quite large, so it grows radically. And we recently added a simplified version of a Gaussian that doesn't store the entire covariance matrix, but only the diagonal of it, and only the same element on the entire diagonal. So the number of parameters is essentially linear to the dimensionality, and it scales much, much better, and it allows you to yet again solve bigger problems. In general, this is a quite difficult problem.
I'll ask a couple questions from live chat, if that's okay. Okay.
Sure.
Okay. Arun asked, is RxInfer being used in production right now?
We actually have been contacted in the past, yes, but I'm not aware of any company actively using it. We actually have a spin out from Technical University of Eindhoven that we founded a startup from BioSlab Group, which is called Lazy Dynamics, which the entire idea is to commercialize RxInfer, to make it a professional toolbox with really good support. I mean, it's always going to be free for research, but Lazy Dynamics will create nice tools around RxInfer to make process of creating models easier, making process of deploying those models easier, debugging models easier. But essentially, RxInfer is free, and perhaps someone is already using it in production, but we may not know it.
Cool. Great. Okay. Next question from Dean Tickles. He wrote, do your rules self-organize or do they remain constant? Does the rule recognize its own limits of applicability and adjust accordingly? I'm just wondering if these rules can morph into heuristics.
Sorry, you were glitching a bit. Can you repeat the question?
Yeah. Do your rules self-organize or do they remain constant? Does the rule recognize its own limits of applicability and adjust accordingly? I'm just wondering if these rules can morph into heuristics.
No, like message passing, if the question is about message passing update rules, they work independently. And this is also one of the main ideas of this approach, is to not have any sort of global variables. The graph is essentially each message is unaware of any other message or computations, such that we can run them asynchronously and do not have any sort of scheduling mechanism that would decide how the messages should be computed or how they should cooperate.
Awesome. Okay, next question from Bert. He wrote, is it possible to add a deep learning encoder and train it using messages?
Yeah, we actually have, I think we have an example in the documentation where we use a neural network. And we also use a normalizing flows inside RxInfer. So yeah, that's definitely possible. We also have an example where we use differential equations to infer parameters of differential equations. Maybe questions from UP students about the approach? No? Okay. That's good.
What do you all usually do in the meetings, or like how does it go, and how are you going to be taking things in the coming months?
Well, we usually just, we already discussed the recent developments and already showed that. We do exactly that. We go through the current developments and we try to see what we can do next. So maybe here, if someone in the chat would just post what, for example, they want to do, right? Like what kind of applications they try to solve with active inference, that would help us also to change our agenda, because we have some certain things in our agenda. So we want to continue with graph visualizations. So know that, for example, in the current version, we don't have constraints visualization, but constraints are pretty important for the inference. So this is the next step in our agenda, to also implement constraints visualization. We also have non-conjugate posterior computation in our agenda, generalized inference in our agenda. But for example, people can also comment on their uses, or they can also, for example, open RxInfer GitHub repository and open discussions, right? So maybe not right now. Maybe if someone watches this in the recording, or maybe someone who is online but still don't have a concrete example, you can always go to GitHub, open discussions, and just drop your ideas there, and we can discuss, and maybe we adjust our goals of the project together. And we are also looking for collaborators, right? So again, Fraser and Chris were super helpful, thanks. But if more people want to collaborate, it's an open project. You can always just join the organization on GitHub and drop your ideas and collaborate.
Awesome. Also, I wanted to highlight Cobus's examples at Learnable Loop, and also the documentation that you all maintain. And just looking back at our meeting notes from the beginning of the year, and looking at the version history of RxInfer, it's something really new. It's really been one of the highlights of the year, and seeing how it's all developing. And a coin toss, I mean, never has such a seemingly simple statistical situation been such an amazing learning opening. And it's just exciting to see how the examples start to flow in, and then those are useful for learning, and they're also useful for training code models. And the paradigm difference with RxInfer, which I think you very quickly move through with the app model declaration and reactive message passing, is really distinct from the script-like flow of essentially all other active implementations. So it's just really exciting to see. And also that this isn't just about action perception modeling. We also see in the examples more conventional statistical models. So that helps bring continuity between the joint distributional modeling of active inference and all of these more standard statistical problems.
I also noticed, because I stopped presenting, I have the chat on YouTube, and I see a question: what's the best way to get started with RxInfer? And I think the best way to get started is to go to the documentation that is to the page that is called Getting Started. Yeah, so basically, to start with the documentation that goes through the process of installing the library, writing first models, and then we have also a big collection of examples. As I already mentioned, maybe some of the applications you can already find here. We have also examples about active inference, but not only. So this global parameters optimization uses neural network under the hood. So with LSTM-driven dynamics, oh, something is broken. Like live stream issues. We need to open the issue back. But basically, yeah, this example uses Bayesian neural network to train parameters and then later on use it. And we have also external examples from Cobus. We have also a series of tutorials on RxInfer on YouTube from Dogo.jl. From theory point of view, I really like the book that is called Model-Based Machine Learning by John Wynne. So this is also a very good starting point. It also explains the concept of factor graphs, stochastic nodes, deterministic nodes, we run inference, but also it explains the concept of running inference essentially.
Yeah, I have a question actually.
Mm-hmm.
So the project of no-conjugate posterior computation,
Mm-hmm.
to me that sounds similar to variational inference. So how is that related?
So variational inference it's a very, very good question. So variational inference indeed reframes the original problem as an optimization problem, and you can solve it as a black box. Indeed, so you parameterize your distribution, you take gradients, and you do a simple optimization problem, and actually it does already solve many problems. But in RxInfer case, we actually do not treat models as black boxes. We decompose those computations in a series of smaller computations, which in a sense helps us because we don't need to run this big global optimization procedure. But in the result of this decomposition, so this individual computations messages, they still may be difficult. And this projection algorithm is indeed, sort of a variational inference, but at a smaller scale.
Okay. Yeah.
But what you maybe referred, I can also refer to this ADVI algorithm that I also showed in my slides, automatic differentiation variational inference, which takes the entire model as a black box that just differentiates through it, and it doesn't care about contribution.
Thank you for this. Any last short comments from any of the RxInfer team? Okay. Thank you again for letting us kind of wander into your lab meeting, and really looking forward to the collaborations that will continue. Okay.
Yeah, thank you again for inviting us, and we are looking forward.
All right. Till next time. Bye. Hello, we're back with Samuel Nerer, Jonathan Larson, and Peter Waade discussing ActiveInference.jl, staying with the Active Inference plus Julia theme. Thank you all for coming on and sharing this work. So, looking forward to it.
Hi, everyone. It is a pleasure to be here. So like Daniel said, we'll present on a new package for doing active inference simulations, but also for applying it to data in Julia. And we will leave time for questions at some moments during the presentation, and then some time in the end. Additionally, we're 3 people because we've been working on this together, so we'll alternate a little bit with the presenting. All right, let's rock. So first, it's nice just to mention who we are. So we're all at Old University. I'm a PhD candidate, and Sam and Jonathan are students who have been working on developing this package with me. And we all come from computational cognitive science. Specifically, it's called cognitive modeling, where you model behavior with computational models. And of course, within that, specifically predictive processing models, including active inference models, and that's why we made this package. And we use this in the context of computational psychiatry for clinical questions, and also more broadly for just modeling behavior. And this package is part of a somewhat larger process or project of developing software for these kinds of research questions in Julia. And I'll start with just giving a brush up on what cognitive modeling is in general. So some members of the audience might be familiar with this, but others might not. Just to set the stage for an introduction to active inference, you all have seen this before, so we'll go through it briefly, but it's nice to have this on our fingertips. Then we'll get to the meat of the matter, which is, of course, how to do this specifically in code with ActiveInference.jl, both simulating behavior and also fitting it to data. And finally, if there's time, we have some applications and some future work that we'll be happy to spend some time. We might skip that as well. All right, cognitive modeling or computational cognitive modeling comes out of psychology, cognitive science, where the main question in those fields is to find out what are the mental mechanisms that makes us do the things we do. And so the classic perception action loop we've depicted here, people will maybe be familiar with that too. It's from the R Active Inference book, where you have some agent, which could be a person, but it could actually also be an animal or even an organoid or even a simulated system that receives inputs from its environment and takes actions that changes its environment. And we are here interested in essentially, and I don't know if you can see my cursor, but essentially the relation between those observations and the actions that are created. So basically the part after the observation error ends and before the action error starts. And traditionally in psychology and in cognitive science, this has been done experimentally. So you take people out of natural situations and controlled laboratory situations where you measure, well, you control both of these. So you decide what they observe and you measure what they do. And so the kind of classical example of this is you have a computer screen, you show people some images, something, maybe you ask them to classify them or predict what's going to happen, and you measure what they do. And then you have a measurement of inputs and measurements of outputs. And you then create some theory that will make some prediction as to how they relate. And of course, this is a big field. You might have theories of personality types where you predict that actions will change faster depending on inputs. There's theories of reinforcement learning, etc. And so importantly here, we're using already natural science approaches, experimental approaches with quantitative analyses, but still with purely conceptual theories. So the theories are not formal as they often are in, let's say, physics, where you have mathematical theory. And the trick is often to go from some conceptual theory to a quantitative prediction that you can then test. And specifically, give me a moment here. Sorry about that. Specifically, as many people know, there's been what's called a replication crisis in psychology and cognitive science, where the whole issue is that the experiments don't replicate. And that's partly due to statistical methods issues, but also partly due to problems stemming from the fact that our theories are not clearly formulated. So one sentence that's saying that there is social learning might mean many different things. And so a recent attempt to address this is to move into formal theories, just like in physics. So computational models of this, again, relation between observations and action. And this is inspired by physics. So in physics, people are no strangers to having things they can observe. In our case, it's the behavior, but in physics, it can be, let's say, radiation from the sun, and then trying to make inference about something you can't observe. In our case, the mind, and in physics cases, perhaps the molecules or of the sun. And so the methodology is exactly the same. Create mathematical equations that will describe how actions evolve over time given observations in the environment, and test them on how well they describe empirically collected actions in observations. And here I just put on one of the very classic cognitive models, which is the Scholar Waade, where you have some very, very simple equations that describe how actions depend on the observations in the previous time step with some learning and a classic learning data. And that's just to say that many of the first cognitive models were very simple. In a few equations, you would kind of describe these relations. I think primarily in 3 fields is this approach used where you have some person or some system and you want to find formal models of its behavior. That's in computational psychiatry, where you want to use it to understand psychiatric conditions. Mathematical psychology, which traditionally has been broader. It's essentially the same questions, but a different community and different types of models used. But also broader, just behavior in general, not specifically psychiatry. And computational neuroscience, where you want to relate these models to, for example, neurobiological processes that could implement. And they also overlap with artificial intelligence and engineering and so on, which I'll touch. All right, so I think a primary use case, especially in our field of active inference, is theoretical simulations, where you just take some phenomenon, let's say learning, or let's say learned helplessness. You create a simulation that can do that, create that kind of behavior, and you suggest this as a proposed mechanism of how that behavior comes about. You can use this for one agent doing one type of behavior, or you can use it for many, and then you're doing agent-based models, specifically cognitive agent-based models, where you rely on actual cognitive theories to make them. But you can also apply it to behavioral data. And here you're often trying to either find out what mechanisms provide actually empirically observed data. You might want to distinguish, let's say, clinical populations from each other in what's called computational fingerprinting. You might also use results here to inform future theoretical simulations. So you can have ABMs where every agent has parameter values that you found in experiments. And you can also use this to design future experiments, where you use simulation to make sure that your experimental design will give you as good results as possible. And finally, you can also apply these approaches in machine learning and engineering. And here, of course, you can make robots that use cognitive models that people might also use, in the way that in general technology and our knowledge of biological systems have always worked with each other. And so in the same way you might be inspired in how to build a plane by looking at a bird, you might also be inspired in how to build an image recognizer by looking at a human being. Our packages specifically target the application to behavioral data. So they can do theoretical simulations and also in principle be used for engineering purposes, but we've optimized them for this situation where you have participants, you put them in an experiment, you get behavioral data, and you use those models to understand that data. And that's what distinguishes it from some of the other software tools that are present. So PyMDP now has this capability also, but otherwise many of the, and there is in the MATLAB SPM software also some ways to apply it to data. But otherwise the focus has often been on theoretical simulations or on machine learning. And if you look at packages like RxInfer, which is incredibly powerful and well made, that also, at least to my understanding, focuses more on the machine learning and engineering part, where the ultimate goal is to use these models to build tools that can do things, or maybe for simulations, but not to specifically apply to behavior. All right, and I'll just give a sense of what a workflow here looks like, because if you come from theoretical simulations or engineering, this might seem really foreign. To start off designing hypothesized models for how people work. You then check these models before applying them to anything, to whether they are worth applying. So you do what's called parameter recovery and model recovery, where you first simulate behavior with some parameters. You then estimate those parameters, and you see if you can actually estimate the real parameters. If you can't recover parameters that you know are true, you can't trust this in when applied to real data. And also prior and posterior predictive checks, where you just check that your model can actually generate the kind of data that you might see in an experiment. And if it can't, it's also not worth applying to behavioral data. Then you fit it to data, which means finding out what parameters of my model, what they must have been to generate the data that I did observe. So in classical models, there would be learning rates. We ask, oh, this person adapted this fast, so his learning rate must be this and this. In the context of active inference, it's usually parameters of the generative model, the A matrices and B matrices, for example, that we want to estimate. And finally, we can also estimate how well the model fits our given data. Because some models might describe some data better than others, we might want to use this to select them. We use this to relate parameter estimates to some measure that's across participants. Often this is clinical populations. We might say our learning rates or our A matrix parameters different between clinical populations, but it might also be relations to, let's say, age or psychopharmacological interventions, etc. We can also relate it to within participant things, let's say physiological correlates, and there could be eye, pupil dilation, etc. But the primary use case, of course, is neuroimaging, where you say, oh, according to my model, this participant now has a high prediction error. Do I see a difference in brain activity at this moment compared to when he has low prediction error? This is often to find out what the neurobiological implementation of the computations that we think people do. And finally, you might compare models and ask questions like, which of these hypothesized models are the ones that best describe the data, and therefore perhaps the actual mechanism here within people. And so you could compare an active inference and reinforcement learning model, or let's say two active inference models with different generative models inside. Finally, it's worth mentioning that fitting this to data, there are many different approaches. Broadly speaking, there are Bayesian and frequent system methods. They have different advantages and disadvantages. We usually use Bayesian approaches, and that's a long discussion of why that's nice. They propagate uncertainty, they're good when you don't have so much data. But I won't go into that, just to say that there are also other ways to fit models to data. And within Bayesian methods, because you can't do exact Bayes to fit them, there are also approximations. One classical approximation is variational methods, where you choose some arbitrary distribution, we call it Q, and you make it be as similar as possible to the true posterior belief about the optimal parameter estimate. You do this by minimizing a variational free energy. And as it happens, that's also what active inference agents use. Another in cognitive modeling widely used method is sampling approaches, like Markov chain Monte Carlo. There are also others, where essentially you try out many different parameter values, and for each of them you calculate the likelihood of that value. You do this in a smart way, but it still takes a long time, and you get a full estimate of the probabilities of different parameter values. They have different claims to being useful for different use cases. So sampling is good for parameter estimates, but they take a long time and they might not probably work. Variation based has some claims to being a better estimate of qualitative fit or model evidence. There's a whole field where people are still fighting, and if anyone's interested, we can take questions on that. But importantly, the tools we make here can do either of these two approaches. Finally, it's just worth mentioning that we as researchers use Bayesian methods to understand people's behavior, but within active inference, we also theorize that people use Bayesian methods to understand the world. It's nice to keep those separate. So we might use a sampling approximation to Bayesian inference to fit our models to data, but still believe that people use variational Bayes to understand their environment. And so in the following, when we talk about generative models, we're not talking about our model of people, we're talking about people's models of the world. And again, do ask questions in that. That's one of the tricky points sometimes when we're doing this, what's called meta-Bayesian modeling. Good. There are many paradigms within cognitive modeling. Mathematical psychology have many ways of modeling, often specific behavioral tasks. There are these old cognitive architecture models, ActR and SOAR are the biggest ones, where people are also trying to do unified models of behavior in general, which rely on very different assumptions than active inference. And often we're not aware of them. Perhaps we should be, so I'll just bring them up here. And they are kind of raw, old school computationalist models, different modules interacting. There's of course reinforcement learning models where you assume that people do actions, get rewards from their environment, and then try to find actions that maximize those rewards. There are many others like deep learning models, etc. But of course, today most relevantly, there are Bayesian mind models, where you think that people's minds use Bayesian inference of some sort to understand the environment. There are many schools of Bayesian mind models. You might look at Josh Tenenbaum for a different school than ours, but active inference specifically belongs to a variational Bayesian mind model, where we use variational approximate Bayesian inference as our model of how people work. And this has close ties to predictive coding and predictive processing. So broadly speaking, we might call this variational Bayesian predictive processing models. They can be just a perception, like hierarchical Gaussian filters or plenty of models out there, or they can include action as well. And when they include action, it's called active inference. So variational Bayesian predictive processing models of perception and action is active. And now we'll give an introduction to that. But we'll leave time for one question before we move on. Are there any questions?
Sure. I'll ask one. Maybe you'll revisit it later too. Arun asked, what's the biggest challenge you faced building this package?
That's a long and technical discussion. I think the main thing is that in Julia, there are many ways of doing what's called the auto differentiation, which is a technical thing that you need to do the parameter estimation. And there's just a whole ecosystem of packages doing that. And we've had to become very familiar with those to find the ones that work the best. And that's not an easy task. The part of the package is to hide that from the user so they don't have to engage with that. Yeah. I don't know if you agree with that. Perhaps.
Probably, yeah.
Yeah. We can revisit it in here. Okay.
All right. And one more question, just while we're paused. Yeah. Fraser asked, is there anything in ActiveInference.jl that is particularly suited to compositional agents or collectives? Kind of leading you into your paper, I know.
So I'll return to that in the end if we have time, but basically you can use the same method that we use to make inferences about a given human participant in an experiment. Instead of a human participant, you can use it on a simulated collective and treat that collective as if that is also doing some kind of cognition, or active inference at least, which is of course fundamental to active inference in general. We expect a cell to do active inference, but also a person and also a collective. And so if we treat a simulated collective as, let's say, a foreign system that's doing something we don't know what is, we can fit a model to that in exactly the same way we do to a person and make inferences about, let's say, the parameters of that simulated collective's generative model of the environment. And in the end, if we have time, I'll just show like the results from that paper where we do exactly this, just demonstrating a laboratory example. But that's an exciting question, obviously.
Yes.
All right.
All right. I will just briefly touch on the software ecosystem that we built the package in. So firstly, why Julia? It's fast and it's very intuitive, meaning that if you come from Python or MATLAB, you can carry a lot of the same intuitions over into Julia. And then it has a community that is growing quite fast of people doing data science, machine learning, and cognitive modeling, as we're doing. Then Julia is natively auto-differentiable, which means that you don't need to have a backend in another language to do auto-differentiation, which makes it very fast in Julia. For this, there's a very nice package called Turing.jl, which is just a package for probabilistic programming in general, and it can do both sampling methods such as MCMC or no U-turn sampler, and variational inference as well. Then in Julia, there's also a sister package to ActiveInference, which takes different kinds of cognitive models and make it very easy to fit data to those kind of models by kind of like wrapping Turing. And that's where kind of like our ActiveInference.jl package comes into play, as this is a cognitive model that through action models can be used to Turing to fit data quite easily, and we'll show this later in the presentation as well. Then we'll just briefly touch on some of the core elements of active inference with regards to perception, action, and learning. So for the perception part, this is the minimization of the quantity variational free energy, where we through this minimization, we can infer states optimally based on observations. And there's different kinds of variational inference, different kinds of algorithms that we can use to do this. I'll later go into the specific algorithm that we're using in this package. Then we have action in active inference, which is guided by the minimization of a quantity called expected free energy. And this can have a lot of different kind of expressions. If you look at the ones that we show here in the slide, we have one that's information gain versus pragmatic value, which is basically where you get the explore exploit behavior for free in active inference, which is really nice. And then we also use the expected free energy to calculate the posterior probability over policies, where policies are actions. So this is kind of like the quantity that we use to kind of like guide the action selection. We're also going to go into that a bit later. Then we have learning in active inference. This is specifically for categorical distribution beliefs. So there's other ways of learning for continuous cases. However, here we take it for categorical distributions. For this, we use Dirichlet priors over the generative model parameters. This is basically Dirichlets. They have concentration parameters that we can then add counts to, and this is the update equation that we show here, where we have an omega, which is the forgetting value times the current concentration parameter, and then you add the new here is the learning rate, and then you then add the chi, which is the data observed. And in this sense, you just add counts to the concentration parameters, and then through normalizing it, it becomes your new updated generative model parameter. And we will come back to how that's implemented in the package as well. And then a quick refresher on partially observable market decision processes. So we just want to make sure to say that this is one type of generative models in active inference. There's other types of generative models as well. And PMDPs, they're not active inference specific in the sense that you can also use it in other frameworks. And then this, what we have done in this package is a discrete state space implementation of PMDPs. You can have continued state space implementation of PMPD. PMPDs, the Markovian element of it, though, is that the time steps, they are discrete and not continuous. So we'll just briefly go over conceptually the different parameters in the PMDP. And for this, we have created sort of like this little toy environment to explain this. And if you can see this thing here, where you kind of like, if you imagine that it's a dial where we can spin it in different ways. And then the goal is to get state 3 on top in the little rectangle. So then you have 3 actions. You can spin it counterclockwise, clockwise, or you can just make it stay in place, which you would do if you have state 3 on top, for example. But we'll start with the observation state likelihood model. Basically, what this encodes is the agent's beliefs on how states generate observations. So it's a categorical distribution where each column has to sum up to 1. So in this state, in this case, as we have a identity matrix, this indicates that the agent can deterministically infer the state based on the observation. So if the agent observes observation 1, then it will infer that it is in state 1. And this can be more or less entropic, in the sense we could also have a completely uniform column where we just have 0.3, 0.3 for all of these, and then the agent wouldn't be able to infer the states based on the observation. All right, so this was the observation state likelihood model. Then we're going to go to the state transition likelihood model. And this is basically how the agent believes that the states change over time. So in this case, I've taken the example of doing it for the action of going counterclockwise, because this is usually dependent on actions. So here we see that, for example, if the agent is in state 1 and it does the action spin counterclockwise, then it believes that the next state it's going to be in is going to be state 2, and the same if it's in state 2, then it believes that it's going to be in state 3. So that's the state likelihood transition model. Then we have the prior preference. So this is basically where we kind of like get to encode kind of like the preferences or the goals of the agent. This can be done both over states and observations, but in our case, we have done it for observations, and this is the case in our package as well. So here, for example, for observation 1, we have encoded a dislike for this observation, which is coupled to the state 1. And then for observation 2, we have neither dislike nor preference. And then for observation 3, which is coupled to state 3, which is kind of like the goal that we want, we have set a preference. And this is important as this kind of encodes the pragmatic value, which is then part of the calculation of the expected free energy, as you can see here below. Yes, and that's the C parameters. Then we'll continue to the D parameters, which are basically just the agent's initial belief at time 1, which state is it going to be in. And here we just encode it to be certain that it's going to be in state 1. Then we have the prior over policies. He'll just quickly introduce the notion of policies, where policies are collections of actions that can have a specific length determined by the policy length, which is basically how long in the future, how many time steps in the future should the agent plan. So for this case, we only have one time step in the future, which is why we only have the 3 actions here. And this is also sometimes described as the agent's kind of habits, meaning that it has a preference for certain actions. In this case, we have given it a uniform distribution, meaning that the agent doesn't really have any preference over any policies. All right. So now that we have the generative model down, I'm going to show you how to implement this in our package. And we're going to do this by providing a worked example of a teammates environment where the agent is going to learn the reward probabilities in the arms. And for this, I'll just quickly have to introduce the notion of factors and modalities. So factors are basically different kinds of states. So in this case, it would be we have location states and we have reward condition states, where reward condition states are whether the left arm or the right arm is going to provide a reward. Then we have modalities. Modalities are basically different kinds of observations. So here we have a location observation, we have a reward observation, and we have a queue observation. And I'll go into these when we get to define them in the generative model. To start using our package, you can just add it from the Julia registry using the Julia package manager as shown here. Basically, for this code, you can run through it by yourself, and it should be able to run. Then we initialize the package, and we also import the environments module, which is important for the teammates environment that we're using as an example here. And then we initialize the teammates environment, and here we just set a 95% probability of providing reward in the reward condition arm. So now we can create the actual generative model, the PMDP generative model, and you can do this manually by yourself. But then you have to make sure that the generative model parameters are typed in the correct manner, which is shown here, where it have to be vectors of arrays for AB and vectors of vectors for C and D and vector of floats for E. It's very similar to object arrays in NumPy. However, we have created a helper function that makes this a lot easier. And so I'll just quickly go through the arguments that the helper function takes. So the first argument is the number of states in each factor. So remember, we had 2 factors. We had the location state factor and the reward condition factor, where we had in the location factor, we had 4 states. We had the sense, the queue location, and the 2 right arms, so that's 4. And then we have two reward condition states, reward condition right and reward condition left. So we take this as a vector and give it to this function as the first argument. Then the second argument is the number of observations in each modality. So we have three different modalities in this case, where we have 4 observations in the first modality, the location modality. We have the location sensor, Q, and the arms. Then we have the second modality, which is the reward modality. It has 3 observations. It has the observation of no reward, reward, and loss. Then we have the last observation modality, which is the Q observation modality. And these we also take as a vector and give to the function as a second argument. The third argument is a number of controls for each of these factors. So we have 2 factors, the location factor and the reward condition factor. We only want the agent to be able to control the location factor, so it can move freely between the locations, but in the reward condition state factor, it shouldn't be able to control what arm should be the reward arm. And so therefore we just give it a 1 in this case. Then we have the policy length, which I have described before. It's how many steps in the future does the agent plan. And then we have the fifth and last argument, which is the initial fill, which basically says like when we have made the structure of these generative model parameters, what should be the initial filling of these. And here it takes both, it takes zeros, which we have chosen in this instance, and it also takes the argument random, which is nice for testing, and uniform, which is the default in this case. Good. So now we just, having created this helper or these generative model parameters, we just need to fill them with the appropriate values. So we'll start out with the observation state likelihood model. And remember, this is the one that encodes the agent's beliefs of how states generates observations and then infers states based on the observations it receives. So in this case, we have the location observation, which is not as interesting to us. Basically, it's an identity matrix, meaning that the agent just infers the correct states because we have encoded it to do so. And then we have 2 matrices here because we have for each of the location states, which is 1 matrix, and then we have 2 matrices, 1 for each reward condition state factor. If you go to the second modality, which is the reward modality, this is the one that is interesting to us because if we look at the first column and the last column, this is the Q and sensor location. We see that it expects that these are going to provide the observation of no reward. However, for the second and third column, which are the right and left arms, we see that in the second row, that it has a 50% chance that it believes that this state is going to produce a reward observation. And then if we go to the third row, we see that it has a 50% chance of generating this, or the agent believes that there's a 50% chance of it generating this observation. So in this sense, the agent doesn't know which of the arms is going to provide the reward observation. And this is the modality that we want the agent to learn. We want it to approximate the actual reward probabilities in the teammates environment. Then we have the Q observation modality, which basically just tells the agent that only when it's in the Q location does it correctly get an observation that informs it on the reward condition state of the environment. And then we're going to add a prior over A, and this is where the learning part comes in. The prior over A is the Dirichlet distribution, and the way that we create this is basically just that we copy the structure of A, and then we add a scaling concentration parameter, which basically says that these counts in the Dirichlet distribution, if they are very high, like if we give a high scaling concentration parameter, each new data observation is not going to matter as much. If we set the scaling concentration parameter low, then each data observation we have is going to matter a bit more. And then it's important to say that, and this is a bit clunky, but this is now going to define the A matrix. So the prior over A is going to define the A matrix, meaning that the A matrix that we just made is not going to be exactly used. However, we used it as a template to create the prior over the A. Great. So now we have the observation state likelihood model. Now we need to encode the state transition likelihood model. And this is the matrices for the first factor, the location factor. And basically we just note here that we have rows that are filled with ones, meaning that from wherever the agent is for that action, it goes to that place that it wants to go to. And then we have the second factor, which is the uncontrollable one, which is the reward condition factor. And basically this identity matrix just tells the agent, or the agent believes that the reward condition state doesn't change over time, that it stays the same. Good. So now we come to an interesting parameter, which is the prior preference over observations. So we have a vector here for each of the modalities. However, the one that we are interested in is the reward observation. So in this case, the first index is the index of the observation no reward, and we set no preference or dislike for this. The second index is the observation of reward, which we set to have a preference for, that it wants the reward. And then we have the third index, which is the loss observation, which we set a dislike for. Yes. And then we continue to the D parameters, where we have a vector for each of the factors. We have the location factor, where we basically tell it that it's going to start. The first index is the center location, that we're just telling it that it's going to start in the center location. And then for the second factor, which is the reward condition factor, we just have a uniform distribution, meaning that the agent does not know what the reward condition is going to be. Good. Then we have the last of these parameters, which is the prior over policies. And we're just going to here provide it with a uniform prior. So this means that as the E parameters are the habits, it's not going to have any habits in this case. We see here that we have 16 different policies because we have a policy length of 2 and we have 4 actions. So the total number of combinations of these 2 actions is going to be 16. And then, as said, we just give it a uniform distribution over these policies. Good. So now we're almost ready to initialize the active inference agent. Before we do that, we have to specify some settings. And I'll just briefly go into these, what they do. The policy length we have talked about. The use utility basically means should we include the C parameter preferences that we just set, and we've set this to true. Then we have the use states info gain, which basically says that in the calculation of the expected free energies, which is going to guide action, should we include the expected information gain. And then we have the use parameter info gain setting, which basically says that when we calculate the expected free energy, should we include the expected learning or updating of the generative model. Then we have action selection, which can take 2 values, either stochastic or deterministic. I'll go into what they do when we come to the function that actually uses this setting. Then we have modalities to learn, which basically specifies what modality do we want the agent to learn. In our case, we wanted it to learn the reward observation modality, so we specify this by giving it 2. We also have factors to learn. This is only relevant when we're doing B and D matrix learning, so it's not going to be relevant in our case. Then we have the fixed point iteration, number of iterations, and the fixed point iteration tolerance, which is basically saying that when should the inference algorithm stop. So you can set it to either, as we do here, after 10 iterations, or when the difference between iterations are equal to or lower between this threshold. Yes. The last thing that we need to define to initialize the agent is the parameters here. I'll just briefly go over what they do. The gamma is an inverse temperature function on the expected free energies. Then we have the alpha, which is inverse temperature on the action selection. And then we have the learning and forgetting rates for the priors over A, B, and D parameters, which are the ones that we currently have learning for. The ones that we're interested in at the moment, though, is the prior over A, which is the learning rate and forgetting rate for this, which we're going to set to its default value of 1. And the values here are all the default values. Good. So now we can initialize our active inference agent by providing it with the generative model and the settings and these parameters. And we're almost ready for the perception and action loop in itself. Before we do that, we just have to specify how many iterations does this loop need to contain. And then we reset the T maze, which just gives the agent like an initial observation. And this is the perception action learning loop, and it has 5 functions, and I'm going to go through them and just briefly explain how they relate to active inference. So the infer states function is the one that actually does the minimization of the variational free action, the variational free energy. And this is the perception part of active inference. Here in our package, we use an algorithm called fixed point iteration, also known as coordinate ascent variational inference. And here we also just we provided a picture of an observation where you can see that we have these 3 observations: the location observation, reward observation, and the Q observation. Then we have the infer policies. This is the one that actually calculates the expected free energies, and it's affected by the settings that we talked about before, and the gamma and the E parameters. It returns the expected free energies, and it also returns the posterior over policies, which is, and it's this posterior probability that we are going to be sampling from when we are sampling actions. So basically this function sample action just samples from this posterior probability over policies, and it is affected by the action selection, where it could be either stochastic or deterministic. If it's stochastic, it just samples from the probability distribution, but if it's deterministic, it always takes the policy with the highest probability. Then we have the update A, which is where the learning occurs, and this is where we basically add the Dirichlet counts to the prior over A, and then it updates the A by normalizing the concentration parameters. Then we have the step T-maze, which is basically just the agent interacting with the environment, and then it provides the observation for the next iteration in the perception action learning loop. So this is the loop, and this is the one that is also going to be used in the model fitting part. And we are, I think we're taking some questions now. One question. Yes.
Okay, I'll ask one question from Tintin in the chat. They wrote, "Hello, thanks all for this great work. Have you implemented Bayesian model reduction or incremental model construction / structure learning with ActiveInference.jl rather than manual construction?"
We haven't.
No.
That's the
No.
short version.
Yeah.
So the package is just now ready for deployment. And there's many ways to extend it, which we'll work on, but also, I mean, if people are interested in collaboration, to develop the package, it will also be wonderful. So this is exciting for two reasons, like in two ways, by the way. Basically, model structure learning. It can either be model structure learning from the perspective of the agent, learning the structure of the environment, but it can also be model structure learning from the perspective of us as researchers wanting to find out what kind of structure a given agent has of the environment. And both of these purposes are something we would like to do. Yeah.
I think a useful kind of connective tissue question. Where would you put ActiveInference.jl in relationship to what PyMDP does in Python and what RxInfer does in Julia?
So PyMDP was originally a port of the SPM functions into Python. Brilliant work by CogNarr and colleagues, where they make it modular and easy to use, but made for theoretical simulations only. And I think this summer they just finished JAX re-implementation of PyMDP, which means now you can also use it to fit to behavioral data. But it's not designed, it wasn't primarily designed for that. And it was also not made for engineering purposes. Python is too slow, although I'm sure you could in principle. And since then has come the C++ package, right? Which is much faster, and I think, but harder to use because it's in C, although there are wrappers in different languages. That would be useful for machine learning. RxInfer implements active inference and many other things on Borneo style factor graph, which is a very efficient and powerful way of thinking Bayesian inference and variational Bayesian inference. And that is optimized much more for engineering purposes. So if you want to build something that does something using active inference, go C++ or RxInfer. And if you want to apply it to behavioral data, then go PyMDP or ActiveInference.jl. And there are some tools for this also in MATLAB. But I think our package and PyMDP are made to make this easier. And as you might notice, we use much of the syntax from PyMDP. So we're heavily inspired by that. And in the next part, you'll see how to use it to apply the package to behavioral data. Does that answer those questions?
Cool. Yeah, perfect. Definitely. The functions look great, and your team's understanding and clarity around the problem setup, taking that all the way through the helper functions for the major Cs, that's where so much of the friction is. So this makes it really clear. It's a great open source point.
It's also where a kind of future development would be also happening there. so the API can be improved for sure, and we will work on this also. Yeah, to make it, because I think one of the main challenges active inference has faced as a tool for cognitive modeling is that it's hard to use and hard to understand. And that's why much of the mathematical psychology world, for example, just leaves it. They say, we have a 2 or 3 equation model. Why would we use your beam of a monster machine instead? But just as it has been the case with many other methods, making tools that make it easy to use and conceptualizations that make it easy to understand is the kind of thing that will make these models feasible and therefore used more broadly.
Yeah, that's making me think like RxInfer is the car factory, this is the bike, and active inference is the wheel.
You can think of it, yeah. We need a logo. Yeah. Cool. All right, let's do the last important section and let's see how much time.
Okay, and because we're short on time, I will need to skip through a few of the sections, but I hope it's going to be all right. Okay, so I think Peter already mentioned that we have this sort of environment of packages in Julia, and one of them is action models, which is sort of a sister package for us, which mediates the data fitting process for us, right? So here we are essentially going in the opposite direction where our inputs and the actions of our, let's say, experimental subjects are known, but now we are interested in the hidden or latent parameters of the subjective generative model. So there's a sort of core component of action models is the action model function, which depending on our model can be an arbitrary function which takes a single input, which in our case is a single observation. It updates the states of the agent, and then it sort of quantifies the probabilities of actions. So we end up with a probability distribution from which we can sample our actions, right? And so in our case, we have this nice function called ActionPMDP, which is our active inference action model. And it takes these 2 arguments, which is our initialized AIF object with the parameters of the generative model, settings, etc. And it takes the single observation, and then it outputs the action distribution. So in this particular case, we have 2 action distributions, 1 per each state factor. Right, and then another core component of action models is an agent. So it sort of wraps our action model function and our active inference object in a more abstract structure, which we then will be using for fitting and for simulation as well. And then it also stores parameters, states, history, etc. Right, now I will just allow myself to skip through some of the convenience functions so I can just go straight to the data fitting, if that's all right. Okay, so this is I would assume the most interesting part of this. So how to actually fit active inference models to data. So all of our fitting functions kind of operate on Turing, and we wrap all of the necessary Turing operations in our convenience functions for fitting. So let's say, for example, we want to fit a single subject and we want to recover a single parameter, a sort of minimal, simple example. So we start by specifying the prior. So here, let's say we want to recover our action precision parameter alpha. So we set a prior for it, let's say the Gaussian with a mean of 6 and sigma 2, and set it in a dictionary. And then in case we want to put more parameters at once, we just add them to the same dictionary and their corresponding prior distributions. And so now we can use the create model function, which will instantiate our probabilistic model on our data. And it takes these inputs, which is our initialized agent, it takes our priors, and our collected observations and actions, which we collected, let's say, from a behavioral experiment. And in this case, we're just using some data from simulated T-maze. So here our actions is a matrix which has rows corresponding to time steps, or let's say trials, and columns corresponding to state factors. And similarly in observations, we have columns corresponding to observation modalities, right? And then we'll have our model object instantiated, which we can easily fit in a single line using our fit model function, which will run the sampler with appropriate defaults. And then we can, like, obviously people would want to pass some more specific settings into the sampler. So here I'm passing, for example, the number of iterations per chain, and I'm running 4 chains. And then I'm using the distributed module to run the chains in parallel. Right, and then after the sampling is finished, then we will end up with the results object, which contains our chains, and then we can work further with this, right? So here I'm just gonna quickly go through some of our other convenience functions, for example, to rename chains, which will rename the names of the parameters in our chains to something more intuitive. And we can extract quantities from our chain, so we can just simply display the results of our chain. So we can get the summary statistics, some information about the conversions of our chains, quantiles, etc. Right, or then we can just use a sort of native Julia uploading functions, and we can pass our chains to it to take a look at chain traces or posterior distributions. Or we can, what we can do is we can sample from our prior. So here I'm taking 1,000 samples from the prior, and I'm using our plot parameters function to plot the posterior distribution against the prior distribution for our synthetic participant, let's say. Okay, and this is a part which is going to be mostly interesting, I think, for people in computational psychiatry and cognitive modeling. And it's the case where we want to fit a full data set. So in this case, let's say that we have some data with 10 participants, and let's assume that we have 2 clinical groups in our data. It can be, I don't know, control and whatever, psychotic, or it can be young, old, right? And we can simply pass the whole data set with our collected data, let's say from our behavioral experiment, to the same create model function. So it instantiates the probabilistic model on the whole data set. And then an additional things that we'll need to tell the function is which column to use to differentiate between individual subjects, and which columns contain our observations, and which columns contain our actions. And again, we have our model instantiated on the whole data set, and we can just pass it on to our fit model function. Right, and again, this following is sort of the same procedure as before. We can play around with our recovered chains. Here we have the recovered values of alpha for each participant, using native Julia functions to plot the chain traces. And again, we can, let's say, sample from the prior and plot the posterior against prior distributions for each participant. Right, and then sort of keeping also with this default procedure in cognitive modeling. Now let's say that we have our estimates, and we want to see whether there is actually a difference, right, in our 2 groups, right? So here I'm just extracting the quantities from the chain, and I'm getting the estimates, which in this case are medians, and we can see here that there are indeed 2 groups present in our data, right? And then after, let's say that we run some statistics on our estimates, then we might be also interested to see whether there's any correlation with other states of our agent, and let's say some physiological data. Like here I'm plotting the state action prediction error, which then my people want to correlate, let's say, with brain data or pupillometry, for example. And for people who might want to use variational inference for various reasons over sampling, the good news is that Turing can do variational inference too. So here I just sort of remade the tutorial, which you can find on the official Turing web page, where I'm in the beginning just initializing the variational inference algorithm with a sort of default number of samples and a default number of iterations. And importantly, I'm setting the automatic differentiation backend to reverse mode automatic differentiation. And then in the VI function, which runs the variational inference algorithm, I'm just reusing our probabilistic model, which we have already created previously. Right, so this is very nice. And what we end up with is our variational posterior, which is a type of distribution, so we can sample from it or work further with it then. Right, and just to rather quickly wrap up, so we're currently working on the documentation. We know it's important, so it should be done in the next few weeks, let's say. Until then, you can either reach out or you can refer to action models documentation, which is really nicely written. Okay, and yeah, just briefly, just to summarize what we need to do in our next potential future. So we need to optimize. The package is fast, but there are still a lot of things that need to be improved. Then the idea was to, for example, be able to fit all parameters, because for now we're only able to recover the sort of hyperparameters, or what's being called the non-matrix parameters. But in principle, one should be also able to fit an entire, let's say, A matrix or C matrix, which would be really nice. And then, okay, we can extend the parameter learning to all other parameters of the generative model. Another idea was to introduce a sort of custom parameterizations where the user could introduce a sort of temperature parameter also on an A matrix, and this could be also in principle then recovered using data fitting from empirical data. And lastly, I'm just going to say that for our fitting, we are using reversal automatic differentiation, which is fast, but we're also planning to start experimenting with other engines which are currently under development in Chile also, which includes Enzyme and Mooncake, which might be potentially faster. And then on the side of action models, Peter has been working for some time also on the possibility of adding linear regressions. So the idea would be that we could fit the data, we could recover our estimates, and we could run linear regressions with our estimates or with other variables that we might have
in one model.
Yes.
Which is statistically optimal.
Yes. Okay, and the last thing you're going to hear from me is that when you decide that you want to start experimenting with our package and you encounter any issue, or do you have any specific feature in mind that you would like us to implement, please feel free to open an issue. Any kind of feedback will be greatly appreciated.
Thank you. And we're out of time, so I'll just briefly mention this point that you can treat a whole group of agents as one agent and do cognitive modeling out. It's a separate paper, so I'm sure there'll be time to talk about that at another time. To reach out if that's interesting as well. Yes.
Thanks.
I think that's it.
Thanks, Saul. This is a huge advance. It's really awesome. Brings a lot of features a lot closer to people's hands and minds, and it's exciting that we'll continue developing and learning about it.
Thank you.
Okay. Thank you. Till next time. Hello, welcome back. We're here with Shanna Dobson discussing descent conditions on Hyperphantasia, a new model of self-information. Looking forward to this presentation followed by questions at the end. So thank you, Shanna. Super looking forward to this.
Hi, Daniel. Great. Thank you for the invitation. I'm excited to present these new ideas on Hyperphantasia. So I hope this relates to someone, and thank you all for listening. So a small outline, I'll be discussing the Phantasia spectrum and its two extremes, aphantasia and hyperphantasia. And then we're going to discuss what I'm calling the memory continuum. Then we're going to review what I've been calling the oniric self, constructed as the profinite set. Then we're going to review Grothendieck's one categorical theory of descent. And then I'm going to try to present a new model of categorical mental imagery from the hyperphantasia perspective, using, I think, these very beautiful categorical sheaf techniques of specifically Grothendieck descent. So descent theory is a super powerful tool, and I hope you all like kind of what I'm trying to do there. Then we'll pause at what are called descent conditions on hyperphantasia, pretty much how the sheaves work, and why I think sheaves are really good for something like hyperphantasia, which is characterized by pretty vivid mental imagery and profound episodic memory recall. And then last, we're going to actually model surprisal itself, or self-information, functorially as a category of descent data. So if you've been following my work, I tend to like to categorify everything. And so we'll see if we can actually categorify hyperphantasia. All right, cool. So I'm just going to start with the big results, because it's going to take me a while to get there. So I always start with the main idea. So pretty much I'm going to categorify episodic memories as what are called fibered categories. And then so the idea is that you're going to fix a particular memory, M, and you're going to study memories over that memory. So this is in the vein of fibered categories. So fibered categories are very beautiful. They're almost like parameterized categories. And so fibered categories, particular category over a fixed category C. So for me, episodic memories seem fibered. They seem like they're memories over memories. As I think selfhood is fibered. So I've given many talks on that. Clive Wearing, the famous case of having both a retrograde and anterograde amnesia. Clive has about a 6-second working memory with purely semantic memory and not a lot of personal memory, besides remembering his wife, but everything else not so much. So the selfhood of Clive is in question. What's the perception, the frequency of perception of Clive? I think that's very, very tricky stuff. So if selfhood itself is fibered, we're going to consider these categories of memories over a fixed memory. So I have the idea to use descent to actually represent hyperphantasia. So the idea is that you have these memory sheaves that are satisfying descent, and to satisfy descent means that they form a stack, which is a very particular sheaf that takes values in categories and not sets. Okay. And so then this pair at the end, this F star phi, which I'll describe in these maps, is going to be our what we call the categorical descent datum. So I call it, this is our sheafy surprisal. So if you could sheafify surprisal or self-information, I think you do it this way. So surprisal would be constructed as the sheafification of memory. All right. So, and you would say there exists the following, the descent conditions on Phantasia, and it would be those. Cool. All right, so let's start with the Phantasia spectrum. So this is what I'm going to get to. I think they're pretty good ideas. And then, so let's actually dive into Phantasia itself, which I think is very, very, very beautiful topic. So what is Phantasia? What is this Phantasia spectrum? And so it has to do with the characteristic of, creatures having visual imagery. And so the Phantasia spectrum itself is a relatively novel neuropsychological spectrum used to classify to what extent an individual constructs mental imagery and visual imagination, which is quite strange. We're so used to it, but it's very strange that you have these pictures, quote, in your mind, that where do they actually exist? In this Phantasia spectrum, so this ability to imagine visually has two extremes, and they are quite extreme. So aphantasia is characterized by the absence of mental imagery, and hyperphantasia, characterized by profound, extraordinary mental imagery, heightened visual imagination, so detailed and vibrant, it imitates reality, I myself seem to fall on this scale. And the reason, again, I know this is that one of my dear colleagues introduced me to this spectrum and said, Shanna, I think we were writing a paper together and said, actually, I think we lie on opposite sides of the spectrum. Everyone knows I tell this story. And together, I think we've written like the most amazing things. Okay. All right. So let's start on the aphantasia side. So when you say, the tendency to say lack, it seems to say something negative, but it's not really. So aphantasia is just characterized by the absence of just particularly mental imagery. Doesn't mean all imagery. So it is an image-free mind, but it has conceptual imagination. Okay? So if you were to say, so the imagination of anyone who falls on this, in this classification, it involves other senses and abstract concepts, so besides visual imagery and sensory details. So perhaps the way of thinking is and visualizing is analytical. So everybody knows my little girl Artemis, and I talk about her a lot. So if I was aphantasic with respect to like saying, someone said, how do you imagine Artemis? And I would say, well, I cannot mentally picture Artemis, but I can think about the idea of Artemis. And there's Artemis, all right? So perhaps like her fluffy tail and her being white like wouldn't actually appear to my mind, but I would think about the idea of Artemis and I think about it very deeply, right? So contrast this to what is hyperphantasia. So hyperphantasia is characterized by sort of extraordinarily vivid mental imagery and heightened visual imagination, and also episodic recall. Heightened sensory details in episodic memory. So, Shanna, what was your first ice cream cone? And there's, just lush, sort of Dali-like exquisite imagery that comes out of that. So detailed and vibrant, it imitates reality. That you actually say, well, which one? Which one is, quote, more real? The one, quote, in my head or the one like outside of my head? Tricky. And so I can actually picture Artemis so vividly as if I'm really seeing her in real life. Okay. And so for episodic memory, these are personal memories sort of based on sensory perceptual data, of which mental imagery is a particular form. So that is why hyperphantasia and how you recall episodic memory are so incredibly linked. So with this, I've started thinking about sort of the distance to and from memories. So this is a concept that I think would be exciting to explore, which is why I'm doing it. And so if you ask yourself this strange question, like what is the distance to a memory? Normally people would call this a timestamp. That happened, to you 3 weeks ago, something like that. What happened to you then is not what's happening to you now. We call this a timestamp, sort of a way that you can mentally file away an event and to keep it a little distant from you. So, but I have a question. So for hyperphantasics, what if there were no distance to a memory? I find this to be the case for myself. People say, well, that happened then. That happened then, it's not happening now. I sort of have a problem with that sort of thinking, that sort of logic. I question the timestamp that people are using to actually say a statement like that, right? But let's imagine, what if there was no distance to actual memory? Would that mean that it's always happening? Would it mean that it was always happening? Well, what if that distance were actually not measured by sort of the counting numbers or the real numbers with a linear ordering before or after? So this is sort of the profound leap I want everyone to try to imagine. So an event happened to me 2 weeks ago. If you were thinking according to the sort of like standard number line, you would say, well, 2 weeks ago was before, like now. It's like now is the 0 point. And so, normally events with a timestamp have a linear ordering. That happened then, this is happening now, that was yesterday, this is today. And so I just want to ask, like, what if that distance were actually changed? The metric on that distance was actually changed. So if there was no linear ordering about before or after, this would be very curious. So for me, the distance to and from memories seems more like it's a p-adic. So I invite everyone to sort of try to think of the distance to memories as more non-Archimedean. in the sense that there is no before or after. So if you've been following my work, I'm pretty enchanted by the p-adic numbers and things like this. And so the p-adic numbers actually have no sense of linear ordering. They are kind of more fractal-like. Now this property that you're sort of just zooming in, but there's no notion of like bigger than or greater than. And I think that would actually be very interesting to try to evaluate memory on a timestamp of something that's not bigger or less than. Right? So my claim is that the distance of, or to, or from memory is p-adic. And that's going to lead me down this exploration. So the second concept I want to talk about that I've been playing around with is the idea of a memory continuum. So I want to ask the question, like, what is the space of memories? If anybody saw like the latest Blade Runner, you see like there's like the memory maker. She's in charge of actually making memories, and she's actually sort of kept away because she says she can't really leave this prism that she's in, but she's charged with making memories. So I want to ask the question, like, what is the space of memories? Right? So you have them. My great colleague Chris Field and I are always asking the question, like, why do you experience memories? It'd be very interesting to find the first creature who experienced a memory. Not why you have them, but why do you experience them? All right. So what is this space of them? If you were to actually put them in a category, you could. I was actually more interested in, like, you know, if you dive a little bit into that, well, what is the actually topology on the memory space? Could you actually cover it with something? Can you think about memories in terms of open sets? Are memories topological? Do they sort of intersect, which it sounds like they do? What sort of properties do they have? And so to think about memories mathematically, I think is kind of a new idea. So not only what is the space of memories, but what is actually the shape of memories? What do these actually feel like, look like? And so I want to actually think about the concept, like, can you actually mathematize the duration of memories? How long do they last? Some memories seem to have expiration dates, and some memories seem to be, holographic. I'm really interested in how memories last, how long they would actually last if they were actually considered with a different metric. Okay? So for myself, I notice a certain density of memories. And what do I mean by that? So density in the mathematical sense, not heaviness of densities. Although that would be interesting, like some memories are so heavy, they'd probably, implode. Some memories are sort of big, but light, they'd float in the bathtub, right? So the density of memories, I'm not talking about the physical property, but what is often called emotional valence sort of has this positive, this plus minus charge associated with experiential memory. So if memories can act like sort of black holes, or memories are sort of like black holes, they can literally warp the thinking, if you would think about it. So black holes, actually can tend to, if there's they're dynamical, but when they're rotational, when they're rotating and things, and spewing out these plasma jets, they can actually warp the space-time around them. I've always been fascinated by that. I seem to have memories that do the same thing. So if they warp the thinking, what happens? Well, any object can be turned into a black hole. You just have to squish it beyond its Schwarzschild radius. So memories as objects, something to think about. So density in the sense of, okay, like a teaspoon of a memory that was as heavy as a black hole would do something, but not that kind of density. I want to talk about the mathematical density of memories. Okay. What would that even mean? So if you take density from the standard form where you normally prove that, the rationals are dense in the real numbers, this is the sort of density that I want to think about. So the rationals are dense in the real numbers, which means that between any two real numbers, you can always find a rational number, which means between any two real numbers, you can always find a real number. So that seems like a light statement, but then it sort of gets terrifying to know that between any two real numbers, you'll always find another one. Unlike the property, say, for like counting numbers or the positive integers, between the positive integers 2 and 3, I will not find another integer, but between the real numbers, I will. So I thought, for me, it seems sort of the same. between memory A and memory B, there seems to exist a memory C. And I can continue this forever, it seems. For me, between any two memories, there is another one. And another one. I can always find another. Right? So the memory density and the memory continuum, I think, is something that could be looked at as a hyperphantasia. Until I run out of memories, right? So between any two memories, there is another one and another one. I can always find another one until I run out of memories. But that's where the hyperphantasia kicks in, right? Now, between any two memories, there exists a hyperphantasic memory, right? So this hyperphantasia for me is a sort of memory continuum. So one of my brilliant colleagues at Art Center constructed this beautiful image, which I think for me actually shows me, this is sort of what I think about as a hyperphantasic, right? So the density of memory that I could be brushing my hair and you know, inside that memory of me brushing my hair with my favorite brush, there's more memories inside my hair, memories inside of memories inside of memories inside of memories, right? And it just keeps going on and on and on and on. So I want to play around with another concept called meso memory that I've been thinking about. So is there actually a duration issue with the density of memories, whereas the real numbers always exist? So if I'm talking about between any two memories, there's another one. How long does that last? The real numbers seem to always exist. Seems that between any two real numbers, I will always find something. But what about memories? Not sure about that. What is memory at the meso scale? So this is a scale that Daniel and I, we've been having talks about. So sort of between the micro and the macro, you have this meso, which is sort of this slippery sort of interstitial happenings. And so what is memory at that scale? I'm very curious. Is memory just the thing that sort of comes through at the macro side? What would meso mean in terms of that? Is this like an almost memory? So I have almost memories at the meso scale, but then what does that mean? So what would a meso memory actually be? Well, thinking in terms of density, it would allow more variations of what memory looks like. So sometimes you have memories that aren't quite out of the oven yet. You have some memories that have been mixed. Some memories are fluid. Some memories can phase change. And so I really think it's really important to think about the density of memories by opening up this new scale. So sort of from micro circuitry of neuronal processes, micro memory. This is sort of what I'm interested in. So for me, memories feel non-Archimedean. I'm going back to the p-adics. P-adic metric, it's a fantastic metric in my opinion, right? So the p-adic number system, again, just a brief recall, is a non-Archimedean system that is the completion of the rational numbers Q under the p-adic metric. Repeated notes a prime number. Interestingly, so this is sort of the Oz-like property of these numbers. So p-adic numbers are close if their difference is a high power of p. P-adic notions have no notion of linear ordering. Their shape resembles a self-similar set. That's the fractal language I was talking about. Okay, so just a little more technical. So again, for me, the memories feel non-Archimedean. And so informally, the ring of p-adic integers, ZP, are written in base p, and they admit infinite expansions to the left of the decimal point. So p-adic integers take this form of sort of the sum an pn, where an is between 0 and p. Addition and multiplication are performed on the p-adic integers with the sort of carrying method used to add ordinary ones. So the p-adic metric introduces a non-Archimedean norm on the rational numbers. And the fun part of this, fun fact, is that for a non-Archimedean norm on the rationals, every point of an open ball is actually the center. So I want to think about that. Instead of actually having like a canonical center in the Archimedean case, every point of an open ball is the center. So this sort of what some would call a disorientation, maybe it's sort of a superpower. This could be the space from which hypermemory is made. The fact that every point in this open ball would be centered. So really, what metric are you using? Do hyperphantasics and aphantasics use different metrics on the topology of the memory space? This is what I'm interested in. So are they using different distances to and from memory? So at best, you'd probably just have isomorphism classes of these timestamps instead of, I'll just say, yeah. So for me, memories feel also profinite. This is a concept you've been following me, I talk about a lot. inspired by Schultz's work. So a profinite set, also called a stone space, is a compact Hausdorff totally disconnected topological space. I've been enchanted by these for a little bit. It's also defined as an inverse limit of finite sets. That's our notation, the inverse limit over SI for SI finite. So the smallest, what is called light, so a light profinite set, everybody, is just a countable inverse limit, finite sets. And so the smallest infinite profinite set, it's actually called the one-point compactification of the integers. So you go all the way through the integers and you join infinity. And then also the Cantor set, which I will talk about in a little bit more. All right. So fractality is this concept that I'm studying for my thesis work. Fractals are such strange, beautiful creatures. They actually sit between Berkovich spaces, which are famous rigid analytic spaces, and the p-adics. So they're between these. And the p-adics are totally disconnected. So Berkovich spaces are these topological spaces, like I just said, in the setting of non-Archimedean analytic geometry. So fractals are sort of in between. And so fractals have this property. It's very difficult to define what a fractal is. So there's been some contention about the definitions back and forth. And so, but everyone agrees that fractals obey one property, that they're self-similar at all scales. So I want to ask if memories are self-similar. What would it mean to actually have that? What is the shape of memories in something like the dream space? So we're going to call that like the oniric self memories. What does it actually mean to have like the memory space in an oniric setting? We're going to explore that in just a little bit. So memories seem local, confined to some sort of particular area, but they also seem meta, right? So in some great work with my brilliant colleagues, Hector Manrique and Paul Walker, we're trying to figure out sort of how would you construct the oniric self? Had this idea like, I think you could construct the oniric self as itself as a profinite set. And so what we're looking at here is the different topologies and like on the memory space in the waking state and in the sleep state, and actually the construction of selfhood in the dream space and then selfhood in the waking state. So just to quote one of our passages here. So we say, in stark contrast, the oniric state events occur disconnected from one another in a profinite space that's compact Hausdorff topological, so namely a profinite stone space, where events dreamt by our oniric self are not stored relative to linear time. So hence a plausible model for dream time would be a ring of p-adic integers ZP considered as a topological space. So we're trying to figure out like an event in a waking state and an event in a sleep state. These seem to be stored differently and to construct different narratives of personhood, right? That was Hector's idea. How do I construct the notion of self in a waking state versus self in a dream state? So self in a dream state, you know that you can be here and then you're all of a sudden you're flying with like Falcor, and then all of a sudden you're at Erewhon. These are my dreams. And the question is, you can get from one place to another very, very, very quickly, instantaneous, or you seem to be nowhere in particular at no time. And so the question was like, if I had all these events happening in my dream space and I couldn't store them as dream, I may start having waking state fights with people who did stuff to me in my dreams. And I'm like, Daniel, how did you do that to me? And he's like, Shanna, that never happened in the waking state. And I'm like, oh, okay. So you have this very separate storage space, which keeps dream things there, and you're not constructing the sense of waking self based on the dream state events. Beautiful idea. And so why did I say like, okay, let's construct the dream state as a profinite set? Well, the Hausdorff criterion ensures that there's no simultaneous experience occurring in the oniric dream state. You need to keep these events separated. So every point in the profinite space uniquely represents an event that has occurred onirically. Simultaneous experience is something that I'm after as well in my work with my brilliant colleague, Robert Pretner. Also my work with Chris Fields. So what would it mean to have a simultaneous experience? That is something that we're still working on. More like that is a waking dream. But so you want to have these events being Hausdorff, that they are kept separate in the dream state So you don't have sort of an inception going on. Thank you, Christopher Nolan. All right. So the total disconnectedness condition actually accounts for a crucial difference between awake time and dream time. So Chris and I had this idea that a key aspect of the construction of waking time, however, is the assumption that between any two distinct events experienced by some agent A, other things happened, non-agent specific events occurred that A did not experience, but some other agent B may have experienced. Okay, so in the waking state, between any two distinct events experienced, say I'm agent A, right? I'm giving this, lovely talk for everyone listening, and then I'm going to go give another talk. And so the fact that in between these two talks for me, something else, happened to Daniel. Events in the oniric state, though, I think don't have this property. They're actually totally disconnected, so that you wouldn't have this notion that between any two things that happen for me, something else happened to somebody else. All right. So a canonical example of a profinite set is the actual Cantor ternary set. So do I have an image of this? Okay, yeah. So the ternary set is constructed iteratively from an infinite process. I take this closed interval 0, 1, represented by this solid red line. And what I do is I actually remove the open middle third from the actual closed interval 0, 1, leaving me with two intervals remaining. So I actually have two line segments, closed 0 to 1/3 union 2/3 to 1. And what do? I do it again. So I remove the open middle third, leaving me with the remaining line segments. And I continue this process infinitely. So the Cantor set actually consists of all the points that remain that are never deleted from the original interval. You can see there's end points of the line segments that are never deleted. And so beautifully, that Cantor set is actually uncountably infinite. So it's the scary infinity, having the same number of points as the closed interval 0, 1, right? So shown here is like just the first 7 steps of the infinite construction. It's always nice to be defined as an infinite process. So this sort of this is the Cantor set. And so the points that remain are sort of like this Cantor dust. But if you add them all up, it's the scary infinity. Okay. So this Cantor ternary set is nowhere dense, has no interior points, and it also has measure 0, so it's considered negligible, small. So back to our paper. So if the oniric self is composed of these events that occur in a stone space, then the oniric self would be like Cantor dust, everyone, and negligible. So the self-similarity of the Cantor set, it's sort of like fractal, and it could experience what we're calling these time loops by the oniric self. But of course, the cerebral neuronal microcircuitry is yet to be demonstrated, which maintains alternative storage systems, right? So do you have these alternative storage systems? And what causes the switching between them? How do you actually know to file event A as a dream event and keep it separate from event B? So strange. And what would happen if this actually sort of flipped? All right. Okay. So the self-similarity of the Cantor set, I'll just show you this image, is the fact that there is a P, like the Cantor set is similar to itself upon magnification and translation of its pieces. So if you look at this highlighted piece pink, that I have like the pink highlighted piece. So you can have 2 copies of that diminished by a factor of a third and translated produces the original C, right? So very strange that this set is self-similar, and that's why I think it's actually very curious. But the self-similarity is what I'm interested in the actual memory space. Cool. All right. So let's get just a little technical and then I'll wrap up. All right. So this new model is going to be based on these categorical sheaves, like I showed the main results in the first slide. So the idea is to model for hyperphantasics, model episodic memories as light profinite sets, which means these countable inverse limits of finite sets. So then we're going to actually use a claim that a theorem that Chris and I have in our paper that entropic categorizations are actually condensed sets. I'll recall all these terminologies, and then recall in terms of representable functors. So I think recall could have a very beautiful form as in terms of representability, and I'll go over that functor. Then you want to construct hyperphantasia by adjunction, and hyperphantasia will be constructed as surprisal. So Fantasia itself is sort of like self-information. And so self-information by the way of the actual visual spectrum, or if you're aphantasic. So then you would reframe further these memory sets as categorical sheaves and put the descent conditions on them. And then you'll model self-information as a category of descent data. Okay, so it's like, firstly, everybody always asks me, why sheaves? You know, like, why are you so fascinated by these things? Well, I really believe and support Grothendieck's work. So Alexander Grothendieck always said that it was sufficient to study the category of sheaves on a topological space. So he is so brilliant. He really revolutionized just algebraic geometry, descent theory, really beautiful things in order to comprehend the topological space. So all you need is a category of sheaves on the topological space. Love that. So sheaves enable what? Well, they enable this local analysis of the space. They assign data to open sets. You don't really get this local global phenomena a lot. And then the category of sheaves on a space actually encapsulates its geometric properties. Like cohomology groups, these capture topological invariance and structure. So the category of sheaves on a site is actually called a Grothendieck topos. A site is going to be a category with a topology. So unlike like a topological space, but a categorical version of this. So a Grothendieck, and particularly a Grothendieck topology on a category, is going to be a set of morphisms which act like the open sets or the covers of a topological space. Right? So this Grothendieck topology is going to be very rich, and I just think he was really onto something here. All right, so a site. Let's define that real quick. So a site is a category equipped with a Grothendieck topology, and so given a Grothendieck topology J and a small category C, you can define the category of sheaves on C relative to J, which is this SHC, J. And this is a reflective subcategory of the category C off of sets. That's a functor category of pre-sheaves on C. And so reflective subcategory refers to the images, image maps reflecting each other. So this, you're going to have this functor from C to the category of sheaves of C relative to J, given by what's called the composite of the Unida embedding, which I've talked about before, with the reflection. That's called, or the sheavification. And so this composite functor is going to be fully faithful, which means injective and surjective on the POM sets. If and only if all the representable pre-sheaves, which are these set valued functors, are actually sheaves. So descent is going to be, you know, the sort of generalization of the sheaf condition from pre-sheaves on these higher categories. So a topology with this property is really importantly called subcanonical. So let's define a profinite set. A finite set is actually a compact Hausdorff totally disconnected set, as I said. So it's defined as an inverse limits of finite sets. So let's just talk about what an inverse limit is. So you have some sort of index set I, and so the pair, this pairing is going to be a partially ordered set. And so say we're working in groups and group HOMs. So we'll let this AI be a family of groups. Suppose we have a family of homomorphisms, Fij. Note the map goes Aj to AI for all I less than or equal to Ij with. So Fii is going to be the identity on AI. And then Fik is Fij precomposed with Fjk. And so this pair, AI, Fi, is going to be an inverse system of groups and morphisms. Right? And so the inverse limit is actually a subgroup of the direct product of the AIs. So you construct A as the inverse limit, which is all the A's in this direct product, such that so AI is Fij Aj. So Fij of Aj is pulling out the AI component. Okay, all right. So a little technical, sorry about that. Right. So light profinite set is actually just going to be. I'll just make this nice. So a light profinite set is just a countable limit of finite sets. Right. So you can define it in terms of size and weight, but countable sounds good. So again, an example of a light profinite set, the finite sets are, the smallest infinite profinite set is the 1-point compactification of the integers, and also the Cantor set. All right, so let's go back to what a condensed set is, and then I will be done in about 10 minutes. Okay, so what is a condensed set? So remember Schultz and Clausen, they had this idea of like, how do I define a sheaf over a point? Super revolutionary, very cool idea. So there's condensed sets and there's light condensed sets. And so a light condensed set is a sheaf on the category of light profinite sets. So this is not a Hartshorne sheaf. This is a categorical sheaf, right? So you write it as this. So light condensed sets are actually sheaves on the category of profinite sets. And so they have this proposition that there's a more general way of thinking about these. A sheaf on a category is normally a set valued functor. So you let condensed C denote the category of condensed objects of C, where C is a small category. And then, so the condensed C can be represented as a category of small sheaves on C. Great. So what we need is this, the equivalently category condition. So condensed C can be represented as a representable functor, which takes this form, C opt to set. All right. So here's the cool part, right? So to summarize, we're trying to get like episodic memory as forgetful functors. All right. So if you model memories as these profinite sets, and you reframe recall as working as left adjunction, which is kind of like an inverse map. So we recall the famous proposition that any set valued functor with a left adjoint is actually represented. That's powerful. So what is a forgetful functor, right? So it's a map that sort of forgets some sort of structure in the original space. I think memory is all about forgetful functors. What do I need in this moment? What do I not need? Short-term memory, long-term memory, personal, semantic. You're eliding something in order to create meaning, right? So the forgetful functor, for instance, from compact Hausdorff topological spaces to all topological spaces, we'll call this functor U, has a left adjoint. You can informally call it an inverse map from the topological spaces to the compact Hausdorff topological spaces. And it sends a general topological space to a compact Hausdorff topological space. This is very beautiful. It's called a stone check compactification, and it comes up in the work of profinite sets, right? So the stone check compactification is in general very large, but this is sort of like an example of what you're forgetting, right? Yeah, I'll just say that, right? So you're like forgetting the compact condition and to get to topological spaces. Great. Okay, so let's get just a little technical, but I'll just like kind of go quickly through these slides. So why is Grothendieck interested in descent theory? What is this, right? So kind of a scary definition, but it's okay. So the theory of descent can most aptly be characterized as, so from the point of view of infinity category theory, which I've given some talks on. So descent is a study of generalizing the sheaf condition on pre-sheaf, right? So pre-sheaf is a tool for tracking this local data. And sheafifying it pretty much means you're giving very strict gluing conditions on these things. So you want to study the generalization of that sheaf condition on pre-sheaves to pre-sheaves with values in higher categories. Right? So that's why we're calling this the infinity category point of view. So those higher pre-sheaves that satisfy descent are called infinity stacks, right? And so again, I think like gluing and recall, or like gluing, sheaf gluing would be a nice mathematization of vivid, profound imagery that imitates reality. That's what I'm saying. So I think it's in the gluing conditions where the hyperphantasia works. Okay. So more generally, descent theory studies the existence and uniqueness of an object in a higher category, provided some inverse image functor, which produces an object in some other category. So you can sort of reconstruct the object from a higher category itself. I'll just say this. All right. So the non-uniqueness is normally parameterized by equipping this object F star U with an additional gluing data, which we'll call Kazai. So this pair is called a descent datum. So you have a reconstruction procedure of U from the actual data. And so that's actually called a descent. Okay. So this action of descending is formalized as what is called a descent condition. So again, getting this F star map. So you have an object U in a higher category CX and an inverse image functor, right? So F star is just an inverse image functor from the higher category to not a lower category CY. Okay. So think of F star as an inverse image functor, and that's what we're looking for. So inverse image, pulling this thing back, and then this gluing data, okay? That's what we're looking for. So to get very beautiful with this, you could say every infinity one category of infinity one sheaves is a sub-infinity one topos of the infinity one topos of pre-sheaves on a small category. So once again, that something, an object that you have, is reconstructed from another object, right? So it's this sort of like local to global phenomenon, right? I will say, each infinity topos is a reflective infinity one subcategory, and a localization, which is sort of like a way of saying adding inverses of an infinity one category at a collection of morphisms, which are sent to equivalences by the left adjoint of the inclusion. So precisely those objects such that the pre-sheaves are precisely the local objects. This is an isomorphism in the homotopy category. Homotopy just investigates these continuous, these deformations of objects. So the descent condition is how you actually descend from the higher category down. So hyperphantasia is going to be this particular reflection, localization. That's what I'm thinking. Another one of my colleagues did this self-portrait of herself in a black hole. This is sort of like, for me, what I think about as descent as a hyperphantasia. You have a memory upon memory. Between any two memories, you have another memory. So memory of self, memory of what I was, memory of what I could be. Since there is no linear ordering, the time for the memory space can go both ways, I think. And so, you know, having like spaghettification in the black hole, and having redshift around the black hole, time sort of stopping, but then you have that layered on the sense of like self. So I think for someone like me, if you're like, oh, describe yourself, it'd be something like this. And so the image itself has so many layers just sort of on it. Okay, all right. So descent ingredients would be something like, so a more gentle way of saying this is that that descent has a somewhat formidable reputation, as you can see, amongst algebraic geometers and almost everybody. So in fact, it simply says that under certain conditions, homomorphisms between quasi-coherent sheaves, which is just sort of like a sheaf of modules over the structure sheaf of a ring space. You have the structure that conditions, that homomorphisms on the quasi-coherent sheaves can be constructed locally and then actually glued together if they satisfy a certain compatibility condition. And then while the quasi-coherent sheaves themselves can be constructed locally and glued together by isomorphisms that satisfy something. So going from local to global is actually the same notion that I was saying earlier in the category theory sense of reconstructing data from higher category to a lower category. All right, so you have this notion of category theory, of a category in which descent theory works, and these categories are actually known as stacks, right? So what you really want to say is that in working in descent, you naturally work in fiber categories. So that's why I said, you know, you want to fix a certain memory M and consider the set of memories over M. And so you actually call a fiber category as a generalization of a functor. It's called a lax2 functor or a pseudo functor. And then a pre-sheaf is going to be a functor, a pre-stack is a fiber category, and a stack is a category of sheaves on the site. So this is how everything sort of works. So you associate with a fiber category over C the data for a pseudo functor. And then so stacks are going to be the correct generalization of sheaves. You're going to get this nice notion of the sheaf of categories. So if you want to actually say, so in a nicer way, like what does descent mean? When you're gonna hear this everywhere, like in that sort of literature in arithmetic geometry. So to say, you know, descent for quasi-coherent sheaves, these sheaves of modules, or to say something satisfies descent, you're going to say quasi-coherent sheaves satisfy descent with respect to a particular topology. FPQC stands for faithfully flat quasi-compact, just a specific topology in the gluing map. To say something satisfies descent is to say that they form a stack. Okay, that's all we're going for. So when you say that, you know, the memory sets satisfy descent, I mean that you can actually stackify them. So this word subcanonical is again very powerful. I want to mention it one more time. When I'm talking about the topology on the memory space, I'm hoping that you need something that's like the topology needs to be subcanonical. Okay, so topology on a category is called subcanonical. Every representable functor on C is a sheaf with respect to the topology. So every representable functor is a sheaf, and then a subcanonical site is a category endowed with a subcanonical topology. Great. So a fun fact, because this is fun. All right, the name subcanonical comes from the fact that on a category C, there's topology known as the canonical topology. This is the finest topology in which every representable functor is a sheaf. Very beautiful, right? So these concepts of subcanonical, I think, can be infused very beautifully into this notion of surprisal. Right, so what does it mean to sheafify a functor? So the construction of the sheafification of a pre-sheaf on sets, on a topological space can be generalized. I'll just say, so to sheafify a functor, right, we're just going to add the sort of categorical definition of what a restriction map is. In the interest of time, I'm just going to go over this. All right, so if C is a site and F from C op to sets is a functor, then we're going to say that FA C op to set is a sheafification of F, any morphism from F to a sheaf factors uniquely through FA. These are diagrams. So there exists a sheafification F to FA, which is unique up to a canonical isomorphism. This is the thing that I'm actually using in my work. Okay. This is technical. We don't need this. Okay. So let's get to the descent condition. So why is this actually important? Again, why am I looking at like descending or pulling back memories? Because I think that's what leads to the vividness and also the notion that there is no distance between these things. So let C be a site. A fibered category over C should be thought of as a functor from C to the category of categories. So you fix a category, we want to look at the categories, the category of categories over that category. So a stack is morally a sheaf of categories over C. All right. So if C is a site, the functor from C op to set, we also consider it as a category, fibered in sets. Big note that F is a pre-stack if and only if it is it's called a separated functor, but F is a stack if and only if it is a sheaf. So this is the reason why you need this is the reason why I'm working with like sheaves and what it means that if something satisfies descent, sheaf becomes a stack. Okay. So there's an archetypal example of descent that you work with the category of continuous maps, and that category is fibered over topological spaces by this functor P, sends each continuous map to its codomain, and then so suppose that F goes from X to U and G, Y to U. These are two objects in the category of continuous maps, mapping the same object in the topological spaces. So you want to construct a continuous map phi from X to Y over U? Yes. Okay. So I don't want to talk about this. Okay. So in this, because I'm already like out of time. All right. So in the new model, the idea is, again, if you categorify these episodic memories as these fiber categories I've been showing, fix a memory, look at the set of memories over this. And then so episodic memories would seem to be fibered in the sense that they lie over each other. And so it's this sort of stack that I'm sort of interested in. So memories as stack for the hyperphantasic, and the sort of stackingness is what leads to the vividness. So the descent conditions would be the following: use descent to represent hyperphantasia, memory sheaves satisfy descent, and then this pair F star phi would actually be the categorical descent data. So therefore, if you actually use this stackification method, then you get surprisal as a sheafification of memory, right? And so what you can do is, I don't know this, all right. So the way that, so I have some results that I'm sort of thinking of. And so you construct this functor from the category topological spaces over a profinite set. And then you just get the final, the ideas, right? So there's a specific topology called the pro-Attell topology, which is sort of like the Attell topology for specific morphisms. And that topology is a subcanonical. So based on some of Schulz's very powerful theorems and his work on perfectoid spaces, remember the subcanonical topology is very important, that every representable functor is a sheaf. So Schulz has this lemma that says the fibered category sending any perfectoid space to the category of locally finite free OX modules, a structure sheaf, is a stack on the V site. This is a V called the V topology on the perfectoid space. Okay, so using these using that lemma and his other work on the V topology, I thought, okay, we're just going to sort of shift these to the memory setting. So I'm going to say let Y be a condensed set of episodic memories and the functor which assigns to an extremely disconnected space. This is a profinite set. The category Y over S is a stack for the Pro-Hotel topology. So this right here would be the way of actually showing that, showing the actual descent conditions on the episodic memories. Second claim, recall a topological space is a condensed set, remember, which is a sheaf of sets on the Pro-Hotel site. The fiber category is sending any X in the category of continuous maps to the category of locally free, locally finite free OX modules. This would be a stack on the Pro-Hotel site on condensed C. So on the actual condensed, the category condensed sets on C. All right. So these results would be, how do you actually get, how do you sheafify the memory space? And these themselves would be the descent conditions on Fantasia. So these two claims would be actually like my new model of self-information. Would be, okay, you construct surprisal in this sheaf condition, and surprisal is actually just how far stacked your memory space is, and rethinking surprisal in terms of descent, in terms of what I can recall back. Because if I could actually theoretically recall everything, I think I would have no surprisal, you know? And I'll just say thank you. Okay. Sorry, Daniel, I went a little bit over, but yeah.
It was amazing, Shanna. Thank you.
Okay.
In the last minutes, I'll quickly ask some of the great questions in the live chat. Okay, I'll begin with the one and only Dean, who wrote, if p-adic as nonlinear, do we suspend the concept of next? Do we begin at a place of all? With all as our moves starter, do we need thresholds? I.e. all puzzle pieces are present and each is connected regardless of order of application, all pieces simply fit.
Wow. Go Dean. Yeah, I don't know if Dean's still there. Yeah, Dean, please respond. That's a great idea. Do you get rid of the idea next? Yeah, I think so. I think so. That would be pretty phenomenal. Does this happen next or does it happen at the same time? So Dean, yeah, do you mean like all in the sense of, it's not that everything happens at once. I like your idea of all. I think all can be zoomed into. And so, yeah, abandoning the notion of next. That does sound a little radical, doesn't it? Yeah, there would be nothing next. It's more sort of like it's more now. So I don't know if you're abandoning it. You're just sort of, it's phase changing.
Okay.
I love Dean. Such a good question.
To the next question by Bert, who wrote, what about memories of imagined objects or events?
Yeah, so Bert, that's actually what I'm trying to like poke at here. Memory of an imagined event. So if you're like me, that between any two memories, there's another one, and then between any two memories, there's like a hyperphantasic memory. I don't know. I'm starting to call into question like memory of an imagination of memory. And so how do you work that sort of discursively? And also, like, does the event get like when are you able to realize that the memory of that thing was imagined? I don't know. But yeah, I think the questions that you're asking is sort of the mess that I'm in on this meso scale. On this meso scale, when does the memory of the imagined object turn into the memory of like a real object? And so I think, Bert, you're in the same space that I'm in. Why is it that the thing you call memory is just the thing that comes out and it's in the macro world? But Daniel, I don't know, what does it mean to have a memory of something imagined?
Would we even know?
Right. And that's so, I like your language there, Bert. I'll just say thanks. I'll look into that because on the hyperphantasic scale, I'm not sure if I'm doing that like all the time. So, you know, Meisner Acting says you're living truthfully under imaginary circumstances. I think this is pretty much people all the time. But yeah. So in what, that's why we're interested in these sheaves. And what layer does the imagination, the imagined object flip into? Okay, that didn't happen. Store it over there.
Okay, and a question string of questions from Sonia, who wrote, could this lead to a typology of how hyperfantastics, quote, picture conceptuality, a space of abstractions, and how aphantastics conceptualize or perceive, e.g. visually, complex visual situations? Do aphantastics abstract infinitely into the future? No GRU/Bleen spatio-temporal ambiguities possible, and hyperfantastics hold periodically GRU/Bleen for experience all the time, implying a different type of spatio-temporality or conception of infinity.
Yes, Sonia. Sonia, hey. All right. Yeah, Grubline. Like, okay, that's yeah, fantastical. I love that. Yeah. So, yeah, sure. Whatever you're calling your spatial temporal construct and whatever that space is, yeah, I think absolutely has to do with the topology, the typology of how your memory space is constructed. Yeah, so on the aphantasia side, you will have no problem working with just the idea of the space. You aren't, in a sense, limited by trying to perceive the visualization of a tesseract. Well, this is a 4D spatial object. I can't perceive that. But as an aphantasic, I can go in the infinite process of working on the idea of the tesseract, which Sonia does so well, right? Sonia is the master of discursivity on taking a concept and just looking at every possible part of it and how it reflects on itself. And so I think both of these extremes are going to work with the absolute reflection of these two spaces. So yeah, the topology of something like an aphantasic in the memory space and the topology of a hyperphantasic memory space absolutely is going to reflect, just like based on Sonia's talk, reflect your spatiotemporal like construct, but also I think I'm interested in like the frequency of the spatiotemporal construct that you're working with. And then even that itself would have like an expiration date. So I love that. Space-time for an aphantasia, is totally different than space-time for the hyperphantasia.
Okay,
So cool.
last question with a short answer.
Yeah.
Dave Douglas wrote, are aphantastics actually devoid of imagery? Blind from birth would be considered separately given that their fantasies are kinesthetic, or do they, quote, fail to access their fantasies?
Oh, I love that. Yeah, that's great. So again, I'm more versed on the hyperphantasic side, which is why I went that way. I like that, failing to access their fantasies. And again, and so I don't think any of this is sort of like negative by any means. They sort of, you can say they go beyond visualization. Why do I only need to see in the 400, 700 nanometer range? So I think through, I think they could be actualizing their own fantasies in the analytic, in the fact that they don't need to actually be hindered by a visual representation, that they can access it through the idea of it. So say Artemis was my fantasy or something, okay, that I don't have to like visualize her, it's weird, but that I can, the idea of Artemis, I have immediate access to. So I really like that claim, but I also think it's not a failure in any way. I think they're actually getting the fantasy on the idea front. Such good questions.
Thank you, Shanna. It's been a great year with Math Art and all of our colleagues, so looking forward to how this all continues. Thanks a lot.
Thank you so much.
Bye.
Thank you so much, Dino.
Hello, welcome back. We're here with Matthew Brown discussing real-time active inference for adaptive robotic control. So put away the memories that you haven't had yet, and let's talk about robotics. Thank you, Matt.
Yeah, thank you, Daniel. Yeah, this is going to be a bit of a change of direction, although that was a really great talk. I'm looking forward to reviewing a lot of the talks from the last day, but that was pretty amazing from Shanna. So yeah, I'm Matt. Great to be here. Super excited to share updates about what we're doing. Just to give a little bit of background on myself, I've been working in artificial intelligence for a little over 20 years, including time in the defense industry, writing AI for video games, things like Halo, Bioshock, Splinter Cell, those franchises. And over the last 10 years, I've been working in more serious AI, particularly in deep reinforcement learning and now in active inference. Notably, built the first commercially available deep reinforcement learning platform, which was bought by Microsoft in 2018, is now the autonomous systems platform there. Currently, I'm at a startup at ThoughtForge I began about 5 years ago. ThoughtForge's technology started as a personal research project back in 2007 that never really ended, exploring biologically plausible alternate approaches to machine learning, and over the last couple of years, I've been applying it to adaptive real-time control for robotics. So that's what I'm going to be going through today. Just a quick brief agenda on what I'll be talking about, and go through a quick, well, not so quick. I'll go through an introduction a lot about the high-level concepts, then dig into briefly the history of the project and the implementation, and then go into some of the more interesting topics in depth here. Network self models, embodiment, synchronization, a lot of the tools that we're using to get these robots to do interesting things. And then spend some time talking about what we've been doing with robotics, so show some videos perhaps, and just explain a little bit about the direction that we're going over the next couple of years. So I'm not going to spend very long on this slide, as it's probably redundant, as the topic du jour. I will just briefly emphasize the last point on this slide here, which is about how the free energy principle provides a unifying framework that explains how adaptive behavior, perception, and action can emerge from the drive to maintain a stable internal state in a constantly changing environment. This is going to be a theme throughout the talk, so I figure point that out. And this one as well, I'm probably not going to go into too much, but it's worth noting the last 2 points here about organisms don't passively respond to sensory input, but also actively shape their environment through actions that fulfill their predictions about their sensory experience. And then also about how active inference explains how organisms achieve complex self-directed behavior by combining sensory processing with active exploration. This is also going to be a common theme throughout the talk. Now we're going to go a little bit deeper into what we're specifically using for our robotic models and the roots in cybernetics. In particular, the relationship between the free energy principle, active inference, and cybernetics, which might be obvious to many people at the symposium. Cybernetics here, being pioneered in the 1940s, also describes self-regulating systems that adapt to their environments, and also kind of views agents as goal-directed systems seeking to maintain equilibrium through feedback loops. The goal here being to minimize free energy or surprisal in the FEP and active inference. And active inference kind of operationalizes this through continuous adjustment of beliefs and actions. And these cybernetic ideas are foundational, I believe, to how the free energy principle and active inference view organisms as systems that maintain their states within a predictable range, and also resist entropy and disorder by adjusting internal and external variables over time. Now, digging one step deeper into the approaches that we're taking here, I'm going to talk a little bit about the cybernetics of Ross Ashby in particular. Cybernetics Ross Ashby, he formalized many key ideas, homeostasis in particular as the process by which an organism regulates internal conditions within a narrow optimal range in the face of environmental changes and disturbances. He's known for, these are probably the two biggest things he's known for, the good regulator theorem and the law of requisite variety. The good regulator theorem commonly is quoted as every good regulator of a system must be a model of that system, or more accurately, every good regulator must contain a model of that system. And with the law of requisite variety, the common quote is only variety can destroy variety. And, another way of thinking about this is a system must be as complex or more complex than its environment in order to manage it effectively. Or if one system wants to effectively manage or control another system, it must be at least as expressive and at least as complex as the system it's controlling. In the active inference framework, an agent maintains homeostasis by minimizing prediction error, effectively predicting and compensating for environmental fluctuations. So this is how Ashby's ideas really kind of come into play here. Ashby's emphasis on adaptive regulation through internal models aligns very closely with active inference's process of continuously updating beliefs and taking actions to minimize prediction error and maintain desired states. Ashby's view of homeostasis as a self-regulating feedback system is effectively a form of active inference. Both involve an agent using internal models to anticipate and counteract environmental changes, preserving stability and adaptability through continuous self-correction. And Ashby's law of requisite variety here highlights a lot of the successes of active when active inference is successful and of maintaining homeostasis here, relying on the system's capacity to generate a diverse and precise range of predictions and actions. Without sufficient variety of responses, the system would fail to adapt, leading to a breakdown in homeostasis and an increase of predictive error. To exemplify these ideas, Ross Ashby constructed a device known as the homeostat. This was back in the 1940s. This was a demonstration of learning as adaptation as stability. And he believed that behavior is adaptive. It contributes to the maintenance of these essential variables. And there's some various ways of looking at what he was doing here. Some called it an isomorphism generating machine, using feedback to generate distributed homeostasis via ultra-stability. And I'll get more into that in a little bit. But that's kind of the approach that we've taken here at ThoughtForge. And then there's kind of a long description here from one of his books about what the homeostat was and how to construct it. And I'll also talk a bit more about how you would construct a homeostat in a moment here. Here's kind of a quick high-level abstract view of Ashby's original homeostat. And this is abstracted away in a way that reflects kind of modern views of mathematical networks here, where you can define a network as a set of nodes with connections and weights. And then he defined ultra-stability as kind of the mechanism that powers the race of state space exploration, which is used as part of this law of requisite variety. And I'll talk in the next slide a bit about that. The network as a whole creates a dynamic attractor set as a kind of self-consistent, self-reinforcing model. And the network can be seen as kind of a network of reciprocal constraints. The original homeostat only had 4 nodes here, constructed from recycled World War II bomb parts. So this is pre-digital computer era. And this there's a diagram here kind of conceptually explaining how it worked. The original homeostat itself, I think, is at the university right now, but the description of how it actually works is somewhat abstract. We used at ThoughtForge, we used a lot of his technical journals, which were released by his family, I believe, online in the last 15 years or so, to kind of get more detailed information about the properties and how they're constructed to get a more accurate reconstruction of the homeostat. Briefly, I'm just going to talk a little bit about ultra-stability. Ultra-stability is the property of the individual node in this network that enables the group property of homeostasis. The ultra-stability here is talked about in Ashby's books and papers, so I don't think it's necessary to go through a deep analysis of it, but the ultra-stability mechanism is kind of the local mechanism within a node that drives the active process of self-organization and criticality across the network. And it's core to the function of how the homeostat works. And it is constructed by a double feedback loop with a low-level feedback loop that performs like a linear transformation, and then a high-level feedback loop that updates or changes that linear transformation over time. This is just I like including this letter. This was a letter from Alan Turing to Ross Ashby way back when they were kind of debating on whether or not to go with analog computing or digital computing. Here being Ashby being supportive of the analog computing paradigm, and this letter from Turing is basically saying that his his computer, the ACE, was more general and more universal than Ashby's computer because you could implement Ashby's computer on Turing's machine. And it's just kind of a fun little piece of history here. I like including it just to provide some context about the time when Ashby was kind of considering these ideas and why they were kind of lost to time in a lot of senses, at least within the computer science world. And I also like to bring this up because I think it's the first, at least in my mind, it's the first time that we really started conflating computation with cognition here, and where Turing had a universal computation machine, while Ashby was kind of envisioning like a universal adaptation machine, something closer to cognition. And it feels very similar to a lot of the debate we're seeing today with whether or not deep learning machines are intelligent, or if they can get to AGI. I think that a lot of the conflation of computation and cognition goes all the way back to the origins of the analog versus digital debate within computer science. So the next question is, how do you actually build a homeostat? And I took Turing's advice and simulated it. We built a simulation of the homeostat. And the reason why a simulation is useful as opposed to like an analytical solution is because of the chaotic nature of how these systems reach equilibrium. And I used to have a quote here from Ilya Prigogine, but essentially you can't account for a lot of the chaotic interactions in the systems with loops algebraically. The circularities and the chaos that's necessary for these to stabilize require that you do this iteratively, and that means building a simulation that you can kind of step forward and on the fly generate the chaotic interactions, essentially, as opposed to analytically. There's lots of references here with the three-body problem, a mapping of a line onto itself. This kind of concept of deterministic systems. Once you have three deterministic systems interacting with each other, you inevitably get chaotic behavior. That is kind of leveraged as the creative energy that drives the learning process in this kind of a system. The techniques that we use to actually simulate this, and this is, oops, I'm getting ahead of myself here, it come from a field known as software radio. We started out by going through Ashby's technical journals and his writings about how the homeostat was constructed. And we started out by building out accurate analog level digital simulations. And then from there, we kind of abstracted out all of the mechanism-specific machinery in the analog systems that are not necessary for the actual function of ultrastability and homeostasis. So kind of going from this kind of very, very precise analog system to kind of abstracted implementation of these four nodes. Once functional, and this was simple enough to kind of further abstract into more kind of modern day network theory implementations where we can kind of build out very, very large networks, similar to how it's done with deep learning, that could be connected into arbitrary network topologies as opposed to the original four-node network here. And again, just to kind of reiterate here, the network as a whole can be seen as a self-model. Each node in this network is effectively trying to predict its neighbors as it seeks equilibrium. And the local ultrastability process tunes a node's local connections and the resulting positive and negative feedback loops that define it. And these overlapping loops become self-reinforcing or self-repairing over time. Once you've reached kind of convergence with these feedback loops, the final self-producing set of loops is a kind of self-model where each node is trying to predict all the others. And so once all the nodes kind of reach a global consensus, this can be considered self-consistent and reaches homeostatic equilibrium. This can also be seen as kind of like a generative model composed of emergent self-stabilizing homeostatic feedback loops. And these loops are maintaining this homeostatic equilibrium in a critical state. And this is kind of an important note for why it is incredibly sample efficient, which is going to be very important for robotic applications here. The idea here is that maintaining this homeostatic equilibrium at a critical state makes it very, very sensitive to prediction error. The smallest predictive error can trigger a global structural change. So you don't need to back propagate with a large data set in order to change the model, the behavior of the model. A single misprediction can effectively trigger a cascading set of redefinitions where the whole network destabilizes and then reconverges on a new attracting set. This can also be seen as a form of synchronization, and we'll get into that a little bit later. And the prediction error reaching zero kind of marks the establishment of a new adaptive synchronization manifold. And the synchronization first starts with immediate neighbors at each node, and then spreads through the entire network as a set of like compound hierarchies of feedback loops. Looking at the time here, sometimes I could show actually I could switch screens and show demonstrations of this, but maybe I'll share some of the. I'll wait a bit later to do demonstrations of the original homeostat or kind of larger homeostat, just so that we're not switching screens too much, in case that's useful. All right, now we're getting into some of the more interesting stuff, less talking about history of cybernetics. So the homeostatic network itself seems like a lot of work in terms of, there's a lot going on there, and it's not connected to any environment. It's just learning itself reaching to convergence without kind of any sensory or motor actions. So we have this model that can adapt to its internal structure to reach homeostatic equilibrium through a kind of self-synchronization process. Next step is, how do we actually get this to drive behavior? And this took, a couple years to kind of work out the engineering. Conceptually, it's pretty simple, but it will get very complicated very quickly. The short version is that the sensors and the motors, basically we define sensors and motors, and they define how an agent is embedded into an environment. And the network topology separately kind of defines the adaptive capacity of the homeostatic agent's model. The sensor definitions themselves here are kind of defined externally from the model itself. They provide a mechanism to influence the behavior of the system by providing priors in the form of preferred sensory states or preferred environmental states. And these act as teleodynamic priors, kind of externally defined dynamic set points for the homeostatic adaptation. And these sensors can be seen as input attracting sets, which can even be modified in real time or animated in real time to generate, different kinds of behavior from the same model at runtime without having to change the model structure or anything like that. The motor definitions then provide, kind of critical affordances for how the agent can modify the environment to help provide a basis for future sensory predictions. And the preferred states of the sensors become the preferred outcomes of the motors through this reaching equilibrium state. And the model's behavior ends up being biased as desired. So this is how we get it to do useful behavior in a robot, for example, from something that is seemingly just reaching equilibrium. And I guess one important or salient note here is that in a real world environment, it's reaching pure homeostatic equilibrium is actually quite difficult unless you're in very special circumstances. So to expand a bit more on that, the network diagram here is kind of an overly simplified version of our homeostatic network, but meant to kind of visually explain how to think about these, and in particular here, embodiment of these models in kind of an environment here. Coupling a model like this to an environment through sensors and motors is kind of a form of embodiment here, meaning there's a kind of a specific time and place that this model is operating, and there is kind of a temporal component here where the model's sequence of sensory behavior actually is relevant. The inputs to the system are not independent, which is kind of different than traditional, what you would imagine, backpropagation based perceptrons, how they function. And one thing that's interesting about this, and it's worth pointing out here, is that there's no forward or backward, no feed forward or feed backward directions in this kind of network. There's no front or back or top to bottom. The only thing you can really kind of direction you can kind of take from a model like this is distance from sensors or motors, or how close to the environment a particular node is. Otherwise, relative location is pretty much everything. You know, where as an individual node, where am I relative to the rest of the network? And it's common for people to think of machine learning models these days, especially if you're used to thinking about deep learning or traditional perceptron-based backpropagation models, to think of it as a sequential flow of processing. Like I take in an input, I perceive or I do planning on that input, and then I generate an action. That's not how these networks function. Instead, everything kind of happens all the time, and everything's overlapping. What I mean by that is this is not a sandwich model, I guess is the term. Time simply advances, and information moves from one node to another, all in parallel. You know, so in traditional deep learning, it's kind of an atemporal process where information goes from the inputs to the outputs instantaneously, and there's no internal time unless you're working with recurrent neural networks, and there are ways of adding a temporal aspect of it, but the temporal aspect is really a fundamental feature of these types of nodes. What that means is the network itself, the homeostatic feedback loops, come to be dependent on expected sensory signals, meaning the deeper parts of the network are generating predictive signals forward to the sensors, and so in order for this to function, the deeper parts of the model have to be actually actively predicting the sensory inputs that are coming in. This, I believe, also means that it ends up becoming grounded in the embodied experience itself, meaning the homeostatic self-maintenance of this network is composed of environmental signals from the environment, from the real world, or whatever embodiment you've put this model in, and as part of its kind of predictions and expectations, meaning the actual sensory experience is what is being predicted, and so what the model's actually generated is derived originally from this essentially embodied experience. The expectations and predictions for the consequences of motor actions are kind of embedded in the behaviors that are being generated, embedded in the signals sent from this to the sensors from deeper in the network, at the same time as these kind of predictive signals are being sent to the sensory regions. Actions are being sent to the motors. And these actions at any moment are not based on the latest input, but based on predictions about what the model believes is going on in the real world, and how best to kind of satisfy the sensory inputs, or get the model into a preferred state, or a lower energy state, or a lower surprisal state. These motor actions are accompanied in parallel by sensory predictions that are all moving kind of to the I don't want to say the front of the network, but the abstraction that defines the embodiment, you know, to the sensors and motors, in kind of in parallel. This may be familiar to people who have read about perceptual control theory and predictive processing, and very much along those same exact lines in terms of what's going on here, in terms of actively generating predictions to counteract sensory input. The motors here end up being kind of a critical part of making those future sensory experiences easier to predict, or as part of this whole process. Another way to look at this homeostatic process is through synchronization. The homeostatic process can be seen as generating an adaptive synchronization manifold between the agent and the environment, based around minimization of prediction error, basically minimizing the difference between what I'm predicting the environment is doing and what the environment is actually doing. This is kind of a synchronization as prediction process, where when the two systems are synchronized, they can be thought of as predicting each other, anticipating the other. Individual nodes are using ultra stability to predict their neighbors, and then when at equilibrium, all the nodes are synchronized through these feedback loops. The synchronization between the nodes spreads to whole network synchronization at this point. Ultimately, this synchronization spreads across this sensory and motor abstraction between the environment and an agent. So you kind of get a agent environment synchronization process through this. And looking at it another way, these overlapping feedback loops interact and synchronize with each other as part of the homeostatic self-maintenance. As these feedback loops extend from motors through an environment back into the sensors, the model gains the ability to anticipate the consequences of its own actions. And the capacity to synchronize internal states with something in the external world, without direct communication is kind of critical to this. The synchronization means that the internal states become they come to resemble internal states of the other system. When at this kind of synchronized homeostatic state, it's also in this kind of critical state, sensitive to local prediction errors. And this, like I mentioned before, this is kind of critical because that allows internally the model to completely restructure itself or redefine how it predicts sensory experience at the very slightest misprediction. This is very, very critical for sample efficiency. To contrast this with deep learning models or deep reinforcement learning models, you need a very large amount of data to kind of change the domain of the way in which the models are behaving in the world. While in these kind of models, it can kind of change with the slightest one piece of data can kind of trigger global restructuring. So one interesting aspect here is that in order to maintain the synchronization manifold, the network must be able to converge to equilibrium faster than the environment can destabilize it. And so this kind of goes back to Ashby's theory of the good regulator theorem or the law of requisite variety, where the model has to be more complex than the environment is trying to control, and has to be at least as expressive as the environment is in terms of coming up with solutions. Yeah, actually, I was going to go a bit more into synchronization and how once the network is synchronized with the environment, once two elements internal to the systems are synchronized, they can kind of coordinate without direct communication. And this is kind of important to the whole process, so that the sensor and motor abstractions don't have to be the direct link between an aspect of the model and an aspect of the environment. Once synchronized, those two pieces can coordinate in terms of their behaviors will be coordinated without direct communication between the two. So now onto some more fun stuff. The killer application of all this is robotics. Other early avenues we looked into is, for example, applying this for anomaly detection, where you can kind of use the network as a thermometer for surprisal. The other way you can kind of use this applied to like modern deep learning is for like a model drift detection, where you can kind of use the model to detect when a deep learning system is being used on a if the input stream to a deep learning system is diverging from the model domain. So like if the training domain. So if the data set you used to train it on is starting to differ from how it's actually being used, this could kind of be useful for that. But really, I feel like robotics is really the killer application for this, especially when you consider the embodied nature of it. The embodiment is kind of a requirement for how this model works in terms of having to be embedded in an environment with this could be a virtual environment as well, but it has to have some sort of sensory motor coupling to something external to itself. Also the ability to kind of understand context over time and understand that even for a sensory input that is the same as some other a sensory input at another time, the things that have happened previous to it are relevant, and so building up this context awareness through interaction with environment is kind of critical to how our models work, but also very important for robotics. And then real-time adaptation of the model, being able to update the model in real time as actions are being performed, is kind of a really useful technique in robotics in order to enable dexterity and adaptation in the moment that is missing from a lot of robotic applications here. And specific to deep reinforcement learning and deep learning ways of doing robotic control, there's this field known as sim to real. And so sim to real problems come from deep reinforcement learning is where they're commonly referred to, but it's where the models are sensitive to simulation fidelity. The idea being you've trained a model in simulation, and how the model behaves is very sensitive to the specifics of the physics in that simulation, or the actual fidelity of that simulation. And so moving to the real world often shifts the input domain, and deep reinforcement learning and deep learning models are not usually robust to these kinds of changes unless you drastically increase the amount of data through domain randomization, which causes other problems such as the curse of dimensionality. There's all sorts of solutions to the sim-to-real problem. For us, we sidestep all of this by leveraging real-time learning and adaptation. So when the model is presented with something new or unusual, in the moment, we don't separate the training phase from the deploy, the inference phase. It as it's inferring, it's doing the updating and the learning, and this kind of solves a lot of the sim-to-real problems as the model is able to adapt to whatever differences happen in the real world that were not represented in the simulation. So this is a lot of a long-winded explanation of why we went after robotics for applying these kinds of models. To get into the more kind of robotic side of things in terms of technical detail, in terms of how we're actually implementing this, for a lot of our interoperability between a lot of different robots, the model itself doesn't really care what kind of robot you apply this to. So you get a lot of hardware agnosticism where you can take a model built for one arm, robot arm, and apply it to another robot arm, for example, and the model will adapt to any kind of kinematic differences between the two, that kind of thing. This is a diagram of how we fit into ROS. ROS is the robot operating system, and it's the open source academic software framework that is used across that supports a lot of robots. It's not used in a lot of industrial settings, but it's incredibly flexible in its ability to experiment and try new things. And so we've kind of used this as our kind of beachhead robotic stack implementation. These homeostatic models are particularly small, so they only operate like typically about 30K of memory. So they can operate on edge devices, no GPU needed, no cloud needed. In fact, you want to run it as close to the robot as possible to minimize latency in the control phase, and just runs in a single CPU. Because of our implementation of ultra stability and this homeostatic networks are quite efficient, model update times are sub-millisecond. So this enables us to update the model and update that synchronization manifold as a task is being performed. We've clocked the networks being able to run up to 80 kilohertz, but for most robotic control algorithms, 500 hertz or 1,000 or 1 kilohertz is typically fantastic, and most robots don't support anything above that. And there's also some other interesting aspects to the technical side of things where the models are small enough. We're talking 30K here, where analytical explainability is possible, where we can take a look at a robotic's action and actually analyze the homeostatic network to figure out which sensory inputs or which motor output, which sensory inputs led to a particular decision. And because the models are small enough, we can kind of use different kinds of network analysis approaches to figure that out. On the more technical detail side, in case it's useful, our models are built in C++, and we have a Python wrapper, so that gives us a lot of integration to capabilities to lots of different robots, which is useful and fun. So I'm just going to go through some of the applications that we've done in the past, and I could bring up a demonstration and do it live. This was a use case we did for a company for adaptive inspection. So they had a use case where they have autonomous vehicles going through a field, and they needed a robotic arm to kind of compensate for movement or unexpected orientations and configurations of the autonomous vehicle base without knowing ahead of time what it was going to encounter. And so, yeah, this was kind of a fun, interesting, pretty simplistic model we built for them. And you can see kind of a fun video here of it in our lab, kind of tracking this QR code. And going one step further in terms of difficulty, this was another use case from a different customer. They had a challenge of they were seeing an injury with turning high pressure gas valves, and they wanted to automate this with robots. The problem was that they never have a good accounting for what kind of valve or what kind of thing that needs to be turned, what it was going to look like, what the shape of it was going to be, if it was going to be rusty and difficult to turn, or if it was going to be covered in oil and slippery, or if the edges were going to be worn off. So they needed something that can adapt to this high level of variability in real time without access to the internet, because this was on remote locations. And so we built this model for them. And this is kind of a fun little video of it. We've turned this into an interactive demo that we've brought to conferences, which is kind of fun here. This is just recorded on a cell phone. You can tell it's real based on the production qualities. but this was that valve turning model that we created before, except we've just kind of adapted it here so that we can, show off people torturing it in real time, live, as it tries to kind of turn these bolts of various shapes and sizes. Some interesting things to note here. The original model that we built for this only took about 15 seconds to train, 3 examples essentially, and it was only trained on a single bolt shape here, the square, in fact. And then what we do is we kind of show how it can kind of generalize to all these other different cases here in real time without having seen any of these examples before. And at the beginning of the video there, you can kind of see on the screen our internal, it's our internal debugger, but it's a fun visualization because you can see the homeostatic network learning in real time as you kind of move this panel of bolts around. I'm just stalling a little bit. There we go. So you can see those little squiggly lines there on the screen. That's kind of a viewpoint into the 30 of the nodes of the network, kind of updating in real time as we're kind of having it turn these knobs here. Getting into the less interesting stuff, but just to kind of show where we are as a technology, this is a platform we're building. Currently, this is used internally to develop new models, and we have some interesting tools here that allow you to effectively search ranges of topologies to experiment with different kinds of network topologies for a particular task. And then see what the performance looks like in simulation and kind of iterate on this. Eventually, you'll also be able to connect your robot to the platform and download the model directly so that you can go straight from designing a goal specification. We call it a goal specification, but really what you're doing is you're defining those teleodynamic priors in the sensor definitions as part of that embodiment definition. And then you go and you evaluate what topology is optimal for that definition, and then you can deploy this directly onto your robot in the real world and try it out. Next steps, or the direction that we're heading, is kind of interesting. Right now, a lot of the models that we're building are very kind of small and task specific, but we're building them in a way that is recomposable. So the idea here is, instead of building one model that does a task like turning the valves, that task is actually composed of 3 smaller models. And the idea here is we're building up a library of recomposable submodels so that we can kind of recompose them in simple ways to go after new tasks. So the idea here is we can take, right now we only have a handful of submodels, but over the next year or two, we're building out this larger library of submodels that can be recomposed to go after a much wider variety of tasks. So this diagram here is meant to show how we're kind of looking at building up this framework of recomposable models. Eventually, that platform you saw, this one here, eventually we'll probably open this up for the public to go and compose their own models from these recomposable submodels, and then we can even string together, many models together and have a framework for deciding when to use which model. Because they're only about 30K of memory, you can really kind of load up a robot with, let's say 1,000 models, for example, and you can kind of get a lot of generality just from a collection of sub problems being solved individually in a robust manner. So I went through this talk pretty quickly. I figure I'll just end with some current work that we're looking at. Right now, we're working on this is just kind of an early look in simulation of an insertion task. We're working on. What's interesting about this is that we can't use vision for a lot of this, because once the insertion process happens, the arm kind of includes the view of it. So we're incorporating force sensors so that we can kind of wiggle, tight-fitting pieces into a housing, for example. And you really kind of need to build in this kind of nuanced feeling of wiggling something into place. This comes very naturally to humans, in terms of like feeling your way through a problem. And so we're kind of working on building out the submodels needed here for high frequency force torque sensors for wiggling things into place, to kind of broaden the amount kind of applications that we can start attacking with this approach. So that's kind of some current work that we're working on. I kind of blazed through that really quickly. I could show some live simulation demos, but maybe questions. Maybe it makes sense to just move on to questions.
Thanks, Matt. That was awesome. I'll ask some of the questions in the chat. Maybe we'll still have time to see the demo, but that was really exciting. Okay, I'll start with Black Cat, who wrote, very cool. How would you say interoperability challenges change from software to hardware?
That's a good question. There's different ways to think about it. Moving to software, things I think get a lot easier. Hardware is always hard and always time consuming. For us, we're using ROS to get a lot of interoperability between different kinds of robots, but ROS is non-optimal for a lot of situations. And so there is going to be some sort of low-level drivers that we'll have to write that are kind of going to be hardware specific. But for the most part, most robot manufacturers or OEMs, they have an interface that provides some sort of joint control. So the models right now are generating effort-based controls that we then convert into positional-based controls, because that's the most common. Most robots do not support effort-based controls. But pretty much all robotic arms in particular have some sort of joint space control interface. So we can basically, all we need is kind of a driver to translate the output of the model into joint space controls for that particular robot. The other thing that's kind of interesting, and you don't get this with deep reinforcement learning, is that we don't actually specifically tell the model what each motor output does. We do specify how many motor outputs there are from the model. Although I guess we could overestimate. We can give it more actions, larger action space than it actually has, and it'll just kind of learn to ignore, or there will become no correlations between the unused actions and the sensory space, so it ends up being unnecessary. But because we don't actually specify what each motor action is doing, it learns that. Meaning, like it will, in the first couple of milliseconds of interacting with it considers the robot part of the environment. Let me put it that way. So in the first couple of milliseconds of controlling this robot, it will build up those correlations of, oh, if I apply a positive effort on this joint, it moves me away from my target, or if I apply negative, it gets me closer to it. It kind of figures out those correlations, and as a process of it learning how to get to equilibrium, if that makes sense. And as a result of that, we get a lot of hardware agnosticism. So with that valve turning model, for example, it was originally built for a different robot. It was originally built for a heavy 6 degree of freedom arm. The customer ended up deploying it on actually a different heavy robot with an additional actuator. And the model can kind of, we basically added an output to it, but the model can kind of adapt to that situation there. For those videos you just saw, and at that conference, we then took that same model and deployed it on a different manufacturer with a 6 degree of freedom arm, and it kind of just figured out, what it needs to do differently. That robot is really nice because it fits in a suitcase, so it's really great to travel with. So from the moving to software, and especially moving to this particular way of looking at the interface, it buys you a lot of interoperability bonuses that you don't get with other approaches. But you're still dependent on the hardware OEM's driver level interfaces. But generally those are all the same. With the interfaces are all the same, even if spinning up the robot might have different mechanisms.
Awesome. 6 degrees of ActInf. I'm going to cluster 2 questions together. So Arun asked, how much of this is or will be open source? And Alexandra Rorbia asked, wonderful talk, Matt. I'm a huge fan of the homeostat, as you know. Have you given thought to perhaps translating the homeostat to its core set of equations dynamics and contributing them to open source projects like NGC-Learn so others can appreciate its value?
Oh, great question. And great. I'm glad to hear Alex is on the call. These are both great questions. I'm always torn in terms of like what to open source and what not to open source. I think eventually we are going to open source a lot of this. Right now, the intellectual property of this approach is one of the things that is most valuable about our current business. So from a business perspective, in the short term, we're probably not going to open source a lot of this. We are expecting to open up our platform to a wider audience over time. And actually, I should follow up with Alex. We have actually kind of distilled down our implementation of the homeostat, at least. There's a lot of interpretations. I want to say there have been 5 or 6 implementations of the homeostat over the last 80 years or so. And they're all different, which is kind of interesting. There's a lot of room for interpretation. But at least our implementation of it, we have kind of distilled down to a relatively simple set of equations. And they they are very, very similar to kind of the equations used in the perceptron, with a couple of very subtle changes. The subtle changes here having drastic effects. One is that we've added state to the node, which really changes how you think about these things, as perceptrons are generally stateless, and so the adding of the state there kind of adds that temporal notion. So even though it's a subtle change, it has drastic implications for how the actual model works. And actually, I was trying to see if I have it as an extra slide here in the talk. I might follow up with Alex and share those the equations. I'm less concerned about sharing kind of the approach and the equations for our definition of the homeostat, just because these are very, very difficult to implement, and I would kind of welcome more ideas and activity in the space. And I need to take a closer look at NGC-Learn. I keep seeing things being added to NGC-Learn, and it's a relatively new package, but there's a ton in there, and I really kind of need to take a look at what's in there. And if we do open source, it does make sense to maybe integrate that as potentially an option in NGC-Learn. A lot of it depends on whether or not the interface is compatible with what we're doing, and I say that not because as a limitation of NGC-Learn, but more of as a limitation of how people think about machine learning models, as kind of most frameworks that are built around deep learning, their interfaces kind of assume atemporal behavior, where each input is kind of independent, each input output relationship is independent of the others. But I think it's a matter of me just taking a look at NGC-Learn and how it's structured and how to actually interface with it. But I think if we do eventually open source the code, that might be the best avenue to doing it, just because that way it would be alongside a lot of this other great ideas for non-backpropagation based machine learning.
Thank you, Matt, and also really appreciate sharing that insight. It isn't a open and shut. And just because we can open source something doesn't mean we could in that way, or should tomorrow, or whatever it happens to be. So hearing your well-worn experience about all of this is really insightful. Okay, another question from Alex. He wrote, how do you go about designing the structure of your homeostat net? Is it a random graph that you instantiate, or some other graph type? Does it depend on the robotic control problem?
That is a great question, and just right off the start, I'll mention that it's unsolved. It's something that we're still working on. In terms of how we do it now, so longer term, I would love to start with a random graph and then have some sort of metric for evaluating what graph is better than another graph for a particular use case, and we're probably pretty close to there. And then we could have some sort of mutation function, and that way you could kind of evolve what the right topology is for a particular graph. I think that actually has a lot of promise, and I'd really love to get into that kind of stuff. Right now, what we're doing is a half step in that direction. We have found that the topology has a big impact on how good the model is at performing a particular task. Meaning, you can take a random model and then try to have it turn valids, for example, but often it'll do a pretty poor job, or it'll be slow, or it'll be a little wobbly. And so really kind of fine-tuning what the topology is for a particular task is critical if you actually want a really effective robotic control model. And so the way that we've been solving this is for specifically robotic control, we've come up with a way of parameterizing the topology, and this kind of constrains the search process for what is finding the right topology. And then what we do is, in that platform you saw, in this platform, the primary thing that this platform is doing is providing an interface to do that topology search. So in the back end here, when you actually are trying to find what is the optimal topology for a particular use case, what's actually going on is that it's using that kind of parameterized search space and doing a big search. And so we're actually leveraging some cloud compute here for this. Not a ton. It's not particularly expensive. The training process only takes about 15 seconds per model. So what we're using AnyScale, which is built on an open source technology called Ray, which is really good at spinning up, let's say, thousands of CPUs at once. And so the idea here is we can go and spin up 20,000 different topologies and then evaluate, of those 20,000, which one is optimal for a particular use case. And this process takes about 5 minutes. And so we're trying to get that as short as possible, so that this is kind of a compilation time interaction, as opposed to training the model for a day and then coming back and seeing how it performs. You can go and explore 20,000 different topologies and figure out which one is optimal for your particular use case. So that's our current approach, which is kind of like a brute force approach. But longer term, I would love to get to that evolutionary approach where we kind of start with a random model. Maybe we can estimate what a good starting size is, or maybe we have some sort of heuristic for deciding whether or not to shrink the model or grow the model. But to contrast it with deep learning, this is one of the downsides of the approach, is that the topology itself is very critical for good performance. As opposed with deep learning, you can often just go with a larger model and just give it more data, and you can kind of get the same performance as a smaller model. I think this makes sense from a biological standpoint, in the sense that our brains are not just randomly connected; they are evolved over time. And you can imagine how some brains might perform better at certain tasks than other brains. And so I think this topology dependent behavior is not necessarily problematic or wrong. It's just something we have to deal with.
Awesome. I'll read a comment from Scott David. This is, as most emissions from Scott's language model, it's not necessarily a question. So if you have a response, go for it. And then I do have a question that also connects with Ian and a little interoception. So Scott wrote, "It is interesting to consider the hardware-software question of application of active inference in light of the historical encounter of Claude Shannon with von Neumann, when Shannon was encouraged to apply the second law of thermodynamics to his quantitative theory of information, thermodynamics at the edge of tangible and intangible information domains. The ubiquity of the expression of the second law results in it being a foundational vector for interoperability, including across tangible hard and intangible soft domains."
There's a lot there. I might need to take a look at that in text form and come up with a coherent response textually. But there's a lot there. There are a lot of information, Shannon level information constraints you're right, at the hardware level, especially when you're talking about update rates. For example, the model as a part of its embodiment has a temporal aspect to it too, in terms of the frequency of updates of the model has to be consistent. Like, you can't update it 100 times per second for 1 second, and then 1,000,000 times per second for the next second. So there are kind of interesting information theory problems here with Nyquist theorem. Like, as the sensory inputs are coming in, are you getting sensory inputs at a high enough frequency to actually make interesting inferences about them? Or is on the robotic side, there are absolutely control constraints. If you're only able to take an action once per second, you're very limited in terms of what you can do with a robot, as opposed to if you can take an action every 500 hertz, every 2 milliseconds. There's a lot more nuance in the feedback process in the control. So there's absolutely some information theoretic stuff on that interface, in that embodiment definition. For the most part, I don't want to say we've done anything particularly innovative on that side. It's just, these are all things that you kind of have to understand as part of the constraints of the implementation. But definitely send me the text for that question, and I'll try to come up with a more coherent and thorough response. There's a lot in there.
Cool. And the historical part was epic. Okay, here's a question. So Ian, not sure which parts you listened to from prior. Maybe Matt, give a first pass, but I was really interested when you mentioned the difference between the position sensors and the effort sensors. So how does that play out in robotics? And then, like, Ian, to the interoception and introspection angle, in what ways does our postural adjustment relate to positional inference and effort inference?
That's a fun question. Unfortunately, I have a feeling my answer is going to be not too interesting. In terms of, we're not doing anything particularly innovative here either. The outputs of the model are almost unitless in the sense that they'll kind of adapt to their embodiment in terms of, like, so we've kind of been interpreting them as efforts, or, like, you can think of this as like torque controls. For robotics, this is problematic though, because first of all, like, I want to say 90% of robots, or 95% of robots, don't support torque-based controls. That requires there are just a few robots out there that require that, and for the most part, they're confined to research applications. The reason why they exist and the reason why there's a lot of interest in it, especially with deep reinforcement learning, is there's if you can go to effort-based controls or torque-based controls directly to the robot, there's a lot of nuanced behavior you can get. You can get really kind of compliant behavior where the robot's applying just enough force to perform a task. That way, if you bump into it, it's not going to hurt anything, and it'll be compliant. And you can kind of get a lot of nuanced behavior with torque-based controls. But the reality is that 95% of robots don't support that. They just support either velocity controls or positional controls of some kind. And so to solve that, we basically convert the effort output of the model into a relative positional change. And then we basically integrate that relative positional change over time to get an absolute positional control. So not particularly interesting on that side, but it is kind of a technical note that's a bit challenging on the robotic side of things. It does, I hadn't really thought about it enough from an active inference perspective in terms of like, what does that mean for the attracting set that you're bringing in. A lot of it is because it's somewhat disconnected from the sensory inputs, like you know what I mean, like the positional controls end up impacting the environment in some way, and then connecting the dots kind of indirectly that affects your sensory inputs, but it's not like a direct it's not like the positional versus effort outputs of the robot are directly changing how our sensory experience happens. It's more that like it might change the effectiveness of or the capabilities of your robot to alter the environment, if that makes sense. But maybe I need to think a bit more about that because that is kind of an interesting aspect that I hadn't really considered enough.
How does that play out in the body, Ian?
Oh yeah, that's really interesting. I've joined this conversation late, but thanks for including me, Daniel. So yeah, I was kind of listening to that with interest and thinking of, how we, as a human, something simple like the concept of being hungry, and angry at the same time, and how that affects our behavior when you've got competing kind of interests or physiological variables that you're trying to deal with. And then thinking about, okay, a robot, something simple to start off with, like maybe a one of these robotic lawnmowers that needs to go back to its docking station to charge up for fuel. So it needs to end the task it's doing and move back to its docking station and charge up. But as robots get more sophisticated and they're trying to please humans more, but there will be some kind of, I don't know, some limit to its capabilities, its internal processing or power, and maybe at some point it will
absolutely
have to weigh up all of these and come to some computation about what it needs to do next to satisfy its own internal
and this
state.
honestly I think ties into some of the stuff that Alex has been talking to about with like moral computation as well. If I'm going to be honest, the robotic control models we're making are far less complex than an actual biological entity like a human. But you're absolutely right, because you're going to have all sorts of here. Right now, we're kind of having these kind of first layer sensory inputs, kind of defining the teledynamic priors. But you can imagine like a hierarchy where you have like other models that are feeding outputs that feed into your motor controls, because these motor controls are kind of the end point for modifying the environment. But you can imagine why you would be reaching for a cup of water is driven by some other network that's saying, oh, you're thirsty. And so we just, I'm just not nearly there in terms of complexity yet, but I think you're right. Eventually we will be, especially if you want to have robots that are fully self-sufficient, fully autonomous, know when they need to repair themselves, and then going out and performing those repairs, whatever that might be, or maybe it's charging. I think you're absolutely right. I think that's the future, longer term. I love it.
Thank you, Matt. Great times. Till next time.
Yeah, likewise.
Bye.
Hello, Octopus, and welcome to the 4th Active Inference Symposium. Thank you for joining us. We're looking forward to your session titled Cognitive Bifurcations and Mathematical Explorations.
So in case you need a reminder of what the abstract for this talk was, and I had to look this up this morning, thinkers and thoughts have a co-evolutionary relationship. This relationship is especially clear in the arena of mathematics, where mathematicians forage for mathematical statements and structures in a process governed by complex and potentially unstable rules. We will give a partial mapping of the structure of this space, which necessarily relies not only on rigorous mathematical logic, but also on subjective beliefs, metacognitive heuristics, and creative play. So I've done a magic trick here. All of these things are claims that are in need of evidence from my perspective. And the goal here will be to provide some evidence in that direction, but also to engage in conversation. So in the construction of expertise, I have no ambition here to play the role of expert. There are certainly qualifications and evidence that I could point to, my experience as a math professor for 7.5 years, my lived experience as a neurodivergent individual for 42 years, my time spent in an octopus identity for the last 3 years openly, and none of those things makes what I say here more valuable than what you think about them. The only request I will make is that I've given a lot of effort into thinking through these thoughts, some of which were quite difficult, that showed up for me. And I ask that you will give some level of effort towards finding the value in those thoughts and how they can be mapped to your reality. So let's move from the abstract to abstraction. When people think of mathematics in the modern sense, they often begin here as both its value and its difficulty. We might imagine that Bob and Alice both have some cows. Bob has 2 and Alice has 3, and they're curious how many cows they would have if they combined their herd. Alice can bring her cows to Bob, and they can count them then if they have the physical process of counting at their disposal, the cognitive tool of one-to-one mapping between objects and objects. But they can also do it conceptually. One of the things that abstraction enables is the ability to move information about physical perceptions more quickly than the physical things themselves can move. In other words, Alice doesn't have to bring her cows with her. If she can bring the concept of 3 or the idea that she has 3. So this is another aspect of mathematics that is often highly valued and highly contentious in relation to the ways in which we realize and reify scientific practice, education, and other ways in which mathematics shows up in our lives is how are we actually giving a physical body to the concept that we are hoping to represent. The fact that 2 apples are conceptually in some sense the same as 2 cows or 2 fingers is one level. A level above that is the fact that we can attribute symbols to these representations. Anything from 2 interlaced eyes in the Roman numeral setting to 2 in the Hindu Arabic numeral setting to words like 2 and du to 2 dots to 2 fingers. The 2 fingers are physical, yet somehow they're also a basis of abstraction, because the idea of abstraction includes the fact that there must be something concrete to abstract. And this 2 fingers I've included on the page of abstract representations, partially because I like the idea of things having bodies. I like the idea of the number 2 having lots of different bodies. How many bodies can one idea have? But also, I like the ambiguity here between the 2 and the 3, because in some systems, the way that I'm showing this here would be interpreted as 3, and in others as 2. So with that ambiguity in mind, there is no slide 3. Please do not discuss slide 3 later. We will not bring it up again. And in fact, it is not advantageous to you to do so because the claim that there is no slide 3 is an idea wholly owned by 8 arms, 9 brains. And if you want to discuss the fact that there is no slide 3, there will be a licensing fee involved. Thankfully, some ideas are open to discussion with no financial transaction involved. And one of them, as we finally come to slide 4, is a very important concept in mathematical pedagogy called the rule of 4. I think this encapsulates thinking that might have been going on for a while before it was formally published, but the first time I encountered it was in the excellent calculus textbook by Hughes, Hallen, Gleason, and McCollum et al. This was the first calculus textbook I looked at when I was an undergraduate student. And it was also the first calculus textbook I looked at when I was a beginning professor, beginning to teach my first calculus class. I'm afraid that far too many students probably completely skip this section, which is in the preamble. But one of the key concepts that it elucidates is how to think about mathematics. And it's not saying this is the right way, it's saying this is a way, and this is a way that the textbook uses quite profitably. It's called the rule of 4, and it says essentially that when you encounter a new mathematical concept, there are 4 distinct but interrelated ways that one might think about it. You could give a verbal description or a definition. You could draw a graph or some type of diagram. You could use numbers in the sense of data, or you could use a symbolic representation, like a formula or an equation. And the extent to which these are distinct and interrelated highlights the value that each of these may have to individuals as a latching on point for thinking about difficult mathematical concepts in calculus. It also eliminates some of the privilege that might exist around specific representations, around the idea that symbols might be real math, whereas when we explain them at a high level, somehow that isn't real math. For instance, if we look at the types of mathematical works that mathematicians actually produce, it might be surprising to undergraduate students what percentage of this is not what they would traditionally think of as symbolic. And what I would mean here is equations and formulas. Like we get to page 3 and finally we see something that looks like a symbolic mathematical expression. But the majority of the work here is spent on words and diagrams, visuals. A large portion of this is in the theorems, of course, which are something that is a very individual feature of pure mathematics. But let's not get bogged down there. Let's simply say there are many different representations. And one of the challenges of an effective instructor is to map between these different representations so that people who might feel most at home in one of them can use that as a leverage point for accessing the other ones. Based on my background, I'm a defrocked math professor voluntarily, also a chaos magician. And so I'm very, very tempted to try to build a functor between this rule of 4 originating in mathematics and this 4 quadrants model of human experience advanced by Ramsey Dukes in his book known as Sysoptomy, which says that there are these 4 lenses through which human beings can process and structure experience. There's art, religion, magic, and science. It's so tempting to try to do something like say the symbols are the magic and the words are the religion and the numbers are the science and the graph is the art. And I'm going to resist that temptation because I think it might be a useful initial temptation, but the resistance of the temptation provides its value. Instead, I'm going to hold this as an idea. We'll return to it in a moment, where it will play against some other concepts that we're likely to encounter. I will stop here for a moment and say something impromptu, though, which is there's a practice in this world of chaos magic called belief shifting, where the magician consciously and intentionally adopts a specific belief as if it were something they believe to be true. And there's a very related practice in mathematics, which is the construction of the axioms, or the adoption of the axioms. So in mathematical proofs, once you adopt specific axioms or specific assumptions, the conclusions should follow, not without effort, but in a clear logical flow. Mathematicians are capable of adopting different axioms. And this produces what I'm going to call a cognitive bifurcation. So a cognitive bifurcation, since we've already split things into 4, that may be too much. Let's try to get things back together and just split it into two. One place that a cognitive bifurcation might show up in the history of mathematics is in the different types of geometry that geometers think about. So one of the features of modern geometry is the realization that the parallel postulate in Euclidean geometry is not possible to prove from the other axioms of Euclidean geometry. And so the parallel postulate says that given a line and a point not on that line, there is exactly one parallel line, or there's exactly one line that passes through that point parallel to the original line. And if you choose not to adopt this belief, as Riemann played with in the idea of one of his lectures, it opens up a whole new world of non-Euclidean geometry, both spherical and hyperbolic. So the axioms that we adopt and the beliefs that we intentionally choose to consider are powerful tools that can open up new conceptual playgrounds, but also quite dangerous. Alice and Bob probably feel very safe in this world. Even if we don't admit a slide 3, we admit a number 3 to describe how many cows one of them may have. And then the question is, are these all the numbers? And if they are not, in which directions would we be willing to consider? Perhaps we were asking what comes after 5, or after the number after 5. And like a child, we realize that we can continually add 1, and there is no a priori upper bound, and we come across the idea of infinity. Perhaps we start to look for what could be in between the numbers. And so we discover numbers like 1.5 or 1.1. Or perhaps we make a dangerous leap in the other direction, and we admit the possibility that there is a number which says that you have no cows. And why you might need such a number is an intriguing question. But let's say that we do have one. When we introduce a number in this way, we need not only to consider the fact that the number exists, we need to consider the ways in which it will interact with the other numbers that exist. In other words, the rules. So as we begin to, if we want to, we know how to add numbers that were 1 through 5, but how do we add the 0? And this is a cognitive bifurcation, because now we have a symbol that plays by its own rules, and we've opened up a whole new world of numbers to where when we added positive numbers together, they always increased, and we were always heading to the right. The fact that we can now introduce a number where we add it an identity for the binary operation of addition is an interesting split that opens up more possibilities on the left-hand side. And I would say this is a cognitive bifurcation. It says in the definition that I'm adapting from Wikipedia, a bifurcation occurs when a small, smooth change made to the parameter values of a system causes a sudden qualitative or topological change in its behavior. It's hard to imagine a change smaller or smoother than putting the circle here and declaring that it doesn't do anything on addition. And yet there's an immense cultural controversy when these numbers are being introduced. So I'm going to make the claim that mathematical thinking systems are complex systems. I'm going to give the highly unsatisfactory proof by authority that this claim is obvious. One piece of evidence we could point to is that the existence of a parameter bifurcation almost immediately suggests that we're dealing with a complex system. And yet that is not quite the right way to think about it, especially if we're going to be looking at it from the active inference context. So let's ask for more evidence, and let's not accept proof by authority. What evidence do we see for the belief that mathematical thinking systems are complex systems? And one way that we might conceptualize this through a model is at the agent level, where we think about the types of agents who are involved in these systems. I've heard that there would be people here who like ants, so I made sure to include some. And here's my anthill, and here are my ants. And I have these ants foraging for formulas that they bring back to the colony, which then feed other ants. which are part of the ecosystem, the formulas and the symbols that they bring back in this mathematical world of semantics is more than just symbols, right? It's something that actually contributes to the survival of the colony. But in order to do that, it must be converted into other things. So it'd be easy to just try to be efficient through this and reduce it as much as we could to something useful. I'm sympathetic to that viewpoint because mathematics has to be useful at some level to human existence, to justify its existence, I believe. So if we were looking at this on a belief level, on a probability level, we might say something like, with certain axioms as priors, mathematical theorems are simply beliefs such that an agent, in order to survive, who will quickly adopt correct beliefs with probability 1. If you want to make 2 + 3 = 6, you will quickly run into issues in which everything collapses and it ceases to be a useful tool. And I'm not opposed to this model. I just want to say it's oversimplified. Because many of the beliefs that mathematicians choose to adopt and choose to spend their valuable resources thinking about don't have any immediate mapping to applications. For instance, the question of whether or not 0 is a natural number is something mathematicians will argue about. What is the utility in foraging for this belief? Perhaps you can think of one. But I think it speaks to something else that could be happening that mathematicians throughout the centuries have seen, which is that the claims of truth that you make are not entirely limited by the axioms that you assume and by the process of logic. There are larger questions here, cultural questions of identity, ontological questions of what is real. What does it mean for 0 being a natural number to be a true statement? Mathematicians find it useful to disagree about this. The conversations that we have about these things make us better mathematicians, I feel. I'll never forget when my PhD advisor explained to me why he believed that 0 was a natural number. But there's no mathematical proof that can provide this. It's an axiom that you accept or do not when you define these numbers. And when we talk about types of numbers, there's a famous cognitive bifurcation that occurred at some point in history, which is the division, the discovery of the fact that not all numbers are rational. Not all numbers can be expressed as a ratio between two integers. If you're not willing to accept this, then you cannot come up with a solution to x squared minus 2 = 0. And of course, you could, by authoritarian fiat, simply declare that there is no solution to x squared minus 2 = 0. There's a legend that the mathematician Hippasus, who discovered that the square root of 2 was irrational, was thrown overboard by the Pythagoreans so that he would not share this information. And I imagine this as a kind of cyberpunk reimagining of ancient Greek geometry, not as an insult in any way to Pythagoras, who I think would appreciate this, but to imagine that there is a geometer who is not opposed to the idea, but opposed to the pathway by which it came through, and willing to use force to ensure that that dangerous doorway stays closed. So another model of a math person, perhaps that we could view as a boundary between wherever math comes from and the quote-unquote real world. And the real world is full of agents already that we can easily map to. There are institutions, educational institutions, governmental institutions, professional societies. There's politics, where the government may decide certain levels of funding for those institutions. Business, which may choose to fund the institutions, to insert itself into the process of politics. There are funding sources, there's media. One thing that occurred to me as I was preparing this talk is we don't often think of mathematical journals or scientific journals as media, but they are. They're media that's made and constructed like any other. And then is the question of where math comes from. Where does math come from? This is one I've wrestled with a while. One reason is it opens up some doors that from the materialist utilitarian perspective of like a school of engineering feel really strange. Where did Alice and Bob first get that idea of numbers? And does doing math involve some type of contact with these strange things that could happen? We don't see very much of this in our schooling, which is often about producing symbols, producing people who can follow precise rules with respect to symbolic manipulation. And at that point, it can become a type of overcorrection. And I'm sympathetic to this I'm sympathetic to this perspective that opens the door a bit more to the strange, not only by my own temperament, but also through the lived experience of people who accomplished very effective physical and engineering uses of mathematics, but were willing to express that they were sympathetic to this viewpoint. So Heinrich Hertz, for whom the unit of cyclic repetition and a computer processing unit is named for, says one cannot escape the feeling that these mathematical formulas have an independent existence and an intelligence of their own, that they are wiser than we are, wiser even than their discoverers. In other words, if the intelligence is in the symbols and not in the humans who are trying to work with them as tools, this provides a very different perspective on the creation of mathematical thought and on the ways in which mathematical thought not only originates, but also can be applied. It also points out, to some extent, the horror that we can be doing when we do this non-consensual cognitive bifurcation of a person, of people, of persons, into math persons and not math persons, often by their ability to match some preconceived rule to arrive at a correct answer, often with an overemphasis on speed. So as we think about the fact that the people, the persons, the mathematicians, the math persons may be foraging for these symbols and formulas to bring back to the real world, what happens if we begin to give, if we, as Hertz did, begin to give these symbols their own ontology and their own agency, to realize that they are also likely out in the wild, searching for the people with whom they will engage productively. So this takes us back to our stranger ideas, where we intentionally left the door open. And here I'm indebted to Gerhard Meyer, who in his article, Magicians of the 21st Century, pointed to Ramsey Dukes' four quadrants model as splitting reality into the irrational and the rational. I intentionally left the rational box off here because I wasn't sure where to put it. I would put religion in the rational category because there are very clear apologetic logical arguments. It's clear that religion at least attempts to play in the same sphere of the rational as science does, whereas art and magic would be in the irrational category. And I am intentionally echoing the splitting here of the real numbers into rational or irrational, with whatever consequences this might have. To quote Heinrich Hertz again, outside our consciousness, there lies the cold and alien world of actual things. Between the two stretches the narrow borderland of the senses. No communication between the two worlds is possible, excepting across the narrow strip. For a proper understanding of ourselves and of the world, it is of the highest importance that this borderland should be thoroughly explored. And the problem, as map makers in an ever-evolving, and some would say chaotic territory, certainly highly dynamic of this moment in space-time where we find ourselves, is where to draw, where is the border? If this is the border that we're supposed to be exploring for a proper understanding of ourselves and of the world, how do we know when we are on the border and when we may be inadvertently crossing it? And how can we enrich our tools for finding each side and productively bringing ideas from one side to the other, or whatever travelers are wishing to cross, whatever we call them? I've recently been reading this book, Symbolism, by Alfred North Whitehead, and he speaks to this, but he speaks to it in a different way, and in one that I would challenge, which is very intimidating, to be honest. But in this essay on symbolism, he talks about essentially two types of symbolism: the symbolism of the church and the symbolism of language and of algebra. So he initially says that there is a symbolism of the medieval cathedral, but because that symbolism can be dispensed with, it is on the fringe of life and has an unessential element in its constitution. And then he says, and on page 2 here, there is another sort of language, a written language, which is constituted by the mathematical symbols of the science of algebra. In some ways, these symbols are different to those of ordinary language, because the manipulation of the algebraic symbols does your reasoning for you, provided that you keep to the algebraic rules. How can something do reasoning for you if it is purely mechanistic and has no agency? And then he says this is not the case with ordinary language, which puts up that boundary again between words and symbols, that the symbols can do something, the words cannot. So I would disagree here with how he draws the bifurcation between cathedrals and mathematical symbols. Pythagoras would also have quibbled with that. For the Pythagoreans, mathematics was very much a religious practice, and they believed that numbers had a spiritual dimension. But that takes us to very weird places very quickly. I tweeted this. I don't necessarily believe it, but you don't have to tweet everything you believe or vice versa. So let's go to slightly a bit more out there. But this is coming back to relevance, I promise. It has to do with the notion of sovereignty. And so here I'm looking at the article Sovereignty in the UFO by Wint and Duval, where they talk about how sovereignty is constructed. And so this might go back to our definition here of a quote unquote real world. An institution, a government, a nation state, even an individual as being sovereign has a particular construction in the world of our experience. But this has not always been the case. I loved this quote that they said, anthropocentric sovereignty might seem necessary. After all, who else besides humans might rule? Nevertheless, historically, sovereignty was less anthropocentric. For millennia, nature and the gods, which nature would be in science and the gods would be in religion, were thought to have causal powers and subjectivities that enabled them to share sovereignty with humans, if not exercise dominion outright. Authoritative belief in non-human sovereignties was given up only after long and bitter struggle about the borders of the social world. So again, we're trying to place a border in which who what could be sovereign depends on who what should be included in society. And there's a great footnote here. Anthropocentrism need not mean all human beings, since historically many physical humans were not considered human socially. And let me go back here and say that perhaps there's a similar construction occurring. Perhaps this division, some humans are human and some are not. We would not recognize that today, but we do recognize this bifurcation into math persons and non-math persons. And I would say it's equally as social and equally as artificial and equally as dangerous. So where are we now? So I've opened some doors here. Perhaps some of them should have stayed shut. But regardless, they're open for the moment and we can shut them when we wish, hopefully. I love this quote at the end about sovereignty in the UFO. The UFO can be known only by not asking what it is, because this has been totally obverse to my process. Here I have tried to know mathematics by asking what it is, by struggling very hard with its identity as an egregore, as a concept. But maybe some things can only be known by not asking what they are. So I'm sure that this has perhaps been an interesting metaphysical exploration of some different historical ideas and ideas of history. How is this applicable to ourselves as scholars in an active inference environment? Well, what I would like to point at is the ways in which some of these ideas that are already dynamic may be changing very rapidly at this moment. So if we look at the identity of mathematician, if we are solely confined to a meat space identity that has certain connotations, but what do we do with someone like Blue Cow? And I did request Blue Cow's consent to use their likeness and their thoughts. The creator of the first hyperdimensional computing OS and the super prompt, a prompt god, someone who is a self-proclaimed mathematician who does impressive mathematical work in prompt engineering of mathematical prompts via GitHub, and whose appearance is an anime person dressed as a cow. Can they be a real mathematician in the way that we currently conceptualize math? And are the mathematical ideas that they're bringing ones that we are prepared to reckon with as math? And then when they post things like this, what do we do? Self-identified schizo. And it's helpful here perhaps to remember that schizo means split. Another scholar in this emergent, one might call parallel or underground genre, whose work I respect, is Sir Lupin Watson. His conjecture: soon you'll be able to buy an AI hacker for less than $100,000. He'll or she do anything for free. You'll need to pay only once and it will last forever. This is exactly the bargain of the theorem. Once you have proven a theorem once with a finite amount of human effort, it remains irrevocably true and will do whatever you ask it to do for free forever. So if we believe there is a world where theorems come from, what does that say about other objects or other constructions that might share their properties? I don't have a conclusion. If I were going to have a conclusion, it would be going back to the thoughts of slide 3, but one reason I don't have a conclusion is that this is not the end of a completed research journey, but the beginning of something we are all experiencing together. So I'm gesturing at what I know. And then the next question is, what do I hope to know? Well, one challenge that I think this immediately offers, but also an opportunity, is what does it look like to be an institution in a world where these agents, these human agents, are seriously considering the same ideas as you are, and perhaps offering insights that are not being produced at the level of your institution. This may be fringe, but I think it's to be taken seriously. And I offer it because many people will see the work that, for instance, Terry Tao is doing on leading larger mathematical teams that use AI to modularize math and prove more efficiently in an engineering type framework different from the idea of the individual math. It's less likely that the average academic, I believe, would encounter these types of people who are also doing interesting mathematical thinking, not only about the mathematics itself, but about what it means to present oneself as a mathematician or to present mathematical work. So I hope these thoughts have been interesting to you, and I'm excited to see what they may have brought up in the form of questions and comments.
Thank you ever so much, Octopus. I really appreciate the number of different ways that you've kind of viewed this topic. If I may start with a question.
Sure.
So, as you were talking about this idea that the formulas maybe exist and that they're kind of waiting to fit onto something, it was reminding me of a song by the Icelandic artist Björk. I'm not sure if you're familiar with her. Yes. She has a song called Modern Things, where it says all those modern things, they've always existed. They've just been waiting in a mountain for the right moment, and it's their time now. And so, yeah, I was wondering, what do you think about something like the global economy, which it kind of acts like an entity in itself. So it's the invisible hand of the market, for example, but it's the humans that kind of assemble around it and imbue the meaning on all the interactions and all the dynamics.
Yes, I think again that there might be a border. For instance, if we view economics as purely human transactions of material capital, it misses a lot. I think a lot of economists would say that. But symbols are important even there. If you look at a unit of currency, it is imbued with symbols that are highly non-functional, almost overridden with symbols that are highly non-functional. And one of the ways that one can assert authority and or immortality is to issue a coin. And that's what we see now with crypto economic systems, is a debate around the individual sovereignty and the right of who is allowed to issue something that can be used as a unit of exchange. But that's not a new debate. There were certain Roman citizens who had the authority to issue a token. And then the question is, where does the value of that token come from ultimately, right? So again, it kicks back very quickly to questions around beliefs and identity and sovereignty. I guess the thing there is, when something is real, to me, it must have more than just a material component.
Thank you. Daniel, are there any questions from the chat?
There's a lot of great commentary, Octopus. It was a great presentation. Do you have any final comments?
Oh, well, I really appreciate the invitation to be heard and the ability to show up as Octopus. That's so meaningful to me, and grateful to the organizers and the audience, and looking forward to seeing what conversations can emerge from this beginning.
Awesome. Thank you. Till next time. See you, Octo.
Thank you. Welcome to the fourth Active Inference Symposium, Dr. Giacomo Rossettini. We're very pleased to have you here and looking forward to your session titled Placebo, Nocebo, and Contextual Effects, the missed link in clinical practice. Over to you.
Thank you for the presentation and for the invitation to use this talk. It's a pleasure for me to be here for the Active Inference Symposium. And today I talk about placebo, nocebo, and contextual effects showing the missing link in clinical practice. As I mentioned, I'm an Italian physical therapist. I'm involved in clinician and research and teaching session. I come from Verona, that is a city in the north of Italy, and it represents the city of love, of Romeo and Juliet. And if you have never visited, my suggestion is to do it. Before to start, I want to declare that I have no conflict of interest for my speech. I have organized my presentation to discuss contextual effects. Firstly, we will analyze the definition and the constituent dimensions of contextual effects, the mechanisms of action, the impact on outcomes and treatments. Next, we will discuss the possible link of contextual effects with the active inference and the implication for clinical practice and research. Finally, we will conclude with a take-home message. Contextual effects are defined as the effects of the context around the therapy and are generated by contextual factors. Contextual factors were recently defined in the international consensus in which I participated. In the slide, you will find an excerpt of the final shared definition, where contextual effects are the perceived cues that affect both the patient and the practitioner and can arise from previous experiences and the immediate dynamics within the therapeutic encounter, or a combination of both. And from a clinical perspective, contextual factors fall into 5 broad categories or dimensions that you can see represented in this graph. On one end, we have the characteristic of the clinicians with their professional reputations, the appearance, the beliefs and behaviors. On the other side, there are the patient's characteristics with their expectations, preferences and previous experiences. Between the clinicians and the patients, there is the relational dynamics in terms of verbal and non-verbal communication, what we say and how we communicate. In addition to the relational component, the treatment characteristics also play an important role. They represent the rituality of the treatment. Finally, the 5th dimension is represented by the characteristics of the setting within which the encounter is being delivered, such as the environment, the architecture, and also the interior design. Well, all these 5 dimensions interacting with each other influence the overall therapeutic outcomes. The question we have to ask ourselves is, through which mechanisms does this happen? I will tell you in the next slides. Contextual factors have been studied for their ability to induce placebo and nocebo effects, which represent the effects of the psychosocial context around the therapy. And to explain how this occurs, I want to start with a clinical example. This illustration shows a common clinical encounter in which patients with a musculoskeletal pain receive a therapy such as the joint immobilization, therapeutic exercises, or an ultrasound injections. And during the administration of the therapy, patients are influenced by the specificity of the treatment, but also by various different psychosocial cues, such as the clinician's words, the sight and the sound of the healthcare devices, the smells of the hygienic, and also the taste of the drugs when receiving, for example, painkillers. Well, all these cues can influence the patient's perception, shaping the experience in a positive or in a negative way, triggering placebo or nocebo effects. Thus, the positive use of contextual factors can produce placebo effects. When these elements are used negatively, it produces nocebo effects. And the clinical effects of contextual factors can be explained through conscious and unconscious mechanisms of action, such as expectation, learning processes, personality traits, mindset, and even its genetics. However, among the most important psychological theories, expectation, classical conditioning, and social learning are the most widely accepted. The expectation is a conscious phenomenon through which the patient expects that something will happen in the future. We need to consider patients, for example, who are waiting to receive a therapeutic exercises or a manual therapy for musculoskeletal pain. Well, they will predict a positive therapeutic outcome by evaluating all the contextual factors around the therapy we offer as a clinician, such as our words or our behaviors. Instead, the classical Pavlov conditioning is an unconscious phenomenon concerning the past events. In fact, patients can learn over time to associate a certain therapy, such as, for example, an injections, with specific contextual effects that represent the rituality of the technique created by the needles that produce a certain outcome which can be positive or negative. But patients can also learn from others. They can learn from positive or negative experiences of other patients, family members, friends, or from information they get from social media or blogs regarding, for example, musculoskeletal pain. But how the contextual factor works in practice? I will use this image to explain its mechanisms of action briefly. Whenever patients interact with the healthcare context, they are always influenced by the 5 contextual factors. And these elements are encoded by the patient's brain, who interprets them and provides an evaluation and a prediction of their meaning. And if this interpretation is positive, placebo effects are triggered. If the interpretation is negative, nocebo effects are stimulated. And these effects are sustained by a cascade of psychoneuroimmunoendocrinological events at multiple levels of the central nervous systems in terms of the release of neurotransmitters. For example, negative contextual factors can activate the release of cholecystokinin and the deactivation of dopamine and the opioid systems. Instead, the use of the positive contextual factors can facilitate the release of opioids, endocannabinoids, and dopamine. And also different brain areas can be activated. For example, the dorsolateral prefrontal cortex, the anterior cingulate cortex, and the grigio-periaquedutal gray, and the dorsal horn of the spine are modulated. And all these specific neurological pathways translated into changes in clinical outcomes. And using, for example, musculoskeletal pain as an example, if the context offered is positive, the patients will perceive a relief of symptoms. Instead, if the context adopted is negative, the patient will have an aggravation of symptoms. And contextual factors interacting with the treatment specificity are able to influence more the patient's subjective outcomes or the illness dimensions than the objective outcomes that represent the disease component. For example, pain, disability, experience, satisfaction represent typical examples of outcomes influenced by the contextual factors. However, not all the changes of the therapeutic outcomes are due by contextual factors or by the specificity of our treatment. In fact, several confounders can explain the improvements or the worsening of the patient's clinical condition. An example are reported in this graph. For example, the natural history of the disease can explain the natural fluctuation of symptoms, or the regression towards the means, which represent a statistical phenomenon. Or, for example, the presence of unidentified co-intervention, as in the case of patients that present a musculoskeletal pain or receive a manual therapy or a therapeutic exercise and concomitantly receive also a painkillers. Another question we should have asked ourselves is what is the weight of contextual factors influences the outcome? And for a long time, it was a common opinion in the scientific community that about 33 to 35% of the total therapeutic effect depend on the contextual component. And even if it seems limited, it is actually not, because it is a component influencing clinical outcome that we should know and we should use in our clinical practice. And the international debate on the weight of contextual effects has continued to the present day without finding a conclusion. Several recent systematic reviews with the meta-analysis has assessed the weight of contextual effects. What the different authors have observed is that the contextual effects can vary from small to large. And I report here different examples. You can see what happens for non-specific low back pain, neck pain, fibromyalgia, and also knee osteoarthritis. And the heterogeneity in these results can be explained, for example, by the characteristic of the patients, the clinicians, by the characteristic of the condition analyzed, the interventions considered, and also by the characteristic of the statistical metric adopted. So, some students have also provided data on the contextual effects for treatments. For example, in this meta-research, the contextual effects of different treatments was evaluated. And what we can observe is that the contextual effect is progressively higher in treatment with the highly realistic features. To go into details, in psychological treatments, the contextual effects account for the 38%. In pharmacological treatments, it accounts for the 61%. And in the physical treatments, such as manual therapy or hands-on techniques, it accounts for the 65%, 64%. And having reached this point, I think that we need to understand how contextual effects can be related to the theme of this conference, the active inference. And to understand this, we need to start with a clinical example. We need to think about the management of patients with persistent musculoskeletal pain who have negative expectations based on their previous experiences, psychological characteristics, or personality traits. And for example, if you consider a patient with the neck pain that in the past has been exposed to exercises and learned that these exercises produced pain, consolidating a negative internal model towards this. In our outpatients clinic, we offer exercises to our neck pain patients in accordance with the best evidence. And as a result of this direct experience, the patients can have two main outcomes. At first, for example, it can confirm that the exercises can produce pain, or the patients may not perceive the pain, violated their expectations. And this violation of expectation is interesting because it can result in two main scenarios. One adaptive, ideal, where patients makes an update of their expectation and on their internal model, and a dysfunctional one, where the patients consider this violation as an exception to the rule, or as a result to the chance, and therefore maintain it. And this is referred to as a cognitively immunized patients. And we suggest that such a difference in updating responses can be understood, at least to some extent, from a Bayesian perspective. And in fact, the ability to make an update of the patient expectation can be interpreted in the light of the Bayesian model and will depend on the strength and accuracy of the patient's prior beliefs and behaviors. And from a Bayesian perspective, our brain is conceptualized as a predictor machine that generates predictions, known as priors, about the expected sensory inputs. And the integration between the prior and the sensory inputs results in a posterior, the percept, which can be more or less influenced by the prior and by the sensory data, depending on their level of precision. And let us think about the patients with neck pain who has negative prior or expectations toward exercise that represent the sensory input. And if these priors are very precise and reliable, it will be much more difficult for the patient to rely on the sensory input given by the exercises. And the prediction error is really minimal, and the patients consider the experience as a result of a chance or an exception of the rule existing in maintenance of the initial expectations. Instead, if the interpretation are less precise and reliable, it will be much easier for the patients to rely on the sensory inputs given by the exercise, because the prediction error between what it is expected and what it is experienced will be more significant and will contribute to improving the patient expectation by generating an update. And I think it is very fascinating and complex, but it does allow us to think about how we can use the context to challenge or make an updates of the patient's priors. And I will try to help you to understand this point with another clinical example. With this Bayesian model in mind, it is possible to better understand the clinical scenario presented in this image, where we have a patient with a musculoskeletal pain of the shoulder who has had a negative prior. In that situation, the patients prefer not to raise their arms because they have been told that the tendons can snap. On the other hand, we have the clinicians who try to challenge the patients prior to the tools that he has at his disposal. For example, the exercises, the manual therapy, the virtual reality, and the education. But the clinician also has another secret weapon to use that is called as the contextual factors made by words, cues, behaviors, rituality that can influence the patient's brain and the patient's prior. And as an outcome of this challenge, we can have, for example, an expectation violation following by an update, which is realized when the prior with low precision of our patient is updated accordingly with the newly acquired evidence. The patient lift the arms without any pain and without any types of lesions. Another possible scenario is represented by the expectation violation, followed by the maintenance of the dysfunctional beliefs as the consequence of one having a highly precise prior, which is considered really reliable, and therefore the newly acquired information and this confirmatory evidence is not sufficient to disprove and update such strong prior. And for example, in this case, we have a patient with a musculoskeletal pain that during a clinical session managed to lift their arm without any negative consequences to their shoulder, but still believe that lifting the arm will possibly create and lead to the shoulder to break, unlikely to have, for example, a very high precise prior and might discard the positive evidence. For example, the success in lifting the arm, which might be classified as an exception instead of the rule. So, try to pull the string of this speech. What might be the implication for this, from this talk to our clinical practice? The use of contextual factors represent an opportunity to enrich the evidence-based therapy. We know it as a clinician. But as a clinician, we also need to consider that using contextual factors, such as words, touch, the rituality of the technique and environment, could help to challenge the patient's prior and improve the patient's musculoskeletal pain. However, these observations that arise from the clinic need to be supported by data and more study to substantiate their effectiveness. Thus, researchers are called upon to integrate contextual effects into their study on musculoskeletal pain, using, for example, the Bayesian brain and the active inference lens. And to do this, it is important to produce experimental work in the lab and in the clinical work in patients to validate these theoretical models by using, for example, subjective outcomes, but also objective physiological metrics. We are in the end. So I conclude that I want to greet you, wishing you to remain curious clinicians, capable to see the things from different perspectives and accept the complexity presented in the clinic and also within this image. Let's not just focus only on the details, the technique. It is important, but it is not all. Let us always remember that the scenario in which we operate, it is much more complex, and both the context, the moon, and the confounders, the stars in the sky, comes into play. Only if we embrace this opportunity and this complexity, we could find new strategies to best manage our patients with musculoskeletal pain. Thanks for your attentions.
Thank you. Thank you. Till next time.
Welcome, John Boik, PhD, to the 4th Active Inference Symposium. We're really pleased to have you here and looking forward to your session, CogNarr Ecosystem, Facilitating Group Cognition at Scale. And over to you.
All right, thanks, Ian. Again, my name is John Boik. I'm a fellow at the Active Inference Institute. And I will be talking about the CogNarr ecosystem to facilitate cognition at scale, as Ian said. I do want to say that the links for this, there's a bunch of links on the Institute project page. I think these slides will eventually be made public, but in the meantime, if you're interested, you can just simply search on CogNarr and Coda, or CogNarr and my last name, Boik, and you'll find the Institute project page. There's lots of links there. All right, so what is the CogNarr ecosystem? CogNarr means cognitive narrative. And in concept, it's an open source, online, extensible ecosystem, technologies, tools, libraries to facilitate group cognition, especially for large groups. And although there are many, many use cases, the use case that one of the prime use cases is deliberation, strategizing, collective problem solving, and decision making in the large group setting. CogNarr essentially helps, what I like to say is it helps users to tell their story. That is, convey their beliefs to a group about how the world works relative to some situation. And even more specifically, convey their belief model to a group, make the belief model explicit and transparent to the group. So they might answer or address questions like, what's the problem or situation? What happened? How did it happen? What might happen next? Why did it happen? Who does it affect? Who does it involve? What does it mean? What should be done? What can be learned? All of these kinds of questions. CogNarr allows users to tell a rich story. And by rich, I mean potentially long, complex, nuanced, dynamic, conditional, quite different, in comparison, quite different from some kind of online collaborative architecture that, for example, asks you to a yes or no question, or asks you to give a thumbs up or thumbs down on some issue. No, this CogNarr will allow a user to convey very rich information. And there's a back-end computational system that assists the digestion of that information so that the group can better understand the many different stories. So the computational system assists and guides users in constructing stories, helps the group digest the information, make sense of it, assesses stories for their quality. You know, is the story on topic? Is it comprehensible? That kind of thing. And then the backend system also performs inference for queries that various group members might have about a story or for a storyteller. It is important to say that the computational system does not predict the future. That is, it's not going, if a bunch of people, if the issue at hand, say, is garbage collection in a local community, the computational system is not going to assess stories and then predict which of them is most realistic. That's not really its purpose. What its purpose is to convey, to make transparent and explicit the beliefs of members. And the members, when they create their story, when they tell their story, they include what they think will happen in the future. The users make predictions. And also the group assesses the realism then of any of the stories that are submitted. So what is a CogNarr group? A group is a set of people that sense their world, process information, anticipate outcomes, evaluate options, make decisions. And in other words, we can think of a group as an organism that performs cognition. And then the question is what design of CogNarr might actually facilitate functional cognition as opposed to dysfunctional cognition. So examples of groups could be, every group, informal group who like polka dot shirts, a social club, volunteer groups, civic organizations, professional groups, corporations, nonprofits, political entities such as cities, and more. So groups can range from formal to informal, flexible to structured, temporary to permanent, small to large, autocratic to democratic. The platform is really a tool that can be used for many use cases by many kinds of groups for many purposes. There are, of course, some rules to keep it all functional and transparent. And when I say large group, what does that mean? Often in the literature, when they talk about a large group deliberation and cognition, they might be thinking of dozens of people, but here we're thinking about perhaps dozens, hundreds, thousands, millions. This should scale up to cities, states, and perhaps even a nation. Who knows? If I should say, if CogNarr were ever built, if it works as advertised, this is all possible. And maybe I should also say at the moment, this is just I've published I've posted two articles on CogNarr so far, 2 research articles, and that's all that's been done. So this is at the beginning. This is a vision really of what this could be. I'm presenting a vision. So the question is, what kind of design for CogNarr would allow some large group, say 100,000 people, to gather online synchronously or asynchronously and share the potentially complex dynamic belief models about some situation? How could that be done? That's the question here. And obviously I have some ideas on how that could be done. So, but first, maybe I should say that the CogNarr project is inspired by active inference, and in particular, active inference from the vantage point of this project, active inference provides a description of functional cognition. That is, as I think everyone probably knows by now, watching the seminar, that cognition, we can idealize it as maybe a 4-part cyclic process of predict, act, sense, and learn, and it involves many components. For example, memory, recall, attention, and the entire picture of that process can be as it plays out in a human or an agent, it could be either functional or dysfunctional. For example, an agent that it cannot predict the future with accuracy is going to make decisions that are suboptimal in general, typically. So that would be an example of dysfunctional cognition. If you can't remember what happened, or you can't predict accurately what's going to happen in the future, those would all be indicative of dysfunctional cognition. So in active inference, an agent favors choices that ensure the greatest resolution of uncertainty under the constraints as preferred outcomes are realized. And all of that provides a framework such that the components of cognition could be recognized, and each component can be focused on as a design element, and the process of cognition in any group could be assessed, whether that is a functional or dysfunctional or somewheres in between. And of course, that would be a multi-valued scale. So what is CogNarr really? CogNarr essentially is designed to be part of the cognitive architecture of the group that is using it. That any organism that performs cognition has some kind of cognitive architecture. For an animal that involves a nervous system, it involves for a human it can involve external objects such as computers and tools. And for a group, it includes a set of norms, rules, mechanisms, institutions, sensors, analytic processes, systems, and any other procedures that facilitate or guide cognition. And then CogNarr is obviously designed to be a component of the cognitive architecture of the group that uses it. And viewed differently, and I'll talk about this more in a moment, CogNarr technology provides a means to digitize and make explicit a person or an agent's belief model. And in that sense, some of the technology behind CogNarr could be used far beyond CogNarr. Could be used in medicine, psychology, and unlimited number of other applications of how you would take an agent or a person's belief model, make that explicit in a way that computation can occur, and include that into some kind of inference models or generative models. So CogNarr stems from some past work that I've done. And it's this past work, that CogNarr and this past work are related in that all of it is about cognitive architectures. In the past work, I was looking at social systems as cognitive architectures. And by social systems, I mean economic systems, financial systems, governance systems. I view those core societal systems as a means, as a part of the cognitive architecture of the society that is using them. That is, we think through our governance systems, we think through our economic systems, we make decisions that affect our world through our economic system, for example. And the previous projects asked this question: out of all conceivable societal systems designs, and I don't mean conceivable in, capitalism and socialism and the way it's been implemented in the past. What I mean is like blank slate. Out of all conceivable designs for economic, financial governance systems, which ones might be most fit for purpose? And that purpose is cognition in the active inference set. So reduction of uncertainty, accurate prediction of the future, attaining those conditions that allow for thriving of the population, those things. And I propose in this past work a path, really, of how such a project could be implemented, how, what it would do, how it would go, how would you test new systems, and so on. So I referred to this earlier work. And again, the links are all on the CogNarr project page, if you can find that. All right, so what is maybe the core element of CogNarr is what I call a story graph, and essentially it's a meaning representation. It's the explicit representation of a user's belief model. And this, of course, is a very difficult problem to solve. How do you take some belief model that is in say the mind of a person and put that down on paper, so to speak, such that computation can occur with it, inference can occur with it? This is a very, very tough problem, but I think there's possible ways to move forward with it. I think I mentioned, or I should mention, that there was 2 papers published on CogNarr. The first paper is more of an introduction overview. The second paper is really all about, it focuses on the potential meaning representations. So story graph is the sort of the core innovation on which CogNarr is based, and its story graphs are used to curate, understand, reason with, conduct inference on high quality information about human experiences, beliefs, and expectations. And essentially the way it works is a user might type in or say some passage, a few sentences perhaps, a thought, and that passage would be translated into what I call a story graph fragment, just a small little graph, a meaning graph. And that little fragment would then, the system would merge that fragment into the growing story graph, the overall story graph. And then eventually by inputting passages or after passages, the story graph gets built up, the meaning representation gets built up. And then once it's complete, or once it's almost complete, then it can be translated into alternative meaning representations that might be appropriate for various, logical models or other kinds of models, probabilistic models. can maybe be translated more directly into some types of probabilistic models, and could also be translated into a natural language. So in time, eventually, if CogNarr is successful over time, it should be possible to have the system read back your story. Like, tell me, read this back to me, and let me make sure that it's what I think, what I'm intending it to be. Even in the far future, it might be possible to make animations as an output of this, a little movie of this is what I think happened, and this is what I think will happen in the future. So what is a meaning representation? I have a picture here of a abstract meaning representation. That's a very common one used in the research world. In natural language inference, there's in the research world, there's lots of different types of meaning representations. This is just one of them I'm using as an example. And this is for a story, a sentence. A similar technique is almost always impossible to apply to other crops, such as cotton, soybeans, and rice. And you can just, I won't go into detail about this, but you can kind of see that there's a graph and various words are connected to each other. Ideas are connected to each other. Concepts are connected to each other. And this kind of meaning representation is used throughout research. And the story graph, you can think of a story graph as a much more complex version of this. It consists of layers. One layer might be predictions that the story is making about the future. That could be one layer. But a story graph is actually more like, instead of this sort of static picture like this, static graph, a story graph is really more like a movie. It's an evolving graph path, really. And it involves high dimensional vectors of word meaning. So it's far more complicated than this, but this gives you a really rough idea of what I'm after. CogNarr has many use cases. If CogNarr were successful, it could be ubiquitous in social life. So a group, and there again could be all kinds of different groups, many different groups, defines a group event, its topic, its purpose, how decisions were made for this event, what kind of methods and rules will be used. The group then invites people to participate, and communications in this for this group event could be many to many, many to one, one to many. I have examples of all of these in the paper, but and I'll go over a couple shortly. Use cases could be decision-making, customer service, emergency reports, public polling, instructions on how to build a shelf or something, how to run a machine, system descriptions of how this system works, educational use cases, and more. And the later versions of CogNarr could include role-playing, strategizing. Here's what I believe. Here's what I think my competitor believes, and I'm going to do this. What would my competitor do if I did this? Or all kinds of various versions of strategy. How do I get the girl? Should I wear a suit and tie? Should I wear jeans? How should I act? Like whatever the issue is at hand. So this is an example use case for decision making that I've written out a little text here, but obviously this would be passages that a user is inputting into the system, and a graph is being created, as passages are implemented. So this person says, whatever this issue X is, we better first address issue Y that caused X, and issue Y started when blank, and it has the effect of blank, and if we don't solve Y, then we can't solve A, and this is likely to occur if that happens, and just on and on and on about some kind of conditional story, complex conditional story. And in this kind of setting where it's group decision making, what could occur is that at the top of this graph here, story input and editing, there could be 10,000 users or something, 10,000 members of this group. They each create their story, and the system would be helping them create the story too, to make it easy. And then after, say, the first round of input, the system would perform a bunch of computations, assess what the variety of different stories are, report back on how stories cluster with each other and all kinds of other things, story quality and story components and all kinds of things, so that the group can better understand what the picture of all these stories is. And then there would be opportunity for group dialogue, feedback, story digestion, asking questions, users asking questions about different other people's stories. And then after that is finished, then we can go back to the beginning and users see everyone's story and all the results of assessments. And then maybe they want to change their story to reflect what has been said. Maybe I'm involved in this group, and I put down my story, and then I eventually get to see what other people are saying, and I think, oh, that's a good idea. I want to include that piece in mine. I like that, or I don't like this, or I'm going to comment on this one of this part of this guy's story. So over a series of rounds, the idea is hopefully that the belief of the group would start to coalesce around core models. Maybe one person's story really captures the group sentiment, or maybe the group as a whole, the synthesis of their stories captures the group's sentiment. And over a series of rounds, the thinking of the group, the belief model of the group, starts to coalesce around central themes. And then there could be voting at the end. Various kinds of voting would be possible. Another use case is emergency reports. Again, this is a text passage, but it would be formed into a story graph. But somebody might say, hey, I might call a utility and say, I just witnessed an accident near this intersection. A large truck began swerving. It was wet, shouldn't have been going so fast. There have been many accidents at the corner. As a kind of an aside, the truck hit an electric pole, the wires started sparks in the grass. There's a school nearby. All of this, there's all kinds of implications about this story, right? The implication is that there's some kind of danger. Maybe the operator should send a fire truck, ambulance, send the police, something like that. There's there's implied dangers to the utility workers. This is just a short little paragraph, but it's actually quite rich, and there's opportunity for many kinds of. There's quite a lot of information that can be inferred from this little story that isn't said explicitly. In the second paper, I list a desiderata of about 20 aspects of what a meaning representation should be like, or should be capable of doing. I just list a few here, but it should be graph-based to be amenable to computation. Should be capable of handling document-length stories. The equivalent of, say, a few pages of text, or maybe even a chapter of text in a book or something like that. And should be able to handle a wide variety of linguistic phenomena. Should be reproducible in the sense that similar stories should make similar graphs. And there's more and more and more. Components should be compositional and reusable, and more. I won't go into any more detail on that, but there is a whole list of requirements. So the last couple of slides are just sort of fun to think about how some of this might be done and what might happen in the future. Are there applications of category theory here? This last paper on group interactions, belief sharing via sheaf and topos theory, I think is actually might be quite appropriate, because that's exactly what is happening in this group setting. The group is sharing their belief models. Those belief models are they evolve according to how the group thinking is going. They're unifying, or generally the group would be unifying around one or a few stories. And I think all of that could be studied mathematically, using some ideas from category theory. But also in category theory, one of the ideas of category theory is to reduce the complexity of a project or a system. So that's important because this is obviously a complicated system. C-set property graphs might be a basis for story graphs. Functors might be allow for graph to graph, graph to text, and other kinds of transformations. Some ideas from category theory might allow us to zoom in and zoom out. If you can imagine some very complicated story graph, but the user just wants to focus in on just one little piece to verify that the system understood him or her correctly. And for that, you might want to do a kind of a zoom in or zoom out summarization of some more complicated components of a story graph. So there's applications for category theory, and there's, I think, applications for Friston's From Pixels to Planning paper on renormalizing generative models. That I think there's potential there too, because a graph really represents a path, an evolving path of the graph itself is evolving, right? It's like a movie, as I said earlier. And so the renormalizing approach might be potentially useful there. And there's many opportunities for agent-based agentic models. For example, group members understanding each other's beliefs. So that's about it. Yeah. And again, the project page has all kinds of information about this.
Thank you, John. Ian, if you have a question, otherwise I can read one from the live chat.
Oh yes, maybe a quick one before the live chat. So it's a lovely optimistic sort of view that every member's story can be heard and understood and contribute to the collective, and it's sort of making me think about citizen kind of involvement in cities and knowing what issues are important to a community. Then is there a way that it can help with sort of this perennial issue of top-down opinion and bottom-up needs and wishes? So how would you weight let's say the stories from opposing members,
right,
of a group, if there's
right,
that sort of power
so there's the bigger issue that around what you've just said, and that's how do you keep this whole thing to actually represent functional cognition? And obviously, if one party has enormous power and another party has little power, that's the cognitive process is not going to be functional. So it quite clearly a lot of work would have to go into the design of this to prevent one party from dominating the entire discussion, for example. And there's work would have to go into preventing hijacking of the process for some dysfunctional means or purpose. But some of that is quite addressable. So it should be. It seems to me that it would be quite possible to create a system that is fair. If everyone has only one voice, that's one way to prevent one person from dominating the discussion. That is, on a very simple level, if there's not bots, if a person can't create imaginary bots to be broadcasting their version of what should happen, then the person would only have one voice. And over time, maybe a group would get to know its members a bit, and some members would be more respected than others just naturally because they've contributed in the past, they've had intelligent things to say, they are experts in this field or whatever. So we only have a minute here, so I can't go into much further of how that would, the ways that kind of fairness and transparency and all that kind of stuff would be addressed. But I would think that there's many opportunities to do so.
Thank you, John. Thank you. Awesome presentation, and looking forward to continuing the collaboration. So, see you.
Welcome, William Gebhardt, to the 4th Active Inference Symposium. We're looking forward to your session titled An Introduction to NGC-Learn, a computational neuroscience library. Over to you.
Yeah. So today I'm here to talk about the NAC, the Neuroadaptive Computing Lab's Python NIM tool called NGC-Learn that is really focused on getting your ability to prototype your ideas and work with your ideas in the field of computational neuroscience quickly and efficiently in Python. So before we're going to start off with all this, first we kind of want to briefly cover what we mean when we talk about computational neuroscience. So this is just the study and investigation of brain function using mathematical computation and tools and theories. We have a focus on biologically plausible and biologically grounded systems and neurons and neuronal systems, and we pay very high attention to the constraints and dynamics that are found in the real world when we talk about these. For instance, we model things like, we have the resistance from membrane potentials, we have currents, we have a bunch of other various internal components to everything that make sure that we are modeling faithfully all of the neurons and components that we can find inside NGC-Learn. We don't just take from humans. In fact, there's a couple of various things that we have that are based on findings for things like rat hippocampal neurons and whatnot, for stuff like synaptic plasticity and transfers. So we kind of look at this biological interpretation of the world. And so one of the main things that we also like to look at is like, what is realistic when we talk about an interpretation of our world and how biology looks at it. And so, like, for instance, our human eyes, it's been studied that they process information at about 60 frames a second. We can certainly detect things that move through our visual field faster than that. But as far as like visual updates and whatnot, once you pass 60 frames a second or 60 updates per second, we have a hard time distinguishing. And then also processing for a lot of things in our brain is not just we see an image, we process the image once, and then we just sit around idle until a new image comes into our brain. A lot of the time what we'll end up with is we'll end up with a continuous stream of data coming into our brain, and then we have to do continuous updates and processing on that. And it's that continuous update and processing that we really are trying to hone in on and identify here. We also so we do all of this inside of a biological framing. So we use neurons. Now, these are not necessarily neurons like deep neural networks like to talk about neurons, where it's just an abstract point in space. We actually model them as physical objects that have things like internal states, and that also embody what they look like in brains and just other neural structures in the body. We have our like the center of the cell where we store a lot of our values. We have synapses that connect these to other neurons later down. And one of the key things that our library very much highlights is the use of spikes in spiking neural networks in order to actually achieve all of this happening. What this means is that instead of working in continuous values where you have a real valued image coming into your network, and then it passes through your entire network as a bunch of other real valued numbers. Images, as they enter into our networks, tend to be converted into what are known as spike trains, which are just a bunch of discrete either ones or zeros on whether or not there is signal. And then from neurons to neurons in our systems, we tend to transmit these things only as spikes. So everything is dealt with discrete signals rather than continuous signals. And then the other thing that we really heavily rely on in NGC-Learn is stateful modeling. So as we're dealing with these models that are constantly taking in signals over time, it's to be expected that we require many signals and many iterations over the signals before we will actually produce any given output. What that means is that all of our neurons have internal states and are stateful. And so we can, for instance, stop getting any input and we can actually still watch what happens to the neurons in our models as they basically return to their rest positions. And so we have our biological components that have our internal states, and then these states do change over time. And so we tend to think about all of the models that we build with NGC-Learn and just computational neuroscience in general, somewhat akin to state machines. with the idea that we progress through time by changing the state of our own model, and then there's certain actions that happen that can affect our model and transform it from one state to another. And so that's kind of the basic framing behind what we're going for with this, right? We're not trying to be the next TensorFlow. We're not trying to be the next deep neural network library. What we're trying to be is we're trying to be a library that is specifically catered to computational neuroscience and the biologically inspired and biomimetic systems. So why do we need this? So building these complex systems has a lot of overhead. If we need to make a system that tracks all of the different internal states of all models and can communicate between different components easily, that can run efficiently. So at the bottom here, you can see here. So in one of these models that we built early on, we had a pretty standard spiking neural network that was not big by neural network standards, that took about 8 hours to do an epoch of MNIST. And that is due to the fact that when we are looking at an individual image in MNIST, we have to go over it. I think this model was doing 200 forward passes effectively over it. Basically, we take the image and we convert it into a spike train that's 200 time steps long and feed it through a model. In addition to this, because in our brain we don't have really the concept of mini batching, you don't perceive 18 different worldviews at a time and then update off of them, or 8,000 or 500 or however many big batch sizes have gotten to these days. We do everything in a continuous online updating. And so because of that, we can only look at one image at a time. So if we're doing roughly 200 forward passes per image, one image at a time, this can get really, really, really slow. And up to 8 hours for us to do an epoch over MNIST. And so when we looked at some of the other existing libraries out there, like Brian2, BindsNet, SNN Torch, and whatnot, they all worked, and they all have their strengths to be able to implement these systems. But some of them very much operate like black boxes, with the idea that you can modify parameters on the outside, but then you're entrusting that your various existing library is doing everything you expect it to mathematically inside. And what this also does is this makes it hard sometimes to actually either dig in and see what those dynamics specifically are, or even just want to modify some of those dynamics. And so what we wanted to focus on was building something that was incredibly modular, but still fast, right? So you have this trade-off between, you can have a system that's incredibly fast, but incredibly limited in what you can do with it, or you can have a system that is incredibly modular and can do a bunch of things, but tends to trade off speed. And so we were kind of aiming for the middle of that, with errored more while trying to expand it to make sure we didn't sacrifice too much speed to be able to do all of the modular stuff that we wanted to be able to do. And so with that, we have some highlights of NGC-Learn here. So first off, this is an open source project. It's available on pip. It's available on GitHub. We are an active development base, which means that if you write us messages, like if you put errors or message notifications in GitHub, we'll see them. If you email us, we will see them. We will respond to them. We can work with you on them. So NGC-Learn specifically is built using JAX, which is basically built on the underlying library called the Accelerated Linear Algebra Library, or XLA, which is a bunch of C Python bindings wrapped around basically C functions for doing linear algebra. And what that allows, and so those are really fast because we get to use C. So JAX is built on one step on top of that, which basically creates a bunch of NumPy bindings for said C Python functions. And so JAX has this really, really cool and component to it called just-in-time compilation. And what this allows you to do is you can put a pure method into JAX's just-in-time compilation, and it will give you a pure method out. But when you run that method, it runs entirely in C. It does not actually do anything in Python. And so the advantage of that is if we can take our giant models' state transition functions and make them be pure functions where you give it an initial state and it gives back to you the final state, we can pass that into JAX's just-in-time compilation and basically take the entire model and its entire state transformation, and we can do it really efficiently in C. And actually, as a matter of fact, we can take that and we can do state transitions hundreds of times before we ever return to Python. And so this is kind of how we get that speed up. And in our testing, that same model that took 8 hours to do an epoch over MNIST, we got down to roughly 15 minutes, 12 to 15, running on the same hardware to do an epoch over MNIST, which is, a 40 times speed up there. There have been other examples that we've had that have gotten up to a 50 times speed up. This is not me promising that you will achieve a 40 or 50 times speed up in your work. This is just me saying that, like, sometimes you don't realize how fast it can be running. We also wrote this so that way if you want to be writing your own new components, because we all know that, past models are great, we can work with those are great, but the fun part about science is actually getting to build new things and try out new ideas and new modules. So we made it really easy to write new stuff, write new components, write new write new learning rules, write new, neurons. All of this stuff is really easy to write, and they wire directly into the compilers without any problems. And then one of the other things too that we have is that it interfaces with Intel's Luihi 2's simulator. Now, the Luihi 2 is a neuromorphic chip developed by Intel for doing neuromorphic computing. This is basically taking spiking neural networks and putting them at purely a hardware level, which is where all of the energy efficiency that you've heard people talk about with spiking neural networks comes from, is the fact that when you put it onto a neuromorphic chip, it's really efficient. And having worked with physical Luihis and whatnot, it can be somewhat of a struggle to actually get those chips running and get them working well. And so what that kind of comes down to is when you want and you actually get access to one of the physical pieces of hardware, you want to make sure that your model probably at least works in their simulator that they provide. I will tell you that the simulator does not one-to-one match with reality, but that is something that Intel knows and is aware of, and I presume working on. But what we allow you to do is that we have a sub-project of NGC-Learn called NGC-Lava. And what that gives you is a couple changed object classes and a couple more restrictions that you have to follow while building things. And then after that, you can run NGC models directly in the Luihi 2 simulator. This means that you can take your model and you can run it on a GPU, you can run it on a CPU, and you can run it on the Luihi simulator, all without actually having to change any of your code base. You're basically just like changing a flag somewhere on where it's running. And that's all you have to do for that. So, how do we actually build models in NGC-Learn? Because now that I've pitched it to you as this great tool, let's see if it holds up with how easy it is. So, overall, it's a modular system, right? So the goal of NGC-Learn was to be incredibly plug and play. And also, it has to be effectively one giant state machine. So we can see on the right here, we have this context block. Now, for us, a context is generally our model, but sometimes you'll have multiple models that you define, or some models that are defined inside of one giant overarching context. It's just the container that holds everything. Now, the parts that we're the most interested in, the things that actually do all of the updates and hold all of the fun bits of research, are the components. And so components tend to consist of a couple of things. So we have parameters, and we have compartments, and then there are the cables that connect them. And we'll talk more in detail about what each one of those are in a little bit. But the components are the new things, right? If you build a new neuron, if you build a new weight matrix with a new learning rule or whatever, those are what you're building. You're just building those little tiny parts. And because of the way that they interface with one another, is you don't have to worry about, oh, does this have the right number of outputs to line up with the right number of inputs and whatnot. If you build the components in such a way that you follow just the standard practice that we've set out, all of the data will flow from component to component without any problems. So if we want to actually talk about the components, these are the backbone of what you're doing. So on the left here, I have the leaky integrate and fire neuron. Now, this is one of the most common neurons to see when you're starting out in spiking neural networks. It is the idea that you have an internal voltage that slowly builds up, passes over a threshold, and then depolarizes and emits a spike. And it does that by taking in current, and V equals IR, and you do current times resistance, and you get a voltage, and it slowly builds up your voltage. So inside of your LIF neuron, or our leaky integrate and fire neuron, we have a couple of fixed parameters. Now, for us, fixed parameters are values that don't change during runtime. These are the static parts of your model, but they're not fixed across all of your components. And what I mean by that is that I can have a leaky integrate and fire neuron like with a voltage threshold of 1, and I can have another leaky integrate and fire neuron with a voltage threshold of 2. And you can build both of those. It works perfectly fine. But the 1 and the 2 can't change while it's running because just of the way that it all works out internally with the compiling. But for instance, here we have some fixed parameters. We have neuronal units. So when we talk about having a neuron or a component that is a neuron, it is more in reality a layer of neurons. So for us, and neuronal units is just the number of leaky integrate and fire neurons that exist inside this little component or cluster of neurons. They all have a voltage threshold, and then we have tau m, rm, a v reset, and a v rest. These are just all of the various parameters that you need to get a leaky integrate and fire neuron running. And then below all of these, we have the compartment values. Now, this is where you actually store the stateful part of your component. These are the values that change over time. These are the values that we are transmitting from component to component. And so, for instance, here in our leaky integrate and fire neuron, on the left, we can see that we have current coming in on the left. We have this voltage value that kind of floats around in the middle because we're not expecting to have it as an output. We have our output spike, which is just whether or not our voltage did spike. And then we have time of last spike, which is just, well, the last time step that it spiked, because there's multiple learning rules that require that. And so what we can see here is that if you can kind of think about the various parts of your model that you like to build, the neurons, the weight matrices, any other auxiliary system that you have in your model, if you can kind of fit it to a component, it's incredibly straightforward to get these to be built. And then once you have them in component form, you can then plug them into any part of any model. So then what we're going to talk about here is we're going to talk about cables. Now, cables can be a little bit confusing at first. So cables are what actually connect our components together. So if we look at the top, we have component A, and we have component B. And basically what this is that, and then they're connected with the cable. And so we have our output compartment, which is the brown box that's on the right side of component A. And then we have our input compartment that's on the left side of the compartment's box for component B. And then they're connected with this cable. And so the idea is that data will flow from the output compartment of component A and get copied into the input compartment of component B. And so this is basically how we get data to move from one to the other without necessarily having it know where it comes from. So this was one of the main things that we wanted to make sure was a founding principle of kind of what we were going for when we looked at the component and cables, is that a component downstream, so in this case component B, it doesn't necessarily need to know, and it shouldn't know, where the incoming values are coming from. So these cables are all one-way cables. You cannot go backwards up the cable. Basically, the components are just told, hey, this is the value that has been transmitted along this line, and thus this is the value that you have, and you don't get to know where it comes from. Now, what this does mean, though, is that sometimes what we'll have is we'll have a component that knows that it's getting values from two places. For instance, in the bottom explanation, we have component X and component Y. Each one of them have an output. but we're trying to put both of their outputs into the same compartment in component Z. Now, if we were to do this without the summation that you can see, what would happen is the value from component X would come down and it would get put into the compartment in component Z. And then the output of component Y would come down and it would also get put into the compartment of component Z, effectively overriding component X. And so, but what we do have is we have this concept of operators, which are just simple transformations that can be done to the data that are being transmitted along cables. So in this case, summation. This is you just have two pieces of data that all flow into this little summation operation that just flows into your output compartment. It's important to note that the value, like the intermediate values inside of things like summation, are never stored anywhere. They are purely just an inline operation that happens. Yeah. So that's all you actually need to build a model, right? Is you have components and you wire them together. That pretty much talks about everything you need to know for the physical parts of your model and how they talk to one another. But that doesn't get us anywhere. If I just hand you a model that has a bunch of wires around it and a bunch of values in it, but I don't tell you how to actually change any of the values, that's fairly useless. In addition to that, it's not a particularly great, just research project. We all care about how do these models adapt over time. We all care about that whole temporal and evolving nature of everything. So with that in mind, we want to talk now about how do we actually transition a model and what goes into that. So for transitioning a models across, so we have state transitions across just a component. So if we just zoom in on what a component is, we have component A here, where we have our fixed parameters across the top here. You can see we have 4 fixed parameters. And then we have 2 different state transitions that we're going to allow. We have the reset transition, and then we have the advance transition. And so in this example here, we can see that the reset transition takes 2 fixed parameters in and sets values via like the dashed lines that we see, sets values into all 4 compartments. Or we have the advanced transition that takes in, again, 2 fixed parameters, but different fixed parameters than reset. And then it also uses 3 of the compartment values. We can see the input compartment value on the far left and the 2 floating compartment values with their solid lines that go into advance. And basically this is, we have written an advance function. So basically this is just, we're doing a state transition called advance that requires 2 fixed parameters and 3 dynamically changing compartment values. Advance internally does some transformation of this data and it outputs 2 values. One of those values gets looped back into the floating compartment that we see on the right, and the other one gets sent to the output compartment that's also on the far right. And that's really all these state transitions across components are. When we write them internally, and we'll look at some of what this looks like in a little bit, what we'll notice is that each one of these transitions is relatively simple, right? It's just, you just take values in, do something to them, and send values out. And that is really, again, you'll see this throughout all of NGC-Learn. That is basically how it all works under the hood, is that we take values in, we transform them, we send values out. And we don't necessarily need to know where those values are going or where the input values came from, that we just know how to move them around. And it's important to note here again that the parameter parts are fixed. It's only the compartment values that we can change. So you couldn't see advance draw a dotted arrow up to one of the fixed parameters because they are once again fixed. So now that we know how to do a transition across one component, what if we wanted to do a transition across 2 components? And I'm aware that the parametered little circles are missing their arrows. The images got significantly too cluttered when I tried to draw those arrows in as the diagrams get smaller. But what we'll notice here is that we now can take a group of components and we can talk about taking the advance action across a group of components. And so what this basically does is we will do the advance operation or transition along component A. We will then transmit all of the data along all of the cables going between component A and component B. So whatever that outputted value of advanced state was would get sent into its output compartment and then sent to component B. And then component B would once again also do its advanced transition, in which it would take on all of its values and compute its own output value. And you could chain these together ad infinitum. There's no limit to how many of these you can chain together. I will say that eventually it's probably, might want to look at making your model a little bit smaller, but there's no actual limit to it. There's also no limit to how complex you make these. There's nothing that says that you can't have recurrent connections in your cables. There's also nothing that says that outputs or inputs need to actually have values. You can clamp values to them, which is basically the process of we just set the value and then just let it go. But there is one thing to note, especially when talking about recurrent things and recurrent connections between neurons and groups of neurons. And what that is that the order of operations in a state transition is deterministic, and thus it's also something that each one only goes once. So if you have component A wire into component B, and then component B wire into component A, it will still only execute a transition across A and then across B, or across B and then across A. It will never actually loop itself. It will always do one and then the other. And so now all of this really, really works itself down to compiling. So the compiler of NGC-Learn is not actually found in the main repo of NGC-Learn. So NGC-Learn is built on top of what is known as NGC Simulation Library, or NGC Symlib for short. And that is where all of the, I don't want to say messy or ugly, but that is where all of this code behind the scenes that are making everything work exists. And that is, all of that library can be found in that little tiny compiling arrow that we see down here. Now, for the way compiling works, though, is we have our state transition, right? We have the state transition that we talked about in the previous slide, and we want to turn it into a pure operation. And what we mean by that is that the same inputs will always produce the same outputs, and no value outside of the outputs of the method are ever modified. And so how we can do that is, with the way that the transitions all work, is we can just pass in the entire state of our model, and then based on the transitions inside each component, they know what compartments they have to be looking at. And so they will look at those compartments, and they will then update and modify the values in the model, and then it'll move from that one into the next one, and from the next one into the next one, and so on and so forth, until it's actually done. And so these produce pure methods, and if we think back to what I talked about with JAX all along at the beginning, that means that we can pass these compiled methods into JAX's just-in-time compilation. And so what this gives us is this allows us to basically call advance or reset or any transition function that's defined across all of our components effectively at once in one operation. Here we have it as advance the model. And so this is truly where the speed up of NGC-Learn comes from. Even if you do not use JAX, or if you don't use JAX's just-in-time compilation because you're debugging, it is still a fairly large speed up just to go from Python being written like the way it is into compiling into just running the compiled operation. So if you really want to look into and care about how are we getting the speed that we're getting, look into the compilers. And once again, the compilers are actually located in NGC-Learn, NGC Symlib, which still can be found through all of the NAC Labs GitHub pages. It is also public. So now what does this actually look like in code? And so I wanted to take a brief look because pretty pictures are a tool that helps us understand the thought process behind the models and they understand how the models actually work. But sometimes people will show us really pretty pictures, and then when you go to actually implement it in code, it looks a whole lot different, or things just are not quite as pretty of a picture. So we do have a short section here where we're going to talk about all of the different code that we do have. So here's an example of a component in NGC-Learn. Specifically, we are going to be looking at the dense synapse. Now, all a dense synapse is it is a weight matrix that has both a resistance scale value on it, so just a constant multiplication scale factor being applied to everything, as well as a bias term that is added to everything. Now, so here we have some compartment values on the left. So as you can see, defining compartments is incredibly easy. So now everything right here where you see self dot is all inside of the constructor of our object. So here we have self dot inputs is just compartment and then some values. For us, that's the pre-vals. So that's whatever we want. It's a matrix of all zeros of the correct shape. And then we have self.outputs, which is just, again, another compartment defined with post-vals. And then we have our weights. Now, weights are just our weight matrix, which is defined previously in the function. But it is just, again, simply compartment value. And what this does a bunch of stuff under the hood, but this basically actually associates. So when you build one of these objects, when you build a dense synapse and construct it, this will actually build a bunch of this will build 3 compartments under the hood and basically register them inside the dense synapse and link everything together correctly. So that way we know that they exist and we can wire into them. And it does a little bit more than just Python knowing that the object has these fields in it. They exist and they have their own set of properties. And then we have our fixed parameters, which if you look exactly like just values that exist on a class. Right, we have self.shape, and self.rScale, which is just a resistance scaling. And I'm sure everybody here who's worked with Python is very familiar with what that looks like. And so finally, we have defining our state transitions. Now, there's a couple things to note about this. We'll notice that our state transition definitions are static methods. And what they are really is they're just these have to be pure methods to define our state transitions. So here we have advanced state, and we want to still be able to use our scale inputs, weights, and biases inside of advanced state and have them all correlate to the values that exist inside of our component. But due to the way that the compiler works, is we still need this to all be a pure method. So how do we combat that? Well, we combat that by just doing effectively pattern matching, where as long as your names for the various inputs, so our scale inputs, weights, biases, whatever, as long as those values are found inside of the component that this transition is acting on, it will automatically grab those values out of those components when it's doing the transition. And so here we can see this is a pretty straightforward matrix multiplication with a scaling and a bias term to compute outputs. And we'll notice that once again, outputs is something that is keyworded on the component. And because when it's done resolving its transition, it needs to know where to put the output value, or in this case, outputs of the state transition, like what values are changed. And so it knows how to put outputs back into self.outputs. And so this is kind of the key to how all of NGC-Learn's compilation and just plug and play models work with these state transitions, is that you can define these methods that can pull in values from the components that they are being applied to without actually having to have an instance of the component itself. Now, there's one other aspect of these that's not actually shown in this example, and that is parameters at runtime. So for instance, let's just say that we wanted to add the current time to our output. I don't know why we would want to be doing that, but let's say we wanted to. So if inside advanced state, inside the parameter list, we had another value, say time or t, And T doesn't exist on the component that this transition is being applied to. What we'll see with this then is that and we'll see this a little bit later in an example, what it will want to do is it will say, hey, I can found all of these values, but this specific value T is not found in this component. You need to give me T for whatever I need to do for this state transition. And so this is how you can get runtime parameters to be passed into your state transitions and modify them that way. So now that we have a component and we kind of figured out how to define a component, and I should note that we can define as many of these state transitions as we want because they're not actually bound to any specific component, we need to do something. So how do we actually define these components in a model? Because generally we want multiple of them in a model. A component is one piece of a model is not very useful. So in order to do that, we use with blocks in Python. For us, we call them contexts. So we do a with a context, and then we give our context a name. In this case, we've named it model. And so what we have here is this is a with block. And so what this does is this is just saying every time we define a new NGC-Learn component or initialize a new NGC-Learn component inside of this with block, it will automatically be added to the model. So there's no model.register various built things, no model.components list that you need to make sure is up to date, nothing like that. If we call Hebbian synapse here inside of this with block, the Hebbian synapse exists on your model. Now, what this does mean, though, is that the names of all of our synapses are required to be unique. But I feel like that shouldn't be super challenging because in our models, just for clarity and human readability, we try not to name things the same. For instance, it wouldn't really make sense if I have 3 different parts of my model that I've named Z1. So with that, we can see that we can define components like this. But what if we have complex models in which we have one overarching model with submodels that run maybe at different times or at a different frequency, and we want to be able to have those still be a part of this bigger model, the bigger scope of the model, but run on their own? Well, luckily for you, we can do that. So contexts are fully nestable. You can nest them as deep as you want, and when you actually look at the structure internally, you'll notice that it follows very similar to a file structure, where everything just ends up with paths based on context name. And so you can nest these as deep as you want. Generally, in my own personal use, I've never found really a need to go more than an extra layer deep, but there's nothing that stops you from going 3, 4, or 5 layers deep. And so as we can see here, though, it's incredibly straightforward to actually build the model. This here is built a model with 2 Hebbian synapses in it. Now, I'll give you a brief note. There's a bunch of other components that are defined below this to get the model to do something. But those all look pretty much exactly the same as this, just with different objects and different components being built at every line. So now we have our components. We have our components defined inside of our context, but they don't do anything. They don't interact with one another. If we think back to the way that we get components to interact with one another, we have to wire them between each other, right? We have to get data to flow from a Hebbian synapse into an LIF cell. We have to get it to flow from an input Poisson neuron into a weight matrix into an LIF cell. We have to get all of this data to flow. So we do that with cables. And luckily, defining cables is incredibly straightforward. So we have overridden the left-hand bit shift operator, basically, to say, hey, if we're going to read the top here, so unfortunately we end up reading right to left with this, is we're going to take the Z0's outputs, whatever's in the outputs of Z0, and we want to wire it directly into W1, which is one of our weight matrices, inputs, or INP. And we just write that line, and that cable has been connected. Everything under the hood is done. And then, and I should mention, all of this is still inside the with block found that builds the context of our model. Anytime we're dealing with building parts of our model, it is all done inside of the with block. And then on the next line, we can take Z1i's spikes and we can send that into W1i's inputs. And we'll notice that this pattern of just taking an output and wiring it into an input is pretty easy to follow. And so if you build your component with the inputs that you're expecting and the outputs you're expecting, and you make it really clear to yourself what you need to do with that, when it comes to wiring up your model, it should be incredibly straightforward. But if we think also back to the wiring example, there was a point where I took two outputs and wired them into one input. So we can see that actually happening inside the second part of this, where we connect two compartments into a single destination. So we can do this with, for us, the operation summation. And so what this will do is this will add together any number of compartments that we put here. So in here, we just have it as 2. But if we had 4 compartments that we wanted to wire into there, it would be easy. Now, one of the advantages of doing this, instead of just having 2 input compartments inside of Z1e, is this allows for a variable number of connections. So if inside of one model that you define, you need Z1e to have 3 inputs, or 3 values being added together, or inside of a different model that you're defining, you have Z1e needing to have 7 inputs going into it, you don't have to build new components. There's no additional logic that you have to do. You just add them to this list of parameters that are being passed in, and you're done. And another thing to note is that these parameter chains are entirely nestable as well. So for instance, if we wanted to invert or negate for W1IE's output value, so it would effectively be W1 out minus W1IE outputs, you just put negate around it and you can just nest them down. So if you wanted to sum a bunch of things together and then negate it, you can. If you want to negate 2 of them and add them, it all works. And I should also again mention, it does not actually store these values anywhere, so they are never actually inspectable outside of just looking at the value of the compartment. So, compiling. So compiling an NGC-Learn, we didn't want it to be a painful process. We didn't want it to be something that you had to make sure that everything was like touched the specific right way, where you're holding it in with all your fingers, and then it happens to work. So for compiling, it's just a list of components and a key. So if we think back to the example at the beginning, where we had advanced state as the name of the transition method that we have, that's all we need. It's that name, advanced state. And so what this one I'll do in this line of code here is we'll do model.compile by key. And so this is on your context model, the whole model. We give it a bunch of components, W1, W1IE, and so on and so forth, and then we tell it compile advanced state. And so what this will do is it will go through, and this just, if we think back to the thing where we're like composition of functions of everything together, it will go W1 goes through its advanced state, and then W1IE goes through its advanced state, and then W1EI goes through its advanced state, and it goes down the list. Now, obviously, if we reverse this whole list, that will change the output. It won't change what it's really doing, but the order that the advances happen in does matter, and it is dependent on the order that we find here. And so, and the other advantages is that we can compile many of these. So in this case, we can see that we go through all 2 layers of our model here, and all of our neurons in our model. Everything that's a Z is in neurons. But let's just say we only wanted to go through the first chunk, right? We only wanted to do Z0, and then we just wanted W1, and then we just wanted like Z1E. That's all we wanted to compute. Well, all we would have to do is we would just have to put those 3 values in a compile argument, and it would just go. We don't have to compile every component in our model. And what this means is that we don't actually have to have every transition defined for every component. For example, when we're updating weight matrices, we tend to call it evolving them, right? They're changing in time, they're evolving. We don't evolve neurons. It's not something that we do. It's not something that makes even, doesn't make sense in the context of most models. So from that standpoint, we would only call evolve on the weights. Or we might only call reset on the neurons if our weights don't actually, if our weights never have anything static in them. I mean, a variable in them. There's just like, there's a bunch of different things where we can pick and choose which components and the order of the components that these operations happen in. And so in this, again, just to fully explain, we do have two different output values coming out of this compiled key, this model.compile by key, as well as one hidden aspect that comes out of this model.compile by key. So, but first, the outputs, we have this advance. Now, advance here is the pure function returned by the compiler. So this is the function that takes in the model state and all of the arguments it's expecting, and will return to you the final model state. ADV args, these are all the arguments it's expecting. So as it goes through and it compiles down W1, W1IE, W1EI, and so on and so forth, it's slowly collecting a list of all of the keyword arguments that it needs to actually compute this transition. So if W1 requires T, and Z0 requires T and DT, and Z2E requires a J, what that means is that it would end up, you would have a list that is, we need T, DT, and J. If two things require the same parameter, it does assume that they're the same parameter. The same keyword argument. So if you have T used across all of your components, you only have to pass in T once. So that's everything that's visibly returned by this function. In addition, what this function also does is we can now call model.advancedState whatever this compile key here, or an optional name flag that's not currently being used. We can take that advanced state and we can do model.advancedState, and it's the same as calling model.advance. And this just has its benefits of you don't have to necessarily keep track of the actual advance function. If you have a bunch of them, you can just name them. So that's everything on actually how we get the compilation to run. So what if we want to perform many of these state transitions in a row? And what I mean by that is, if we think about a spiking neural network, we have a forward pass where we take one look at an image. But also in spiking neural networks, usually we have to do many forward passes up our image before we say we have an output. And so when we look at that, we're doing like 200 forward passes before we ever actually care what the output value is. So because of that, we don't want to just do a state transition from T0 to T1, get T1, plug it back in over here to get T2. What I want to do is I want to plug in T0 here and then do T1, T2, until I get to T200. And so for that, we have scanners. Now, the NGC-Learn scanner is built on top of JAX's scan function, which is effectively a method of doing a for loop inside of their compiled, inside of their just-in-time operations. And the way this works is we have our scanner. We have an observe function for us, but this is just whatever you want to name it. There's no actual hard, fast rules on what this needs to be called. We have compartment values, or the model state. And then we have args. And so what the arguments are is these are the keyword arguments for that specific loop in time. So T0. So at T0, we would have arg0, T is equal to 0, and dt is equal to, say, 1. At T2, or the second loop through, so at T1, or the second loop through this, arg0 would be 1, and so on and so forth. And we define that down here in loop args, and we'll talk about that in a moment. But then we'll notice that inside of this, we're doing two actual transitions for every loop. We go through and we advance all of our state forward, and then we do an evolve step over our model. And this was done on an STDP, or spike timing dependent plasticity trained model, which means that we do an evolve step at every single forward pass. We do one for every forward pass over an image, we do an evolve step over the image. And we'll notice that this gets a compartment values because this is a pure function that takes in the component, the model state, and returns the new model state. Evolve is another compiled method that takes in the current state and returns the final state. And then we just return the final state at the end of that loop. And it just loops. And this will loop over for however long you give it arguments for. So if we give it 200 loops worth of arguments, it will loop 200 times. And this part right here at the end is just how you can actually get an output out. So this will return the compartment value located at SRAW, the raw spike output of Z1E at every time step will be what _S is equal to. And finally, to call it, we just call observe. It's whatever the name of this function is. So if you named this foo, it would just be model.foo. We try to use slightly more of that useful name. So here we have observe, and here we have observe. And then the loop arguments is a 2D matrix where every row is, for every row is just the list of arguments that are found here. So this is a 200 by 2 matrix, basically. And that gets us our state transitions. And so this is how we can look at a model this is how we can transition over many steps without ever having to come back to Python. And since this is so scanners automatically put things inside of just-in-time compilation, just for the way that they work internally for JAX. But what this means is that we can go from an incredibly slow forward pass over one image to a compiled forward pass over one image to a just-in-time compiled pass over just like one pass over an image to a just-in-time compiled 200 passes over an image, and just do that in a single function that we have defined. This is where all the speed comes from. Finally, I just want to mention monitors. So what a monitor is sometimes we have a desire to actually look at, well, the internal state of our model as it's running. And when we're doing things with just-in-time compilation, we never get access to those internal states because they all exist in C and they never exist in Python, and we can't look at them very easily. Again, due to the way that just-in-time compilation works, you can't put print statements in compiled code. It does not work. So what this means is that we have monitors. And so the way this monitor works is it's just a component like any other component in NGC-Learn. Admittedly, it does work differently under the hood, but that's fine. What we have is we have a monitor by name, and then we have this default window length. What this is doing is this will keep a rolling window of the last n values that you define. So in this case, 100. So it will keep the last 100 values of whatever you tell it to. Now at some point you might say, well, why don't we just make this really long and do it for every value? Well, that gets really big really fast. If you're storing floating point numbers and you're storing millions of them, you can run out of memory in your computer. So you do have to be slightly careful with that. But generally, if you just keep the things that you're looking at to relatively small amounts, you'd be fine. And the use case for this, we'll notice too, is slightly different with the way we wire things into it. So we'll notice that there isn't a compartment value right here. There's no m.compartment name. We just wire directly into the monitor. And this is why I was saying they work slightly differently. But as far as the outside user is concerned, you just wire into them like any other compartment. You can think of it as one giant compartment that stores everything. So here we take the spike output of Z1E and the spike output of Z1I, and we wire them both into the monitor. Now, somewhere in between this, we have run like the observe function that has gone through and done a forward pass over an image. Now we want to actually look at the states as we're running. And so what we'll notice here is in view, the contents of it, we can just do m.view, and then we just give it the compartment that we want to look at. And this will give us the concatenated matrix of all the spikes. So if Z1E has 10 neurons in it, it will produce 1 by 10 like sets of neurons. Well, basically just 10 by comma spikes, either zeros or ones. And so as it goes through, the output of the monitor will be 100 by 10, because that'll be all of the spikes for all 100 time steps. And so that gets us the ability to look at models as after they have run, but the internal states of the models as they're running. I will say there are a couple future things coming with monitors about the ability to actually get them to print out and integrate with Matplotlib, and getting it so you don't even actually ever have to view. You can just make plots of compartments and they will just plot nicely for you. It is currently working mostly in our development branch. Finally, how has this been used, right? I've been marketing this to you as like, hey, this is the thing that we have made, and it's really cool, and it's really fast, and it works really well, but let's see it actually work in action. So the paper that started this all was this paper called Neurocoding Frameworks for Learning Generative Models by Dr. Arurbia and Kiefer. And so this was kind of the founding idea for NGC-Learn. This was built in the original version of NGC-Learn about 2 years ago. And it built this incredibly complicated looking model here that has both excitatory and inhibitory connections, as well as a bunch of lateral connections. Every line that we see here is part of the weight matrices. And sometimes, depending on the way that the connections go, it's multiple sets of weight matrices. This is a model that you can build in NGC-Learn, and it will look no more complicated than a bunch of little brackets telling compartments where to wire to. In addition to that, we have reproduced Deal and Cook's paper from 2015 called Unsupervised Learning of Digit Reconstruction Using Spike Timing Dependent Plasticity. This is another model that we had. This is more of a historic model that we have built inside NGC-Learn and gotten up and running without any problems at all. We have one of my papers, actually, with my advisor, Dr. Arurbia, called Time Integrated Spike Timing Dependent Plasticity, in which we built a patching model that does what it does, that basically is this whole structure, where we have a sensory input layer, an image, and it breaks up into a bunch of different subcomponents, or submodels, basically, that all learn small patches of our image. And then we have one final part that aggregates them all together. This sort of model is also very easy to build in NGC-Learn and there's no actual time difference between running some of these. And so again, this is just something that we can build, and this is all able to be built with components that already exist in NGC-Learn. If you wanted to build some of these models, this one, the TIS-DDP Synapse, isn't quite in there yet. But this model is fully in there. You can build this with every component that we have inside of NGC-Learn. And it doesn't, without you having to write anything yourself. But even if you wanted to rebuild this whole model inside NGC-Learn, writing everything yourself, it still would not be that challenging. In addition to that, we also have this contrastive signal dependent plasticity, which is a self-supervised learning in spike neural circuits, again, by my advisor, Dr. Arurbia. And this is, again, another model that, like, this whole thing gets expanded to this, which does this. And this model is actually inside NGC-Learn as well. All of the components that are needed for it are inside NGC-Learn, and you can build it and you can look at it, and it's all linked to in his paper. And what that kind of wraps me up to here is the NGC-Learn Museum, or just NGC Museum. And so NGC Museum is a public repository for NGC-Learn that houses the biomimetic, the brain-inspired computing, and the computational neuroscience models. Basically everything that we've built for all of our models can be found here. It makes a very convenient place for if you have code that you want to publish somewhere, you can publish it here as just a, hey, here's your paper. You can, it is organized, and it's working on being more organized into different groupings of stuff. There's a whole exhibitors section for it. So if you have multiple pieces of work that are all done using NGC-Learn, you'll have your own, you'll have your ability to have your own folder that you can organize however you want, that will have all of your papers that you've built together, which would mean that if somebody is looking for similar papers that you have done, they can come here and they can see, here is a spike timing dependent plasticity paper that you've done, and here's 4 other spike timing dependent plasticity papers that you have also worked on, as well as here's just other spike timing dependent plasticity works by other authors that would allow you to cross-reference things and just have a good community-built platform for models. Because as I'm sure we're all aware, it's really frustrating when you read a paper, it has a really interesting method, you go look to reproduce it yourself, and the code is not available, or it's in a Git repo that's been deleted. I think we've all been there. And so from that standpoint, our goal is to make it so that that doesn't happen again, and that everything built with NGC-Learn can be found all in one place, so we can all see how much it can do. And finally, some upcoming features. Reinforcement learning. So once again, this is actually currently in our development branch. So we have grid-based environments. Technically, you don't need to make them grid-based. It's just the easiest one to visualize. So it's using components. So with the way that components work, if you can basically chunk your environment into its own individually run state machine, you can display it and run it in NGC-Learn. Currently, we have rat water maze, rat T maze, another model that I'm currently using for a paper that's not published yet, that are all navigation-based tasks that have to perceive the world around them and get updates. I will say right now it is only limited to 2D. You would not stop you from using it in 3D. You just might have to see how to visualize it differently. And since it is built up out of components, it is fully compilable. And what that means is that we can compile the rat T maze into a C function and integrate it directly with the compiled version of our agent, meaning that at the end of the day, you can do your entire training over your RL environment in C, never having to touch Python. And I will say egocentric and world views are both available. So obviously these are rendering the world view, and then the little highlighted section is your egocentric view. Both of them are very easily attainable. Yeah. And so with that, there's some links to everything. And if anybody has any questions, please don't hesitate to ask. I'm slightly early on time, but that was kind of the goal.
Thank you, William. Okay, just while I'm getting back into the game here, maybe just share a little bit of your journey to working on this. Like, where are you at in grad school? How did you come to be working on it?
Yeah, so I am a fourth-year graduate student working under Dr. Alexander Arobia at the Rochester Institute of Technology here in New York. And so this kind of all started, so my journey on spiking neural nets started about 2.5 years ago or so. And very rapidly, I found just like the speed problem to be incredibly annoying on like, how do I actually get this to run in a way that's efficient? And as I started moving to bigger and bigger models, specifically RL and some other models, it started getting really, really slow. And so around that time, so around like 2 years ago or 3 years ago or so, Dr. Arobia had started working on the first iteration of NGC-Learn, which is what his original paper, this one, was written using. And then I got a hold of it, and it works. It works beautifully. But since that paper came out, there were some pretty large advancements in the just computational things. JAX had really taken off a little bit since that had come out. It was all originally built in TensorFlow, which works, but it really felt like we were hammering a square peg through a circular hole to get it to do what we wanted. And so starting about 1.5 years ago now, we kind of set out to make NGC-Learn what it is today. And then probably 8 months ago, it really kind of took off on where it is with its compiling and the speed. And we've been using it and developing it ever since.
Cool. Epic. Okay, I'll start asking some questions from the live chat, and if anybody wants to add more questions, they can go for it. Okay. Okay, I'm going to read a possibly unrelated comment, but if you have a thought, otherwise it's not necessarily a direct question. Okay, Scott wrote, lawyers say that contracts are a meeting of the minds. Singers and choruses experience aesthetic amplification of group identity. Here, the meeting of voices in storytelling equals a smart mirror for group identity.
That's okay. It's interesting. I do kind of thinking about it is like just my initial gut reaction to that is that I think especially when we're doing science, sometimes we can get a little bit too bogged down in being scientists and not enough time in being like free thinking and actually just coming up with like new ideas, right? We get too ingrained in like ruts of how things have been done in the past. And so I think that's something that we all do need to work towards more. It's just being a little bit more embracing of just new ideas that might not work.
Awesome. Okay. First question. Mobina wrote, does it only work with discrete value spiking?
No. So I'm going to flip through a couple of slides here. So when you go to these wires here, there's nothing that says that the wires actually move discrete values. But the advantage that we run into is that the fact that they can move discrete values. So when we look at here, so the weight outputs, so like the weight outputs are actual matrix multiplications of weight outputs. We can see that here. This is not a discrete value. But for us, when we're dealing with spiking neural networks, the input coming, so the short answer to the question is no, it works fine with floating point values as well. It just also works with discrete values, which many other systems do not.
Okay. To give you a breather, I'm going to read an interesting quote that your last comment reminded me of. It's from Henry David Thoreau in Walden. He wrote, I had not lived there a week before my feet wore a path from my door to the pond side. And though it is 5 or 6 years since I trod it, it is still quite distinct. It is true, I fear that others may have fallen into it and so helped to keep it open. The surface of the earth is soft and impressible by the feet of men, and so with the paths which the mind travels. How worn and dusty, then, must be the highways of the world, how deep the ruts of tradition and conformity.
It's a good quote. It's a good quote. I've seen his cabin. I've been to that lake.
Cool. Like I had a sense that you would.
Yeah, it's a really cool place.
Okay, reading down. Viet, your colleague and previous presenter, wrote 2 questions. So first question. I saw that JAX also has a method .lower to lower the pure function down to machine code, but not compiling. Do you see any fruitful exploitation of this function in the context of NGC simulation library?
Possibly. So that could get us definitely some of the beneficial parts. So right now when you compile a function and then it throws an error, debugging that error is a nightmare because it's all compiled under the hood. I would have to look more into it, but if we can just get to machine code, that would be really cool. Like if it didn't end up, like if it ended up skipping over, like it's going into C, but I'm not sure if it does. On top of that, something else that would be kind of interesting is, and I've actually spoken to my father, who also does computer programming, about this, is if we can get it all written into C or machine code, theoretically, you should be able to pre-compile this, which means that you could get your entire model and all of the state transitions as a program, basically, that sits on your computer without actually ever having to touch Python, which I also think would be a really cool place and direction to go.
Yeah, I think the presentation and the package architecture reflects it, like many octaves of computer science. You're really getting down into the compilation details, but understanding those is critical because the point you mentioned, sort of by the by, that there's the possibility with only some constraints to run a model on CPU, GPU, and neuromorphic. That's an incredible cross deployment of potentially identical models. So you could have certain models deployed across hardware to better understand the hardware, forget the model. Or of course,
for sure. Inside of the tutorial section of like the documentation for NGC-Learn, there's a part with NGC Lava, and it actually will walk you through how to run the same model both on the Loihi simulator and your computer, like in the same time. And you can look and it will get the same output. Like it's got some randomness to it, so like your filter might be in a different spot, but it will produce the same model.
Yeah, I mean, what is it even like to, or how is it similar and different to be programming on a neuromorphic simulator?
So the simulator is relatively straightforward. actually going on to the physical Luihi itself, and this is why we have to stress simulator everywhere, is a challenge. So first off, Intel's NeuroCore, which is like their proprietary code for running on their Luihi chips. Well, it's proprietary code, which means that I don't have easy access to it. Like I have a couple working groups that I can have access to it through, but it's not something that I can just put on my own machine and test. In addition to that, microcode is needed, which is basically what is usually used to like patch CPUs and GPUs and whatnot. But the microcode, it's the level between like machine code and it looks somewhat like assembly. You need to write a lot of your models in that, which gets complicated. So until we get a good translation layer between Python and either C and then C to that layer, or between just Python to that layer, the physically putting it onto hardware still is a hurdle.
Yeah, again, super interesting how this is really spanning the gamut with different layers of computer science and bringing in
for sure
all these unconventional compute. Okay, another question from Viet. Have you also considered automatic operator, such as when we add two compartments A and B together, instead of summation of A comma B, it is A plus B, and the library would wire them to the summation operation?
Yes. So yeah, we definitely have considered that. You run into... So it works. So the long story short is like that can work. The problem that you can run into is it can become a little bit syntactically weird to look at when you have compartment plus compartment meaning one thing and compartment.value plus compartment.value being another thing. Like basically the problem is that if we start overloading those operators, you now have to be careful. Like right now, if you try and add two compartments together, and you forget to do like compartment.value, it'll just error because compartments don't have an addition with one another. But if we produce an addition with one another, it starts to you have a lot more silent errors. So until we find a good way to overcome that problem, it's currently on pause.
But this brings in a lot of interesting category theory type questions about concatenating nested systems and putting them in parallel in series. And what are these operators?
Oh, yeah, for sure.
What does it really mean when just to have a certain symbol? And then what do you really want to do? What are the operations supposed to do?
And that's kind of been why, like, we overrode the shifting operator just because I wanted something there that was not just like dot connect. But beyond that, I've been a little bit hesitant to override them.
Okay, I'll read two comments from Professor Aurobia. Okay, first,
it's just my lab so far.
Yeah, but first, a historical note, I guess. The nod from Will to the old, many years ago, NGC-Learn was nice. Wink. The original NGC-Learn was written in TensorFlow and started by offering generic customizable support for predictive coding. First note. And then second note, I posted a link to where we've curated many implementations of active inference. And Alex wrote, we would love to have community contributions translating these active inference models to NGC-Learn. We would love to feature and maintain these in the NGC Museum. I mean, that was an incredible insight to have a package-centric repository.
Yeah. The whole goal of this, so all four of these models that are shown here are all in the museum already, or on their way to being in the museum. And yeah, the goal is just so that way, like, if you guys have this repository of here's all the papers, well, what's better than here's all the papers than here's all the papers and the code to reproduce them all in one place.
Yeah. Okay, you mentioned a few pieces of this, but Mobina wrote, what improvements are currently being explored to enhance NGC learning?
Yeah, so again, one of the main ones is just getting reinforcement learning up there and available for people to use easily. In addition to that, there's an overhaul of our visualization the tools that I'd want to have. So we already support things like the raster plots, all of for plotting spike patterns. We support, obviously, Matplotlib does all of its stuff, and since all of our NGC-Learn stuff is built inside of NumPy, it all plugs and plays into that really easily. But we do have a couple other just additions to all of this that we're trying to get up and running. Basically, there's an overhaul to the visualization library. In addition to that, I'm sure there's other projects that I've been thinking about, but I don't have my notebook with my list of plans in front of me. But those two are probably the first two on my list: is the reinforcement learning and then visualizations.
Cool. And this is a question.
And the help section. And the library built help section.
Yes, the lobby of the museum.
Yeah.
And then the art outside. Here's a question that we've discussed with each of the previous package developers today, ActiveInference.jl and the RxInfer. Like, what was the most challenging part of developing this out?
Definitely the compiler. And it's not, the funny thing is it's not the compiler specifically that was the most challenging part of developing this out. It was, how did I want the user to actually interface with it? Because one of the most complicated things, and I can go back to here, right, was getting this to all work in a way that didn't feel clunky. So, and it still isn't perfect. It's just the best we've figured out so far. But the way to define your compartments and your fixed parameters, and then write transition functions that can pull them into itself and do the operation, getting that workflow down in a way that made it so that way if you want to build a new component, it doesn't take very long, was a challenge. That was probably the most challenging part. The next one's definitely just actually getting the simulator to plug and play everything together. I could give another 3-hour talk on how the simulator, the NGC SimLib, actually works under the hood, because it does a lot of metaprogramming and pattern matching and function generation. Like, your actual compiled method that you're running is 3 steps of dynamically created functions deep, basically. And so getting that to all work without bugs was hard. And it's been doing pretty well. We've only had 2 very, very minor bugs in the past 5 months, so I'll call that a success.
In entomology, we love minor bugs.
Oh yeah, of course.
Okay, I'll read another question. Rorik wrote, "Is there an active outreach program to the museum, as such treasure ought not to be buried?"
So we're not actively going out and trying to seek things, but it is open source and anybody can make pull requests into it. And we are and for whenever for our lab or for our own personal research, reproduce a model, or either a baseline or just as we're learning something new, that also ends up in there. But I think as the going out to people specifically and being hey, we're going to, it's a lot of it is we're trying to get the people that use our tool to just, when they've published the paper using the tool, put it also up there.
That's a very humble answer. Also, you're doing the active part now, so that can't be discounted. Okay, I'm going to read another. This is not a question from Scott, but just if you have any thoughts. Okay, he just wrote, "Things get interesting as our new computational and information processing systems, computers, internet, AI, etc., 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 more faithfully reflect human cognition, active inference, and biophysical models than our existing institutions and organizations. The latter are historical artifacts not yet improved and socialized to new learnings about physics-supported flows."
mean, I think this is just my first thought of that is many modern AI systems and giant structures that are made do not reflect well on are not faithful to biology. And we should definitely have a goal on making them more faithful to biology and getting basically there's a bunch of things that like biological models can achieve for us, with one of the biggest ones just being the energy efficiency of neuromorphic computing. And the fact that we have things like ChatGPT and whatnot that have used power draws of small cities to train kind of goes against all of that. And so I do think that like this is definitely a way of the future. I don't think it will ever beat out everything, but I do think it's definitely something that we do need to continue pursuit of.
Okay. I have a question. What is the putative or possible title or topic of your dissertation overall? Like, is this one puzzle piece, or is this the major work?
So I've done my dissertation proposal. Off the top of my head, I do not remember what my proposal name was. But so I do spiking representation learning. So up until now, most of my focus has been specifically on the learning rules and credit assignment plasticity rules of spiking neural nets, specifically spike timing dependent plasticity. This is my paper. Time integrated spike timing dependent plasticity. And then I wanted to do all of this with the direct goal of putting it into reinforcement learning, which is why one of the reinforcement learning parts of NGC-Learn is on the way, is because I need it for my research. And since other people have also expressed an interest in it for their research, I'm like, let's all put it in the library together. And so I've got that, and then the actual and then all of this basically played together to go with the representation learning of how do humans actually represent stuff, because I'm not a fan of directly going from like pixels to thought process. I want to go pixels to representation to thought process. And so that's kind of where I've been at right now in my career path.
Cool. Okay, another comment from Alex. He wrote, "We should also mention that NGC-Learn is going to offer support for dynamical systems and even more detailed support for differential equations beyond the basics we have now." Smiley face.
Yes, that is the thing too that we are on track for. We've got currently a bunch of different integration methods that are in there, but they allow for some complex dynamical systems, but not every complex dynamical system that we want. And so the goal is to be able to put all of those in there too. Pretty much anything you think of that can be represented as a state machine is something that we would love to be able to support. Just because at the core of it, it is just a giant state machine moving pieces around. And so while it works really well for spiking neural nets, it works really well for so many other things that use that are, a dynamical system, something that changes with time.
Yeah, from the active inference side, when I see that, well, first the reinforcement learning and the ability to have the egocentric and the allocentric, I think is very fascinating. Yeah. And it makes me wonder, how do epistemic value inferences come into the picture when we zoom out beyond utility or reward maximization and include these networks with structural fixity or with a dynamic structure doing learning? That's kind of just an interesting.
Yeah, for sure. I don't have any great insight on that right now, other than it sounds really cool, and I would love to be there working on it.
Cool. Well, I don't know if I should say that I do or don't hope your PhD ends before then. Do you have any?
I hope to get work on this.
Do you have any?
I'm pretty sure even after my PhD ends, I'm still going to be working on this, so it's all good.
Cool. Do you have any last comments or thoughts to add?
Not really. Just that if you are ever trying to set up NGC-Learn and it's you're struggling with anything, do not hesitate to reach out to either myself or my advisor, Dr. Aurobia. Both of us are on the main dev team of NGC-Learn, and we would be more than happy to help.
Okay, I'll just read a closing comment from Dr. Aurobia. We really hope the active inference community and audience considers community contributions to NGC-Learn, especially if they want to go beyond using backprop/standard deep learning. Also consider using it in the classroom to teach computational neuroscience. Cool. All right.
Excellent.
Thank you, William. Farewell. Hello, welcome back. We're here with real Bradley Alicia and recorded Steffen Bollman. There will be a pre-recorded talk with some discussion too. So thanks all and looking forward to the talk. Go for it.
Okay. Let's see. Okay. Is this coming through? Yes. Okay, wonderful. Well then, yeah, welcome everyone to my presentation about Neurodesk. My name is Steffen Bollman. I'm a senior research fellow at the University of Queensland in Australia. And sorry, I can't be there live, but the time zones were just too difficult. I want to start with why we built Neurodesk and then introduce what it is. But we saw a couple of challenges in open science. And one of them is really non-reproducible workflows. So we have different great tools. They run on lots of different data sets. But the challenge is that if underlying dependencies change, they produce slightly different results. And that's really not great if we want to infer anything on this data. The other challenge that we saw is infrastructure disparities. So lots of people have access to different compute resources. So be it their own notebook, their HPC cluster, or their cloud provider to process their data. And wherever they want to run data analyses, they need to come and install their software again. And the software will always be different across these installations, and it often costs a lot of time. Again, it produces different results, but also costs a lot of time in maintaining these different installations. The other challenge that we see is data management. So when you acquire experimental data, then from an MRI scanner, for example, or behavioral data, then we have to organize it in some sense, and there are lots of different tools. But we wanted to see if we could make that a lot easier. And then also data storage and privacy. So where we store this data, how we collaborate with others, how can we make this data openly available to others? These are really questions that we had and thought, well, can we somehow make this nice and nicer for people and easier to use? So why is this so difficult? In the end, all the software that we use for neuroimaging analyses are software pieces that depend on other software pieces. And these we often call libraries. And what they do is these libraries provide functionality that you don't want to re-implement. For example, it's you have your software here that does some brain imaging analysis, and then you don't want to reinvent how windows are drawn on a computer, or how data is plotted, or how images are processed. So you want to use what other people have already built to do these functionalities. And then what happens is your software starts depending on these because you're using functionality from these. And this usually works quite well. And the reason is that we have in Linux, for example, we have package managers like apt, yum, or if you use Python for your work, we have CogNarr and pip. But pretty much all languages systems have some kind of package management system that keep dependencies compatible with each other. And that's really how it looks like. It's like a puzzle piece where if one thing upgrades, another thing has to upgrade as well. They have to have matching versions. And then we're hoping that this all works. The challenge is with a lot of the scientific software that we work with, it's often built by scientists who don't have a lot of time. They're not really software engineers a lot of the time. So what happens is they have unpackaged scientific software. So these scientific software packages are not available in standard package systems. And that means that if the operating system upgrades, the package manager doesn't know about this software because it's not registered there. And then what happens is the package manager changes something, and because it didn't know about the software, then it breaks. And that's happens, unfortunately, quite often with scientific software. And it leads to two problems. Again, here's our reproducibility problem, because if we just depended on a library, and even if it doesn't break, let's say it just changes functionality, our results will be different. And that's really bad for reproducibility. And also this means portability, because if our software is tightly integrated with the system, it means we can't install software on our notebook and then run exactly the same software on a high-performance computing system, because that will have slightly different dependencies. So we need to install it again, often compile it from source code, which can be really a lot of work. So just to show this reproducibility problem in a little bit more detail, this is a great article that looked at software that depends on glibc. glibc is a very fundamental Linux library. And what they did is they varied only that library version, and they left the main piece of the software intact. So they used FreeSurfer and lots of other pieces, but I'll focus here on FreeSurfer. So it's the same software installation, just on different operating systems, just in different Linux versions in the end. And what happened is in glibc, the exponential function, for example, was altered and was made more efficient. But unfortunately, this meant that the precision of this function changed. So now you would think that this doesn't matter, right? It's like very a couple digits after. So it should be quite insignificant. Unfortunately, it's not, because FreeSurfer in particular is a long-running pipeline where we segment the human brain. And this means that if you have small changes, this accumulates over thousands of processing steps. So this means in the end here, they found differences in millimeter up to 0.2 millimeter in the cortex, where this is a change that's only based on the software version of this underlying glibc. So FreeSurfer was identical. The only thing that changed was the operating system. And the thing is this was even statistically significant in some areas. And that's really not what we want, because if you acquire patient data on one software version and then you have matched controls on another software version, then that would really lead to significant results that are actually meaningless because they're just based on computational noise. So the organic solution that I've seen in my career is that we just have people set up different computers and don't touch them, don't try to update them, because people are aware of these problems. And this is not great because it's not a great use of resources. And also it means we can't easily take our software and run it in different computers. And this is this portability problem where, let's say you want to run the same software on your notebook, on your lab workstation, in a secure environment, on a cloud provider, on a high-performance computing cluster, or even on the instrument where you're acquiring your data, like your MRI. You can't just easily build an algorithm on your notebook and then run it on the MRI scanner. It's currently not possible. But that would be cool, right? For translational studies in patients, it would be fantastic if you had a model that you build on your notebook, you validate it on lots of data, and then you can actually deploy it in real clinical environments. That would be fantastic. So this is really the problems that we're trying to solve with this project. And we adopted one solution for this, which is called software containers. So I quickly want to introduce what software containers are and how they work, because our software is based on all of this. So software containers, if you've never heard of them, a very simple thought pattern is they're just boxes. They're boxes to put software in. And they're really like the stuff where you put food in and put it in your fridge. It's fantastic because it keeps things separated and you can move them easily. They're very portable and they don't depend on each other. And that's really what software containers do. They use specific Linux kernel features called namespaces and C groups. They isolate processes and dependencies from each other. So this means we can put everything our software needs into a standardized box, and we can move that across operating systems. And what it basically changes from our mental model, when I said earlier, we have this Lego piece where this piece depends tightly on the other things in the system. This now changes to where we take these dependencies, we put them into the same box. So now we actually don't have a dependency on the system anymore. The box got a bit bigger because we have these dependencies now included, but in the end, storage is cheap, but scientific experiments are expensive. So this is a very low price to pay for a lot of great features. And the whole cloud world, everything the internet depends on today is based on software containers. So this is really a very mature standard that has been adopted everywhere in the computing industry. So in science, we should just do it as well. So what we can do, we can package all of our software in these boxes. And then because we have these standardized interfaces now, we can run this on Windows, Linux, and Mac. On Linux, this is a standard kernel feature, so no performance penalties, very easy to run. On Mac and Linux, we have some virtualization technology that we need, but that got really good over the last years, so you will not feel that it's slow. It still feels very native, but there is some virtualization, there is some overhead, but it's tiny compared to what we had a couple of years ago. So then let's come to what we built. Before I show what we've built in Neurodesk I want to acknowledge all the people working on this project, because yes, I'm giving a talk here today, but I'm just one of many contributors. We started this project really during COVID because we were all bored and sitting at home, and we said, well, let's solve that problem. Why not, right? We have time. So we got together, a couple people all highlighted in bold here, and said, okay, let's build this. We built a prototype during a hackathon at the OHBM, and we got funding from the AIDC to build a bigger version of this. And then, yeah, we got lots of people involved. Slide change, sorry. We got lots of people involved from across the world, and lots more supporters, like the big cloud providers, AWS. Google had supported us in the past as well, and then also the university cloud providers like EGI, Jetstream, AIDC Nectar Cloud. So that helps a lot. And yeah, we're currently funded by the Mark and Chan Zuckerberg Initiative and the Wellcome Trust to build that system out further over the next years. So this is what we built. So I'll start here at the container level. So this is really these software containers that I introduced earlier, where we build a software container for every piece of software that people want in this. So here we have a couple of neuroimaging pieces, so fMRI prep, FreeSurfer, FieldTrip, ENS, and then we can control everything in there, from the binaries, the libraries that we have in there, up to the actual software that people want in the end, like M&E, which then depends on Python, which then depends on CogNarr, and so on. So we can control all of these dependencies. And then if you've used the software container before, they are fantastic, but they're not always easy to use. Like you have to run specific commands like docker run, or if you're on an HPC, you need to run Singularity or Aptainer run. And we didn't want that people have to think about this, and we build an accessibility layer, we call it. But in the end, it's just an abstraction across multiple container technologies that we use. And it's also a way how we can stream containers to end users, so people don't have to download these containers. So this little block here was actually the most of the work that we spent on. How do we get these containers to end users, and how do we make it easy for people to use that? So, but ultimately, what this allows us now to do is we can run these containers on any system. So we can run this on macOS, on Linux, on the cloud, on Windows, on high-performance computing clusters, in Jupyter notebooks like Google Colab, on the terminal. pretty much anywhere. And we try to indicate this here with this little script that goes between systems. And that's now the thing that wasn't possible before. We can code up an analysis on our notebook, and we can move it across all these systems, and it will perform identically and behave identically across all of these systems. So this really is fantastic for collaboration, for translation of results, and for reproducibility in general. And then the community uses that, interacts with the system, but also finds problems, bugs, and then reports back and contributes new containers, new things that people want to use in the system. And that's really the ecosystem that we've built. So the best way to get started with Neurodesk is go to our website, neurodesk.org. There you find two very quick ways to get started. If you want to run a hosted version of this, which runs on the cloud, or if you want to run a local version, which runs on your computer. And it depends on your use case. If you have data, patient data, you definitely want to run this locally. If you have open data, you can use a hosted version and you're fine. And then we have a more fine-grained table down here where you can select what your compute platform is, what your operating system is, what the interface is that you use, and then you get guided to the documentation where we guide you through how to run this on your system. So in the end, what you're getting is you're getting a virtual desktop, which is just a Linux desktop with all the tools installed. And the cool thing is all the software is ready to go. So you don't need to install anything. Everything is there. We have no dependency issues. So we can even have the same software in different versions. So for example, FreeSurfer is almost impossible to install different versions of that software on your computer because it will replace dependencies that other pieces depend on. But because we wrap all these dependencies in a software container, we can actually provide all versions of Neurodesk, of FreeSurfer, for example, going back over the last years without any problem. Because of this containerization, the analysis is reproducible down to the software level. We're not reproducing anything hardware effects. I can show this later. But yeah, if there's like a CPU difference between Intel and AMD or ARM, we don't control that. But down to the software level, it's reproducible. And then this whole system is only 1.5 gigabyte in size. And the reason is we can stream all the software we need on demand in there. So when you actually click on a software, it is streamed live to this endpoint. You can also choose to download it, but then we realized we're really look at brain imaging data and check if things worked or didn't work. Then also we wanted to support high-performance computing systems. So high-performance computing systems, they don't often come with a desktop interface. So you need to work from the command line. So we built everything to integrate with these HPC systems so you can easily run Neurodesk on there. Often you can't install things on there. So we took care of making that possible. So you don't need any elevated privileges if you have Singularity or Aptainer already installed on your HPC. And then we also support Jupyter and notebooks, computational notebooks in general, because we think this is a great way of documenting analysis, experimenting, collaborating with other people, and sharing results in the end. So we really build it into Jupyter Lab as well and provide with this very nice interface to people that they're already used to, that I know how to work with. Then it's also very easy to contribute new software to it. It's all automated on GitHub. So we have GitHub Actions where people can propose a recipe for a software. This gets then automatically built, tested, and integrated into this whole system and made available. And then we have a system which is called CVMFS. This is the streaming of software that I mentioned. It's developed at CERN. So CERN used CVMFS to stream software and instrument data across the world. And we use exactly the same system and also collaborate with the people who run these servers. So we have a primary server where we ingest all the software and then we distribute it worldwide. So wherever you are in the world, you should get a quick access to the software. And there's a client in there that localizes where you are and gives you the closest server. And even if a server is down, it just goes to the next server. So it should be a quite reliant system. And we're using this since a couple of years and had never had any issues with that. And then for the end user, it just appears magically there. They just see the software there. And when they start it, it just magically works. It's just on the first start, it's a little bit slower because it has to download certain things. But then on the second start, it's cached locally and it behaves like it was installed locally. So the uptake in the community is pretty impressive, and we saw really big growth over the last years. So we have more than 1,000 monthly users on our systems. They come from over 60 countries, so really worldwide adoption. We see that more than 16,000 people downloaded our main software container that provides a lot of these things. It's used in university courses for teaching. It's used in conference workshops because it's fantastic for standardizing teaching material, because you don't have the problem that students have different software requirements on their computers. They all log into either a cloud-based system or they install our software container, and then they can run all the same analysis, which is fantastic. And we also have various collaboration models that we support with this, because we realized that in some instances, it's nice to have a central compute instance where people all log in and they all work on the same data. And this is fantastic for open data sets. This is fantastic if people are actually all on the same institution and they all collaborate on an institutional server. And that's really useful and used a lot. Also for teaching, obviously, that's a really great setup because teachers can then log into the other students' nodes and quickly have a look what's happening there if they struggle, if they have a problem. But then we also have this federated model where let's say researchers are collaborating from different institutions. They just install it on their infrastructure, on their computer, and they run analysis on their data. And then they can, for example, aggregate high-level results in a publication without sharing any confidential data. So let's say brain extraction or brain, let's say cortical thickness measurements, right? So you could easily share those without actually exposing the patient data that's underlying this, and then that can be shared across different institutions. So that's a really cool model as well that we see often used with our project. And with this, I claim that we made maintaining and installing scientific software fun again. So it's now very easy. Basically, you install Neurodesk on these different systems, and we make sure that the software runs on these systems. So even very recently, we managed to get our containers running on an MRI scanner. So this is works particularly well for the Siemens ecosystem. So Siemens has a software platform called OpenRecon. So we can actually build a software container that can directly be integrated into a reconstruction running on the system. And that is really closing the loop. So now you could acquire data, build a cool model, and then deploy it on an MRI scanner where patients can directly be scanned and the results end up in the PACS system for people to look at. So that's really great progress for the last months that we've made there. So I want to quickly show the open data workflow in Neurodesk. So this is something that we also focus on a lot. We want to make consuming and producing open data a lot easier. And what we've built there over the last years is that we support a lot of tools and databases that make that possible. So I'll start with importing data. So usually if you produce open data, you would start from, for an example, an MRI scanner or an EEG system, or you would download data from, for example, OpenNeuro or the Open Science Framework. And then we have a tool in there that's called DataLet that can handle a lot of these cases where we can download data from these systems. Also XNet we support, which is a tool commonly used in the neuroimaging space to archive data. And then we of course support any cloud provider or any local connection. So pretty much anything. This is not a complete list. This is just a couple of examples of what we support. And then once the data is in the system, we can process the data using pretty much any software out there. If the software is not yet there, it can easily be added. We currently have more than 100 pieces of software in there that the community wanted. And then we can organize the data and we can document our analyses. So for this, we highly work with the BIDS standard for the brain imaging data structure, but also BIDS has been extended to the EEG world. So we support this as well. We support Jupyter, as I said, as a way of documenting this data, but you can use also your own script system, whatever you're used to, you can install it. And then we wanted to make it very easy to share data with the community. So we support Google Colab, for example. So you can write your analysis in Jupyter, and then you can provide, for example, a Google Colab notebook with your paper where all the analysis run, and we stream the software into Google Colab. So with this, we can even run software that wouldn't be able to run in Google Colab. So for example, because you couldn't install it, because Google Colab doesn't have enough disk space, for example, to install a certain piece of software. And we can actually run the software in Google Colab through our streaming service. But also we made sure that we can easily upload data back to OpenNeuro, again, through Data Lab, or we can share data out to OSF, or that we can share our analyses quickly on GitHub. And then people can start again from this and can use our data that we produced or our derivatives that we produced and then start the cycle again. And then really, enrich the open ecosystem out there. So people often ask, what is our sustainability model? Will it be around in the next couple of years? And of course, that's a very good question, because if you start adopting a framework like this, you invest time in learning it, and you want to be sure that it's around. So we try our best there. So we, as I said, we have been funded through an AITV platform grant in the past. We're currently funded by the Mark and Chan Zuckerberg Foundation through Wellcome Trust. And we're applying for grants left and right to keep the system growing and developing. But of course, grant funding is very competitive. And of course, grants always want to fund things that are new. They don't want to fund things in maintenance mode. So that is definitely something that we anticipate. So that's why we really want to build the community. So we already have more than 10 active contributors. We have a lot of the infrastructure hosted through the community, through the Open Science Grid, the EGI Foundation, where we don't have basically cloud builds for us, which keeps our costs very low, which is good. And also, if we have helpers from the community, we can also lower our costs because we don't have to do certain work. And then we provide Neurodesk as a service as well. So this goes through a non-for-profit foundation, which is called the Queensland Cyber Infrastructure Foundation. And what they do is they provide Neurodesk at a certain cost for example, a conference, for a workshop, or for a university. So let's say you don't want to use the open source software and do everything yourself. You can go to QCIF and say, I want this professionally managed. I want a service contract. I want an SLA. I'm happy to pay money for that. And I want to use cloud resources, for example. And then QCIF can provision that and set it up in a way that it's really at scale and working really well with certain guarantees as well. And then this money flows back to us to develop things further. And then we also have a lot of support from cloud providers. So as I said, we heavily rely on cloud technologies. So we had been supported by Oracle Cloud in the beginning, then Google Cloud, and now currently our main sponsor there is AWS and the research clouds like EGI, Jetstream, AIDC, which support us with cloud resources and make that all possible. So I want to quickly show you some results from this reproducibility aspect, because I'm always claiming that Neurodesk is reproducible, but is it? And how reproducible is it? So this is something that we looked at. So a PhD student in my group took that original paper that I showed earlier from Tristan Qatar, where they found these reproducibility issues with software. So we took that paper and thought, or tested, can we reproduce the non-reproducibility of software? So the analysis is the following. We picked this part where we have data was scanned from an MRI scanner in anatomical space. What we have to do is we have to register it to the MNI space. So this means we align it to a template space, with a tool called FSL Flirt. And then we take this data and we segment it. So we segment subcortical areas and we measure, for example, the size of that. So it's a very simple pipeline where you think that should be pretty easy to reproduce. So what we did is we used a very similar setup than what Qatar used in their paper, where we have a local installation of FSL. So FSL is the same. But then once we run on glibc versions 2.3.1, so on a Ubuntu 20.04, and in Neurodesk, we chose a quite old version of Ubuntu with a quite old version of glibc. But the cool thing is the glibc version is consistent, whereas here the glibc version is 2.28, so something in the middle. It's on an Alma Linux 8.5. And then also what we varied is we varied the processor. So here it's an Intel i7, and here it's an AMD EPYC processor. So let's see what happens. So of course, we compare these different systems. Now let's see what happens. So the first thing is image intensity differences. So the first thing is we were able to replicate the problems from the paper. So if you have a local installation with 2 different glibc versions, then you get different results. And this is really intensity. So we only focus on the intensity in the area where we will later do an analysis. So it is actually the intensity changes whole brain, but just to show where the problems are. So we basically see that the intensity of a voxel is like up to one integer value different. And this is small because when you think about the images are usually like 0 to 1024. So a change of 1 doesn't matter much, but still it's a change and it shouldn't be there. So the cool thing is when we run this in Neurodesk where we control glibc, the glibc version, this effect is not there. There's nothing there. And that's exactly how it should look like. There shouldn't be a difference between this. It's a fully deterministic analysis. There shouldn't be any variance between that. And that's cool. So then when we look at the classification differences, so this is now when we segment this data, we see again in the local installation with different glibc versions, we see quite high disagreements between labels. And this is now dice score. So this is between 0 and 1. And a 0.16 dice score is quite a lot when you think about it. So this means we actually disagree in certain areas quite a lot between segmentations. And again, that shouldn't be the case. Now in Neurodesk, you still see something there. However, note that the scale is an order of magnitude scaled down. So we had to scale it down to make anything visible there, but we wanted to show it. And why is that? Why is Neurodesk here showing some non-reproducibility? Because I just claimed that we are reproducible, right? And why are we suddenly not? And we looked into this. So we traced the executions of this program. And we found that, as expected, in the local installation, the software diverges. So we're doing different things on different computers with different glibc versions. And that's why we're getting different results. So that explains it. It's great. On Neurodesk, we're not diverging. We're doing exactly the same thing on both computers. So this means on a software level, it's reproducible. But why is there still a different result? And the reason is that we use different processors. So it was an Intel processor, one was an AMD EPIC processor. So different instruction sets, different floating point precisions can still have an effect that we cannot control for. Even if we do everything the same, we get still small differences. They're tiny, but they're still there. So it's something to note that 100% reproducibility will only be possible if you also control the hardware. But then in the end, you have to have a trade-off there, right? When is reproducibility enough? And how much effort do you want to put into having reproducible results there? So yeah, that's just our results there. So a little bit of an outlook, what we're working on next. So there's a lot of things we do work on, but one thing that I really want to see alive in the next years is interactive papers, because that's what we can do now. We can have an analysis in a Jupyter notebook where we describe what we've done, we can show all the results, we can show all the analysis, and we could run everything, and everyone could rerun it as well, and then base their analysis on it, and fork papers, and really say, well, my analysis is based on that paper, and have open data for pretty much everything, and really, make it easy to contribute to this open science world. And we already see some adoptions from this from bigger journals like eLife. They already have like some of these executable papers. So we're seeing this coming through. There's still quite a bit of work required to make this easy and very doable. But our Neurodesk paper, for example, we already did that. So the Neurodesk paper, you can go and reproduce it, and you can reproduce our reproducibility analysis, for example, which we thought was quite nice. So with this, I'm at the end of my talk. So I just want to highlight that it's an open community. So if you we need community. We need community engagement. So if you like what we've done, if it's useful for you, get in touch, help us build new things, find bugs, and we also have a little bit of time still left to show Neurodesk in action. If this is something you want to see, go to our website, neurodesk.org, click on hosted, and then you see we have different services. And I said we choose the place service with different regions, Australia, US, and Europe. So if you're roughly in one of these regions, pick that one. So I said I'll pick Australia. I just want to quickly highlight here that all of these servers require some kind of a login. Australia, you need to be an Australian researcher because that's how the service is funded. In the US and Europe, you need to have a GitHub login at least. So I'll click Australia. Then what happens is we'll authenticate you with an account. In case of Australia, we use an Australian Access account. Then you just say, okay, I want the default environment. There shouldn't be anything else available for you. This will start up a Jupyter notebook on cloud resources that are in that country. So you don't want to put patient data there, of course, but you can put open data there. And in terms of storage, you have a home directory, which has about 2 GB of storage. You will get a warning if it's full, and then nothing will work anymore. So you need to be clear that this is not happening. And then everything else you change in the system will be reset after your session is done. But that's basically how it looks like. You go into the system, and then it's just a very familiar Jupyter notebook system. So I quickly want to show now, we have, for example, an example repository, which I quickly want to show. So I'll just show it on the website first. So what we've done is we build an example repository of lots of different workflows where we, for example, show how to use pipeline systems on here. We show how to do diffusion analysis for MRI, lots of different things, and we're currently building that out. So if you have a tool that you want in there, please go and contribute an example, contribute a tool. And what we can also do is I can easily take this and also run this on our website. So for this, we will just check out this repository. So I'll just show that. So just clone our example notebooks, and then that will take a couple. Yep. So here are our example notebooks. And then we can just pick an example here. So I'll pick structural imaging, and then I'll take the I'll take the functional imaging. Where is it? Intro to pre-processing. I just wanted to have a very quick one to show. Yeah, okay. So NiPipe short. So that's a really quick one to show. So what we do is we have a first cell where we set up Neurodesk. This is not needed if you run this in a Neurodesk environment, but it's needed outside, for example, in Google Colab. And then we output which CPU you're running on, just for reproducibility reasons. And then you can import any software into this notebook. So for example, here I import FSL, and this is a software that we provide. So this software will now get streamed into this notebook, and then we can run any tool from this software. You can also install any Python libraries, anything you need. But yeah, that was really the streaming that you saw. So this BED tool was now streamed into this notebook and now can be used in anything. And this is the same way we can load pretty much any software and have it also documented what software we're using, in which version we're using it. And then I'll just download some test data and show that. So I'll quickly run this notebook. While this is running, I want to show something else, because notebooks are great, but sometimes it just needs more. It needs a desktop. And this is what we can do. So we can launch a full virtual desktop in the system, which should look familiar if you've used the Linux desktop before. But ultimately, it has a little start button down here where you go into Neurodesk menu, and you see we have lots of different categories right now for functional imaging, electrophysiology, diffusion imaging. And then you can start pretty much anything from here with visualization software. And you can just start the software. It should start, it should run, and should behave exactly as what you're used to. As I said, the first startup will always be a little bit slower because it has to stream the software. But then you can browse brain imaging data and access everything you want. So now I want to show quickly as well one more way of using that. So I said earlier, we have this Jupyter notebook. So I can also open this in Google Colab. So when I open this in Google Colab, I'll just do the same thing here, run all. This is now really cool, because this is what I mentioned, like this you could attach to your paper where you have your whole analysis coded up in there and then run it on Google Colab. And it will behave identically than what you just built on the Neurodesk instance, for example. While this is running, let's see. Yeah, I'll keep this running. I just want to show one more way of doing it. So, oh, yeah, okay. But that will not work currently with just sharing the screen because I only share the browser. But yes, so then there's ways of how you can run it locally on your computer with a Docker container. So you only need Docker installed. It can run on high-performance computing clusters. Pretty much anywhere where you should need it, it should run. And when I just go back to our website quickly, yeah, your high-performance computing system, we have instructions here, how to do this. And even if you don't want this whole setup around, we have ways of just installing a single container, and you can use that in Docker or in Singularity. So it's really a very layered approach of this whole system. So if you just want everything and no work, then just take the top hosted versions, and then you can just go down the technology stack and use what you need for your work. That's really what we've built. And let's see if that now finished by now. So no, this will still take some time. Let's see. I'll see if this one is finished by now. Yeah, so basically now this ran the analysis, it downloaded data, and then maybe I can show that one. Let's see. We also have built-in visualizations, which is quite nice. So we can, in a Jupyter Notebook, this is using a library called MeView, where we can browse and visualize neuroimaging data. So yeah, so the notebook is still running, so that's why it's not executing it yet. But yeah, once it's getting there, it will. So yeah, that's really what we've built. So yeah. While this is running, we can take some questions. Bradley, if you have anything that people might want to ask, I can show that while we wait. But otherwise, that's pretty much what I had prepared.
Yeah, that sounds good. Thank you. I'm interested in the containerization aspect of this. So this is something that you can run kind of on any machine, in any kind of computing paradigm, like if you want to run it in the cloud or on your laptop.
Correct.
So a lot of the people in the group, they're interested in active inference. They're interested in sort of building their own tools, and then how maybe to do containerization as part of that strategy.
Yes.
So can you speak to that a little bit?
Yeah, exactly. So if you build your own tools, you can just basically build them in here, just get them to work first. And then once they work, I'll quickly show how this would look like then. When you want to containerize it, so for example, let's say it's a Python tool or a MATLAB tool. MATLAB we have to compile and then we download it. I can show that quickly. So for example, SPM is an example there. So SPM is a brain imaging software as well. And if you're ready to containerize it, you can send us this build.sh file where you basically build a container based on a certain Ubuntu version, and you set everything up yourself. And here's an example where we download a compiled zip file for MATLAB that then runs in the MATLAB runtime environment. And we have lots of tricks to make this recipe quickly writable. So this is actually a higher level language, which is developed by a NeuroDocker team. And this higher level language makes it easy to build containers, because if you want to build containers yourself, there's actually a lot of optimization that has to go into it. And with this higher level abstraction, it makes it easier to build these containers. But then, yeah, once you have a software, it's pretty easy to run it in here. And even if you don't want to containerize it, if you got it to work in here and you have the steps to do it, it will run on any Neurodesk system pretty much. So that's the cool thing. So if you have a Python library and it's just got 3 steps to install it, you can do that as well. You don't have to containerize it. Only if you really want to freeze it in time, make it really robust across different systems, then this is the way to go. Yeah. So does this make sense?
Yes. And then I would like to ask, what does the future look like? I mean, do you have a roadmap where you're going out 5 years or so? And if so, what are the needs that you need to kind of address in that roadmap?
Yeah, exactly. So yes, we have lots of ideas how to go forward with this. It always will depend on funding, what we can do in terms of new features. One thing we do want is, and we're heavily working on this right now, is getting into the clinical space more to make it very easy to run the software anywhere. So currently, we're still needing some containerization like Docker, Podman, Singularity, Aptainer. We want to, and we just have a prototype for that, where we actually bring everything we need, like we use a Qemu-based emulation or virtualization. And if the virtualization framework is enabled on a computer, it's not even emulated. So it's really native speed. And with this, we can run anywhere on any system, really, and we have no limitations anymore. Currently, you still need some privileges to start a container on a system, and this is really needed for these clinical scenarios where we want to get into. So this is one thing we're building out. Running these containers on an MRI scanner, that will be a lot of work in the next months. And then the other thing is lots of other communities have contacted us. So this is now focused on brain imaging, right? But Active Inference might have lots of different tools there, and they might want to build their own flavor of this, like an Active Inference Neurodesk. And we have communities like the genomics community, microscopy, dermatology. They want to do this as well. So what we will be doing is we will refactor everything that's not neuroimaging and put that into a new project. And then we have spin-off projects like Neurodesk that use this underlying technology, but then they build the software around it, and then community maintains that one and builds their own flavor of this. This is something we were going to do in the next years. We still need some funding to accomplish that, but I'm thinking that is absolutely needed to support other communities there. And there's also a whole underlying thing of what cloud technology we're using, right? So all of these things don't have to be reinvented if another community wants to use that. So that's really our roadmap for the next years, making that more general and specific at the same time, like more clinical as well.
Yeah. Well, thank you. Yeah, it's good.
Cool. Okay. Not sure. So now some presentations came through, so I can quickly show that. So this is something which is, I think, really valuable for a lot of brain imaging people. So you can just quickly, look at the brain, which is really cool in a browser. So you don't need any fancy software there. And that's what, for example, in this case, NeView makes possible. And I think this is really our fundamental philosophy with this, right? We want to just bring the right tools to the right people and make it easy to use them so they can do awesome work. That's really what our project is about. Yeah, thank you very much. And
that was wonderful.
If people have questions after this talk, shoot me an email and contact us through GitHub or GitHub discussion forums, and we're happy to help. Thank you.
All right, thank you. Yeah.
All right, that's all that we have for that. I don't know if we have any questions we want to ask. I can try to answer them.
Okay, if people have any questions in the live chat, they can add, but thanks for sharing this and for bringing this important flavor into the mix. Where it took me was right where you asked at the end with stripping back to the desk and then allowing the spin-offs and thinking about how we could use that and just how it's like the through line of the education, the research, the application. That's kind of tracing back the community and information supply chain to applications of active inference. So when we come to a symposium like this, or think about planning a symposium like this, think about making a startup or something like that, using this in an application setting, and we trace it back, and then that's where these topics like reproducibility and research integrity are the foundations of the application. And if there's ambiguity in all these different threads and loose ends, like from the availability of the papers, things that have been focused on in open science across fields, and then these really specific computational issues, and then the example with the versioning of a library having these cascading consequences, to say nothing of like security issues, is just completely, it's like an empirical open science point that was very well made. And so now, where do we go from that observation?
Right, right. Yeah, I mean, I've had experience with containerization. In the OpenWorm Foundation, which I also work with, they've developed a container for demos, and they run their simulations in a series of demos. And the idea is to be able to get people to use the demo and get everything to run. You don't need any dependencies on your machine. You just worry about running the container, and that's it. And it's been successful. I mean, it's a little tricky to use and get to work, but the idea is to make things reproducible. So if you see something in a paper or see something that I show you a demo of, you can reproduce it for yourself. And everything's the same, so you get the same answer. And you can even maybe like modify some of the variables or parameters in that model and see, work with it on your own and know that that's that what you're seeing is an actual result, not just some noise or difference that comes from the computational environment.
Yeah. Like practically, what are some interesting ways that as we digest all of this year and think about what projects, like as a scientific advisory board or just as an institute or as part of coalitions, what would be interesting? How do you see that popping up across these different research communities?
Yeah, I think, well, for one, you could use some of the packages that we've seen in the symposium. You could run them in a container, and it would help people if you're running them in different locations, like if you're in a research group or if you're in a just a casual, learner who's trying to run an analysis. It would equalize the ability to run those tools. But also, we can develop demos if people are interested, where you demonstrate active inference and you put it in a container. So someone might run a container, someone who is learning about active inference could run a container, and they could run these simulations, and they'd be, able to run them no matter where they are. And it doesn't take them a lot of effort to sort of install dependencies, because sometimes when you want to say demonstrate something in a simulation, you need to have people run like, a bunch of things on top of one another. And not everyone can either do that or can run them on their own machine successfully. So that hinders what we can do in terms of demonstration and education and research. So that just takes care of that layer. And then everything else is like, you can worry about like doing the good stuff, doing the demos, doing the science.
As you've had many years of working in open source, like what heuristics or intuitions do we have in our toolkit when, again, just because something could be open source doesn't mean it necessarily should. So how do we add signal, not noise or worse? How do we navigate between getting overwhelmed with the technical complexity of trying to take on all of these new research practices and just like we could spend all of our computer time making something reproducible. I don't know exactly where I'm going with that, but just how do we guide and just put out, especially if we're putting out capacities related to cognitive modeling, perception, control, then is there any kinds of considerations that we should think about before just releasing really effective containers for that?
Yeah, so I mean, I guess what's in a container is basically the software that you release as open source. And of course, there has to be a strategy for releasing open source software. You just don't dump software out on the web, or you just don't like kind of produce a bunch of files and then, with limited documentation and tell people have at it. Every group has their own strategy. And a lot of that is, to think about the utility of what you're releasing as an open source package. So sometimes you're interested in the commercial value, sometimes there's proprietary value in releasing something or not. Sometimes you have code, but it's not well documented. So the utility there is limited in that people can't reuse it. So that doesn't necessarily make it good to release. So you want to be able to have, I think, and I say this as being a full supporter of open source activity, but to release things that are very polished in the sense that you know why you want to release it and you have the right support in place. And sometimes groups will have the resources to do that, and sometimes they won't. So if you're a small academic lab, then you can't spend a lot of time, polishing the software. In the talk I gave earlier, I think it was yesterday, I talked about like kind of these practices of software engineering and that sort of thing. And that's something that not every group can do. So that means that we maybe need either organizations to kind of have that layer of, making things work well before we release them, or having meta organizations that can help scientific organizations do these kind of releases. And I'm not against like making something open source for like a paper. I'm just saying that like in tool building, you have to have a deliberate strategy for it, and it pays off if you do.
Yeah, that's very wise. Like your talk in part one, and seeing this again, and the prior talk on NGC-Learn and the Museum of Examples, and going beyond just curating links to hosting more and more. And that is what will allow learners to have access to these tools, build their intuition about the topic, maybe continue on and kind of converge into the development attractor, but even finding friction points and bugs and reporting it and just putting up a yellow flag or just asking a question. A lot of times it feels like people who are outside of the development don't realize that those visibilities that and experiences that they have into the outcome can be in the blind spots or just forgotten by bandwidth constrained developers. And then that is like our research community with people who are at different stages and using tools differently. So it's like, how can we not have this? Yet it's hard to hold that.
Yeah.
And it is a commons for computational science, which wasn't really part of the pre-internet, pre-computer research world. And so there's all these forms and functions that we're barely even able to describe, let alone what has really been tried in different epistemic niches. So it's super exciting because there's so much experimentation across multiple scales, people doing things on their own, being their own program manager, on through just with friends, working with AI, and the kinds of things people are asking and the artifacts they're getting to, and then even up to like the MetaGov type coordinations of organizations who want to have commons and be particular, but also find the interfaces that will help them do things together they can't do separately.
Yeah.
Do you have any sort of last thoughts or questions? And what would be some exciting directions for you and or the Institute in the year to come?
Yeah, so I mean, Daniel asked me to contribute something on this topic and kind of in the abstract, because looks like we do a lot of open source and things, and it's just kind of, to develop a strategy there, to develop a vision there is the thing that we want to get to. So, I would say that like, one thing might be, and I think this is very useful, is to have a sort of educational component where you can have some, tools for active inference and to teach people sort of how do we usually use simulations as an educational tool, and making simulations are, a nice tool because people can interact with them. And so, and it doesn't have to be like a very high level simulation. It can be a very simple thing, that demonstrations of things, demonstrations of concepts, where we might package some sample data with a sample simulation and say, here, build your own sort of active inference model. And, you kind of walk people through how to do it. And then eventually they'll start playing with it and they'll say, oh, this is great. And I want to get in more into some of these topics. And then that's sort of a gateway into the Institute for people who may not feel comfortable with a lot of, kind of diving right into the technical jargon. They want to have like a nice sort of way to ease in and something that's intuitive. And then that helps. But other things, like as Steffen said, that kind of the thing that they're working on, Neurodesk is for neuroimaging, but you can use different versions of this for, different sorts of things. And there are also different versions of Linux that you can build like your own custom version of. So in the talk that I gave earlier, there's Neurodebian, which has the ability to build these builds where you build them as like a specialized operating system for a certain thing. They have Neurodebian, which is for neuroscience, but there can be other versions of Debian for like, musicians or data scientists. And maybe, I don't know if it's useful, but to have something for active inference with all the tools included, and you just, download that repo, that distro, and you get the tools and they work.
Thank you. These are all great directions. A closing note, I think it'd be very appropriate in a history rhymes kind of way that the more generalized cybernetics arose out of neuroimaging, and we saw SPM package in one of the presentations, and then also neuroimaging and the special constraints like computational resources, patient privacy, those constraints in that community of neuroimaging also leading the way on the tooling, which we can also learn from with more general systems.
Yeah. Yeah.
Okay. Thank you for this.
All right.
See
Thank
you.
you.
All right, welcome back. We are here with John Clippinger, and we will be discussing active inference, biofirm, homeostatic agents for bioregional and regenerative finance. So thank you, John. Looking forward to this presentation and discussion and more.
Daniel, thank you so much for doing this and hosting this. It's been a great set of sessions. It really has. It's been very informative. And this is a follow-up on a session that we had yesterday on basically what active inference agents and why they're important, and looking at them in an application. And in this case, in this session, we were going to look at active inference agents in terms of a concept called biofirm as a homeostatic agents for bioregional and regenerative finance. We're really looking at taking the thinking behind active inference agents and applying it to a new notion of the firm that's inherently biomimetic. And what I wanted with these series of slides is to sort of set up the conversation and the discussion that we're going to have later with Andrew and Daniel on providing an in-depth look at biofirms as a homeostatic agent that is capable of interacting with the environment in a way that preserves it and preserves itself and the environment. So what I'd like to begin with is sort of this premise. I've been involved in looking at regenerative finance and issues around climate change for at least the last 10 years. And I think there's a growing consensus that we need a new kind of science-based economy based in enhancing life and nature and equality. We really need to think about what are the economic incentives to make a transition to an economy that values the preservation of life and nature rather than the extraction or destruction of it. And what we don't need is what we're now feeling the consequences of, and that's the commodification of nature in people, turning them into objects and assets that can be bought and sold and trade without any discrimination between sort of what kind of asset we're talking about. Are we talking about something that is coal, is water, is life, the biosphere? They're all assets. They can all be priced and they all can be traded. And so you just have the problem of total fungibility when actually some things are essential for existence and they exist in relationship to other things to be preserved as living things. And then the other problem, and we're seeing it, experiencing it widespread just today, so that the unbounded sort of concentration of wealth and power. So you have a system that works towards monopolies and the concentration of wealth and privilege. And this, of course, has created enormous pressures, not only sort of on the ecology, but on the whole society itself. And you have this notion of maximizing individual utility. So everything is about freedom of the individual as an atomic agent, independent of the context in which they live and their impact upon others, not just other people, but their other species, the whole environment. And so we have extractive metrics that with a negative externality. So in other words, you can create economic returns, but what you're doing is creating a negative externality. It would be pollution, or it'd be air pollution, destruction of species or habitat. This is not reflected in the price. And then it's left to some other party, to a public good party, to clean up the mess. But they're not able to clean up the mess fast enough that it's being created. So we have a sort of a zero-sum, winner-take-all incentive structure, and then we have a lack of transparency and accountability. So there's no sense of collective purpose. So this is really forced people to rethink what an economy should be, and what it would be to have biomimetic firms in an economy, something that actually worked in concert with nature, not against nature. So the first thing is important is not to have any negative externalities. This idea that you can offset the cost of something is going to be picked up by other parties. Since there are carbon credits and offsets are really a failed attempt to deal with negative externalities. And we need to have non-zero sum incentives. In other words, incentivize the collaboration and cooperation of parties to take joint outcomes rather than maximizing utility for a single individual. And we need to have a new way of recognizing that value is created in a really scientific incredible sense that value is recognized through biocapacity and diversity and resilience. Have that be a notion of value, not just as something that maximizes a price arbitrage, but actually creates new kind of value. The other important thing I think is coming into focus is this idea of agency. And this is a sort of a new concept that thinks that nature should have agency. We should have an agency, and we should have agency of thinking of nature as being given the capacity to be itself, and species to be itself, and people to be themselves, and not have that be restricted. And with that, I think comes the notion of what we call sort of homeostatic fungibility. In other words, how something is the value of that is realized is in relation to keeping other things alive. If you look at the human body, it's like you can't maximize the utility of the heart against the brain or the lungs. They all exist together. So how you allocate resources in the body is really maintaining the balances between those different kinds of organs. And that's true of nature, and that's true of organizations. What we need also is a sort of scale-free and domain-free metrics that's scientific and adaptable. So we really need to have the scientific process be a fundamental organizing principle by how we recognize and exchange value. And this means having something that's really is transparent, explainable. You can't have something that's a black box that's opaque, that you don't know where it comes from, you don't know how to trust it, you don't know how to derive it. It really needs to be something that's transparent. And so we've seen people talk about the blockchain and things like that. But it's more than just the blockchain. It's a whole set of methods, being able to see how something is derived and be able to replicate that. And then the idea of scalable learning. Systems should learn, and they should improve over time. Markets don't necessarily do that. They have clear a market around a price, and then they start again. There's no memory. There's no learning how to do something better. For adaptation as a people and in the planet, we need to learn. We need to learn, improve upon ourselves. I mean, that should be part of our whole economy, not something that's tangential to it. And finally, the whole idea of governance. Governance should not be something applied after the fact or top down. It should really be embedded in the whole system of itself. And so there's been a lot of talk about decentralized governance and decentralized systems, decentralized autonomous organizations. But a lot of that is just talk. They're not really fully autonomous and not fully decentralized. But how do you really realize that vision? And these ideas have really sort of were first, I think, articulated and recognized by the economist Elinor Ostrom, who got a Nobel Prize for her work on the governance of the commons. And she was the first woman economist to do that. And I'd worked with Eleanor when I was at Harvard at the Berkman Center and looking and trying to thinking about a digital commons. And it was too early. But here are some of the central principles that she had. And this is back then when the technology was not very developed, but she developed her thinking based upon how indigenous people manage their resources, their common resources. And that would be their forestry, their fisheries, the things that they've done for thousands of years, and they're able to keep them in balance and keep their lifestyle in balance through that. And here were some principles she extracted from that. So it was clearly defined boundaries. And you needed to have a common pool resource where people recognize as a common pool resources. You had to have it congruent with local conditions. And I think by that, in other words, you had to recognize each little bioregion had its own peculiar constraints and issues that you needed to recognize. And you had to have ways that people could make collective choices among up commons, how bring people together. They couldn't be anonymous from one another. They really had to be, they had to know each other and they'd be accountable to one another. And you had a monitoring process. You had to monitor it and be able to see where you were. And then if something goes wrong, you have what she called graduated sanctions, which means it was the punishment was commensurate with the degree of the violation. But you really didn't want to have a highly punitive system that has its own negative results. And you had various mechanisms for resolving conflict. And then I think the idea of one of the things her concerns with, particularly with indigenous people, is that the legitimacy of those organizations were recognized by the larger nation state, that they had some genuine sovereignty and integrity. And finally, this whole idea of nested enterprises, so recognizing it wasn't a strict hierarchy. There was things that dynamically interacted at different scales. And these are ideas that were sort of more metaphors at the time. They were aspirational metaphors, but it was very hard to realize in any kind of operational form. And she went on to talk about later work on socio-ecological systems and recognize the biophysical and the social factors, how they all work together, and how you look across different spatial and temporal scales and different hierarchies, how they're linked. And she was always trying to think about what were the dynamic complex systems that we can characterize by adaptation if you're going to have governance, but where there really wasn't a mechanism there for how to realize those ideas. Now, there's another more recent development. It's called Tehanu, that was started by a friend of mine. His name is Jonathan Lagarde, in Africa, and they're doing this in Rwanda, and they're doing it with all kinds of species. They're starting out with the gorillas of Rwanda, but the idea is that animals and species contribute to the environment, and they should be paid for the value that they created. So how do you do that? You're giving agency not only to the animal, but to the habitat. In this case, in Rwanda, they want to give not only agency to, say, gorillas, Rwanda gorillas, but they want to give agency to rivers and certain bioregions. And by agency, I mean the fact that these things staying alive can be valued for their capacity to stay alive and create a habitat that creates a successful and resilient environment. And so this is a quote from their literature, their website, which I recommend you taking a look at. It exists with the belief that for these species to live, they must actively participate in the economy. So how do you create a new economy that includes living things, and how do you recognize that value? Another approach is something that's come from Regen Networks, which has been working on this for a number of years, and I've worked with them. And they're talking about creating ecological institutions. And again, it's like, what is an institution? An institution, in the classic sense, is separation of people from a set of principles, like the rule of law. You say, well, here's an institution, and it's set up to do these things, and people should perform certain roles in an institution. But the problem with institutions is that they're run by people get corrupted, and the institutions don't work. In this case, what they're trying to do is develop a constitution for what they call an ecological subject. And again, it's giving agency and recognition to nature. And then they have a number of methods by which to govern that and put in a ledger, create some token system. Region's been doing this kind of work for quite a while. All part of it, a common effort. Another effort is something called a bioregional hub, and this will be my last example before making the transition. But the idea of a bioregional hub is that to pull together different parties in a particular geospatial location and be able to give them a set of finance and incentives by which they can act to actually create the biocapacity of that particular georegion. And so it's really working with core communities that are committed to actually enhancing it could be a river system, it could be one of the areas they're looking at in Northeast bioregion is the Connecticut River. How can you bring it back to where it was with abundance, when they had full salmon, it was a very rich ecological system. But there are other things in terms of landowners and being able to give them the incentives to rewild their property and actually make a living on that and create an economy, an exchange of value in such a way that makes it robust and resilient. And so they're working with different kinds of investors and social impact investors in order to make this going to happen. So this is part of a larger collection of people who are trying to do these things. Now, what we're going to say, and this is a very I apologize for the verbiage here, but what we're going to say, and what you're going to hear in the subsequent discussion is this idea of a biofirm which is a firm that is based upon homeostatic principles And it really, I think, addresses the many issues, both operational and aspirational, that you see in the whole biofinance movement. And to run through this fairly quickly, but you're going to find Andrew and Daniel are going to talk about these things in detail with examples, is that it's first principles based. It's grounded in scientific method, Bayesian statistics, and Markov blankets. In other words, you drill down to it and you really understand it rigorously as a science. You can understand what it's based upon and how things work in a principled way. It's also computationally tractable at scales and with free metrics for doing the whole kind of reporting and that you have this required environmental reporting. They call it MRVs. And so do you have a method by which you can make statements and claims about the state of the environment that scales and can be used for cross comparisons? It's also it's open source. So the bioform is like a kernel. Think of it as a Linux kernel for a new kind of organizational structure, can then generate a new kind of economy that's biometrically based. Another key component is if we're going to scale our capacity to deal with nature, it's going to be a lot is going to have to be automated. There's so many tasks involved in different parts of the world that you have different skill sets. How do you automate some very complex things in a way that can be trusted and generate metrics that other people are willing to accept? This has been a big problem in climate change, and this is where an extraordinary automation of cognitive tasks through large language models, transformers, and agent architecture allows for an automation of many of the tasks of collecting and analyzing the data and learning from the data. This is very significant. And then you have the capacity to create networks of agents working together and to create a system of exchange. So that's a natural evolution that's happening into edge-based computing, that you can have computing on the edge, you can security on the edge. So that's another phenomena. And then I think the idea of polycentric governments, this is made of that, but what does that really mean? Well, it really means if you look at agents that are self-organizing agents and dynamically relating to one another on the basis of the free energy principle, these other principles, you have the effect of a polycentric governance. And you also have the ability to formally give agency to nature, to different species, to different peoples, to different kind of competencies. So that is the whole nature, as I say, of an agentic architecture. And then I think you have a principal means of interfacing between a biometric economy and the current economy. That's going to be really important. So you can't just live in your own little world. You're going to have to interchange with the fiat economy of the world in such a way that actually protects and establishes the value of a biometric economy. And finally, I think it provides a principal basis for valuing nature-based currencies and assets that we can discuss a little bit in the time to come. So that's basically my comments. I think that I always like to end and say, let's make it real. That we're actually, I think you'll see in the following discussions, we're at a point where I think the technology is getting sufficiently mature to actually engage in developing use cases of this and bring it to scale. So with that, I'll hand it over to Andrew. Thank you.
Great. Thanks, John. Quick mention to Daniel. John and I had a really nice conversation prior to this. If it's possible, I might actually start my talk now. And then, yeah, sure. Perfect. I was hoping that would be the case. And then that way, John and I can also have a little bit of back and forth potentially during the course. And obviously, Daniel, you've had such a big hand in the development. So anytime, you would like to chime in, please feel free. Great. So, cool. All right. So my original plan talk for today was entitled, let me get rid of this guy. Active Inference is a framework for social science-based modeling. And, okay.
Something happened on the way to the symposium.
Oh, yeah, exactly. Huge updates. I want to just give a little bit of context. For some time now, I've, I personally gave a talk a couple of months ago, a 3.5 hour workshop, basically at an international conference for computational social sciences, held at University of Pennsylvania, July 17th this year. And what I was trying to do was basically teach computational social scientists, that means economists, sociologists, political scientists, and so on, who are very savvy with computers, essentially, how we might be able to employ active inference in agent-based modeling, which is already, a decades old at this point, method of designing basically simulations of agents inside of environments where agents might be, human beings, and an environment might be, a market system or some other kind of environment that humans find themselves in, where you can play out simulations and test things and so on. I want to introduce that to computational social scientists, and I think more broadly, what's great is that this symposium now gives me the opportunity to kind of flip it to where I can kind of bring some of what computational social science does to other active inference researchers. But to stay on with the biofirm, I really wanted to, again, as Daniel said, something happened on the way to the symposium. I've had these conversations with John since I did that conference, and I have a lot of kind of strong intuition that a lot of what he's been describing is a really wonderful sort of direction for future work in both agent-based modeling, but also applications of that kind of in the real world. We're always operating under conditions of uncertainty and trying to figure out kind of what to do in very adaptive ways, where our environment is constantly changing from implementation of computers, social networks. We have climate change. We have the typical booms and busts of our economic systems and so on. So I'll start here, but I just want it to be known, like, there have been a lot of heavy revisions to this with a lot of development we've made on the biofirm, thus featuring biofirm. So again, I'm Andrew Pashea. My day job, I work as a data analyst / scientist / engineer, always many roles to fill. And so I bring a lot of those kind of skills with me to active inference and how I view things like developing kind of applications for specific use cases and things like that. I think that there can be a lot of rich interdisciplinary dialogue between different fields, and that includes the kinds of things I do on a day-to-day basis versus my interest in active inference, which has been going for the past few years now. So I've been an intern, and I suppose I'm feeling much more like a full-time kind of affiliate of the institute at this point. I've been teaching the textbook group with Daniel, co-facilitating that. I've been involved in various projects, and then now this kind of partnership with First Principles First, and what Dr. Clippinger is trying to accomplish in developing the biofirm. So I just want to put on this title slide here, these are actually links to, if you would like to get involved with the Active Inference Institute, check out all the kinds of things that are being put out by First Principles First. And also, I just want it to be known, like, you can come back to these slides as needed, as well as any of the other kind of learning materials I've been producing, whether it be for the conference that I did a couple months ago, including on the code, how to actually create active inference agents from scratch, moving up to multi-agent simulations and so on. I also did a talk with the Institute recently that kind of walks through some of the code. So the new outline for this talk, we're going to touch again on agent-based modeling, which we already talked about yesterday a little bit in the first workshop. So we're going to kind of skim through that a little bit, but I want to put some special attention upon the aspect that of agent-based modeling, referring to what are called micro assumptions about behavior. Point blank, if we're going to simulate humans, we have to include certain assumptions about how we think humans behave if we're going to simulate them in an environment, right? Otherwise, we can create a list of humans, they do nothing until we give them some kind of rules or behavioral, dynamics or something along those lines. So those are essential for setting up agent-based modeling. And then we'll shift over into active inference. We'll look at the POMDP as a kind of exemplar model, talk about some multi-agent examples, just to give a sense of what kind of work can be done in this area. Many people watching this now who are already involved with active inference. There'll be some aspects of this that are, might come off as a little repetitive, but I don't want to, I want to stick to the textbook, so to speak, right? I want to kind of keep this grounded in a sense that, folks who know about active inference, don't know about active inference, have some vague interest in active inference in this in-between area, like can catch on to the material here. Next, we'll go into this question, are LLMs agents? There's a lot of exciting work being done with LLMs. They're showing incredibly, exciting and surprising, sophisticated reasoning skills and capacities for dealing with natural language. That said, and it's already been said so many times in the other talks given in the, during the symposium, but it's worth repeating. Like, they have limits. There are issues, and I've been doing some work on thinking through how do LLMs relate to things like cognitive theories. How does an LLM think, or how does that work really, so that we can really grasp if we want to incorporate LLMs into, say, agent-based modeling, software applications, or otherwise. Let's come to terms with like the reality of what they are before assuming too much about what they are or what they're capable of, and furthermore, how we might be able to integrate them into kind of more grounded means doing agent-based modeling, such as working with actual agents. The quick answer to are LLMs agents? Are they agents? No, that's the quick answer. They're not. That's what I will claim. And then we'll move on to the biofirm, which frankly will take up the majority of the rest of the talk from there. So what is agent-based modeling? As already stated, we have agents. More specifically, it's a programmed entity. It could be a person, a living organism. It could be representative of an entire institution or otherwise. And basically, programmatically, it receives observations from its environment, and then it returns actions back into its environment. For example, an agent could be a person, an investor. And then with the environment, the environment could be an artificial or real system that elicits observations for agents and then receives the agent's actions. Those actions then impact the environment itself in turn. For example, the environment could be a stock market. So we see that there's a reciprocal relationship between the two things. An agent or environment's action is an environment or agent's observation. So the agent sees a price signal from the environment. They make a purchase. Next morning, prices have adjusted, given that agent, maybe other agents' purchases. You see, so there's this kind of back and forth in a loop, at certain time intervals, such as in time steps, or we could imagine them in days, like on day one, this happened, day two, this happened. In active inference, the agent environment's respective Markov blankets, which kind of define what it is to be that entity, whether it be the agent or what it means to be that environment, including all the structure, the characteristics. If it's a person, then maybe it includes things like their goals or their what it means to maintain homeostasis. So an individual has blood and oxygen flows in their body. What does it mean to be that entity? So from there, we simulate them. We play out the agent environment dynamics over time. Again, as I said, in time steps, some other kind of interval. And then in active inference, we often use the phrase action perception loop. It's like you do something, then you perceive the outcome, and you elicit your next action, receive the outcome. And then, arguably this happens at a very rapid pace in actual human beings, right? This goes beyond just time step 1 or 2, or we measure this in nanoseconds or otherwise. So core guidelines for setting up agent-based models. We want to make realistic yet simple as possible agents and environments. That has to do with, generalizability. If you make something that's so unique to a particular situation, it might not generalize well. So if you want to make an agent-based model of, say, agents taking care of a natural environment, if you make the agents way too specific to that environment, to where they, if you want to set up this agent-based model, get insights into what you can do in reality, you want to make sure that what you test in the model can actually be carried out in reality. It can't be too specific. It can't be off course. Robustness, simply small changes don't dramatically change results. So, if you fine tune something too much, such that, the results of the experiment end up being dramatically different, then suddenly, once again, we have that generalizability problem. Reproducibility, everyone knows reproducibility problems exist in modern science. We need to document and publish, our code, make it available to other people so that they can understand it, recreate the results, etc. And finally, usefulness, which is simply, why do this? If we can't get any kind of additional useful insights out of setting up these rather complex computer models and programs, why do it? And so it's worth having that in mind. Not all models are right, but some models can be useful, right? In the statistician George Box's words. Then purpose. So we do agent-based modeling in order to predict outcomes. We could try and extrapolate from the present. We can entertain different kinds of hypothetical scenarios, design new policies, and have them play out over the course of the simulation, see what the outcome is. And then we can also look at collective outcomes of aggregated individual behaviors. If all stock investors in my simulation all began investing in this particular stock, like, what happens by the next day? Do we end up with some kind of bubble and then bust kind of situation? Like, what occurs, that kind of thinking. And then over the past couple decades, and this is really what I wanted to highlight a couple months ago, and what I would like to highlight now again, and I think it's especially relevant for anyone wanting to do agent-based modeling, and especially folks who are interested in active inference, there's been a cognitive turn. A lot of these traditional agent-based models, they're very interesting. A lot of thought has been put into them, but their agents tend to be very simplistic. In part because 40 years ago we were working with much more, at this point, archaic computers and computer architectures and devices that simply could not run simulations that involved many interacting agents who all have highly sophisticated behaviors. Furthermore, it's called a cognitive turn, not a complexity turn, but a cognitive turn, in the sense that we're looking at actually more closely approximating human behavior. So that means actually looking at other fields ranging from neuroscience, cognition, psychology, social sciences. That means looking at cybernetics, biology, trying to open up the discourse and the dialogues over how can we more better approximate human behavior. So there's some common characteristics for these calls to cognitive agents. That includes like having agents have beliefs. They update their beliefs based upon what they see. They have to infer what to do, in a sense that they're more autonomous. They kind of make their own decisions. Traditional agent-based modeling, it's like, well, if the agent sees X, then they do Y. Otherwise, they do Z. And these highly simplistic, programmatic rules that the program, I program them that way, so I already know that they're going to do that. Whenever it comes to agent-based modeling with cognitive agents, I don't necessarily know exactly what they're going to do. They kind of make their own decisions, right? They have the architecture for that. And then also reinforcement learning, which is kind of a adjacent or subfield in some ways of like machine learning, data science. A lot of these kind of state-of-the-art, but still rather standardized at this point, ways of doing modern data processing and analytics and predictions and forecasting. Reinforcement learning is a way of doing that where you actually have an agent, right? So that's been kind of one of the main ways people are trying to continue this cognitive turn in agent-based modeling. Now, micro assumptions. It's a lot of information for a single slide, so it'll be over soon. But I really just wanted to give kind of a picture of there's so much research that's been done, so many more kind of dialogues between fields that can occur here now. when thinking about how to make cognitive agents, what makes sense, what's realistic, but what also balances complexity and accuracy, keeps things simple enough to where the agent-based model can actually be useful. So there's been a lot of criticism at this point, centuries of criticism of this kind of neoclassical tradition, classical then neoclassical tradition, Adam Smithian kind of tradition that tends to paint humans as utility maximizers. It's often criticized because it's too simplistic. It reduces people to being greedy or immoral, as if they're just going after, profit without any concern for any other, condition or needs or wants or, so it's kind of selfishness, right? Without any form of altruism or sense of community. Some people point to economist Lionel Robbins, kind of a classic in the field, who claim that unlimited wants, scarce resources, that is the fundamental economic problem. Yet this assumption, I think this gets overlooked. I also criticize the utility maximizer assumption, but I want people to be aware that this leads to a really useful tool, which is for agent-based modeling. You can severely reduce computational costs for putting together agent-based models if you just have a bunch of agents who are trying to act to maximize a singular value. There's not a lot of complexity there. You can run those equations quite quickly, right? And then that also assumes that the main thing in your environment is the singular value that is utility, or a stand-in might be money or some general notion of liquidity. And so since then, we've had so many other ways of looking at human behavior, behavioral economics and finance, psychology, cognitive science, social theory. Humans aren't just trying to maximize utility. They're speculative. They don't have fixed preferences. They actually look at one another's decision makings. This goes back to John Maynard Keynes. We had Hyman P. Minsky, who looked at market crashes. We have Robert J. Schiller, who's still alive today and writing on narrative economics, the idea that ideas have an impact on how we interact with our economy and how we behave. There's Kahneman's thinking fast and slow. Like sometimes we just rely upon heuristics, or maybe we do it a lot of the time. It's quicker. It mitigates having to put a lot of thought into things where we just kind of want to get something done, even though it's not necessarily maximizing utility. There's Fowler and Sunstein's nudge. It's like sometimes, you do just go with the default option. Some people, whenever a website asks them, like, do you accept all of the cookies? They will click yes quickly just because they want the thing off their screen, right? And then we have social emulation, mimesis, convergence, ideology, all of these theories. What is money? It brings up the question of what is utility, what is money? Currency actually isn't just a means of exchange. It's not just. It can also be a store of value as its own value changes to try and do kind of economic transfers to make sure that you get higher value out of whatever form of currency you're holding. It's also a social institution, though. Is much broader, right? So having access to money, as many of us know, allows you to be, first you have access to a variety of commodities, assuming you're in a market economy where many things are fungible and tradable in that way. And then we also have social belonging. It's very difficult to maintain yourself in a society where you have no money, right? So it's a whole dimension that is lost if we just look at something like maximizing utility. I've put a mention of Louis Althusser, which is a much more kind of critical theory approach, but it looks at the impact of state, law, different forms of coercion upon people to act and behave in particular ways that go beyond just their ability to try and maximize their own profit. But pragmatism, people update their beliefs. They're forward-looking. They don't maintain the same preferences and ideas and rules throughout history. They change. They have their own circumstances, and so there's a kind of pragmatic approach to life. Karl Polanyi, economic activity is embedded in society, meaning that a lot of the economic activities that we have, they themselves are predicated upon our ability to trust one another, work with one another, and all these other kind of things, where whenever that trust is harmed, it can dramatically change how that economic activity plays out. And then we have neuroscience, biology, physics, and that you can see how we're moving more in the active inference direction now. But we have these are predominant theories now in neuroscience. The idea of predictive processing, that that one comes to a situation with their prior beliefs, and they can be updated in the sense of the Bayesian brain hypothesis, a kind of way of mathematizing that process. We also have, and this is quite old now, but it still stands as a rule like Hebbian learning or associative learning. So someone who associates money with being something bad very well might not, have such a drive for money versus relative to other things. And then homeostasis, allostasis being planning for homeostasis or homeostasis in the future. These are obvious things for us that we deal with on the day-to-day. We need to fulfill our needs, physiological needs, neurobiological needs, unconscious processes in the brain. That goes beyond being able to say that every single thing that we do is necessarily conscious or deliberate, right? I'm not actively trying to think about how to regulate my blood or oxygen flow right now. We also take preventative actions. We do things that might be a cost right now, but they change the impact of whatever happens in the future for us. We are forward looking in various ways, and we do often rely upon habits as needed to fulfill our needs. Habits allow us to do things without having to put in too much expenditure, mental expenditure, metabolic expenditure, to ensure that our needs are going to continuously be fulfilled. And cybernetics, embedded cognition, this is the idea that behavior and even intelligence arise from interactions between brain, body, and environment, which kind of overcomes some of these ideas, classical ideas of cognition mainly being outside in, where you just kind of look at what's around you and then you take that in as a passive observer. Instead, we're actually always in communication with what's around us. Immortal computation, in the sense of we can move in the direction of, if we want to do something like cognitive modeling, then we're looking more at, actually trying to mirror these kinds of processes that are much more realistic. Collaboration, imitation, computational neuroscience, psychiatry and modeling internal dynamics in form of, time series neuroimaging data, applying different kinds of techniques like causal inference to see how one factor impacts another, one variable impacts another. Actually trying to find correlations between internal neuronal dynamics with actual behaviors that occur. So for example, sticking, kind of electrophysiological, like electrodes on, a mouse in a T-maze to see, like, okay, what kinds of neuronal dynamics correlate with, the rat choosing to go left to find the reward, find the cheese, or otherwise, and then taking that and trying to move in the direction of, creating an agent who basically is fit to the behavior of that mouse or rat in the T-maze, right? And that's a classic kind of example that's looked at in active inference. And we also have the Hamiltonian principle of least action, much more in the realm of physics, and it deserves a whole slide or 10 on its own. But the main idea figuratively is the idea of something occurring based on following whatever the easiest path is from one state to another. So a lot of these themes, the idea of social homeostasis, relying upon heuristics versus planning and forward looking versus dealing with whatever's going on in the moment just because you need to figure out what to do now, even though it's not something you planned for. All these kind of aspects start to come together, I argue, in active inference. So it's kind of like, should we be considering something like Homo economicus revised? Again, liquidity is a means for all commodities, at least in a market economy, at least assuming fungibility of things. That liquidity can get you many, many things. In a certain way, I almost want to dial it back on saying it's immoral to want liquidity. It allows you to fulfill your needs, again, in a market economy by seeking out necessities for your own homeostasis or allostasis, physiological relief or otherwise. Even then, even as your bank account increases, that doesn't necessarily mean you're going to have your social needs met, kinship or familial needs met, physical health. If a doctor tells me after I've suffered some kind of injury that I actually need to do stretches now in order to make sure that my arm will move going forward in the way that I need it to. It doesn't matter how large my bank account is, I'm still going to have to do those stretches, right? So there is a simplistic example, but all of this is to say, for agent-based modeling, rather than thinking of utility, especially utility in some vague abstract sense of, is it money, is it liquidity, is it something else, there could be a shift to a kind of alternative, what is essentially a virtually, contextually universal value computed by the brain, which can encompass not just to drive to liquidity, but other aspects of means of life. Simple as possible, yet no simpler. And then it itself becomes a simplified recordable RIP metric for measuring one's capacity for current and future survival. And so that, enter the free energy principle, which is one of the central principles of active inference. Here we're minimizing a quantifiable uncertainty. That by minimizing this, it allows us to achieve our goals, fulfill our needs. We learn, we actually change our minds. We learn new information. We are not fixed beings who, are kind of one-dimensional. We update our beliefs. And free energy is a proxy for uncertainty or surprise. It's computed quite easily, because it's a variational quantity. There's an approximate computation, which, in physical living beings, that keeps our metabolic costs low. And for agent-based modeling, that also means keeping computational costs low. And so it still kind of fits, the usefulness of what utility was for agent-based modeling. I think that free energy can instead be the new kind of metric that we're looking at. And I included this kind of fun fact that there was a nice talk given not too long ago with Active Inference Institute. Some folks who do neuromorphic computing just reminded us, like, despite how many calories our bodies use on the day-to-day, the brain only requires roughly 4 bananas worth of calories, despite the fact that it makes 10 to the 15th calculations per second. It's just a reminder of like this variational aspect, right, of being able to do quicker approximations. And then we talk a lot about free energy, but I really, in the kind of funniest kind of way, I just have always been fascinated by this equation. This is, a textbook equation from active inference, but so G is our expected free energy related to deliberative planning, goal attainment, information seeking, conditioned on our homeostatic preferences, right? So we plan for things to take care of ourselves, to accomplish things we need to. F is variational free energy, another quantity where we balance the complexity and accuracy of how do we deal with the moment. Then we can think of this as like, say you're camping in the woods and suddenly there's a bear. It's like, well, you didn't plan for that. And you didn't expect that, and coming up against a potentially dangerous bear is probably very much against your preferences for maintaining your homeostasis, in this case, your sense of physical safety. So you have to deal with that. And then E, those are your habits, your heuristics. So what I'm saying is that I particularly appreciate that we have a quantifiable way, here of trying to decide what it is that determines someone's actual behavior, the posterior beliefs, meaning what policy or action should I take, right? All of that is kind of all these different considerations, habits, deliberative planning, moment-to-moment planning, all these things are involved in that. So it's an attempt at, from my perspective, like, we're actually combining many of these interdisciplinary perspectives into a single equation there. And so active inference, I think I appreciate this attempt to try and do this kind of mapping of, neurobiological substrates to actually interpretable cognitive theory regarding what is a habit, how does that, what composes that in the brain, what are goals, what is planning, what is action, and then from there moving on to these kind of exemplar initial active inference models, which themselves are highly relatable to reinforcement learning. So it's all to make the case that active inference, I think, it draws connections and kind of builds bridges between all of these, these other disciplines in a way that is very rich, and it's not so exclusive, right? It doesn't it doesn't stop conversations, it starts them. So, and then I also wanted to show, like, here's just a quick list of some multi-agent simulations with active inference that I think, it heavily relates. It is agent-based modeling. You can open the textbook from a couple years ago. Agent-based modeling is there. This isn't foreign to active inference, but I hope those in the agent-based modeling community can start to see how strong these relationships are with active inference. So epistemic communities under active inference, this paper was recreating agents who hold their own opinions about things, and they're in social networks, and so you can study how they share beliefs with one another. And yet, given a lot of these kind of formal principles in active inference, seeing how that plays out, we can actually see what the kinds of dynamics that we start to see on Twitter and other social networks, where opinion polarization begins to happen depending on how the network is set up in the first place. So it's very interesting. We also have active inference. This is much more kind of a biological or zoological example. Where there are ants in a colony who have to adjust to changing contexts, such as changing food locations, and then they leave one another pheromones so that they can actually follow one another's trails, so to speak, to find the food and come back. And then this is very recent, but we had another talk earlier today, but this paper with Connor Hines, who's one of the developers of PyMDP, which we'll be seeing shortly. He and Fristen and others are developing further tools for doing active inference, and this kind of gets at the question of like nestedness and looking at how whenever you have a bunch of individual agents, what are the cases where their collective behavior actually you could fit that behavior back to the individual parameters that each of the individual agents hold. And then again, with social science, like looking at agents who have distinct roles, such as leader and follower, where it could be, you could apply this logic to many other situations. The idea is just looking at how agents who have their own distinct, available actions and beliefs, nonetheless, whenever they can kind of synchronize in their capacity to fulfill, a goal that they collectively have. So it kind of speaks to the idea of having heterogeneous agents with heterogeneous, concerns, but nonetheless with an umbrella collective concern, they're able to accomplish their goal. This next one, rather long title, Active Inference Framework for Collective Parallel Problem Solving on NK Landscapes. This is, I gave this at the tutorial a couple months ago. I just recreated. This was the point I was trying to make. You can recreate a lot of these old traditional agent-based models, using active inference agents. That's what I'm claiming. So I'm not trying to say, oh, all of these traditional models are obsolete. Not at all. I think there's so many fascinating design principles. I would love one day to recreate the Santa Fe Institute's artificial stock market, but with active inference agents, right? We can do that. So here I just recreated one where you have agents who are collectively trying to solve a problem represented on an NK landscape, meaning that they're trying to solve a very complex problem where there are a lot of interdependencies in different subparts of the problem. It's like trying to design a car. It's like, well, you can have a great car, but if you remove the wheels, it's no longer going to really be the kind of car that you need, right? Or you can remove the steering wheel, right? You need to have a certain combination of pieces there to have a proper solution. So agents collectively do that, and then you can study like, well, how well do they do that? Do they get stuck, with a suboptimal solution? And then furthermore, you can look at metrics like, oh, if we run this in different ways, what is the connectedness needed for them to reach the optimal solution or otherwise? So, and then finally, this is not an active inference paper, but this is just a reinforcement learning, based problem. But I included it here because I just want to make the point that this is focused on industry, right? This is focused on multi-agent settings where you can have them kind of work in a manufacturing firm that involves like making a lot of kind of rapid decisions in order to manufacture particular products. You could have agents kind of synchronized in a way that they can accomplish, that goal. And again, similarly with traditional agent-based modeling, where you could, swap them out with active inference agents, so to speak, you might be able to do this, take that same approach with looking at how people are using reinforcement learning today. I think it'd lead to very interesting results. So I just trying to bridge these kind of, dialogues between people. So now we'll move to LLMs as agents. This, I just think it really needs to be addressed. So LLMs have been increasingly integrated into a wide array of potential use cases. I included some resources here, like there are just dozens on dozens of research papers that are being published that try to use LLMs in these kind of agentic ways, where it's as if an LLM is an agent who, supposedly makes decisions autonomously and so on. Again, they're showing more and more sophisticated reasoning capacities. They're having kind of longer context windows and output windows, meaning you can feed them even more information at one time. They can release even more or output even more information at one time. You can also upload your own text files, documents, write your own prompts for them to respond to. So in that case, if an LLM really is an agent, then why not just skip all of this stuff with reinforcement learning, with active inference? Why not go straight to using LLMs as agents? Of course, I'm going to argue like we should not do that. That would be, it would be irresponsible at this current moment in time in terms of LLM development. I would argue that would be kind of irresponsible unless you're just kind of making some kind of entertaining or fun app that uses LLMs or something. But for something that calls for much more discretion, I would not do that. So what are the biases here? LLMs are trained on large corpuses of existing text. We all know this. What that does is it kind of sediments a series of cultural, scientific, explanatory, rhetorical, prejudiced information, figuratively, the snapshot of the retrievable, web scrapable internet, other digitized human and AI produced texts, to which the LLM's internal parameters, which are black box parameters. Now we have LLMs being trained to where they have 7+ billion parameters on the inside. And then consequently, their outputs are just kind of reflective of this. So a lot of these, prejudices have been addressed. Very obvious, in a certain way, very unfortunate things that we saw with initial LLMs were like racist, or sexist or otherwise kind of outputs coming from them based upon the materials they were trained on. People are trying to find different ways of training them differently to get them to elicit the responses that we want. But that's the thing. What's crucial when working with LLMs is the prompt itself. So I want to think, just put yourself in the chair, facing a computer, and you're using an LLM. What's really going on? You as the user, you prompt the LLM after it's already been trained. You have your own purpose or goal in mind that the LLM does not hold for itself. Quick mention, I'm aware that I'm doing some slideshow karaoke. I just, for anyone who's like, just want you to know, there's a lot of information. I want to make sure I cover it thoroughly. So the user must provide the context for this goal or purpose in their prompts in the hope that the LLM will catch on. Less figuratively, they hope that the LLM will be able to predict the series of words and sentences which correspond, in the user's final opinion, to the answer the user needs or wants, right? And so after training, the LLM, it can't actually learn what the user needs. It's always in the user's opinion, and we'll get more into that. But again, it's just making the point that prompt itself is incredibly important. This is kind of a simplified, ever so slightly exaggerated, illustration of the kinds of things I'm talking about. So if I go to an LLM and say, "Hi, my name's Andrew," it says, "Hi, Andrew," it now knows my name. How can I help you today? I ask it, help me prepare, I have a certain goal in mind. I tell it, help me prepare an initial draft for a pro forma business model, for an idea I have. Here are the following details that should go into that business model. Then it produces it for me And today it can even release it as a text file. And so I could click on it, download it. Great. Now, what happens whenever our conversation history is deleted? What happens whenever we exceed the context window that is repeatedly being sent back to the LLM every time I prompt it? We have context loss. So whenever that happens, the LLM, I say, okay, now please help me revise the file. Please provide the file you mentioned. It does not recall anything that came prior, right? What is my name? Your name is me, which is a slightly exaggerated example, but it just really wanted to make the point, like, it will use its reasoning where it's capable, right? And confabulation is a kind of a technical word. LLMs hallucinate in the sense that they can kind of reason things in a way that they end up coming up with false information. We have to be careful about that, right? We have to be very cautious about a lot of these characteristics of LLMs. So they effectively, I would highly relate it to someone who has anterograde amnesia, right? It is where someone cannot actually recall what has happened in the recent past, and nothing you tell it actually gets committed to long-term memory. And so I've kind of crudely used the phrase like the LLMs are kind of like talking heads. You have to repeatedly tell it everything in every prompt. And what's going on when you interact with ChatGPT is that a lot of this conversational history is being stored in the site in some kind of cache and being resent, and you're not seeing that process because they want it to be a nice user interface to where you can more easily use it. So recent agentic frameworks and workflows abound in recent research, yet the issues presented by limited context windows, confabulation, etc., still abound. LLMs with these conversational histories have been considered to be agents in various cases, yet in order to try and overcome some of the issues that I pointed out, there are a variety of frameworks that are being developed. So one idea is an actor-critic framework. You could have two or more agents. You give them different role prompts. You tell one of them, oh, you're a creative, scientist, and the other one, you say, oh, you're a harsh critic and an expert in literature on this scientific topic. And then you can have the first agent try and innovate and come up with something, and then the second agent critiques the former agent. So you have this kind of way of like, oh, in order to better ground the information that one of the so-called agents is creating, you can use another agent to kind of critique that and make it more grounded to reality. Another way of doing this is building up databases of retrieved documents. That is, it's an attempt to overcome the limits of context windows. So what you can do is you can repeatedly query an LLM and any true information, as well as any information you provide yourself through your own documents, your own prompts, any kind of formal documents you want to submit. You could kind of collect these in some kind of organized database, and then you could query that database in a way that you repeatedly send into the context window. Here's only the information that needs to be said right now, based on everything I have. And then that database kind of acts as your ground truth. That's a means of doing it. It's rather sophisticated. There are different ways of doing that. We'll get to that soon. And finally, there's a thinking or reflecting framework. I'm just spending a second on that. It's where you have an LLM come up with things, but then have it revise its previous responses. Very similar to an actor-critic framework. It's just you're viewing it as one so-called agent doing this as opposed to two. In all cases, the prompts are still incredibly important. So what's in a prompt? Well, there are many people who have now, coined the phrase prompt engineering, which is at this point has kind of become a field or even art in and of itself. This is a recent systematic survey of prompt engineering that covers literally dozens of techniques. For anyone who's interested in that. There are many ways of doing this, and furthermore, some other problems include difficulties handling numerical or symbolic problems. So intuitively, if you read 2 + 2 = 4 as a string, as opposed to being able to recognize, oh, these are two numerical values that need to be added via an addition rule to compute a further value. It might not be tokenized properly. And so the LLM doesn't actually know how to deal with that, despite the fact that to you it's very obviously just a mathematical statement. So LLMs are getting better at dealing with math, much better actually, but they still risk this kind of imprecision. So if we want to actually incorporate LLMs into software applications, especially those that have stakes, right? Those that have real world consequences where you're actually employing them in any kind of like in-depth industry related setting in relation to what John was saying, in any kind of ecological setting, situation where you'd want to really carefully take care of things, verify the information and so on. You need everything to be much more precise and trackable than whenever you use LLMs in your application. You could have your applications, such as, if you're developing this in Python or Julia or otherwise, you could have that code actually handle the math, which is something we typically already do, as well as any kind of, like, if you're able to hard code any kind of rules that you can extract out of the text and actually consider those to be kind of, programmable, and then you can have them in your program and have that logic be carried out outside of the LLM, and you can just have the LLM handle the natural language aspects. So kind of my proposal, and this, I don't want to spend too much time on this because we'll see some diagrams that actually represent the ideas here. But I argue that we should be thinking about things like pre-structured prompts with what I'll call empty spaces. For anyone who uses Python, it's very simple. You just create a bunch of pre-constructed prompts that are structured in a way that you can basically supply the prompt. Here, you don't have to do this word for word, but you're effectively saying, here is what I need. Here is how I need it, how I need your output to be structured. Here are my current, thoughts or beliefs of what's going on. Give me what I need. But they make it an F string to where you can have kind of these empty spaces in between the prompt, to where at any given moment in time, say in an agent-based model, you can send the most recent updated information through the F string literal. So it's like you have a really nice prompt that really gets at what you want the LLM to send back to you. But if you want to have this run algorithmically, in a way that let it run autonomously, it needs to be that the information in that prompt needs to be repeatedly updated. Again, like reminding the person with anterograde amnesia what's going on now, and then an hour later, what's going on then, and so on. Bringing it back to active inference agents, we know they change their minds through perception. They act to change the world. They actually have capacity for learning, including online learning in real time, updating their internal model parameters, which might be likened to synaptic learning or modulation in the brain, updating their beliefs about the relationships between observations and states, the efficacy of their own actions, a lot of these other kind of cognitive mechanisms that LLMs lack. So to bring it back, LLMs, if they were like agents, I would say that they're like agents who cannot act nor learn. They only observe and infer. There's been one argument that they do act. It's just they don't quite, that because they don't learn anything, it doesn't quite matter, and they can't really observe the outcome of their action. It's like their action is they output, words and sentences, and that doesn't actually come back and impact them necessarily in any kind of tangible long-term way. They are typically trained once, very expensive process. Some people have tried to specialize LLMs by only training them predominantly on medical text to make a kind of a medical LLM or a legal text for a legal LLM, but still we're stuck in this like lack of online learning or something like clear preferences. From a neurobiological perspective, LLMs have very broad yet immutable long-term memory, and they're trained on a lot of information, and then they have a highly variable short-term memory. Their context window, which if anything happens to that and it's gone, then they've lost all context. And so I argue that we should think of LLMs as a language processing tool. I think they're very effective at that. They absolutely outperform us in terms of being able to feed them many texts and then quizzing them on those texts. Just in the plainest day, they far out. They exceed us, and this is part of why they're so popular now and being considered for software applications. And from this vantage point, we can envision augmenting agents who learn and act, such as active inference agents, with something like the capacity for natural language is how I'm currently phrasing it. So this is kind of my diagrammatic, attempt at formalizing this for anyone. These are a lot of the design principles that are going into our biofirm that we're developing, right? I started developing this whenever I considered how could I have an active inference agent write a scientific paper by prompting an LLM like on its own, right? So each action of the agent was, prompt the LLM to find more literature and citations. Another discrete action is, write or revise your abstract. And these other aspects of writing a paper, and then seeing if it can kind of, choose for itself what to write, rewrite, update, and so on, and how would that work? And so a lot of that thinking has kind of gone into this project. In this case, what you would have is, for a user of the biofirm, they would be able to kind of, submit their own documents, PDFs, text. This is kind of the grounding truth representative of, the user's own preferences, their goals, what it is they want to accomplish. That gets input into structured prompts, F-string literals, like the empty spaces. That way, it'll basically take your inputted information and restructure it in a way that's needed to get the kind of answer and the kind of response that you need. So the documents are sent to the structured prompt, which is then itself sent to the LLM, which processes it and returns your structured response. Structured responses, allows encoding for agent observations, meaning you could, in a very simplistic example, you could ask an LLM, is this a good idea? Yes or no? And that can be encoded as a 0 or a 1. And then the 0 or 1 can then be, read up as an observation for a particular observation modality that an agent, a POMDP, is equipped with, right? That's very kind of elementary approach, but I hope it maybe explains the idea for programmers who are interested in these kinds of things. And so, that observation is then taken in, and then the agent can infer states per usual. What it takes the LLM's, feedback into account in its decision making, and then we have expected free energy, meaning, the free energy it computes condition on its preferences, right? So it's like saying, oh, the agent can take in an LLM's, natural language based feedback to the user's initial preferences as elicited in natural language, and the agent can use that feedback to make decisions in order to follow through on its own preferences or goals, right? So you have this kind of reciprocal relationship between the user and via the LLM vicariously to the agent, and then back again, as you can take the agent's current internal beliefs. It elicited this policy, it now believes this, it previously observed this. Those can be put back into a structured prompt, which could then be sent to an LLM for a new structured response. And that might be something that involves like reporting, like the agent is, in natural language reporting its beliefs about what's going on. And then that can be useful to the user and then be sent to what we'll for now call a knowledge graph. Apologies, I just now realized that this is being covered. And so then this knowledge graph, and we'll get more into that. I was very happy to hear some other people making references to knowledge graphs during the symposium. It can be done in different ways, but a general sense of a knowledge graph is that this is kind of like your database of knowledge that you're gathering over time in terms of, natural language based knowledge. So it's kind of like you're storing the context of the moment. You're kind of storing the truth. You're storing the history of what's going on in terms of these agent LLM interactions. And then that way the user has the means of reviewing for themselves in everyday terms what has played out during the course of simulation. So that's kind of the design principle. And then the knowledge graph, this is a way of kind of overcoming the limited context window issue. So in a general sense, and I'll mention a lot of my thinking about the knowledge graph comes out of this really like very recent, exciting work being done by Marcus J. Buehler, who works at MIT right now. He's been trying to find ways of using LLMs to basically go over many texts in order to find patterns in the text that can then be kind of put together almost in this like a Schumpeterian like innovation way of like just recombining materials that already exist in text, but maybe humans themselves have not yet made those connections themselves of, we know all of these many different things. If we look at it this way, that actually leads to a new innovation that we could come up with. We just didn't make that connection before, but we did now. It's like, you can have LLMs who are highly, sophisticated whenever it comes to going over large amounts of text, having them make those kinds of discoveries. So anyway, that's the kind of where this is coming out of. And then sources for updating the knowledge in the graph may include user documents, up-to-date environment or resource reports and agent beliefs, domain knowledge regarding your use case, LLM responses to structured queries. We kind of looked at that before. Business model as a shared narrative. It doesn't have to be a business model, but it could be you have many in the context of the bio firm, which we'll get into shortly. The idea is agents are working for a firm, and so they need to have this shared narrative between them that kind of captures all the crucial core elements, describing what are the operations of the firm, what are the guidelines, what are things that they need to attend to, regulatory or legal standards, what are their current financial statements, what resources do they currently have available, what are the perspectives of all their different stakeholders, being able to synthesize that information into kind of a singular document that's short enough but nonetheless rich enough that it can be repeatedly sent back to the LLM to remind the LLM, this is what we care about, these are our constraints, these are our central concerns right now or otherwise. So anyway, I'm getting a little ahead of myself, but that's how we can start to develop a knowledge graph, overcoming the limited context window by having a graphical structure to the knowledge. You can keep it nicely organized, and as we know with graph structures, with having nodes and edges, you can have along the edges can kind of be the descriptors that relate multiple concepts as nodes, right? So you can kind of traverse this knowledge graph to make connections between all the entities within it. These are the visuals here. Actually, Daniel created these based on some particular LLM structured prompts that he ran and then kind of analyzed. And so these kind of principles are going into it. So by using pre-structured prompts and querying our knowledge graph, we can repeatedly kind of communicate what is the situational context of what's going on in the moment, as well as here's the knowledge that we've accumulated so far that can help with problem solving during the moment. This allows us to filter down only to the needed information and synthesize it, reducing the final amount of information, in this case, tokens, which also, if you're using the OpenAI API, to use the most recent, like state-of-the-art models, where we're usually spending at least a few pennies per LLM prompt, or well, it depends. But the point is, by reducing the amount of information flow needed, you can keep the costs significantly lower as well, and then also kind of quickly overcome that issue of potentially exceeding the limit of the context window. And I'm interested in finding different ways of describing this. I'm particularly a large fan of Yuri Busaki, a neuroscientist at NYU who does a lot of work on neurobiology and has even worked with Friston at a point in the past. But so I included him to try and give a metaphor of this. This conceptually can be likened to theories of episodic memory in the brain. For example, this one theory that the hippocampus in the brain is something like a pointer. So whenever you try to recall, an episode in your life, that involved, certain many episodes, like in order to tell a story of what happened yesterday, starting from the morning, and then what did you do, at noon, and then what did you do in the afternoon, and so on. Like the hippocampus is a kind of pointer that kind of or almost like a librarian that goes through your long-term memory to kind of pull out sequentially what's needed in order for you to tell that story or narrative in the moment. Or from a kind of more industrial or a modern data analytics example, you could think of this as querying a database, SQL or MongoDB, meaning it could be a structured or unstructured database, where a report is synthesized via joining and querying only the necessary tables or catalogs of logged information needed for the report. So again, it's this graphical structure that allows us to kind of more quickly get the information we need without having to pull too much more than what we need. So now this is an example of, I'm just currently phrasing this as like agent foraging and knowledge updating. So it could be starting from the top left, we have our homeostatic agents. John made a reference to them earlier. But the sense is that these are agents who have their own preferences for, maintaining their own homeostasis. They might be trying to maintain the homeostasis of their environment in the case of an agent who's designed to take care of an environment, which is what we'll see in the biofirm. They'll have their own current beliefs. They're being updated over time. We saw kind of an image of the inner dynamics of what that looks like for a POMDP earlier. They might have their own goals, which again, in this case, would probably align with the idea of maintaining homeostasis. Based on all of those factors, that might lead to, some pre-structured prompt leading to something more specific. So in this case, this is an agent who wants to take care of an environment, and this is an agent who specifically is looking at how to take care of the soil on a natural farm, like a land preserve or farm. And so they need more information about the soil structure. So they prompt the LLM, what are causal determinants of soil structure in farms? This is like an initial, this is whenever you're first making the knowledge graph, you would want to have this knowledge at the very beginning of a simulation, right? So this is kind of building out your knowledge graph to start. So you could ask it this, you could tell it to cite your sources, or you could integrate some kind of API, such as Semantic Scholar or other APIs to try and check if it's actually pulling from real citations. Again, we have that risk of confabulation, making up seemingly true information. And so we want to just kind of keep a check on that. So the LLM can tell you a lot of natural language-based information about soil structure, the determinants, different kinds of management practices that could be used to take care of it, different kinds of conditions and relationships between the soil structure and other aspects of the soil, what's around it, all these different things. And then from there, we could kind of go back to the knowledge graph, store this, deconstruct this information. Ideally, this would be, we'd ask the LLM to structure its output in a particular way, and then we could send those different aspects of its response into different areas of our knowledge graph. So soil structure, determinants, management conditions, and then also track the citations. The knowledge graph, again, it's almost like a three-dimensional structure in that you could add the time dimension, that is, you could timestamp when all of this information is collected as well. So it depends on how sophisticated you want to make your knowledge graph. This is the last diagram I have related to this concept, but I just want to include it. This is what I mean by a structured prompt with empty spaces, right? So we have that same agent from before. Now we're sending a structured prompt. I believe that, so this is pre-structured, right? These curly brackets kind of denote like these are what are the so-called empty spaces. I believe whatever your current environment variables are currently, here's what the agent's beliefs are, but our goal is, here's our current business model, and our current constraints are, here are our current constraints. What solutions exist to address this? This is incredibly short and simplistic just for the sake of illustration, but the idea is you could input, you could keep these environment variables stored in your local environment. Python is storing and processing them. The agent beliefs are being extracted from the agent. You could re-encode those with natural language. You could include information like, oh, this agent's belief is representative of the quality of its environment. So then this gets read as a sentence that's something like the agent believes with a 0.2 probability or a very low probability that the current state of its environment is good. You could re-encode that. So this is really a conceptual kind of move to try and find ways of bridging the gap between qualitative and quantitative information. At no point am I saying that all of this is the absolute best way to do this. What I am saying is that this feels a little bit like frontier work. The LLMs are bringing up the question of how can we properly integrate them into software applications. And I think these are the kind of next steps in terms of our thinking of how maybe we should be approaching this. So, and then you can see again, for the rest of the diagram, we still have this communication. We can continue updating our knowledge graph. We can also pull information back out of the knowledge graph to send into the structured prompt. This can all be sent to the LLM, and so the LLM could do, you could request it to return your response in multiple ways. One way is you could tell it, explain to me in natural language, what solutions exist to address this, and then also ask it in the same move, also give me, these encodings of your answer. So it could be that the LLM responds some kind of natural language explanation of how to handle this problem, but additionally, here's the structured encoding you requested, denoted as follows: a positive 1 approved recommendation to carry out available action 6. Might be the case that this your agent has an observation modality, meaning it has like a sensory receptor for the LLM, where a 1 it corresponds to like an observation level of like a yes or an approval, or go for it, basically, and then 6 is kind of like a second observation modality where the LLM tells you which one of your available actions you should take. So this is just an attempt at trying to find ways to modify an agent's architecture such that it has a kind of receptivity to LLM outputs in a way that can go from natural language to actual directives over what to do given the current context and all the information you've asked of that you've provided to the LLM in the structured prompt. Now we move to the biofirm. So the biofirm, this is a lot of the principles I've described thus far kind of play into this. Again, a lot of work has been done on this by Daniel Friedman here in the talk, and then a lot of initial kind of coding work was done by myself. And then we've, of course, been under guidance and with partnership of John Clippinger as well as David Lovejoy with First Principles First. I really like a lot of kind of the media and writing and podcasts that they've been doing. And so I would strongly suggest checking them out. And it's been a pleasure working with them so far. And so with the biofirm, we have a significant amount of code largely built out, and kind of organized by Daniel with under the ActiveInference.institute's own GitHub repository, currently in a sub-project biofirm. We also have a whole nother library that we'll look at soon, but for now, this is kind of the starting point of the biofirm. Tool highlights. Right now, we're building active inference agents as using PyMDP, which is essentially has already been referenced earlier in the symposium, a kind of port of SPM, the MATLAB library developed by Friston and others, and so it's been a really good library to kind of work with and quickly start trying to implement some of our ideas. The OpenAI API. Many of you who have worked with LLMs and tried to integrate them into code are already familiar with this, but basically it's a way of quickly being able to prompt within your coding environment a wide array of LLMs, including the most recent ones and the new ChatGPT or Llama or otherwise models, Claude, Sonnet, and then Cursor, which this is not necessarily essential to developing the biofirm, but it's just Daniel has kind of opened my eyes, so to speak, to the wonders of kind of integrating for developers, being able to have an IDE where you're editing code, and then you can use an LLM to help you write that code. And obviously, you always want to go back and look and make sure that it wrote the code that you actually intended. But you can dramatically reduce the number of times you need to hop into, say, Stack Overflow, for example, if that makes sense to programmers. So it's great for productivity. And then also some major things. Daniel put out these live streams that cover a lot of the development of the biofirm so far. Both of them are huge. I mean, we're looking at a couple of hours or so of material, and we have close direct code walkthroughs today. Originally, ideally, I might have gone through some kind of code walkthrough. One, I don't think we're quite there yet in terms of being able to we can demonstrate the principles, but in order to have something that's kind of like within the context of, okay, we're doing, the Active Inference Symposium, and we kind of need to keep things streamlined. We're not quite there yet, but you can get a very big picture of what's going on in that code and get an actual code walkthrough by having a look at these live streams that Daniel put out. So the biofirm. Excuse me. Essentially, in a biofirm, agents are working in a firm. It's like setting the scene to maintain the homeostasis of an environment. It could be a farm, natural land preserve, and it could be many things. But for now, I'm trying to kind of constrain to kind of an example. Agents prefer, both in a colloquial sense, they want this, but also in a sort of Bayesian priors computational sense, to observe themselves maintaining their environment homeostasis. Their own survival and health, in this sense, are directly linked with environmental survival and health, mapping internal states to inferred external states, meaning their own internal beliefs are, they're trying to model their own beliefs directly as, kind of these proxies for what's going on outside of them in the environment. So they're very directly trying to map themselves to their environment. All of that being conditioned on preferences. Again, what do they prefer? Homeostasis, right? So they're trying to model their environment internally for themselves while simultaneously trying to keep that environment within some kind of homeostatic range. We'll get to a more concrete example of what that means. But for now, we can just think of it as like, that an agent's own homeostasis involves realizing his preferences, relatable to how humans infer and act to maintain their body temperature, oxygen, and blood flow, sense of safety, security, whether it be physical or economic. So in this case, minimizing their own uncertainty, conditioned on preferences, maintaining homeostasis is equivalent to minimizing uncertainty about if the agent is successfully keeping the environment in a homeostatic state. That's kind of a one sentence, concise way of looking at that. They're minimizing their certainty about if they're able to successfully maintain the environment in a homeostatic state. From there, we, ideally what we would do is move on to building a knowledge base, for example, a kind of knowledge graph, which itself would, in an initial setup phase, would involve user submitted documents. So for our example case, we actually did submit both a real document that John supplied related to this farmland, kind of natural preserve that he himself is taking care of. Of course, it's been redacted. But the point is that this gives us a kind of real world example that we are quite familiar with, contained in a document that we can use, for an initial testing use case. And then you can also do other things. You can send in specific kinds of like structured queries, asking for more domain knowledge or information about, say, how do we take care of a farm or otherwise. And we have all of that. And we follow that up by, structured prompting. Another idea we have that I won't go too much into right now, but one idea is that you could actually extract out of natural language, potentially like syllogistic reasoning-based rules. That there's a researcher, Axel Constant, who's done some work in the legal domain and looking at kind of Bayesian probability and graphs and relating that to syllogistic reasoning. I think that would be a really nice way of concisely extracting natural language rules, turning them into something kind of like symbolic, objects in Python that can be used as formulae for doing different kinds of reasoning that increases precision and reduces the need to make so many LLM calls and having the LLM do that. But it's a thought. Anyway, in any case, all of this, the whole development of the knowledge base or knowledge graph is motivated by agent preferences and beliefs. So social science, and I don't want to get too far away from that. I've been talking about a lot of design principles, but I think the biofirm itself, as currently it is an open source, sort of resource, it's still heavily under development. I'll get back to the aspects of what's going on with that a little bit later. But currently there's a lot of development being made and is being written in a way that we ideally in the future would like this to be adaptable to different circumstances. It might be the case that this could be quite useful actually for continuing social scientific research in the form of an agent-based model. You could consider that these might not necessarily be agents in a firm. They might not have a business model. They might have something else. They might have, a constitution, that links all of them or otherwise. For now, we'll continue working, focusing on the biofirm, but I just want that to be borne in mind that I don't want to present this as if it's a highly specific use case that, doesn't generalize, allow for generalizing beyond itself. But for now, we'll stick with focusing on it. So social science, we have agents who are collaborating in coalitions of agents and networks of agents. We have I'm attempting to say that we can augment agents with natural language, state belief reporting, with the consequent development of a cultural, and this is Dr. Clippinger's view, if we have agents who are motivated to take care of land and then they collect knowledge that corresponds to them, and then they're using and communicating using this knowledge, then this kind of becomes something like a culture. So we're looking at something like a kind of cultural grammar or set of scripts that are being developed via these agents taking care of the land around them, and we have shared narratives. And then on top of that, we also in a realistic scenario, we would have agents who are doing economic resource management and potentially trying to generate some kind of value in some kind of way, basically replenishing or regenerating sources available to themselves or otherwise. And then on value generation, and this comes back to the very start where I referred to utility as being kind of like what was previously the penultimate sort of incentive for agents in traditional agent-based modeling. Now, if we shift that to where now we're looking at expected free energy as the thing to be minimized, and in correspondence with the principles of active inference, then what we're doing is that we're looking at this is like the approximation of uncertainty conditioned on preferences. Agents are trying to minimize that value, where they're with value generation. A whole other thing we could do is look at each of the agents' marginal contributions to the minimization of this quantifiable metric that is expected free energy for the whole firm. Like look at their marginal contributions to minimizing the uncertainty of the firm, and then that itself becomes a kind of value. We can accumulate that and view that as kind of like uncertainty reduction is what generates value. So that crucially, this accumulation, it's not some arbitrary floating value whose own value changes based upon some kind of market speculation dynamics or otherwise. Instead, the moment-to-moment value generation that occurs during the course of a simulation of a biofirm, it reflects the agent's actual learning and capacity for taking care of their environment as proxied by expected free energy. And then the kind of broader multi-agent setting and future vision for the biofirm, their cultural aspects, again, as I mentioned earlier, this kind of an ever-evolving accumulation of shared knowledge. Again, we could have timestamps. That also means that we might need correction of that knowledge over time. We'll talk about that more shortly. Anyway, the evolution of the knowledge graph, it's motivated by and mirrors agents motivated to accomplish collective goals for homeostasis from various perspectives. You might have agents who are specialized in one way, agents in another. You might have multiple stakeholder perspectives that are being fed into that initial knowledge graph or along the way during the course of the simulation. Ethical, ideally, it would exhibit these kinds of principles, like by accumulating different perspectives between agents, between users, stakeholders. In the case of bioregional modeling, where there can be very, very many people potentially involved in looking at or being affected by how an environment is being cared for, or taken care of, or managed or governed. Being able to actually submit these potentially conflicting or at least different perspectives from various stakeholders. Those could be submitted to the program. It could also include financial, regulatory, or sustainability related knowledge. That can allow for comparing and synthesizing various perspectives, again, in some kind of actor-critic framework. As I mentioned earlier, like a lot of methods have been used to try and overcome the issues of LLMs, and so we'd be remiss not to employ those in various ways where appropriate. And that way we can better ensure that the information that's being used and processed and being fed into agent decision making and so on, taking care of an actual environment, we can make sure that it's much more accurate, coherent, also identify faulty or contentious information. If the agents come up with a very aggressive policy, prior to its implementation, it could be critiqued and revised from an ethical, regulatory, or legal standpoint. All of this is collective, and we can kind of synthesize the information. I already touched on this earlier, resynthesizing core information or primary information in the knowledge graph into being some kind of summary business model, constitution, a set of protocols or missions that the agents have. And then sustainability, resource management, making sure that agents are aware of available resources, combined with quantitative analysis. So you could, if you're looking at a real world setting, you'd be looking at things like price information, forecasting supplies needed for a particular policy. You might have qualitative reasoning involved, such as why, like which supplies are needed for a task, what purposes, within what guidelines. That's something I've been thinking about as well for a related institute project called FarmWorks. We might talk about that later. We'll see. And then heterogeneity. Agents might be pre-configured or learn. They necessarily will learn over time, assuming we implement learning and their architecture. We more than likely will. It depends on how and for what purpose. And then they might even, evolve, so to speak, to specialize in different skills and knowledge uses, allowing for agents to collaborate under broad shared goals while working on subtasks. There's some nice, we were joined by Mal yesterday during the first workshop. So Mal's been involved in a lot of this previous work. And then, another reference to kind of the industrial example that I gave earlier as to how we might think about some of these things. Basic form of a homeostatic agent. This is, just take a second. Homeostatic agent. This is the general, just kind of quick natural language summary of its internal architecture. It's incredibly simplistic. This is sort of a kernel of what is the initial formation of a homeostatic agent prior to any additional modification or changes in its architecture that you think might be required for the situation at hand. For now, let's say there's a single environmental variable. What we did, I'll talk more about it later, but the idea is that we have an environment that an artificial environment we generated. We generated it based on the documents I mentioned earlier, including John's farmland document, as well as particular prompts submitted to the LLM to kind of compose what are the initial makings of our knowledge graph. And it came up with soil structure as being one of the essential variables that should be included in our environment. And then we have an agent here who's kind of trying to map itself to this quantitative value. It is a question right now of, I can imagine those who do active inference, like the question might be, why use a POMDP? Why would you not use, a continuous time, continuous state space model? For now, we're going with POMDPs in part because we're assuming that we'll be using agents to model highly complex environments where it's not so simple as to kind of follow a simple up or down scale, or say that the variable is necessarily being defined by, you know, some kind of Gaussian distribution and being sampled from it. It might be the case that this is much more complex. There might be changing conditions or otherwise. In any case, for initial testing environments, which is also a rather quick thing to do, I will admit. So, but for now, the idea is that you'd have a POMDP who can view the data over time at each time step. Daniel ran this one for, actually, I don't remember if I ran it. He probably did, over 10,000 time steps. And so at each time step, the agent observes if the current value is above or below some homeostatic range, which the agent prefers it lie in, right? And so it infers the hidden state of the variable. Is it actually, if I observe low, is it actually low? If it's in its homeostatic range, is it actually in its homeostatic range, or is it actually, in reality, is it really high or otherwise? You know, and another question as to whether this is necessarily a partially observable environment, since this does seem to be reflective of real data. But again, this allows for the space that there might be very complex relationships between soil structure and, let's say, moisture levels in the soil, or microbial activity within the soil, or other kinds of things that really matter here, to where it's much more complex than just being able to say, oh, just because this went low, that means I need to try and bring it back up as much as possible really fast, right? So there might be more nuance, and having more sophisticated architectures might be able to kind of parse through that problem, including increasing inference horizons, or including more other variables that it tries to map. And then actions, the agent can increase, maintain, or decrease the variable, right? So again, very simple. A little more details later on how that can work, but just say straightforward, it's kind of like the agent is trying to balance out this metric, given that all of its fluctuations, aside from the agent's actions impacting it, are coming from its relationship with all the other environmental variables in its ecosystem. So it's kind of like the agent is trying to map its internal understanding of what's going on with the environment's behavior. And then the agent, of course, prefers to see this within its homeostatic range. And so it will choose actions that it believes will help this variable to get back into its homeostatic range. So from there, we can view this like as a whole ecosystem of variables. So this kind of defines our environment that we're looking at, right? In an agent-based modeling setting, we have our homeostatic agents, and then we have our entire environment composed of all these environmental variables. And over in a real-world setting, whether you're running a farm, or otherwise, you know, each of these variables could be mapped to, you know, an IoT device. They could be mapped to, you know, some kind of logged observations, you know, that your team makes as to what's going on with the farm right now. I guess I'll bring up FarmWorks again briefly. We've been looking at a lot of farm data lately that's been collected by farmers, and getting some inspiration on how they go about doing those things. But I will say that this environment that we have here is entirely artificially generated based upon inspiration from text. So if we think about this as something like agents are trying to solve a non-equilibrium steady state, what does that mean? I'll try and summarize by saying that we're trying to maintain the structure and properties of the farm. What is it that makes a farm a farm? Well, if your soil moisture falls dramatically too low, and then suddenly all the organic matter in it dies, and then many of these other things start to fall apart, well, now we're not quite looking at homeostatic soil anymore, right? And so we kind of have like this natural decay or dilapidation of the system, the ecosystem. And so agents are having to repeat, like continuously, you know, kind of actively maintain through control inputs, meaning through their actions, they're trying to keep these variables within homeostasis. And it's worth noting these target ranges, homeostatic ranges, might change themselves over time, right? Due to we can imagine the target soil temperature range might change to adjust for seasonal crop change. It might also account for certain kinds of like exogenous or external shocks to the system. The impact of climate change, there might be a natural disaster that occurs or otherwise that itself can really change the dynamics required to attempt to maintain the ecosystem as it is or as it was, or if it needs to kind of change in order to continue existing given what kind of shock occurred. So to maintain these desired homeostatic states, the agent must continuously work against these natural tendencies towards dilapidation. States, I've already mentioned this many times, these states, these variables may have complex interdependent relationships, may call for agents with forward-looking inference horizons. Of course, if we over-maintain the soil, put too many products in it or do other things that might still be okay for the crops, it might harm local biodiversity, local animals accidentally consuming different kinds of materials that were used to take care of the soil, and suddenly they die. That harms local biodiversity. And yet biodiversity might also include pests in the environment that themselves then harm the soil or crop growth. So it's just being able to kind of adjust to all of these highly complex variables. And crucially, in reality, we might only be able to impact some variables. Some variables and not others. Thus, agents might specialize in handling one particular controllable variable and study its relationship with the other variables, leading to actionable predictive planning. Another kind of everyday explanation of this is like, I mentioned I'm a data analyst. I work in education. And so, I'm frequently looking at a lot of data regarding students and kind of our institution and so on. I'm based in Chicago. Some things that we can change are bus routes for our students to make sure that they can get to school safely. Something we cannot control is the amount of crime in Chicago, which anyone in the U.S. knows is that would be very difficult to do. Right. So we're looking at, there are all kinds of factors in our environment that we cannot control, and then there's what we can, and then trying to find how can we control what we can control in ways that kind of can balance out with all these things that we cannot control, right? So that it's very crucial to be able to identify and then measure and analyze those kinds of relationships whenever trying to design any kind of concrete, actionable policy, right, or intervention that you might want to make. And then John referenced the commons earlier, right, in Eleanor Ostrom's work. Homeostatic agents solving non-equilibrium steady states, the ever solving the commons. So I'm trying, I was thinking about a lot of these principles, and Ostrom was required reading for me as someone who's coming, from a social sciences background. And so it's part of why I find this project so interesting, and why I find it fascinating to try to realize a lot of these things and principles involved. So we have local rules, conditions, adaptation. I mean, the agents necessarily have to adapt to the environment around them. If you provide some kind of kernel agent and give it some space to figure out what it is it needs to do, it's necessarily going to have to adapt, right? So we have that attention towards the local. Recognizing uncertainty and adaptation, agents will have to take care of homeostasis, manage resources through learning, to change conditions in broader, unobserved, uncontrollable environment, in the sense of, there are many things going on that the agents cannot directly observe. There are other things that will occur that were unexpected, and then also there might be relationships within the variables themselves that's, for example, there might be some kind of critical threshold that's hit by one variable that then has some kind of domino or cascade effect on the others, and so that's why I include both the phrases endogenous or exogenous shocks, being able to watch out for those kinds of dynamics. Then governing the commons, that's sort of the benefit of, if it can be done right, if it can be done successfully, integrating LLMs in a very thoroughly considered way that allows for accurate information accumulation and sharing, and then using it for implementing policies. That's the aspect that kind of keeps things grounded, and then gives this kind of natural language-based way of dealing with an environment. This kind of just repeats many things I mentioned before, but we're synthesizing a lot of info from various stakeholders, various domains, that are needed to handle the problem, repeatedly grounding agents in common goals, from maintaining the environment against perturbation, capture, maintaining its Markov blanket, and then nested collaboration potentially. So just as users can practice oversight by running these models, agents themselves, you might have agents who are at another layer, so to speak, who maintain their own oversight over other agents or coalitions of agents, and those kind of hierarchical agents might themselves act as something like an observer role. They might recognize a broader issue going on in the firm that isn't being accounted for by specialized agents, and so you can have those kinds of kind of hierarchical, specialized structural roles that allows for this kind of nestedness in how the environment is maintained. And then it's a very interesting idea that I was going to bring up later, but in the context of like looking at bioregional hubs or something along that line, I mean, if you were actually employing something like a biofirm to a real world scenario, then I don't see any reason why you couldn't have some way of interfacing between different biofirms, right? Because if they're actually playing out in reality and building their own knowledge graphs, say in real time or some kind of way, then you could very much have that kind of interfacing. You could have, structured prompts pulling from the knowledge graph of one biofirm, sending that information to another biofirm and back. So that's, I don't want to get ahead of ourselves, but because the vast majority of the actual concrete work that's been done on the biofirm has only been over the course of, frankly, the past couple of weeks. I mean, longer than that for sure, in terms of John developing the ideas, conversations we've had over the past couple of months, but whenever it comes to developing this stuff and actually realizing it, it's still quite new. So this is very exciting to report. Biofirm for users. Let me just see where we're at. Okay. I'm gonna have, I'll speed this up a little bit. Biofirm for users. Yeah. One, for a user's perspective, first you would submit your documents, as I mentioned many times. Your own PDFs, real world information. If you want to submit textbooks, regarding agricultural techniques and methods for taking care of farms, including formulae that describe relationships or something. You could have, from there, the direction is to have, there are two intended kind of potential paths you could take. Right now, all the testing is being done with the first path, but the ideal is to move it in the direction where you can have both available. First one is for being able to explore counterfactuals. So we generate synthetic data using domain knowledge or historical data. That's what we're already doing. And then second, direct application. That would be where you're actually able to send in data and have it being streamed and have this play out in real time. This is very much, kind of in the future, but that's sort of on the roadmap, so to speak. And then once you followed one of those paths, you could generate an environment for your agents, and then also you could construct applicable agents, meaning agents to your design or ones that kind of fit the situation or be mapped to particular environmental variables, as we saw with the agent who takes care of the soil structure earlier, using Agent Ranker, which is kind of an entire addition that Daniel kind of zoomed through, being able to incorporate included. There's more information on that in the second live stream that was released. From there, you would simulate your agent-based model, meaning there'd be an initial setup phase that takes in your initial documents and so on, constructs the agents, constructs the artificial environment, then runs your action perception loop and keeps things moving. Data and LLM responses are encoded as observations for agents. Agents take these observations, take care of their environment. So we already know homeostasis for the agent, based on how it's set up, is kind of hard-coded into its design. and map to the homeostasis of its environment. And finally, there would be, obviously we would want this, analytics. So having some kind of analytics suites that allows you to derive insights from different kinds of metrics that are being recorded over time. There might be different kinds of like LLM summary reports and recommendations that actually extracts the metrics, and through a pre-structured prompt, as I've said a million times during the course of this, using pre-structured prompts, you can input a lot of these results and then have an LLM kind of put it into a natural language, like just explain for you in everyday words. Here's what happened. Here's what's going on here, what the agents believe, and so on. Bioregional modeling. I wanted to look at this really quickly. This is a lot of Daniel's work on. This is just an initial step. But what's happened is that Daniel set particular kinds of structured prompts. You can find more information on this in the first live stream. But basically asked about information in very particular ways to LLMs and did it programmatically, was able to extract an incredible amount of information about these different regions, different counties. And he started with California and then moved to New England, and then it's expanded from there. And so we have like Maine and Massachusetts. So for example, Massachusetts, Hampshire County, like you can, he sent in like, generate some kind of supply strategist statement. We have copies of these. This is a JSON form, meaning it's kind of set up in a way that can be read by the program. But then here's just a more readable, legible, every day for a user report. It's like, here is, your supply chain strategist report on the ecosystem of that county. References to what's going on in terms of its biodiversity, how climate change is impacting it, how land is used, habitat fragmentation, water quality. So just a lot of the different things that are going on specific to each of these counties. You can do that from a market analyst perspective as well. Try and consider different kinds of opportunities. What's the current economic landscape? What kind of regulatory environment compliance requirements are there, state, federal, local? Of course, these are currently very short descriptions. Ideally, over time, you would build out your knowledge graph, your knowledge base. You'd actually, kind of zoom into each of these, send more follow-up prompts, like tell me more about this. Cite the information you're pulling from, and then you could even consolidate that. So this is the kind of a consolidated report. Very long for all of these different market analyst perspective, ecological perspective, supply chain strategist, and just kind of finding ways to synthesize a lot of information in one move. This was a business case, and I just wanted to show quickly, like, here are ideas of here are defining out potential revenue streams, risk assessment, mitigation strategies. So it's very interesting. 5-year financial projections. Of course, we could pull this kind of logic back into the program, have local computations done that actually comes up with much more grounded, realistic, and precise information based on available resources that you have, or that at least artificially the agents have, if you're doing more of an artificial setting. So yeah, it's making all these linkages. And so, that becomes sort of the basis, the starting point for our for the biofirm. So we then, again, we generated this artificial environment. All we did was send in user documents, structured prompts through an LLM, give a structured response. Let me quickly, yeah. This allowed programming our environment, its dynamics, configuration, generating descriptions for each of the variables. They get stored in this nice JSON structured file, ecosystem config. So I mean, you saw previously, like I was looking at a GitHub repository. We're really building out the code in that base. And so anyway, that sticking back to the artificial environment here, this allows us to pull out, what are our variables or proxies for variables, such as indices. Like, it can be quite difficult to measure biodiversity, so we make an index for that. There might be other ways of doing that. There might be more specific ways of doing that fits your own use case. or otherwise we could, tailor that. Domain-inspired quantitative relationships between the variables. You can even, with more manual control, you can set the noise levels for each of these. Like if you assume that there might be some noisy process, from a more mathematical or statistical perspective, which of these are actually controllable or not. For those which are controllable, how much are they controllable? Can you dramatically change biodiversity in one move? Probably not. Or you could, and I don't want to follow that thought further. Biofirm development and performance benchmarking. This is another crucial part of the biofirm development, being able to actually benchmark how our active inference agents perform relative to, some kind of benchmark baseline, such as having a more reactive or random sort of thermostat style, like reactive control. So basically on the left, we don't have active inference agents. It's just trying, instead this is a more basic control strategy that kind of just reacts to the data it's seeing. And of course, the data is getting very out of hand. I'm not saying it's not getting out of hand with the active inference agent, but it much more so. And that's what we're seeing from an initial test case. And this active inference agent on the right is still that basic kernel homeostatic agent, right? It is keeping its target within range, 21% of the time relative to the random strategy, which is only 7. The next steps would be to actually fine tune and modify the agents to better match the situation. So far, it's very simplistic. It's only looking at one variable, only tracking one variable. It's currently not taking in any information from an LLM. It's currently not taking in any information about the other environmental variables. This was really interesting to see, though, that it already has this capacity for kind of outperforming the reactive model. We've had some instances where the active inference agent doesn't, it maybe matches the reactive model. So it's just, it's prime time to step up the agent development game, so that this was just step one. It's like, can we build it? Yes, we can. So now let's improve it. Analytics suite, we can look at, the variables themselves, their correlations with one another. We track the metrics about the environment over time, then compare how the environment behaved in different simulation settings. That's what we want to do with agent-based modeling in the first place. Typically, we want to be able to run simulations, look at the outcomes based on different circumstances. And then we can compare, how this went using different agents. We could use LLM integration to translate this into like a more readable report for users. This is a whole nother aspect I really wanted to emphasize. I've made this kind of as an additional module, so it can be edited kind of after the fact, like outside of the main program, which also means that you can modify this bit as you want. But basically, the idea is you try and measure the surprise or uncertainty or expected free energy or otherwise of the environment here, and basically look at how the actual variable diverges from where you want it to be. The difference, it's mathematical and it's drawing from active inference in other areas, Bayesian statistics and mechanics. But the idea is you can measure how far away it is from where you wanted it to be in terms of surprisal, actually capturing kind of this more rich or nuanced information about how that variable moves versus where you want it to be. And then you can kind of flip that, say, oh, well, in a non-equilibrium steady state system where more usually than not, the system is going to have a tendency towards generating more and more surprisal. That is the complex relationships between the variables is going to lead to things typically going off course very quickly if you don't touch them. Then in that case, any move at reducing surprise, meaning any move at combating that natural tendency towards kind of like chaos or entropy, it can be viewed as a form of generating value. And so this is the kind of additional metric we could add, saying that there's a kind of value added to having these agents, minimizing the surprise, meaning minimizing the free energy, meaning minimizing the distance between homeostasis and where the data is now, right? So we could see that kind of accumulation over time. And again, it's modularized, meaning for a user, they could potentially experiment as they like. They could change how this value added is computed. I think that'd be very interesting for people who are interested in economic simulations, or doing this, differently, or want to see like how does this work, Then also Shapley value analysis. We have Shapley values. So through the course of these simulations, we have agents trying to solve or take care of their environment. And so in the case of Shapley value computation, what it's doing is that we can compare how do certain coalitions of agents run through the simulation compared to one another, in terms of these different metrics. And so you can see like, oh, all 5 agents together did better at maintaining their environment in homeostasis. They did better than only having this other particular coalition of agents, but they actually did worse altogether versus when you only had these 2 agents working together, right? So it's a very kind of sophisticated way at looking at how agents are actually solving the problems and actually carrying out the actions that they need to carry out. And we can do this, for different metrics. And we can view that as, that can be another way of saying this is how value is being generated by these agents, right? So being able to make those kinds of analytics. And then these are the last couple slides. GNN and Agent Maker. This is very cool. This kind of like, we did so much rapid development of the biofirm over the past couple of weeks that this just kind of like hit me. I was like, oh, I didn't really think about that. But Daniel has incorporated, along with his co-authored work with Jakob Smikel in the past. They've worked on what's called general notation, and it's a way of kind of translating active inference agents, meaning models or architectures, between different programming languages, including being able to compose them using natural language, and then also being able to visualize them graphically. Like that's, it's not quite there yet. The kind of makings for being able to have this kind of translatability. Like, the ideal would be being able to write to an LLM, like, hey, make an agent for me that can do this and this. And then by giving the LLM certain kinds of context, it can fill in the matrices and so on as you need it. Of course, we're still a distance from that, but it's kind of building the framework towards moving towards that. And that way you can make agents who are much more tailored to the situation. And furthermore, ideally, you'd be able to translate them between programming languages, meaning, being able to switch if your application is in Python or Julia or otherwise, being able to have that done for you. And then Daniel has basically forked the PyMDP repository and then built Agent Maker on top of it. So right now it's kind of tailored to PyMDP, but it could be used in other ways as well. And so we already have some next steps on the kinds of agents we want to make. For me, it's agents who should be able to observe the whole environment, but only be able to control their own respective part. To me, that's what would make the idea of like having a shared common goal amongst heterogeneous specialized agents. Like that's what would realize that. So that's kind of the broader view of the biofirm. You start with inputting your documents, your texts, your PDFs, data for fitting, that's optional right now. It would be more ideal for a real world setting, but for now, just generating an artificial environment, just the text is fine. We've been able to accomplish that so far. And then from there, you could fit agents to the situation, or at least maybe customize them yourself using Agent Maker. You have the start of your knowledge graph or base being developed, and you have that ecosystem, all of its dynamics and configuration kind of spun up. Then after that, you just run the simulation, looking at analytics. We want to move towards having an interface in future, having dashboards. We've already seen a lot of these graphs earlier, so it's and then we'd also want to have LLMs that could actually report the results. And this is basically towards an adaptable kernel of a biofirm. This is kind of the bigger picture. We have different kinds of design considerations. couple highlights. We're looking at things like implementing potentially amortized inference. We're kind of accelerating the inference process, using continuous state space predictions and models, and then considering, we have an RxInfer group at the Institute, so we'd like to potentially move towards using a more reactive framework using RxInfer, the Julia library, as well as a kind of complementary library for environments, the Rx environments library. Plenty of different ways we might be able to use different kinds of APIs or integrations with other tools, locally storing LLMs to mitigate the issue of having to necessarily use the Open API, Open AI LLM API. And then obviously integrating, key aspects are like the resource management, right? And that's actually, I would argue, is going to be one of the easier parts of incorporating, because it's like, just as we can currently read real data or generate artificial data and have the agents manage that, like soil structure, we could do that similarly for different kinds of financial resource values, or managing an account or something along those lines, right? So bringing it back, biofirm development and testing. This is just a slide I showed earlier, but it's just to reinforce here some of the tools we use, some things we want to do in the future, some related institute projects related to, we're working on projects that relate to mitigating future existential risk. We've applied to a grant with Foresight. There's the FLI grant project, FarmWorks, RxInfer group. There's a new economic simulations related group. Some people are interested in looking at things like, simulating currencies and so on, in agent-based modeling. And then those live stream updates. My computer's having repeatedly deciding to cover things up. And that's it. So we went much further on time intended. There was a lot to cover. Really appreciate everyone's attention, though. And in these 11 minutes we have left, if you guys want to give anything a shot, please go for it. Oh, the voice is going out.
No. Take some questions.
Yeah.
Anyone in the live chat can write a question. John, where does this take you, and or what will you plan to do tomorrow?
Well, I think what we tried to lay the foundation here in a very thorough way is what is a biofirm, and how is able to address many of the issues that you see in people trying to work out biofinancial, the bioregional economics, and create the proper incentives. And so I think what we're trying to do here is really show that there's a number. When I started to say, here are some of the criteria that we're looking for, in particular building with Eleanor Osterman, the whole idea of how to govern a commons is a profound issue that seemed to be intractable to a lot of people. I think this, in my view, this provides a framework for doing it, a scalable framework for doing it, a way of involving people, a way of applying scientific methods, and creating financial incentives, and automating a lot of the data collection analysis task, and how agents can build up their own competencies over a period of time. So there's a lot here. There's a lot to digest. And it does provide a new metric of value that's based upon you're not establishing value in the classic economics that are price arbitrage or information asymmetry arbitrage. You're actually saying there's such a thing as a free energy principle, a scientific process, and we can show how the value is created and then how to allocate it to those people or those agents that are creating it. So this is really sort of foundational. So we want to take it to the next steps. And what we're going to be doing tomorrow is actually, there's a group of people who are experts in the sense that they work with how to take multi-agent architectures and apply them to, in some cases, to the enterprise. From Deloitte is doing that. Another group, Simon Torrance, is doing it in terms of AI, looking at framework for agentic architectures. There are others who are looking at it and applying to the regional finance issues. So we have that. Susanna Choi. We also have Matt Maroney, who's head of sustainable finance and metabolic, and then there's John Havens, who's been involved with IEEE establishing ethical frameworks for the application of geospatial models in AI. So it's quite a combination of people. But what we want them to look at is what's the impact of this when you're having fully autonomous biometric-based agents. And what happens when you can apply them not just to the bioregional finance, but also the new notion of a firm. And I think it's a real profound issue here. What happens when you really have autonomous agents and you create institutions? We create institutions that are supposed to be above people, but the problem is people populate institutions and they come captured. But what happens when we start to put these agents and build institutions that are function this way, that are verifiable this way? And what does that happen to what we think about employment and jobs? And I mean, there's some really substantive issues here. And how do you create this as a public resource, a public good that doesn't get captured by particularly small interests? So there's a broad spectrum of questions we're putting out there. That I don't think that the public in general fully appreciates the capacity and the power of an active inference free energy principle as applied to an economic and societal issue. So we're going to try to tackle those issues and get people talking about it. And this is a beginning, but we want to take it next steps and really get actual reference technologies out there that we can actually show and demonstrate and be able to replicate. So that's the goal.
Yeah.
And you're very helpful. I got to say, Daniel, kudos to you from all along. I mean, both you guys and Daniel you've done remarkable work in accelerating this process. And we're very, very grateful for that. And what Active Inferences Institute, there's other things the other sessions I saw here that seem to be very relevant to what we're doing. So I'm really looking forward to collaborating. I'm quite fascinated with ThoughtForge, what Matt Brown is doing homeostatic networks, and it goes back to Ashby and the law of requisite variety. I think all of that's applicable to this too. So there's this wonderful synthesis that you've enabled. You really have, and through a singular effort. So again, extremely grateful for this.
Thank you. It's been awesome, and a lot more I could say, but what can?
Well, we're gonna ask more of you. You're
I'm not done yet.
You're not done. No, we're gonna no.
The part that resonated with me in the presentation over the last 2 days of Biofirm and how Andrew laid out all these pieces is like, on one hand, we have that researcher lens, again, about similarities and differences and about treating it like it's an engineering problem. And then I think, John, you've brought in the deeper history of commons and cybernetics and these more open-ended problems about how do we connect any technical capacity to the embodiment and the co-enactment of systems that are livable and regenerative. And that's a little bit of a different kind of topic. That's one, though, that mass convening and awareness can fertilize and make real in a way where the technical understanding, it's like, you can skim the textbook, you can read it for 20 years. It's like, it is just going to be the textbook. It's just going to be something to jump off of and take into another way. It's not like some of these questions about how different regions will work. It's not in the 2022 textbook. So that's applying active inferences, taking the high road and the low road and variational free energy, expected free energy, like all of those formalisms, and then, like, surprise, surprise, applying them to what matters and figuring out that project and operational part. And there's just like, there's so many pieces was just like thinking of the yarn connecting the needs to what we do and don't have at different levels of readiness. That takes us back to the tech tree and all these other ways that we've discussed coordinating around that balanced way to think about regional and what is federated, what is transferable, how do we deal with all of these aspects. And it's been a great journey over the last few months also.
Well, thank you. What I find so reassuring is that, and you see applying the method, and then it starts to explain, and you keep applying it, and so it doesn't fade out. It doesn't. You're not getting ad hoc. It doesn't become ad hoc. And so I feel like we're doing something really principled that is extensible. And when I come from the biofinance community and see all the things that they've been trying to do, or in the commons community, they say, actually, there's a wonderful fit here. And getting these two worlds together is really important. It's a challenge too. But I people want to do that, and they're looking for something like this. And so I really hope that we can be able to create that marriage, as it were.
To add one comment on that, I think when you opened today and said, well, we could make things fungible, we can connect, but that is also part of replicating, if not elaborating, the problem, which is the fungibility of drinking water here and this calorie here and this unique species here. Facilitating that fungibility is facilitating the capture of the underlying resource. So even if it were somehow trivial to make like assertions about impact monetized, and the whole hypercerts and impact certification, even if that were trivial and we can just assume that we have full observability or something like that, it could even accelerate financial capital based cascades. And so what can be an escape grounding to that? And that's where seeing like, whoa, the models on through the paradigm of incentives are maximalist and reward oriented. Can they be homeostatic or allostatic oriented to satisfy and be on paths that bound surprise rather than try to maximize? But then as soon as we look around the world, there's things that don't make sense. We're not trying to maximize or minimize, like the reservoir, but rather within a range. And so there's so many things where we can just connect first principles of intelligence and research questions to just like the calm, subtle, sometimes ways that the technology, because to move too fast also would again replicate fallacies.
Right.
Okay, well, good luck with the session tomorrow.
Okay.
And I hope many people come join and engage in these fun, open source, meaningful projects.
This is just the beginning.
It's just a checkpoint, and
it's a strong one, and I'm very pleased with it. Yeah.
Cool.
Yeah,
all right. Thank you, fellows. See you later.
Okay, guys. Thank you.
All right, welcome back,
Hello,
everyone.
my name is Devin Bay. I'll be presenting accounting for multiscalar and conscious psychobiological phenomena in the active inference paradigm. So for an overview, I'm going to be going over the Markov blanket trick and then critiques of the Markov blanket and address how some of the previous work of Chris Fields and Friston partially addresses these critiques before finally going over problems of consciousness, new approaches and theories on consciousness and how these fit within the FEP and active inference, and then provide some ways to update the framework based on this information. I'm also going to take an epistemological perspective on modeling, and I'll focus on how both the conceptual mathematical formalizations of superposition and entanglement can maybe alleviate some of the problems that are identified in the critiques. So, the Markov blanket, since we are on limited time here, I will assume that most of the people here are already familiar somewhat with the Markov blanket or active inference framework, but I'll give a brief overview of the Markov blanket, focusing on some of its mathematical frameworks as well as some of the assumptions implicit within the framework. So, for the mathematical overview, given a state S of a model, its Markov blanket is the set of sufficient states within the network needed to infer that state, and it essentially partitions autonomous and external states, and is helpful in identifying which variables are conditionally independent from each other, and expresses the joint probability between external and internal states as mediated by blanket states. So the assumptions here is that there's sparse coupling between the different states in the Markov in the overall system, and that there is somewhat of a delineation between external and internal states, and that these external internal states can be properly partitioned via the Markov blanket. So the implications here, the Markov blanket is metaphysically distinct from Pearl blankets, at least in the context of active inference or free energy principle. I think this was raised by Boonberg and his colleagues in the Markov in the Emperor's New Markov Blankets paper, and so this essentially means that they differentiate themselves from Pearl blankets by nature of their application, and the Friston blanket itself by nature takes on assumptions like the existence of external, internal, sensory, and active states. And so this is the main sort of differentiation. Also, the Friston blanket is not providing a metaphysics, at least in my interpretation. And so we assume here the existence of distinct states which may be modeled, and this means that there are distinct states which are properly separable, and that there are either epistemological or ontological grounds for doing so. And so the main problem here, I think, is that there is not enough justification to argue that the Markov blanket partitioning is an epistemological or in a more broader sense, an ontological boundary, and that is causally correct. Or it causally captures, is able to causally capture causal relationships between variables, because the existence of sensory active and internal states and external states is something which can be disputed and which I'll discuss later on in this talk. And so another implication of the Markov blanket is that it allows the modeling of recursive structures and dynamics by use of the renormalization group, for example, which apparently allows the Markov blanket to capture multi-scalar phenomenon. And finally, the question of whether the Markov blanket adheres to the Bayesian-Occam razor, it would simply depend on the choice of parameters for the specific model and does not inherently implicate the Markov blanket. So Critiques of the Markov blanket. Like I mentioned earlier, the ontological critique of the Markov blanket is leveraged by both Brunberg and Raja in their respective papers, although as we've seen in responses to these papers, frankly it depends on the ontological interpretation of active inference and the free energy principle. And if, as Kieferstein in his response to Brunberg's paper claims, the Markov blanket should not be interpreted literally, then this problem partially goes away. However, the epistemological status of the Markov blanket is still under question, as raised in a part of Raja's paper, insofar as the explanatory power of the model is under some pressure. So chiefly there's a broader philosophical question about the purpose of models, and this is not necessarily unique to FEP or active inference or the Markov blanket, but nevertheless, since it affects all models, these issues are raised in the context of the Markov blanket as well. Next, we also see that there is a mathematical problem with the selection of Markov blanket states, because we see that for example, dynamic causal modeling in neuroscience does not demonstrate that that models provide scientists with a plausible account of the behavior of real-world biological systems, since successful applications of causal modeling does not give us any reason to believe that neural systems plausibly, for example, minimize free energy, or that they are ergodic active inference systems. And so this means that even though the model may be applied successfully and may predict some behavior successfully, it doesn't necessarily mean that the model is, number one, an accurate representation of what's ongoing with the internal dynamics of the system, and number two, that it would therefore be able to capture accurately all of the internal workings of the system. And so yes, and on this mathematical side as well, we also see that Ilan published in 2023 a paper on the constraint disorder principle and how that would possibly dictate neuronal function. And so Ilan points out that despite the stochasticity exhibited by the nervous system's operation, there's not necessarily a high level of control, since randomness at the lower levels never stops, and thus it dictates a paradigm of reaction, not action, by organisms. He uses the free energy principle, but does not use it to justify a form of active inference, which would be minimizing uncertainty, but rather argues that the constraint disorder principle is more preferable, where a process of balancing disorder and order is more inherent to systems operation in highly dynamic random environments. So whether all environments are highly dynamic and random, and at what scales this randomness can be asymptotically ignored becomes irrelevant is still up for question. However, the fact that these boundaries are not clear, and in fact that they arguably cannot be made clear, for example, via the existence of Maxwell's demon or limits on computability, etc., should point us in the direction of choosing better models and better parameters for these models. So what can this tell us about the free energy principle and the Markov blanket? First, it points to broader problems with the free energy principle, but these still carry over implications. These still carry implications for the ways in which the free energy principle epistemologically treats the Markov blanket, mainly to delineate across and between scales and causal relationships. In the later portion of this talk, I'll explain why entanglement and superposition are suitable replacements for the Markov blanket, where they actually offer a greater flexibility without constraining the mathematical and philosophical operations. And notably, Chris Field's paper on the FEP for generic quantum systems makes implicit use of some of the same affordances offered by superposition and entanglement, but takes a very specific interpretation of quantum systems, and I think limits the flexibility of such modeling tools by adhering to the holographic principle. Now on to the epistemological status of models, which I think is important to raise here because the question of whether the Markov blanket can accurately encompass multidirectional, what I'll call horizontal pathways, vertical and horizontal pathways, even without the presence of clear attractor states, is still under question, as is the more general assumption of ergodicity within the FEP framework. And so, as experimental evidence from physics shows, systems in general, not simply at macro or micro states, are afflicted by complex dynamics such as replica symmetry breaking, which fall into a sort of gray area between ergodicity and non-ergodicity, and thus render the determination of ergodicity versus non-ergodicity much more complicated, even with suggestions such as local ergodicity, as outlined by Ramstead in the 2018 article. So I think it's important to outline the epistemological status of models because it's important for clarifying whether the Markov blanket itself is problematic within the FEP framework and whether it can potentially be reworked. So from a Bayesian perspective, models should want to minimize both epistemic and aleatoric uncertainty, where epistemic uncertainty is the reducible part of the total uncertainty, and aleatoric uncertainty is basically the irreducible part. Active inference models, therefore, should minimize both epistemic and aleatoric uncertainty and represent possible model configurations and parameters via prior hypothesis space, where the choice of model is informed both by where we believe the quote-unquote truth is located, or at least the most truthful model is located, as well as the model constraints. So here we see in green is the ideal situation where we have an ideal selection of model with an ideal convergence to some truth X. And then the purple shows an example here where our prior hypothesis space does not accurately encompass the true model, and hence by extension the true model is not included in the posterior. Finally, the pink shows where the posterior does not converge to the true model. And so this is illustrating how problems can arise in these two areas. First, the hypothesis space does not properly encompass the true model X, which is the purple or blue example. And then second, the posterior space does not properly converge to the true model X, which is our pink example here. And so constraints on X depend on if you're a realist or an anti-realist. So for example, if you believe that there is some ground truth that is universal and unchanging, and it's physically accessible, then of course the true model would be a real true model. But if you're more of an anti-realist, then it would depend on your hypothesis space, and of course whether you believe that truths can be accurately represented or even be accessed, and that they're universal or whatever. So yeah. Now the question is the Markov blanket the proper choice of parameter for the free energy principle in active inference? So the purpose of the Markov blanket is to provide a statistical boundary which delineates a system from its environment. It ensures that variables are conditionally independent that certain variables are conditionally independent of other variables in the network, and it formalizes the belief or the prior that the system and its environment are separate, either ontologically, epistemologically, physically, like literally, or even causally, right? So Colombo and Palacios actually indict the Markov blanket and FEP, active inference model, by saying that it achieves a maximal generality for minimal biological plausibility because these boundaries can be drawn sort of arbitrarily, and even the existence of cellular membranes, for example, does not necessarily constrain causal relations between or across scales. So notably, Noble argues that organisms are open systems that operate far from equilibrium. And so again, drawing from Noble's arguments, Ilan, in the 2023 paper, argues that organisms develop numerous emergent boundaries between levels which are not present at the single cell level. So even though they may have distinct functional purposes, boundaries like the skin, intestinal tract, or even vastus medialis depend on exchanging matter and energy through cellular membranes. And so a boundary is thus dynamic, interactive, not passive, and cannot always be defined anatomically. So for example, electrical gradients and ion concentration gradients are actively generated across cell membranes, where interactions across boundaries determine an organism's functions, not just the composition of the boundary or the genome. So, of course, one way this has been explored in the free energy principle and active inference is via this sort of recursive Markov blanket. But we see that this sort of recursive modeling is not able to properly capture multi-scalar relationships and interactions across and between boundaries, where essentially we would have, Markov blankets that are causally implicated in more than one way in more than one way that can be described by simply the repertoire of active, external, internal states and sensory states. And so this is sort of where the case for entanglement comes into play, because entanglement has been argued for as a way of causally representing relationships between variables in biology. So first of all, we see that organizational boundaries of living systems are open and flexible, such that these boundaries need not be coextensive with the organism's bodily boundaries, number one. So again, I guess this is just to drive home the point that the Markov blanket should not be taken literally. But we also see that biology is inherently quantum. So these processes of cellular differentiation, for example, are fundamentally fundamentally determined by, or perhaps sort of controlled by quantum processes that dictate, what chemical bonds the cell is able to break, for example, or how certain concentrations of ions, for example, flow across the cellular membrane, and the permeability of the membrane as well can also exhibit quantum effects. So as the field of quantum biology grows, I think we will increasingly see that the quantum level is extremely important for dictating how organisms evolve, and especially if quantum consciousness theories continue to gain support, we could see that quantum processes may also be implicated in consciousness. And so causal entanglement addresses the sort of asymmetry between what were previously considered linear processes and this sort of asymmetry across and between scales. So I basically argued that causal entanglement is a counterintuitive form of Occam's razor, because when we have entangled variables, we don't need to always explicitly represent the dependencies of these variables with each other. So that means that we can, in an infinite dimensional Hilbert space or a finite dimensional Hilbert space, represent the variables in a way that does not necessarily dictate specific boundaries or constraints on these variables, which may impede the causal modeling of certain phenomena. So as the scale and complexity of the model increases, representing relationships via entanglement becomes much more appealing. And of course, quantum computing also offers ways to speed up the computation of machine learning models like an active inference. So Vecchi actually puts forward a case for causal entanglement using DNA, and essentially we see that that entanglement can serve as a form of of sort of outlining the different causal dependencies in a system without necessarily explicating them, without putting too much emphasis on the specific properties of the causal relationships. If we know that certain things are are causally implicated, then we can take the sort of rough approach of assuming that they might be entangled to some degree. And so basically entanglement can serve as a method for representing murky dependencies without necessarily misrepresenting causal relationships by conflating correlation with causation. And so in the paper, Vecchi uses chromatin structures during the interphase period of mitosis to show how, and basically show how it can be characterized in terms of interactions between entities at 3 different levels of biological organization. So essentially the parts or angles between the linkers in the chromatin, and then the chromatin structure or the topological invariant structure, and then finally the feedback loop between how the whole, which is the overall chromatin structure, depends on context properties in the feedback loop, for example via histone deacetylation or histone methylation. And so essentially, we see that they argue that DNA is both a total and direct cause when being manipulated, where it is a total cause because DNA is implicated in its own manipulation, and it's also a direct cause because it's an intervention on DNA will change the functional or structural properties of the DNA without changing necessarily additional non-local properties of whatever substrate surrounds the DNA. And so specificity still allows linear models to capture causal relationships in terms of isolating specific variables, but when we increase the scale and complexity of these of the model, for example, or of what we include in the model, it becomes increasingly more difficult to separate out and to sort of distinguish, okay, where exactly does the specificity lie? And so this takes me to this differentiation between repertoire and connectedness when it comes to causal specificity. So repertoire is basically how many possibilities exist on each side, the cause side and the effect side. And we can essentially, in a modeling context, take this to mean the number of different values that an effect variable and a cause variable can take. Meanwhile, the connectedness is how the possibilities on both sides are connected in particular and relevant ways. So we can see, again, in the modeling context, that connectedness is a condition for a given function connecting the values of cause and effect variables. And so repertoire does not entail connectedness, and connectedness does not entail repertoire, which is important to note, because essentially we see that repertoire but by splitting causal specificity into these two independent properties, we may not be able to compare causal relations from a single point of view, and therefore causal entanglement may allow for the comparison of both without necessarily giving up one for the other. And of course Ruiz notes that you need both repertoire and connectedness in order to come to a complete causal understanding of, whatever processes are implicated or you're examining within a system. And so the form of entanglement between, repertoire and connectedness would allow you to express both of them in the system simultaneously and potentially, extract results from either of them. And so, what are the practical constraints and limitations on this approach? Well, first of all, we might view it as a case similar to quantum versus classical computing, where as the complexity class of the problem increases, quantum computing becomes more appealing. So utilizing entanglement may not be computationally feasible right now, given hardware constraints. And modeling using the entanglement may obfuscate the extraction of direct causal relationships. But as Noble has pointed out, and this previous researchers have pointed out, the extraction of direct causal relationships is a very difficult task, and epistemologically it's not clear whether this is even possible once the system surpasses a given point of complexity where where the dependencies between and across scales simply become too large to properly identify, direct causal relationships. And so, essentially, this entanglement approach may also become computationally infeasible when we have lots of dense variables that are not sparsely coupled. But I think because the Markov blanket also, inherently relies on the sparse coupling, and sparse coupling in neuronal dynamics has been shown. Entanglement can be taken as a sort of replacement for the Markov blanket. And so I'll just get into some previous work involving the free energy principle in quantum mechanics. So Chris Fields integrated quantum information theory with the free energy principle and proposed that physical interaction is a form of information exchange where the holographic principle can essentially be used to formalize boundaries between systems. Additionally, Worthier investigated the potential for tensor networks to represent generative active inference models. So tensor networks, of course, can offer computational benefits when run on quantum computers, and the tensor network itself was originally designed to be used in quantum mechanics. So specifically for Fields' approach with the quantum reference frames, we see it's a different way of approaching the Markov blanket, which still formalizes boundaries using the holographic principle. So it's still assuming that we can properly distinguish the boundaries between organisms and their environments, and that these boundaries are both causally necessary, right? So that there's some causal impact of the boundary that cannot be ignored, and that the boundary itself is, properly distinguishable. So now I'll go into some theories of the overview of consciousness and how it's implicated in both FEP and active inference, and how it fits into the proposed framework for utilizing entanglement. So the minimal causal mechanisms of consciousness, we see that there are regions in the brain that are implicated in consciousness where, if these regions of the brain are damaged or not functioning properly, this leads to changes in the overall phenomenal and conscious perception of individuals. So we also see that non-equilibrium macroscopic brain dynamics are a robust signature of consciousness. So at some level, consciousness can, statistically and physically be proven to be the sort of higher order process or dynamic that is going on in the brain. And so consciousness and the Markov blanket. So how does consciousness interact with the Markov blanket and the free energy principle? Does the link between phenomenal perception, judgment, awareness, observation, etc. disrupt the epistemological application of the Markov blanket? And do competing theories of consciousness pose problems for active inference? So on the first question, I think that when it comes to the Markov blanket and free energy principle, consciousness, as I guess with all neuroscientific theories, is this sort of throws a wrench in things when we are trying to consider how, conscious states or differing levels of conscious states may not be easily or neatly put into boxes of either internal or sensory states, because again, you're assuming that the organism has either the organism itself has some capacity to differentiate between these states, and that the states themselves can be placed into this sort of into these sort of categories for representation by the Markov blanket. So I think this is especially apparent when we are discussing phenomenal perception, judgment, awareness, observation, etc., because these types of phenomena are very, very broad ranging in terms of their phenomenal activity and their corresponding their correspondence to underlying neuronal dynamics. And of course, the research there is still ongoing, but based on, what research there is into awareness, for example, attention or observation, there seems to be varying sort of degrees of complexity and also degrees of causality when it comes to which areas of the brain are implicated in minimal self-awareness, and to what extent these boundaries initially observed can be modified, or modified either internally by the person, the observer, modified by some external causal force, for example, like anesthetics. And so do competing theories of consciousness pose problems for active inference? And I would say it depends on the mechanism of consciousness, right? So it depends on how these theories lay out consciousness, because they may or may not implicate active inference. For example, theories which are more volitional, on the more volitional side, that attribute consciousness to volitional activity, which in itself is maybe distinct from free energy minimizing or uncertainty minimizing activities, then we would see that yes, these competing theories of consciousness do or would pose problems for active inference. And another dynamic that I want to explore here is the unconscious, right? So experimental evidence supports a sort of minimal unconscious, where we can broadly distinguish between type 1 and type 2 thinking. So type 1 thinking is unconscious processing, and type 2 thinking is conscious processing. And researchers have sort of found that there is a form of dynamic unconscious which sits between the sort of conscious processes that are directly under observation or awareness, and then those perhaps autonomic processes, for example, where they're entirely unconscious. And so the dynamic unconscious theory essentially posits that the observer or the conscious agent themselves has some capacity to guide their awareness to processes that were previously unconscious. So you can essentially make previously unconscious processes conscious. And again, the implications for the Markov blankets neat delineation between sensory, active, and internal states. I would say this sort of frustrates the thinking behind the thinking behind trying to separate out these different states, right? And so theories of the brain should incorporate a transition from unconscious to conscious awareness. And of course, this is extremely difficult because we don't have really a solid understanding of what consciousness even is, what are the minimal phenomenal sort of requisites of consciousness, and how sort of expansive the operations of the unconscious are, and whether those unconscious operations are therefore implicated in conscious processing as well, for example, with underlying cognitive biases. So what are the implications for the free energy principle? So both conscious and unconscious processes should be modeled. However, the distinction between sensory and internal states does not do these conscious and unconscious distinction. I think it doesn't do it justice. So why is that the case? Well, first, conscious processes are unconscious processes are processes that may inherently be sort of semi-conscious. For example, when someone is scratching their leg, for example, right? The distinction between conscious and unconscious processes is one that is fundamentally dynamic, and therefore we don't know whether there even is a boundary between the awareness of scratching leg and not scratching leg, and especially if that boundary is sort of is highly dynamic. For example, when someone is slipping in and out of consciousness post anesthesia. And so we see that unconscious and conscious processes could influence active inference in ways that are particularly unique to them. So, for example, unconscious processes could be represented as priors within the model, but that doesn't always necessarily have to be the case, because these unconscious processes could also be interacting as internal states, for example, or they could be present even as active states once they are made conscious. And so the mechanisms of consciousness, various theories which have been proposed, could provide a mathematical basis for expanding active inference and the free energy principle as well. So I think this is very important to note, because theories of consciousness, novel theories of consciousness that incorporate more quantum information side, or that correspond to the electrical correlates of consciousness, for example, are extremely important may provide mathematical frameworks for updating active inference, or potentially may provide useful mechanisms for modeling specific conscious processes that could then be incorporated into the framework of active inference. And so, let's see. And so, yeah, so I think I'm missing a few slides here, but basically the overall theories and most promising theories of consciousness that are upcoming are the sort of the electrophysiological and the electrical field sort of theories of consciousness, which posit that consciousness is actually a result of the electrical dynamics in the brain, which of course would need to be a case as for any minimally causal sort of representation of consciousness. But the presence of electrical fields and the implication of these fields in consciousness is a particularly new avenue of research. And we see that, for example, firing patterns in the brain have produced quasi-crystal representations, and can be represented as well in the torus, for example. So these higher dimensional dynamics within the brain correlating to consciousness, or these sort of unconscious processes, will be extremely important in and determining, what processes are relevant for consciousness and how these might be implicated in inference, for example, or thought patterns, traversing whatever sort of dynamic landscape that exists in the brain, which again may be determined by these higher order or these higher magnitude or dimensional structures. So overall, we see that investigating the mechanisms of consciousness, I think, is fundamentally necessary for FEP and active inference, because these structure or have the potential to structure thought in the ways in which certain energy landscapes, for example, in the brain, are traversed or fundamentally interact with each other. And so the areas for future work here would be to unpack the philosophical dimensions of active inference, which would include implicit assumptions about intelligence, sapience, and sentience. So, for example, you could utilize Denison's conception of intelligence, which argues for a relationship between the model and the modeling. The model and the modeler as a direct form of intelligence there. Or you could utilize Simondon's theory of individuation as a more productive method for explaining the boundaries and cellular differentiation, which I've critiqued previously. You could also utilize quantum computing to take advantage of quantum-specific algorithms and to investigate quantum biology with increasing scrutiny, for example, and discover ways in which quantum biology is implicated in processes of consciousness, active inference, and in the brain. And so essentially the overall theory here when it comes to to active inference and multi-scalar phenomena and consciousness is that we can essentially, if we take that the boundaries between the system and these systems are not actually ontological or physically causally implicated, and we utilize this sort of causal entanglement to represent relationships between different parts of the system. Consciousness can be taken as a form of observation along specific, causal trajectories within the system that would essentially collapse the superposition of these entangled states, which would produce, specific outcomes. And so that's a very broad sort of method for integrating consciousness with, quantum phenomenon and entanglement. But I think that there are many other, there are different methods of integrating quantum mechanics with the paradigm of active inference, for example, that are distinct from the holographic principle and do not rely on the explicit representation and encoding of information in the boundaries, for example. And when it comes to, for example, these unconscious processes, as I've outlined in the abstract, these unconscious processes could be represented more so by the minimization of uncertainty via the free energy principle as always ongoing processes, similar to Elon's argument, whereas conscious and more volitional actions would be represented by sort of observation on this quantum system where we are collapsing the superposition of specific entangled states. And so I think that in that way, entanglement offers two sort of benefits to the active inference paradigm. The first is that it allows for some flexibility when we are talking about different variables and causal connections between and across scales, because we can entangle two variables that are causally distinct. That are distinct across scales, for example, but which may be implicated in some feedback loop, for example. And this entanglement can then represent the causal dependencies between these variables. On the other hand, if consciousness, is a sort of quantum process, then it would allow for the integration of whatever quantum processes that are ongoing in whatever quantum consciousness. So if you believe that consciousness collapses the wave function, for example, then incorporating entanglement would be a mathematically feasible technique for incorporating this form of volition, where essentially the conscious agent is collapsing a specific wave function, and that leads to that allows them to perform active inference, for example, by minimizing specific probability densities. So yeah, that's overall the scope of my talk today. And yeah, I hope everyone enjoyed that. And if you have any questions, please let me know.
Thank you, Devin. Great times. So, I'll ask one question. You'll give the closing word for the live streams for the whole symposium. So, you're the only undergrad presenter. What would you say excited you to get into the game? And what do you say to younger learners to come?
I am mainly interested in the sort of mathematical and philosophical, I guess, ideas behind active inference. And I'm particularly happy to see that the active inference ecosystem has, thriving philosophical and mathematical community. So when it comes to younger participants who may be interested in active inference, I would say, keep pursuing what you're interested in, and if you have any particular areas of research or ideas, you should always be looking to share them, I think, and be looking to expand your horizons. So yeah.
Cool. Well, looking forward to hearing more from you and from others. So thanks again, Devin, for bringing so much together in this last capstone talk.
Thank you so much for inviting me to give the talk, and apologies. I was a little bit short on time to put together the slides, so this was a lot messier than I would have liked, unfortunately. But yeah.
Real life is like that. All right. Thanks, Devin. Peace.
Thank you so much.